Hi and welcome to the Particle Physics Marathon for physics students that really deeply want to understand the fundamentals of particle physics. Here is a timestamp of everything we will see during these lectures. You can also find the same timestamp in the description of this video, as well as the lecture notes of this course, and you can activate subtitles in the YouTube settings. My name is Kamil and I'm recording these lectures from NICEF, which is the Dutch National Institute for Subatomic Physics, where I'm working as a PhD in the theoretical physics group of this institute. Here is the big, huge summary of everything we will see in the next 20 hours or so. And as a student in physics or as a professional that needs to work with particle physics, if you do not really deeply understand everything which is summarized in this blackboard, you will always have hard time understanding everything else. These are the fundamentals, and when I was a student and I was approaching particle physics, I really always had hard time understanding what is fundamental and what is not fundamental. For example, if you take one of these huge books, then we will comment which book we will use for this course. But if we take one of these books, in this book, this is like more than 800 pages book, of course there will be the fundamentals of particle physics, but there is not only fundamentals. Of course there are also parts that are explained for historical reason. For example, that is the way we understood for the first time a certain concept, but it's not fundamental and it's not the most straightforward way of understanding the concept as a student. Then there are equivalent ways of coming to the same result. For example, the path integral formulation for quantum field theory and the canonical quantization give you the same result in particle physics. And then there is my enemy number one, which are difficult, nasty calculations that are not fundamental, but they are very useful to solve some specific problem. I think as a student and as someone who's approaching the subject, you do not need those nasty calculations, but you only need the core of particle physics, because then you will learn those calculations only if you need them. That is why I started doing this course on the basics of particle physics, and when I started a few months ago, I thought it was an easy task. I thought I more or less understand particle physics and I can talk about it, but little did I know that I was embarking in one of the most challenging adventures of my entire life. I really spent around 200 hours studying and preparing these lectures and recording these lectures to make the structure, as you see here, as simple as possible. We will talk about the three main characters of particle physics, as you can see from the color scheme in this blackboard, and we will build the Lagrangian of the Standard Model, which contains almost everything we know currently about particle physics, starting from basic concept of relativity and quantum mechanics. If you're a professional which is working with particle physics, this course can be incredibly helpful for you as well. Because what I realized in realizing this course was that here and there I had some gap on the basics of particle physics. And solving these gaps helped me incredibly in my everyday job. If looking at this blackboard you have doubts about anything which is summarized here, for example, how these indices work, or how you go from the Dirac equation to the Dirac Lagrangian, and how do you go from a Lagrangian to an equation of motion, and then from the Lagrangian how you build Feynman rules, etc., or even worse, what all these pieces in the Standard Model Lagrangian mean, then fixing all these doubts, no doubt, will help you incredibly in your everyday work when you read a paper, when you write a paper, and when you go to seminar or make a presentation. Now we will go through a complete summary of everything that we will do in the next 20 hours or so, but first let me thank infinitely Yamur Zubarolu for helping me in the process of realizing this course from the beginning to the end. Really thank you for the infinite physics discussions that we have, and thank you for making this course possible. Books that we use for this course in particle physics. As you can see, we have this course is based on many books. The principal three books that we will use are these three. And then there is some inspiration from many technical textbook and popularization books that I really enjoy. Here are some of them. It's not all of them, because I don't even remember everything that has been as input in this course, but these are the three main books that we will use during this course. The first one is called Quantum Field Theory and the Standard Model by Matthew D. Schwartz. And when I went to CERN with my collaboration, I saw this book as the first book exposed in the CERN library, as if to say, look, this is the Bible of particle physics, and it's really a Bible of particle physics. I will suggest this book to a theoretical physicist. There is really everything you can think about in particle physics. But of course, I just wanted to explain the fundamentals, so we will not, of course, go through everything that there is in this book. Then we will use this second book, which is called Modern Particle Physics. This book, I saw it everywhere in the hands of many theorists and experimentalists here where I work. And I think it's a great book. It's really easy to read, understandable, but it has a downside. The downside of this book, even though it's called Modern Particle Physics, is that it introduces the Lagrangian, so Lagrangian formulation for field theories, and in general it introduces quantum field theory in chapter 17 when it's talking about the Higgs boson. So despite the title of this book, I would suggest it to someone who's not very interested, is more interested in the phenomenology of particle physics, more than how we build the Lagrangian of the Standard Model and how can we really get everything out of this formalism here. We will use during this course this Lagrangian formalism and quantum field theories because it really simplifies a lot the structure of particle physics, because once you write down the Lagrangian, you can know practically everything about your system. And then there is this book. This third book came after a while when I was already half through this course, but I really enjoyed this book. It's a book about quantum field theory. It's called Quantum Field Theory for the Gifted Amateur from Lancaster and Blundell. It's not particle physics, but it's quantum field theories. Quantum field theory and particle physics are deeply related because quantum field theory is born for explaining particle physics, but then quantum field theory is a subject in its own. And this is a basic introduction in quantum field theory, so I suggest this book to someone who's interested in the broader subject of quantum field theory. Of course, if you don't want to spend hundreds of euros in physics book and you just want the core that we are explaining in this course, I'm preparing the lecture notes for this. For now they are all handwritten, so they are not understandable, but I'm preparing the LaTeX document, which I will link in the description of this video once it's ready. Now let's go to serious business and talk about everything that we will see in these lectures. And of course here it's a huge simplification of what we will talk about in the next 20 hours or so. But what we will do is to start from relativity and quantum mechanics, make a summary of the basic concepts of relativity, for example, how the Lorentz transformation work, and of quantum mechanics, for example, how the Schrödinger equation work, and then follow the orange lines in this blackboard to come to the Lagrangian of the Standard Model. This is a simplified form of the Lagrangian of the Standard Model, so that it fits in the blackboard. But what this huge formula means is just it contains, is almost like a dictionary of every particle and every interaction that we currently know about particle physics. It encapsulates almost everything we know about particle physics. As you can see from the color of this Lagrangian, the main actors of this whole course are three objects, which are these three fields here that we will talk about in a moment. But let's see piece by piece what we will gonna do. So first of all, in the first lecture we will talk about quantum mechanics, and in particular we will explore two main ideas. First of all, what this object here is. In this case, spoiler, it's a wave function or probability amplitude, and how it works. And then what is the equation which tells us how this object here looks like, which is the Schrödinger equation. Okay, Now, what we do in particle physics, many people think we answer to a question which is what is a particle, but that is not true. What we do is answering a question how a particle behaves, which is very, very different. For example, in quantum mechanics, the way we describe the behavior of particles is through this wave function. But the wave function, it's not the particle. Exactly as the trajectory of a ball, it's not the ball. And in classical mechanics, we describe the trajectory of the ball, or of, for example, I throw this. In classical mechanics, I can describe this motion with a trajectory, but the trajectory is not the object. And we never ask philosophically, what is the ball? Okay, what is the object that follows this trajectory? And in the same way, we use fields and quantum fields, these three fields in particular, to describe how particle behaves, but a lot of people say particles are fields. I think it's more appropriate to say particles are well described by quantum fields, and in particular they are described by excitations within quantum fields, and we will see what that means. But that just to say that we will see the basics idea on how we describe particles in quantum mechanics, and then we will introduce this concept of relativity, which is the Lorentz transformations. So we will ask what happens if I start going fast, if I change my reference frame from a frame to another frame, in which the velocity between the two frames is a constant velocity, so they are two inertial frames. What we discover is that the Schrödinger equation is not compatible with relativity because it's not Lorentz covariant, whatever that means. It means that if we transform reference frame, the physics described by the Schrödinger equation becomes different in the new reference frame. So it's, of course, not a good equation for describing relativistic physics. And we will see an example of good equation for describing relativistic physics, which is the Maxwell equation. So we will really start here with Maxwell equation, and we will see the covariant form of the Maxwell equations, which is this one. We do this to familiarize also a little bit with the basics concept of relativity first, and second, we want to familiarize with this notation here, this weird notation with indexing going around that most of the student, of course, is confused about, even though they have a basic understanding of special relativity. Of course, here I didn't specify special relativity, but we do not talk about general relativity. Everything here is special relativity, so gravity is not involved in the picture, and gravity is not involved in any of this discussion. Okay, so we always work under the assumption that gravity is not there, because of course all the forces that we described in the standard model are much, much bigger than gravity. So we can give, like, say, approximately gravity is not there. But okay, we see that quantum mechanics is not compatible with relativity, not like the Maxwell equation, which is compatible with relativity, and so we start our task for describing and for having a formulation of quantum mechanics which is compatible with relativity, and we come across the Klein-Gordon equation. This is a first equation which is relativistic and which is in a way a first attempt of a relativistic formulation of quantum mechanics, but also this equation here has a problem. Namely that if we interpret this guy here as a wave function, then we get negative probability density. Of course, a negative probability doesn't make any sense, and so Dirac, in an attempt to solve this problem, came up with the Dirac equation. The Dirac equation, as you can see here, the solution to the Klein-Gordon equation is this phi here, which we will interpret in particle physics as a scalar field. One moment and I explain you what these are. And the Dirac equation has as solution to the Dirac equation this psi, which we interpret in quantum field theories as a Spinor field. So now we have three equations. The Klein-Gordon equation, which describes scalar fields, the Dirac equation, which solved the problem of this negative probability density and describes Spinor field. We will also see how from Dirac equation this field here must be, or this object here must describe spin 1/2 particles, so it must describe fermions. And also we will see why with the Dirac equation we need antimatter, and why antimatter is associated, and how, let's say, antimatter is associated to the negative solutions to the to the Dirac equation. Okay, so we have two equations now, and then we introduce a third equation, or better, we already introduced Maxwell equation talking about relativity and well-behaved equations in relativity. And incidentally, we end up with these three blocks here. One green, one blue, and one orange. And I gave different color to these three blocks because they describe three different kind of fields. And this is really almost everything there is in quantum field theories, and in particular in particle physics. Because these three kinds of field describe every possible particle and every possible interaction that can be turned on in the standard model and that we can observe in particle physics. So what is a field? I told about field up to now, but what is a field? A field is a mathematical structure that associates to every point in space-time a number or another object like a vector or a spinor. Okay, so for example, a scalar field, this field here is called scalar. The scalar field can be complex number or real numbers, but they associate one single number to every point in space-time. This field here, the solution to the Dirac equation, is called a Spinor field. And it associates to every point in space-time a spinor. We will see what a spinor is. It's not the moment yet. This guy here, this F mu nu, is built from AMU, which is a scalar field. No, sorry, it's a vector field. And this means that this field here is a mathematical structure which associates at every point in space-time a vector. And the differences between these three fields is how they transform under Lorentz transformations. So we have these three fields described by three different equations. So every one of these fields is solution of a different equation. And now it's the moment to introduce this least action principle and the Lagrangian formulations. The Lagrangian formulation of quantum field theories. The Lagrangian formulation is one of the deepest results that math and physics came up with for describing reality. It's really something that it's very close to an ultimate mathematical reality, because with the Lagrangian formulation and the least action principle, I can, instead of writing down the equation of motions from the various fields, I can just write down a Lagrangian. From the Lagrangian, I can go back using the equation which are called the Euler-Lagrange equation to the equation of motion. So I will have, for example, in this case, I just put here the Dirac Lagrangian, but from the Dirac Lagrangian, using the least action principle, I can go back to the Dirac equation using the equation of motion, which are also called the this is the equation of motion. We can go back to the equation of motion using the least action principle, and in particular the Euler-Lagrange equation. So Euler-Lagrange, okay? If we have, so that we can also build, and we will do, we can also build a Lagrangian for the Klein-Gordon equation, which we'll call the Klein-Gordon Lagrangian, and we will build a Lagrangian for the Maxwell equation, which we will call the Maxwell Lagrangian. Here I just wrote the Dirac Lagrangian because I think understanding this and understanding the Dirac equation, so these two blocks here, it's really the foundation of particle physics. That is why we will spend quite some time explaining the Dirac equation and the structure of the solution to the Dirac equation, and then we will go to the Dirac Lagrangian. And really, having this Dirac Lagrangian and understanding deeply this Dirac Lagrangian will allow you to understand deeply all the jump that we will make for building all the possible theories in particle physics. And all the possible theories, all the theories that we will build are quantum electrodynamics, a simplified weak interaction, which I didn't list here, the electroweak interaction, and then we will build the whole standard model. Okay, but everything starts by understanding this simple equation, which is the Dirac Lagrangian. Once we have the Dirac Lagrangian, we also make a little parenthesis of what the fundamental objects described by this Lagrangian are. And in particular, we will see the quantization of the solution to these three equations. So these three are fields, and then we quantize the fields. We will not use a rigorous formulation of this quantization of fields, so we will not do it in a rigorous mathematical way, but we will see intuitively how to quantize a field. When we have the solution of these three equations, they are just classical fields. But then these guys here, in particle physics and in quantum field theory, we interpret them as field operators, okay? For example, in the Dirac Lagrangian, these two fields here are not classical fields anymore, but they are field operators that can create and destroy particles. How does it work? Let's take, for example, psi. Okay, psi can either create a create an antiparticle and destroy a particle through operators. And of course, okay, we will talk about this later. I don't want to confuse you too much. If we take the conjugate of psi, so psi bar, which we also will define is not simply the complex conjugate of psi, but psi bar can do the opposite thing. So if this guy here can annihilate a particle and create an antiparticle, this guy here can annihilate an antiparticle and create a particle. So going from this equation to this equation, we will also see the quantization of the solutions to the free equation of motion for the various fields and how the particles are interpreted. So we will really see what does it mean that particles are excitations within quantum fields. Once this is done, we will really work with Lagrangian and forget about all the equation of motion that describes free particles. Because all of these three equations describe simply, okay, not this one because we have a source. Okay, all these two equations here describe free particles and free fields. And still the Dirac Lagrangian describes free fermion fields. But then we want to turn on interactions. And the first way of turning on interaction, the simplest way possible, is to talk about symmetries of the Lagrangian. In particular, we will start by the simplest symmetry in the Dirac Lagrangian, which is the U1 symmetry. What is a U1 symmetry? Let's say that you take the field psi and you send this field to e to the I theta psi. So you take this field in the Lagrangian and you shift the phase, the complex phase of this field. Then you notice that the Dirac Lagrangian remains exactly the same, because this phase shifting of this field is exactly opposite as the phase shifting of this field, and the two cancel each other. That means that the Lagrangian that we use to describe our reality has a phase, is invariant under phase shifting. Okay, and this phase shifting we call it U1 transformation. Then we ask ourselves, what happens if this phase shifting, instead of being the same in every point in space-time for the field, depends on the particular point in space-time that I'm on. So it's a local transformation, which means I take the fields, which are the fundamental objects in my Dirac Lagrangians, I shift their phase, but not in a constant manner, but I shift their phase in a different way in every point in space-time. And I ask myself, is this Dirac Lagrangian still invariant under this local phase transformation, which is called also local U1 transformation? Well, the answer is no. Okay, so the next question is, how can I make the Dirac Lagrangian invariant under local U1 transformation? Well, for making the Dirac Lagrangian invariant under local U1 transformation, I have to introduce a new field which transforms exactly in the right way for making this Lagrangian invariant. So I will introduce a new piece to this Lagrangian, which is a coupling between the Spinor field and the vector field described by the Maxwell equation. Okay, so for the first time, we introduce an interaction. This describes free particles, and the quantum electrodynamic Lagrangian will contain this block here, which describes interaction between the particles. And in particular, it will describe interaction between the Spinor field and the vector field. The Spinor field can be any particle which is fermion and interacts electromagnetically that comes to your mind. So every quark, not the neutrinos, the electron, the tau, and the muon. And this guy here represents, it's not that these are particles, but these are field operators that can create and annihilate particles. And this guy here, A mu, it's the field operator that can create and annihilate photons. So this describes the interaction between light and matter. Okay? And this is the piece that we have to add to the Dirac Lagrangian to make it invariant under local U1 transformation. This is the first thing that we call a gauge theory. So it's the first example and the simplest example of a gauge theory. And for quantum electrodynamics, as simple as that, then we will also add a term to the Dirac Lagrangian that describes the kinetic part of the boson, so of the photon field, but for now forget about it. It's a term, by the way, that looks a little bit like this, or exactly like this, but the meaning in this Lagrangian here is different. Once we have this piece here, we will build the Feynman rules for quantum electrodynamics. So we have fundamental objects. This particle here is a photon. This particle here is a fermion that can be, for example, an electron. So here we can have various interaction with, for example, in this case we are describing an electron and a positron annihilation, and in this case we are describing also electron-positron annihilation to two photons. And this, in this case, is just one of the possible diagrams of the electron-positron interaction, because we have an electron and a positron in the final state. But just to say, what we will do is to go from the quantum electrodynamic Lagrangian, which contains this piece, to the Feynman rules for quantum electrodynamics. And the Feynman rules are composed, so the Feynman diagrams are composed by three fundamental pieces, which are external legs, like this guy here. Then we have propagators, which are the internal lines. For example, this guy and this guy are propagators. And then we have vertices, which are the interactions between the various particles. And the only vertex that we can have in quantum electrodynamics is this three-particle vertex, in which we have interaction between one photon and two fermions. Okay, we will not go too deep into the Feynman rules, because this is exactly one example of what I was explaining to you before about nasty calculations that are not fundamental, and they are very useful to solve some specific problem. For example, if you want to compute a cross-section for a certain process, you will write down the Feynman rules and build a mathematical expression for every possible term that contributes to this process, and then you will sum all this, you will compute the amplitude for every possible term that contributes to this process, you will sum them all, and then you will build the observable that you need. And there are many tricks, tricks with the gamma matrices, tricks with the fermion propagators, etc., for simplifying the calculation of these Feynman diagrams, but we will not see any of those tricks. We will just see the logic which is behind how I go from the Lagrangian of the standard model, which is this Dirac Lagrangian plus this piece plus another piece, to computing physical predictions for observable. But we will not go through all the calculations, because that is one of the things that you can learn once you have all the basics of particle physics. Of course, there are Feynman rules not only for quantum electrodynamics but for any theory that we can build starting from these basic fields. For example, the electroweak theory and the whole standard model Lagrangian, but we will not see the complete list of Feynman rules for the standard model Lagrangian, for example. My suggestion is this. If you need to understand Feynman rules and how to compute Feynman diagrams, so the amplitude associated to Feynman diagrams, learn it in quantum electrodynamics. So learn very well how the Feynman rules and how to compute amplitude work for quantum electrodynamics, which is the simplest theory possible because it only has electrons and photons, so only electromagnetic interaction. And then once you really understand deeply how it works for quantum electrodynamics, it will be easy to understand the Feynman rules for the whole standard model Lagrangian. Okay, there are many more complications, etc., but the basic idea are exactly the same. After discussing the Feynman diagrams and the electromagnetic interaction in detail, we will go back to the Dirac Lagrangian and make an attempt to describe a new type of interaction. Because we observe in the world, for example, in processes of beta decay, that there are particles, which are the neutrinos, that cannot interact through a photon. So they cannot interact through this kind of diagrams here. And the basic interaction which involve neutrino also involve particles that are charged particles that cannot be the photon. Okay? In an attempt to describe this kind of new interaction, we will start from a Dirac Lagrangian. So the Dirac Lagrangian is really the central piece in which you always start. And instead of having the Dirac Lagrangian in which the fundamental component are simply two spinor fields, one spinor and one anti-spinor, in this case, the fundamental component will be a doublet. In the case of the simplified weak interaction, which I didn't list here, the fundamental component within the Dirac Lagrangian is a doublet containing a neutrino and an electron. Okay? If I write down the Dirac Lagrangian with this doublet and without the mass term for the electron and the neutrino, so assuming that the electron and the neutrino are massless, I spot a new symmetry of the Lagrangian, which is called a global SU2 symmetry. So, if this is the fundamental component of the Dirac Lagrangian is invariant under global SU2. Okay? SU2 symmetry, this SU2 transformation, it's something that takes the electron and the neutrino in the doublet and mix them in a certain way. So the new Dirac Lagrangian, after a global SU2 transformation, will be a Lagrangian in which the fundamental components are not anymore the neutrino and the electron, but they are superposition in a certain way of the neutrino and the electron field. And this new Lagrangian describes exactly the same physics as the original Dirac Lagrangian, in which the fundamental components are the neutrino field and the electron field. So this is a global SU2 transformation. Then, exactly as in the case of quantum electrodynamics, we ask what happens if I make this symmetry here local. What happens if this transformation becomes local? So if I transform in a different way, point by point in space-time, it happens that the Dirac Lagrangian is not invariant anymore. And exactly analogously, in the case of quantum electrodynamics, for making the Dirac Lagrangian invariant under local SU2 transformation, we add a new field. But this field here, this new field that we add, since this is an SU2 transformation, is not made of only one component, but is made of three components, which we will call W+, W-, and W3. These three components will have vertices associated to them, so interaction terms, which are analogous to this term here. And in particular, we will observe that the interaction term associated to W plus and W minus could explain what we observe in the beta decay interaction. But we didn't get it quite right yet, because we have a problem, which is this W3 we don't really know how to explain or with what interaction it corresponds. And then we started with massless neutrino and massless electron. Now, in the standard model, the neutrino is massless, but the electron is not. So how can we explain the fact that we correctly, more or less, explain the weak interaction, but with massless electron? And also, these bosons here must be massless, but we observe in reality that the W plus and the W minus boson are massive, because the interaction is extremely short range. So how to explain all this? First of all, we go through the electroweak unification. So instead of having two separate gauge theories, which are one for U1 and one for SU2, we want to make a unified gauge theory for electromagnetism, so for quantum electrodynamics, and for the weak interaction. This means that we will impose to this Dirac Lagrangian a new symmetry group, which is called SU2 left times U1 hypercharged. This SU2 left is exactly analogous to the first symmetry group that we imposed on this Lagrangian, with the only difference that now only the left-handed chiral components of the field participate in the weak interaction when it comes to W plus and W minus boson. But this is not something that we will go further now, but I refer you to the lecture in which we will talk about these things. So for now, take this L just as a little letter, not as a something physical that is happening with this symmetry here. And then we have this U1 hypercharged symmetry, which is different from this U1 electromagnetism symmetry. Okay, so this guy here, U1 for electromagnetism, electromagnetic, that gives us quantum electrodynamics, is different from U1 hypercharge. Okay, but exactly as with the same logic of the quantum electrodynamics, and exactly as with the same logic of the local SU2 symmetry, imposing that this Dirac Lagrangian must be invariant under local SU2 left times U1 hypercharged transformation gives us the electroweak Lagrangian. And in the electroweak Lagrangian, we turn on, or we have now an electron, a neutrino, W boson, Z boson, and photons, which are all particles that we observe in nature. Of course, this electroweak Lagrangian can be made more general, introducing new particles, so for example, also with all the quarks. But if we talk about the electroweak interaction when it comes to quarks, it's more complicated, so we will not go through the electroweak interaction regarding quarks. And if we talk about other other lepton generations, so for example the muon and the tauon, is exactly the same electroweak interaction that happens for the electron and the electron neutrino. So we will only talk about the electroweak Lagrangian and electroweak interaction for electron and electron neutrino. And we will see that making this symmetry local for this Lagrangian involves introducing four new fields. This is W plus and W minus, Z, and the photon field. The fields associated with SU2 left will be W plus, W minus, and W3. The field associated with this U1 will be a new photon-like field, which is called BMU. So it's exactly mathematical equivalent to what we call AMU in the quantum electrodynamics interaction and in the quantum electrodynamics Lagrangian, but is associated to a different symmetry. It's not U1 electromagnetism, but this is U1 hypercharge. Then mixing these two fields here will give us the Z boson and the photon. But now we have the same problem of before. This Electroweak Lagrangian now explains all the interaction that we saw up to now, including the electromagnetic interaction and the weak interaction, but all the particles in this Lagrangian are massless. For making the Lagrangian stick to the observables that we have in nature, that is that the electron is not massless and also the W plus and minus and the Z bosons are not massless, we introduce in his whole glory the Higgs mechanism. The Higgs mechanism is something that allows us to give mass to the particle that need mass. And we cannot simply associate a mass term to these particles in the Lagrangian, because the mass term would break the gauge symmetry that we used to create this Lagrangian in the first place. Okay, so we need something which is called the Higgs mechanism to introduce the mass of the particles without breaking the gauge symmetry, or at least we will have a spontaneously symmetry breaking that we will talk about, but the whole Lagrangian, it's still symmetric under this transformation. So in the last two lectures we will talk about the Higgs mechanism and how the Higgs mechanism gives mass to the particles, to the Z, to the W plus, the W minus, and how the spinor field, for example, the electron interacting with the Higgs boson acquire a mass. And then we will talk about the strong interaction. So everything in this discussion here, it's always without the strong interaction and without quarks. We pretend that quarks do not exist, but at some point we will have to introduce quarks. And introducing quark and the strong interaction will be made with a new symmetry group, which is this SU3 color symmetry, which only affects the quark sector in the standard model. So this guy here is associated to quantum chromodynamics, which is a more complicated version of quantum electrodynamics, and also in this case we will not go too much into details of quantum chromodynamics, because I believe that if you learn quantum electrodynamics and this SU2 symmetry, then quantum chromodynamics comes naturally, or at least how to build the Lagrangian which accounts for quantum chromodynamics. Then in quantum chromodynamics we have a crazy amount of effects that really complicate our lives because of the strong coupling, which doesn't allow us to make physical prediction in low energy interactions involving quarks. So regarding QCD, we will only talk about why it's non-perturbative, we will talk about confinement, and then we will just use this SU3 color symmetry group for building and for putting in the standard model Lagrangian the pieces that have to do with the strong interaction, which are the quarks. So once we have everything in place, we talked about the Higgs mechanism, we talk about the electroweak interaction, and we talk about also this symmetry group associated with the strong interaction, we are ready to build the standard model Lagrangian, which is the last thing that we will do in this course. And from the standard model Lagrangian, you will be able to understand every possible field that is involved in our theory and every possible interaction between the fields in our theory. So, to the standard model Lagrangian. We had great effort in understanding the three principal subjects of this huge blackboard, which are how to build the Lagrangian for fields that describes free fields, how to turn on interaction, which are described by gauge theories, so making the free Dirac Lagrangian for the spinor fields invariant under local gauge transformations, and then how to turn on mass in this Lagrangian that we have through the Higgs mechanism. Using these three pieces, we build the standard model Lagrangian, okay, which is this huge formula here, and it looks huge, but it's actually a crazily oversimplification of what really is the standard model Lagrangian. So the first term that you see here is the kinetic term of the bosons in the standard model Lagrangian, and it contains kinetic term for the photon, AMU, or better, for this field here which is associated to the electroweak interaction. Then it contains kinetic terms for the W bosons, and then it contains kinetic term for the how are they called? G, let's call them G. G mu, which are the vector field associated to the gluon, which are the mediator of the strong interaction. So it has these three kinetic pieces plus for the theories that are non-abelian, whatever that means, we will see that, which are SU2 and SU3, we have interaction term between bosons. So in this case we have this kind of interaction terms. Okay, so in this piece here of the Lagrangian we have interaction between 3W bosons, 4W boson, 3 gluons and 4 gluons. Then we have this piece here that comes directly from the Dirac Lagrangian. This huge D is called a covariant derivative, and inside this covariant derivative there are all the interaction terms, or are encoded the fields that are mediator of the interaction between the various fermions. So for example, we have terms in which we have the weak interaction, so W boson vertices, we have the gluons, so vertices that mediate the strong interaction, and then we have the photon. Or better, we have this B mu field that then mix with the W3 to give us the photon. So let's call it photon for simplicity. So we have weak interaction, strong interaction, and electromagnetic interaction of the fermion fields. And these fermion fields are, for example, neutrino and electron. If the gluon is the mediator of the interaction must be strong. So these two here must be quarks. And then we have any kind of fermion excluding neutrinos. So this can be quarks or leptons excluding neutrinos. Then we have this term here, which is the term that gives mass to the fermions. And this is a term in which we have the interaction between fermion fields, for example, quark, electron, etc., and the Higgs boson. And we will see how the Higgs mechanism, through this term here, gives mass to the fermion fields. Then we have this term here, in which you can see the covariant derivative and the Higgs boson, and this term here gives us interaction between the Higgs boson and the massive gauge field. So the Higgs boson with the W plus W minus and Z boson. The gluon and the photon do not interact with the Higgs boson because they are massless. And in the end we have the Higgs potential, in which we have interaction with, between the Higgs boson and himself. This was the whole summary of everything we will see in the next hours together in this full course on the fundamentals of particle physics. I hope it will be helpful for you, I hope it will be useful, and I hope you can understand my English, which is mostly Italian and it's not so good. If you didn't understand everything in the introduction, it's completely normal, in particular if you are new to particle physics. But make this test, come back to this introduction after you watched the whole course and see how much more you can understand of this introduction, and it will really blow your mind. If you enjoy this course, please let me know, and let me know how I can improve this course, because of course it's the first time I do something crazy like this. It was completely new for me, everything was completely new, it was incredibly difficult. But I did my best to make this course as understandable and as simple as possible. I hope you like it. In this first lecture about particle physics, we will discuss quantum mechanics and the basic principle of quantum mechanics that we will use in particle physics, which is the probability amplitude and how the probability amplitude works. Knowing how quantum mechanics describes particles will allow you to understand how particle physics describe particles, because now in modern terms in particle physics are described by quantum fields, but in quantum mechanics the behavior of particles in certain systems is not described by quantum fields, but is described by an object called probability amplitude. So we will see what this object is. Probability amplitude. And in particular, we will use the Feynman explanation for the probability amplitude, which I think is very, very genius. We will call the probability amplitude with this letter phi. By the way, the probability amplitude is also called wave function in certain occasions. We will use those two terms interchangeably. And the probability amplitude is the object that we use to describe particles in a certain condition. We will not see in the beginning what is the phase of the probability amplitude, so how the probability amplitude looks like, and we will do, as second step, an example of a probability amplitude in a specific case, which is the plane wave. So, in the specific case in which I have no potential, so the particles are free to move however they want, we describe the particles using a probability amplitude, which is a complex plane wave. So we will describe a little bit how plane waves works, and then finally we will do the Schrödinger equation. We will derive the Schrödinger equation in the specific case of in which the probability amplitude is a plane wave, but in general the Schrödinger equation is something like this. H bar derivative with respect to time of the probability amplitude or the wave function is equal to the Hamiltonian of the system, which we will see what this means, applied to the probability amplitude. Now, the solution to the Schrödinger equation is the probability amplitude. So, depending on how the Hamiltonian of the system is made, for this object here, I will have a different probability amplitude that describes a particle in different conditions. Okay? Let's start with describing how the probability amplitude work. We talked now about amplitudes in quantum mechanics. The amplitude is the way we have to explain quantum mechanical processes going on. As you know, quantum mechanics is absurd. It's something very counterintuitive, and the amplitudes that we call phi, sometimes they are also called probability amplitudes or wave functions, are the solutions of the Schrödinger equation, and they explain how our systems, our quantum system behaves. And what is important here, now we will not see how these amplitudes look like, but what are the rules of the amplitudes. Then after we discover about the rule of the amplitudes, we can talk about how does this amplitude looks like for different processes, for example for the hydrogen atom, for the quantum harmonic oscillators, and so on. We introduce this a la Feynman, as Feynman introduced this amplitude in his lecture, and I think is the most genius way of talking about the amplitude. So we do it through the double slit experiment. Double slit experiment, I'm sure everyone is a little bit, at least a little bit familiar with it. And we have a source here that emits particle. Then we have a detector here that, guess what, detects particle. And in between the source and the detector, we put a wall. What happens here, let's draw first blue particles. What happens here is that this source emits one particle at a time. We try to dig a hole inside this wall here. This we call slit. This we call the slit 1. And the particles go from the source, and we measure the particle in the detector in a certain point x. Okay? In this case, we know that if the particle leave the source here and land on this point x of the detector, the only path the particle could have taken is this one, through slit 1 and then arriving at x. If we measure this, if we leave particle go for a long time and we measure the probability of a particle landing on the screen, which is proportional in the end. If we leave a lot of particles go to the screen, the probability of landing on the screen will be also proportional to the number of the particle on the screen after a certain time t. Will look something like this. So there is a lot of probability for the particle of landing in this point in which is close to the slit, and there is less probability of for the particle to land in this point which is far from the slit. Now we ask ourselves, what happens if I close the slit? So this one I close, and I open another one in another place of the detector, for example here. Well, the situation is the same. For a particle to land here, always in the same point x, she must go through this second slit, which I call slit 2, and from slit 2 must go to x. Okay. In this case, of course, the probability, the distribution of probability of the particle landing in different places on the screen will be somewhat different, something like this, of course, because there is more probability that the particle lands in a place of the detector which is close to the slit. Okay. Now the quantum mechanical part comes in, and the absurdities of quantum mechanics comes in, and we ask ourselves, what happens if I take both of the slit and I open both of the slit? And this is something that you can do. You can try yourself with a laser. If you take a laser and you point it in a wall, you will see a certain interference. And if you take a laser and you point it to a wall, but in between you put a hair or a double slit, you will see completely a different pattern on the wall. And this pattern for other kind of particle, which, okay, we shot same kind of particle, but we draw them in orange, so we distinguish the two situations. But what really changes here is not that these are different particles, but just that they can pass from slit 1 or from slit 2. So in this case, for these particles to land, I don't know, in this point x, let's change the point, they will either pass from slit 1 and then land in x, or pass in slit 2 and then land in x. What really happens is that I don't know where the particle pass from this slit. I just know that the particle starts in this source here and land in this point x of the detector. What happens in this case if I go and measure the probability of the particle landing in every point of the screen? I obtain a figure of interference which is something like this. Okay? And this is completely absurd, because if you think about it, take for example this point x, this one. With only one slit open, there is a certain probability of the particle landing here. And if I open another slit, okay, so I give the particle more ways of landing here. I decrease the probability of the particle landing here. So it's like the particle, what is the naive interpretation of this process is that the particle really takes both paths, interfere with herself, and then lands on a certain point of the detector. And I detect the particle in a certain point with a certain probability, and the probability is changed from the case in which I open both slits, but one first and then the other second. Okay? And this is very crazy, because I can't explain this behavior of particles using the normal classical mechanics. So people come up and trust me, they try to explain this behavior of particles with classical mechanics, with some classical argument, but no, there is no way. And we explain this using the probability amplitude. So we associate an amplitude phi1 to the particle starting from here, passing through slit 1 and arriving at x. Then we associate another amplitude to phi 2, which we call phi 2, to the particle starting from the source, passing through slit 2 and then going to x. And in this case, these amplitudes are complex number. Why complex number? Well, because complex number can interfere. For example, let's take the sum of phi 1 plus phi 2. Phi 1 plus phi 2. If phi 1 plus phi 2, of course, phi 1 and phi 2 are complex, so phi goes like, let's put it in white, a certain normalization factor e to the I theta. Okay, so if I sum these two complex numbers, summing two complex numbers is like summing vectors, because a complex number is completely defined by two real numbers. So summing complex numbers is like summing vectors in 2D. let's say that in a point in which the particle, there is less probability of the particle landing, I can see this case as summing two vectors or two complex numbers which have a phase, so this part here, which is very distant. So I have one vector, then I sum the second vector, which has a length, but the phase is it's short, it's very different, and so I obtain in the final state, let's say, so in this point here, I obtain an amplitude associated to this point, which is smaller than the two amplitudes independently. What happens in a point in which, for example, here in the center, in a point in which I increase the probability of the particle of landing here, well, what I'm doing is to sum two amplitudes with a phase which is very close. So, for example, I have the first amplitude phi1, which is something like this, and the second amplitude phi2, which is something like this. So the total amplitude, the sum of the two amplitudes, will be something very, very large and much bigger than the two amplitudes independently. So this reasoning in terms of complex number can in some way explain why the particles land with less probability in places in which before they landed with more probability. Okay, so let's try to formalize a little bit these rules for amplitudes. We have in particular three rules which we are interested about and which will become very, very interesting in particle physics, even though in particle physics then they will be more complex. But understand these three rules because we will find them everywhere. Okay, so first rule for the amplitude, number one, if I have two subsequent events, I have to multiply the amplitudes. For example, this phi1 is equal to, I can say, there is an amplitude for going to the source to the slit 1, and I can call this amplitude, for example, phi, let's call it in blue, yeah, phi a. Then there is an amplitude for going from slit 1 to the point x in which I want my particle to land. And this amplitude I call phi b. So the amplitude phi1 will be the multiplication between phi a and phi b. Okay? So no interference if two events happen one after the other. What happens if two events are indistinguishable? This is the real part in which quantum mechanics becomes weird. If two events are physically indistinguishable, I have to sum the amplitudes. So I will have a total amplitude associated to this event of the particle going from source to the detector in the point x, and the total amplitude in this case will be phi a plus phi b. And here is where the interference happens. So the principle in quantum mechanics, this is very deep and is an explanation that why, one says why, no one knows why, but this is confirmed by experiments and this is like how nature works. So yeah, it's very crazy, but that's it. And try to understand very well this principle. If two things are physically indistinguishable, we have to take the amplitudes of the two things happening separately and then sum the two amplitudes for obtaining the total amplitude of the process happening. For example, in this case, the process is what I see in the process. All this part here I cannot see. Okay, so I cannot distinguish physically where the particle passed from. I don't know if the particle goes through slit 1 or through slit 2. What I know is just that the particle starts at S in the source and arrives in this point X of the detector. In this case, I will have a total amplitude for the particle starting here and landing here, and the total amplitude must be the sum of all the possible ways this particle can start here and land here. Okay, in this case I have only two ways, so phi 1 and phi 2, and I sum phi 1 and, oh yes, this is phi, of course, not phi A and phi B, because phi A and phi B are this one and this one, but I have the total one. This one is phi 1, and this one is phi 2. Okay? And the third rule is where quantum mechanics becomes, let's say, where we can relate quantum physics and classical physics. So, third rule is the rule of the probability. So once I have computed the total amplitude for the event, what happens is that I can compute, in this case, the probability of the event happening. And in this case, for computing the probability, the rule is that the probability, in this case, of the particle landing in this point x is equal to the absolute square of the total amplitude. So what happens is, if I have two indistinguishable cases, first I sum the amplitude, so I get this object, which is the total amplitude, and then I have to find a probability, but a probability is something that cannot be described by a complex number. You remember that these numbers here are complex numbers. The probability must be a real number and positive number. So for transforming a complex number into a real positive number, what I do is squaring, like complex conjugate of the, it's squaring, taking the absolute square of the complex number, which is the same as taking the complex number, complex conjugate, so swapping the I into minus I, and then multiplying by the complex number itself. This is the sum square, the absolute square. So for computing the probability of certain events happening, I have simply to first recap. First, obtain the total amplitude of the event happening, considering all the possible events, all the possible way this event can happen, and then I square the total amplitude, which is a complex number, and I will obtain a real positive number, which is the probability of that event happening. So in this case, will be the probability of the event of particles starting at source and landing at x. Now that we know how the rules of the amplitude looks like, we have to know how the amplitude looks like for different processes. And we start with the simplest one, which is the free particle. Free particle. What is a free particle? A free particle is simply a particle which is going around with a definite velocity and momentum. So in classical mechanics, this is the simplest thing I can talk about, and it's something like this. I have a particle here, which I can see as a little ball. The particle has a certain momentum p, which is equal to the mass of the ball times the velocity of the ball. And the particle has a certain energy E, which is kinetic energy, which is 1/2 mv squared, and you can check that this is also equal to p squared over 2m. This is simply because p is equal m times v. Now, how I describe this particle? This particle simply obeys to the Newton equation, but the Newton equation for a particle which is not subject to any force is simply ma equal to 0. So mass the it will be the v over the t equals 0, but also you can say dp equals d t equal to 0. This means that the momentum of the particle is conserved and the particle goes around freely without changing the motion of its motion. So the trajectory of the particle will simply be something like x of t. So the position of the particle, depending on time, will simply be some x0, so the initial position, plus the velocity of the particle, or p over m, times t. Okay? What happens in quantum physics is that I have always this particle, but the particle cannot be identified like a single point, so a particle somewhere going with a certain speed because of the Heisenberg uncertainty principle. So I simply describe my free particle, in this case, with a fixed, let's hypothesis. I know exactly, this is already an hypothesis, and we will see later why this hypothesis doesn't hold, but let's say that I know exactly the momentum and the energy of the particle. So also in this case, in the quantum case, the momentum, I put a little hat because it's an operator, but we will talk about that later, and the energy are related. And in this case, if there is no other force acting on the particle, no potential acting on the particle, the energy is simply, also in this case, the momentum squared over 2 times the mass of the particle. And in this case, the amplitude for these particles going around with a fixed speed, for example in this direction, will be a plane wave, what we call a plane wave. In this case, let's say that P is simply equal to Px, so it's only in one dimension, and so the energy will be equal to Px times Px squared divided by 2m, and in this case the plane wave of the particle will be a wave function or a probability amplitude, so it's the object that we saw before, and it will be equal to a certain normalization factor times e to the I over h bar, where h bar is the reduced Planck constant, and also these don't care too much about what these constants are, because these are things that we will put equal to 1 when we will go in particle physics, in the proper relativistic particle physics, and this is px times x. This should be momentum times space, 3 momentums times 3 space, in which, so P times x will be Px x plus Py y plus Pz z, but in this case the momentum is only directed into the x direction, so I can remove this vector symbol here and just say that this is Px times x, and then this, here I put minus e times time t. Okay, so this thing here, this guy, this object, is the thing that describes my free particle. Now we will see a little bit in depth what this object is. Let's work always under the assumption that I have a single momentum of the particle and I know exactly what the momentum of the particle and the energy of the particle are. And in this case, since I know exactly what the momentum and the energy of the particle are, this is a plane wave. So it's just a wave everywhere in space going in a certain direction, which is the direction of the momentum of the particle. So I can't say with this form here that the particle is somewhere. The particle in this case is everywhere. We will see that this is just an approximation, it's something which is simplified, and we will solve this mystery of the particle being everywhere in a minute, but let's assume for a moment that the particle is in a precise state of momentum, and this we call this wave function here an eigenstate of the momentum px and of the energy, because I can extract the information about the momentum and the energy from this particle. And let's see how can I extract the informations about the momentum and the energy of this particle, given the wave function of the particle. So this is the amplitude associated to a particle which has specific momentum p and energy E. In this case I put in orange the momentum p and the energy E, so we have an idea that these are fixed quantities, fixed values. And I ask myself, or I give you this amplitude and I tell you, how can you give me an information about this amplitude? How can, or better, can you tell me what the energy of this particle is? Can you tell me what the momentum of this particle is? Well, in this case we have to solve an equation which is the eigenstate, the eigenvalue equation. And the eigenvalue equation states something like this. If this wave function here is an eigenstate of energy and momentum, let's do it for the momentum, for example. If this wave function here is an eigenstate of the momentum p, so that means that has a specific momentum, and in this case check that has a specific momentum, then this wave function obeys to the eigenvalue equation. The eigenvalue equation tells us something like this. If I apply this operator of the momentum on the wave function, phi of x t, I obtain the value of the momentum, p. So this is the operator, this is the value that is inside the wave function, times the wave function phi of x t. Okay? This applies also for the energy case. So if I apply the energy operator to the wave function phi of x t, then I obtain the eigenvalue of the energy times phi of x t. This always if the wave function is an eigenstate of the momentum and is an eigenstate of the energy. Okay? So in this case we have to figure out what these two operators look like, because the operator, once I have the wave function that describes a certain process in the world, so that describes certain physics of my problem, for extracting information from this wave function I need these operators. But how do these operators look like? Well, we can simply find some operator that satisfies these two equations. And the first one, for example, for the momentum, it's very easy to see that if I derive the wave function with respect to x, what I have is d over the x of this wave function, phi of x and t. This will be equal to n, or better, I over h bar times the momentum, the momentum p, because I derived by x, and the momentum p, let me write it down in orange, times the wave function, phi of x t. So in this case you see that the operator of momentum must a little bit look like this derivative with respect to x. And in this case then I can simply multiply times minus I h bar, so the operator of momentum will look like p equals minus I h bar derivative with respect to x. And this is the operator of the x component of the momentum. In general, the operator of the momentum p will be minus I h bar delta, where delta is d over dx, d over dy, d over dz, and of course p is the operator that contains all three components of the momentum. What we are interested now in is this operator here, which is the momentum operator. Let's do the same exercise for energy. So this is very important part. This is the eigen value equation, so we put it in a little circle, a little cloud. If we do the same for the energy operator, for finding the energy operator, you notice already that here, deriving by time this wave function, we obtain minus I over h bar, the energy, times the wave function. So simply the energy operator E must be equal to I h bar derivative with respect to time. And indeed, if I apply this to the wave function, I h bar d over dt phi of x t, I will get exactly the eigenvalue of the energy times the eigenfunction, the eigenstate, which is the wave function x, or amplitude xt. You see then that this part here must be the energy operator. Okay? So we find also the energy operator in this case of the free particle. Okay? So let us, now we have three ingredients. We have the wave function And for extracting information from the wave function about our physical system, we have found two operators, the momentum operator and the energy operator. This will lead us to the Schrödinger equation in a moment. So this is the wave function for the system. If we want to extract information from the system, in this case we can extract information about the momentum of the particle and about the energy of the particle. And in particular, we can use these two operators that we found out how they look like. E h bar derivative over time, this is the energy operator, and then we have the momentum operator, which is equal to I h bar for only one dimension of the momentum, which is easier to understand, it's d over dx. We saw that for the free particle we can describe it with this specific wave function if the momentum p and the energy E are fixed, and then we can extract information from this wave function about our free particle going around using these two operators. Now it's time with these two operators to build an equation for the free particle case that will be also useful for any case, which is the Schrödinger equation. Well, an important ingredient of our physics for describing our physics in quantum physics that tells us something not only about the particle which is involved in the system, but also about the system in which the particle is involved, is this operator that we call Hamiltonian. The Hamiltonian, which we call H, is simply equal to the sum of the kinetic energy plus the potential energy. In this case of the free particle, the potential energy in which the particle is immersed is zero simply. So the kinetic energy is equal to the total energy, and the kinetic energy is equal to p squared over 2m. So this will be equal always to p squared over 2m plus a certain potential energy. The potential energy depends on the system. So in this case, the potential energy, while we are in the free particle case, can go away. Of course, p squared over 2m, if we see what p is in one dimension, in this case, we can write this like p squared equal minus h bar square over 2m, and the second derivative with respect to this coordinate x, or in general, if p is px plus px by y and pz, we can describe this as delta squared. But in this case, we are let's keep it in one dimension to keep it simple. So we have only the derivative, the second derivative with respect to x. So how do we build our Schrödinger equation through this information? Well, we have two kinds of information. The first one is that the energy of the system, the total energy of the system, can be described by this operator, so deriving the wave function with respect to time. And the second one is that the Hamiltonian of the system is described by this operator, p squared over 2m plus v, in which v is the potential energy. In this case, the potential energy is zero. The third information that we are missing, but which is very, let's say, potential energy plus kinetic energy, also in classical physics, is the total energy of the system. So E, the operator E, which is equal to I h bar d over dt, is also equal to the total energy, the Hamiltonian, which is also equal to p squared over 2m, which is also equal to this, minus h squared over 2m d over dx squared. So we see that if we have the wave function phi, let's call it in blue just to have some color, phi of x and t equal, of course, itself, so phi of x and t, if we apply in one side the energy operator, is the same of applying the Hamiltonian operator. So the energy operator, which is EH bar derivative over time of the wave function or of the amplitude is equal to the Hamiltonian operator, which is minus h bar squared over 2m d over the x squared of the wave function. And this is Schrödinger equation in one dimension for the free particle. So like this we get the Schrödinger equation in one dimension. So one dimension considering only x, the Schrödinger equation is I h bar d over dt phi equal to minus h bar squared over 2m d over the x, but second derivative in x phi. Okay, this is one dimension and free particle. Then we can have three dimension and free particle, which is something like, it's exactly the same, but simply E h bar d over the t phi equal to this operator here, squared. This is a vector, but the vector then it becomes squared, so this is simply d over the x squared plus d over the y squared plus second derivative with respect to z squared. Okay, and this is an operator which is applied to the wave function psi or phi, and then we can have the more general case in which we have three dimensions. So we keep this operator here without only deriving with respect to one component of the space, but not free particles. So we can have a system in which a particle has a potential V, is immersed inside a potential V. For example, an hydrogen atom, an harmonic oscillator, an infinite well of potential. So it's always one particle in a certain condition. It is the wave function of this particle in this certain condition is described by the Schrödinger equation. And in this case, the Schrödinger equation simply, you already know how it looks like, probably. I call this wave function in a different manner because the different wave function is not anymore a wave function of a free particle, but is a generalization in this case. So the wave function psi doesn't look like this anymore. It looks like something that depends on the potential V. And this is minus h bar squared over 2m this operator squared plus V. Also V is an operator that will act on the wave function and in some cases modify the wave function, times C. Now, finding the solution of the Schrödinger equation means finding the form of the wave function. And then once I have the form of the wave function, so we can a little bit familiarize with the principles for the amplitudes or wave function that we saw before. Once we have the form of this amplitude, for example, I solve the Schrödinger equation for the hydrogen atom, for example. I get this form, x t. So the amplitude will have a certain form, and in every point of the space x and the time t will have associated a certain complex number. Then once I have this, for finding the probability of finding the particle in a certain point in space, I just square this, and this will be the probability of finding the particle in a certain point of x in the momentum t. The stationary states, this is a property of the stationary states, which are the states with a definite energy. So if the energy is fixed for a certain wave function, then the probability of finding the particle in a certain point x of space will not depend on time. This I don't know why I'm telling to you, because it's not relevant for what we will do after this, but it's very, very interesting. And what you are seeing now, it's animation of the stationary states, the probability of finding a particle in a certain point for the hydrogen atom, which I made for another video in Italian, unfortunately. And now what you are saying are animation of stationary states of a quantum harmonic oscillator in 2D. This also I made for another video, always in Italian. Maybe one day they will be also available in English, who knows. But this is very interesting result, because now we have a way, an equation of describing my system. And it's perfect, because you see, I don't know, it's really good, because we have this equation. If we solve this equation, we find the form of this wave function, and knowing the form of this wave function or of this probability amplitude, then we can find information, real information about the system. And this is very important, because this is in a way the same thing we are doing when we are doing particle physics with multiple particles which interact and which produce other particles, annihilate, and do all the kind of crazy stuff. Because this is classical quantum mechanics and describes only system in which the number of particles is fixed. We will see then other equation, because this equation has a huge problem, and the huge problem is that it's not covariant, so it's not doesn't agree with the laws of relativity. But we will see that we will find another equation for another object which is analogous to the wave function or probability amplitude. What I want to see before watching what is wrong with this equation is a generalization of this wave function, because this wave function doesn't make sense physically, and there is a very interesting result that I want to show you. Now we talk about what superposition is in quantum mechanics, because it's one of the most interesting parts of quantum mechanics, and we will apply the second rule about wave function that we saw before. That is, when we have multiple waves of a thing happening, we have to sum the wave functions or the probability amplitudes associated to all these multiple waves to find out what is the total probability amplitude. And we see that this way of describing a single particle moving with a fixed momentum p and a certain energy E, it's something that has some problem. The problem being that if I go and plot what is the value of this wave function with respect to x, for example, I see that this is something like this. It's a wave, a plane wave which is everywhere in space, that continues till plus infinity and goes from minus infinity. And so it's not really a good physical way of describing what is the particle and where the particle is. This wave has a certain wavelength, which is associated to, I think this is the correct formula, but yeah, no, that's the correct formula for the wavelength of this length. So it's associated to the momentum of the particle. The more momentum the particle has, the smaller the wavelength is. And this is problematic, of course, because it's not a fair description of the particle, saying that the particle is everywhere. But this makes perfectly sense and is consistent with the Heisenberg uncertainty principle, because if you think about it, defining this wave function, we are saying we have an infinite precision on our determination of this momentum here. We know exactly, without an error bar, without an uncertainty, what is this momentum, what is the momentum of the particle. So for the Heisenberg principle, in which the uncertainty on the position of the particle times the uncertainty on the momentum of the particle must be something like, or must be bigger than h bar over 2. This is the Heisenberg uncertainty principle. We see that if this thing here is 0, this can only be infinite for this to be bigger than some quantity. So the uncertainty on the position of the particle is maximum. What we have in reality is never that we know exactly with infinite precision where the particle is. So how we describe a particle which we don't know with infinite precision what is the momentum of this particle? Well, let's suppose for a moment that we have a particle that can be in three different states of momentum: P1, P2, and P3. Let's say there is a physical reason. Sorry. Let's say there is a physical reason for the particle to be only in these three states of momentum. There is no physical reason for a particle to only be in three states of momentum, but let's say it for a moment. How do I describe this particle? Well, Feynman tells us you have to sum every amplitude that describe processes that you cannot distinguish physically. So if I cannot distinguish a particle being in the momentum P1 or in the momentum P2 or in the momentum P3, I just have the total wave function for this particle, which will be phi of x t equal to the wave function for the particle in the momentum P1. Let's drop for a moment this part of the energy we are not interested in. So this will be n1 or n of P1 e to the I over h bar P1 x. Then I will sum this is the amplitude of the particle being in a state of momentum P1. Then we have another amplitude, which is normalization factor, which depends by the momentum P2 of the particle, e to the I P2 x is over h bar, plus the third possible momentum, which is n of P3, e to the I P3 x. Okay, so these three are three independent, we can say, wave functions that describe the particle being momentum P1, the particle being momentum P2, and the particle being in momentum P3. I have to sum them according to Feynman because I don't distinguish the particle in which momentum the particle is. But this sum, in a more real case, I don't know whether the particle is in one of these three momentum or in one of the infinite possible momentum which are between P1 and P2, or P2 and P3, or bigger than P3 or less than P1. So what I have to do is to include every possible momentum, and the sum of infinite pieces in quantum physics is just an integral. No, not only in quantum physics. In physics, in mathematics, everywhere, the sum of infinite pieces is just an integral. So phi of x t, this will be an integral we can do from minus infinite to plus infinite. And then we can associate, you see, this normalization factor is something that depends on the momentum p of the particle. So the integral will be over the p, and the normalization factor, we can call it a function of p. And let me call it psi of p, okay? And then, in this case, we'll have e to the I over h bar p times x. Okay, and you see that now we have something that it's much more physical. First of all, this object here, the wave function described in the momentum space, is the Fourier transform of the wave function described in the space, in the normal space. And then this is an infinite sum of plane waves. And as you know already, probably from some other physics course, when I do a sum of infinite plane waves, in which at every plane wave there is associated a different amplitude, a different normalization factor or whatever, what I get physically is something like this. Now I don't know where to put it. Yeah, let's put it here. So I have x, And then I can have the wave function, so the sum of infinite plane waves, that is something like this. So I have a wave packet in this case, a wave packet described by, So in this case I have a wave packet which has, you can see, a much more definite position, but the price I pay for having a particle which is in this position here, and I can say the particle is here in this point of x, is that I don't know, I lose information about the momentum of the particle. And this is again another proof, another, let's say, another manifestation of the Heisenberg uncertainty principle. So in one go, we saw the superposition of particles. This is the superposition of different wave functions with different momentum. And we saw the Heisenberg uncertainty principle. Not bad for a summary on quantum mechanics of about 1 hour or even less than 1 hour. Now it's time to see what is missing in the Schrödinger equation and why we have at this point to abandon our beloved Schrödinger equation and abandon our view, our quantum view, as it's written here, of particles. Fear not, because even abandoning our quantum view and everything that we learned, in reality everything that we learned so far, it's very, very useful when we will go to describe relativistic particles. So it's the relativity time now, it's the relativity time, and we'll see what is wrong in the Schrödinger equation. We talked about Schrödinger equation. We saw that the solution of Schrödinger equation is this probability amplitude that describes our physics and everything. And now we have to talk a little bit about relativity. We have to familiarize with this whole new theory which was developed separately from quantum mechanics. And now at a certain point we have to see if these two theories are compatible. So we try to apply the laws of relativity to Schrödinger equation and see if Schrödinger equation holds also and is compatible with relativity, and we find that these two things are not compatible. From this incompatibility we will see that the Dirac equation burns. Dirac which is something like this. Where this element here, psi, it's not a wave function anymore, but it's something completely different. In particular, it is a Spinor field, but we will talk about Dirac equation in a moment. First, we have to see what is relativity, familiarize a bit with relativity and the concept of relativity, and why the Schrödinger equation is not compatible with relativity. To do this, we take a very specific and simple example, which are rotations in two dimensions. So what happens if I change point of view? This is what relativity is all about. What happens if I look at my physics from a certain reference frame? This point of view, it's also called in physics reference frame. And I start looking at my physics from another reference frame. Is the physics the same? Does something change? In principle, we want our physics to be the same in the first and in the second reference frame. So the laws, a law that is well written, describes the same physics in both reference frames. Relativity in particular tries to explain how the law changes when I start to go fast. So if I am in a reference frame in which the speed is close to the speed of light, or it's, let's say, compatible with the speed of light, it's not much less than the speed of light, but we will start with a simple example, which is rotation in 2 dimensions, because in this way we understand two things which we have really to understand and familiarize with. The first one is the concept of invariance, and covariance. These two are very important. And the second thing to understand, and that we will understand in a simple case that is rotation in 2 dimensions, it's the notation. Notation in relativity looks something like this. If I want to change my reference frame, it's something like x prime mu is equal to gamma mu nu x nu. And if you don't understand what is this all about, I get you completely. It's very difficult because it's a completely different notation from what we use in normal physics, in quantum physics and in classical physics, but this will be the notation that we will use in relativity and also in particle physics. So it's better to go slow in this part, understand very well the notation, because then this is a good long-term investment, let's say. If you understand very well this notation here in rotation in 2 dimensions, so what we are about to do now, then you will understand this notation also for relativity, which is much more complicated, and you will understand this notation here also when we go in particle physics. So let's start with our rotations in 2 dimensions. The first thing is to define a reference frame, which this reference frame I call it epsilon, or actually this is sigma. Oh, talking in English and then having to try to remember what the Greek letter look like and sound like, it's very difficult, even though they are the same names as in Italian. But I don't know why, for some reason my brain doesn't connect the two things. This stuff should be called sigma, I think, which is the capital of this other sigma, which is the lowercase of this one. But okay, so sometimes I swap letter, but don't worry about that. Remember that what is written on the blackboard should be right. Okay, so I'm in this first reference frame sigma. I have a point here, which I can describe as a vector. And this vector, for example, is described in this reference frame with 2 coordinates, one which we call x and one we call t. In this case, one coordinate is the space of this point. This we can call it an event E, and one point is the time of this event. So when this event happens and where it happens in 1 dimension. Now what we want to do is to rotate this reference frame sigma, and yes, rotate it from with an angle theta. Now this will be our new reference frame sigma prime. I do it in blue so it becomes very, very easy to understand. This angle here is the rotation angle, and now I want to describe this vector, this event A, or this point in space and time, in the new coordinates, which are the coordinates of the sigma prime reference frame. And in this case, I can just do this. So x prime will be this. For now, we are rotating some time coordinates, so you might be wondering what is this rotation of time coordinate. Don't worry about this, even if it seems strange, it's just for the sake of the example, and then we will see that in relativity things will be even more strange. But yeah, for now this is t prime. So t prime and x prime are how I describe this event E in the new reference frame. T and x are how I describe my event E in the first reference frame. But as you can see, even though I use 2 different coordinates for describing this event, the position of this event in space and time did not change, okay? So now we see what these transformations look like. So first of all, I can write the coordinates of E in the first reference frame as, let's do it here. So it's a bit more clear, but I always lose this. Okay, yes. Let's do it here. So these are the two concepts you have to remember, but for now, okay. Let's start with the reference frame white, the white one, without the prime. So in this case, I will describe the position of this event E like Tx, and I use this notation in which I have a column vector in which the first component is the time component and the second component is the space component. This I can also write like this, the time and 0. So a first vector which is a unit vector. Let's do it in orange so it's easy to understand. This vector here describes this. So a vector which is only in the direction of, in the axis of the time, and the component on the axis of x is 0, plus another vector which will be, you already know, this one. So a vector which is only on the x component and his component on the t-axis is 0. So in this case it will be plus 0x. Now I want to know how this thing look like in the sigma prime reference frame. So I will say that the vector t prime x prime will be equal to, well, first of all, I have to transform this vector here in the new reference frame. And if I transform this vector here in the new reference frame, this is the t vector, you can see that t in the new reference frame, it's something like this. So this orange vector here, transformed, will be a certain t prime. So will be a certain component of this vector get projected on the t prime axis, and the part that gets projected on the t prime axis, if this is the angle with which I rotate my reference frame, the part that gets projected here will be t times cosine of theta. So this will be t cosine of theta, and then there is also a part of this time axis that gets projected on the x prime axis, which will be this component here. Do it in orange, okay. Yes, and in this case, this, you see that it goes negative in the x prime axis, and this angle here is theta, so this projection here is with the sine of theta. So in this case, the projection of the t vector on the t prime x prime axis will belong t sen theta. We do the same for the x vector. The projection of the x vector on the x prime axis will be something like this. So x sen theta is the projection on the cosine theta. So this is the projection of x on the x prime axis. This is negative. We said it, but we didn't put the minus sign. And then the projection of x on the t prime axis will be something like this. And will be x times sine of theta. So if a new, let's say, if I change my reference frame, the new way in which I describe this event E will be transformed, will be mapped on the old reference frame using this cosine of theta and sine of theta. This thing we can also now combine, so this vector here can also be written as t cos theta plus x sin theta. Or can, and the second component will be x cos theta, or better to put first the t component. This will be minus t sin theta plus x cos theta. Okay, and this will be equal to t prime x prime. Perfect. Now we are getting there. We are getting to the relativity notation. For now, all what we did was very normal and very easy classical physics. Now we have the change of notation, which will not add new informations, but will just be, let's say, will just compactify our notation. I cancel this, and then let's see what happens. Okay, this thing here is important, and I can also write this thing here using some matrices. For example, if I want to describe t prime x prime, this is a two-component vector, which is also equal to a certain matrix that will encode the transformation between t prime x prime and t and x, times a vector which is t x. And you can see, in this case, this component times t plus this component times x must give t cos theta plus x sin theta. So in this case, here we'll have cos theta, and here sin theta. And then we have the second two components of this matrix, in which x prime will be minus t sin theta plus x cos theta. So in this case, this component times this plus this component times this must give this part here. So here we have minus sin theta, and here cos theta. As you can see, this formula is very important, because now we have the coordinates of the point in one reference frame, in the sigma prime frame, the coordinates of the point of the event that we are trying to describe in the original reference frame, and then we have the transformation between these two coordinates, which describe rotation in b-dimensional space. What we do now is to indeed compactify the notation, and we can just call these two objects x mu. Sometimes if we are talking about, if we are not talking about relativity, these indices are not mu, but are, for example, alpha, beta, etc. But I think this is a bit, makes a lot of confusion, because then we swap indices, but indeed the mathematics is exactly the same. So conceptually it's different physics, but I think since the mathematics is the same, let's use already the indices that we will use then in relativity. So this one will be x. Also, let me keep the color code so it's easier to understand. This one will be x prime mu equal to lambda mu nu times x nu. In this case, we have this weird notation in which, okay, let's keep this and let's see what does this notation mean. Yes, we have this weird notation, but this weird notation, it's simply like, as you can see here, these two indices are the same index. So in this case, we say that the index is contracted. And when two indices are the same, one is down, one is up, in relativity, in the notation that we use, we are implying a sum between these two indices. In this case, what do we have? We have that x prime 0 is equal to t prime. So that zero component of this vector is equal to t. X prime 1 is equal to x prime. Okay, so the one component of this vector is equal to x. The same holds for these ones. So x nu 0, x0 will be t, x1 will be x, and then these objects here are the elements of this rotation matrix. For example, lambda 0, 0 will be this element here. Lambda 1, 0 will be this element here. Lambda 0, 1 will be this. Lambda 1, 1 will be this. And the sum over the indices means that if I want, for example, the x0, this one, let's skip the blue, x prime 0. This will be lambda 0, 0, x 0, okay, plus, because these two are contracted, so we have to use 0, and then the sum also use 1, plus lambda 0, 1, x 1. And in this case, with this weird notation, but we know that lambda 0, 0 is equal to cos theta, lambda 0, 1 is equal to, let's say, this is not a prime, but is a 1. Otherwise we get confused. And this x1 is indeed x. So in this case we have t prime, which is x prime 0. Now we are just doing translation, but it's just to familiarize with these formulas, because then when we go to relativity, I know that everyone is always very confused by these formulas. So we are going very slow here, but forgive me if I'm slow, forgive me if it's boring or something, but trust me, it's so important that we cannot skip this part. Lambda 0, 0 will be this first component of this matrix here, so it will be cos theta. x0 will be t, because it's the first component of this vector here, plus then lambda 0, 1 will be sen theta, times x1 will be the second component of this vector, which is x. Okay, so as you can see from this simple notation here, this one, we compactified the information that there is here in this system of equation. So whenever you will see something written like this, this is a compact notation, but what is going on, the calculations are going on under the hood, is that we sum over all the contracted indices, and then we get the transformation between the coordinates in one reference frame to the other reference frame. So in this case we have the transformation between the coordinates in the sigma reference frame to the sigma prime reference frame. And as you can see, we recover, in this case, the information about the first component. But if we want the information about the second component, and I invite you to try, you just compute this x prime, not the 0 component, but the 1 component. So in this case will be x prime 1, and will be exactly the same formula, but in which instead of 0 in this upper index here, we put 1. So if this is 1, here is the same, but instead of 0 we put 1, not here and here. Okay? And this gives us the transformation of two-dimensional vectors. This is very important, and then we can, now we saw the notation in relativity, now we can talk about invariance. Let's continue using these two-dimensional rotations to explain the invariance concept. Now let's talk about the two concepts that we have to explore in relativity, which are 1, invariance, and 2, covariance. And we do always in the case of a two-dimensional rotation of our axis. In this case we have the first reference frame in which I describe a certain point here, a certain event, or a vector, as I can call a vector. I do it in orange so to know that this vector is the same. It's not that this vector changes. What changes is the description that I give of this vector in different reference frames. So if I describe it in xt, is different if I describe than if I describe it in x prime t prime. Okay, so I rotate my reference frame. What is the invariance? Invariance are, there is something, always, that when I apply a transformation, this quantity, this invariant quantity, are the same in one reference frame or in the other reference frame. For example, in this case, in the case of rotation, you can verify, but also intuitively, it's very easy to see that the length of the vector is always the same. So if I compute the length of the vector, this vector I can call it v, okay? V with a vector symbol. Or also the squared length of the vector, so the scalar product between v and v, okay? In this case, it will be, in this case, in the xt reference frame, the coordinates of this vector will be x and t, and the scalar products will be xt times x. Yes, we swapped before, so let's put t before and x later, and the lx as last number. So tx scalar product tx. This will be t squared plus x squared, and this is the length of the vector squared geometrically. If I compute this same quantity in the other reference frame, in t prime x prime, this quantity will be exactly the same. So t squared plus x squared is always equal to x prime squared, t, let's put t first again, t prime squared plus x prime squared. So this length of the vector is said to be invariant under rotation of our reference frame, okay? What is covariance instead? Covariance is a bit more difficult to understand, but it does a lot of logical sense. Covariance is that the formulas that describe our physics must be covariant. That is that both sides of the equal sign must transform in the same way. Let me explain. For example, let's say that we have Newton's law, F equal m times a. So this means that we will have a certain vector force which is in the first reference frame. Let's say that now this vector v becomes a force. Okay, so we describe a certain force acting on something in the reference frame x and t. And the Newton law says that this force is proportional to another vector, which is the acceleration of this particle times the mass of this particle, for example. So we will know that there is another vector in the same reference frame, which is something like this. It points in the same direction. It's or shorter or longer, it depends by the value of the mass, but is proportional to this vector f. So we have these two vectors, a and f. Now, what happens if I go to the first reference frame? So this is the law that I use to describe my physics in this reference frame. What happens if I go in this reference frame? Well, in this case, the vector a and the vector f will change. So they will not change physically, but the description I give of these two vectors will change. What has not to change is the physics of the problem. So the covariance, saying that some formula is covariant, is equal to ask that formula, both parts, the right-hand side and the left-hand side, transform in the same way. And in this case, you see that this formula is covariant for rotation in b-dimensional space. Now, I have a doubt that covariance is only used for Lorentz transformation that describe relativity, transformation that we make in relativity, and maybe here covariance is not the right term, but who cares? You get the concept, no? Covariance is something that, covariance is, an equation is covariant when both sides transform like they transform in a right way, let's say, so that the physics of my problem, the physics described by my formula, is the same in both reference frame. Also here I repeat a lot of time because this is so important that if you don't understand covariance, we cannot go. We cannot go to make particle physics. Now, let's translate this concept in relativity. Now, the plan is to, plan for now, see what are the transformations in relativity, which are called Lorentz transformation. These are the analogous of this two-dimensional rotation, but the transformation that we apply in relativity. Then 2, we will see covariance and invariance in relativity. These two will be very easy because now we have built all for this rotation system, and will just be analogies with what we already did. And then 3, this is the interesting part that comes, will be to see an example of a formula that is well behaved in relativity, which are Maxwell equations. This will be very fast. This plan here will not take much time, and then this formula here will be okay, so covariant and compatible with the relativity form, and then we will see that the Schrödinger equation it's unfortunately not covariant. So the Schrödinger equation does not describe the same physics if I start to go fast, let's say, in a sense. So if I change my reference frame and I swap to a reference frame in which the velocity of that reference frame is different, Schrödinger equation does not describe anymore the same physics that used to describe in the original reference frame. So this is a problem, and then solving this problem will lead us to particle physics in the modern terms. But let's do one step at a time and start with the analogy between this rotation in 2 dimension and Lorentz transformations. So to the rotation, it's very intuitive what this transformation is. Lorentz transformations are transformation between 2 inertial reference frames. Inertial means that they go with a constant velocity, a constant speed. How do they transform? How do I transform from a reference frame to another one? Well, this is a product of the principles of relativity, and we have the principle that the speed of light is the same in every reference frame. That means that if I'm still, if I'm not moving, and you are going very fast, you are going 0.5 times the speed of light, you and me see the speed of light exactly the same speed. So if we measure the speed of light, we find the same value. This gives rise to every sort of strangeness, because as here wasn't a physical, we thought it wasn't a physical situation in which we rotate time. What does it even mean to rotate time? And we see that some of the component of x and time in the first reference frame get mixed, and in the second reference frame I describe space and time in a different way, mixing the space and time of the first. Well, in Lorentz transformation, that is exactly what happens. In the first and second reference frame, the space and time get mixed. So I have time coordinate, space coordinate, and what happens is that light take this trajectory for everyone, in this case with c equal to 1, so with the speed of light is equal to 1. Light, the trajectory taken by light is a 45-degree line, and the other reference frame, it's something like this. It closes in a way like this. And the transformation between, so also in his reference frame, light has exactly the same velocity as in my reference frame. Now, the transformations, we already saw that in rotation, in this case, are described by a matrix that is cosine of theta, sin of theta, minus sine of theta, cosine of theta. This is always in 2 dimension. Of course, in relativity we will then go to 4 dimension, but let's keep 2 dimension now to make it easier. In relativity we describe the transformation with this lambda, Lorentz transformation, lambda mu nu, this will be equal to, okay, well, this is weird because, yeah, let's call it lambda mono. And this is equal to gamma minus beta gamma minus beta gamma gamma. These are the transformation between x reference frame and x prime reference frame, such as x prime, so an event described in the reference frame prime, so in the blue reference frame, will be equal to lambda mu nu times x nu. So this is the relation between an event described in the prime reference frame and an event described in the normal reference frame, let's say, in the original reference frame. And this very we could stay here and talk for an hour about this transformation, but we use this mathematically in perfect analogy on how we use this. So we already defined everything in a simpler frame. This is the same mathematics. So this is the transformation, and gamma is equal to 1 minus beta squared to the minus 1/2, which will be 1 over the square root of this quantity, and beta is just the velocity of my reference frame divided by the speed of light. In the case in which the speed of light is equal to 1, beta is just the velocity of my reference frame. Okay? Very good. And now the plot twist comes, because the invariant quantity between a transformation, two reference frames that are rotated one with respect to the other, is not the same as the invariant quantity in a transformation in which the two reference frames are modified in this way, one with respect to the other. So in this case, the invariant quantity, as we saw, was the vector squared, for example. But in general, more in general, if I have a vector A which is equal a component on t and a component on x, and a vector B which is equal to a component on t, so b t a b x. In this case, the invariant quantity will be the scalar product between these two vectors, which I define like a times b, and this is equal to at times bt plus, let's do it white, plus ax times bx. Okay, this will be the invariant quantity in this reference frame. In this case here, the invariant quantity is always a scalar product, but we define the scalar product in a different way. So we call the first vector, we call it a mu, which is equal to, we can say, a0. So the 0 component will be the time component of the vector a, and the second component will be ax. This can be generalized in 4 dimensions, simply saying that the 0 component of the vector is always the time component, and then I have ax, ay, az, and in this case I can also write something like a0, a, so that I know that this is the time component of the vector, this is the space component of the vector, which is 3-dimensional. Then I have another vector which I call b mu, equal to same b0 b, in which this b contains all the space component of the vector. In this case, the invariant quantity turns out to be the scalar product of these two vectors, but defined as this. Let's do it blue again so we don't swap everything. A mu b mu. This is important. This remind that this is lower index, is equal to a0 b0 minus a scalar product b. So this will be a0 b0 minus ax bx minus ay by minus az bz. Okay, this is very important because now we have an invariant quantity in relativity, an invariant quantity with respect to Lorentz transformation. In other words, if I have this quantity in a reference frame, in the white reference frame, I apply a Lorentz transformation, then I recompute this quantity with the first reference frame, so with the blue reference frame, the quantity, the number that I get is exactly the same. So this is invariant. Okay? Very, very important. Take a screenshot of this because this is the analogy between 2D rotation and Lorentz transformation. Now we see a little bit, we play a bit with these elements. We see how do we construct Maxwell equations, so we familiarize a little bit with this formalism, and it's very, very interesting, and then we will recycle everything that we do in Maxwell equation for particle physics, and we have amazing things ahead. I can't wait. Just a little clarification, here I draw the A vector in blue and the sigma prime reference frame in blue, but this has nothing to do. Probably it's a bit confusionary, but and this vector, imagine it orange or something, because this is not in the first reference frame, and this is the, like, they are not defined in two different reference frames. They are in the same reference frame, but it was just to visualize the scalar product, how does it work. So also in this case, I should put this blue and this blue. But blue does not mean in the x prime reference frame, just means that is another vector. Let's see some concept in special relativity, since we will have to use these formulas. First of all, we saw that the Lorentz transformations are something like this in 2 dimensions, something like lambda mu nu equal to gamma minus beta gamma minus beta gamma gamma. This is in 2 dimensions. If I want to go in 4 dimensions, so like this Lorentz transformation describes the transformation between 2 reference frames, one moving with respect to the other with an 2 inertial reference frames, so one moving with a constant speed with respect to the other in a certain direction. If I'm in 4 dimensions, so I combine space and time. This is very important. Why I want to use 4 dimensions in special relativity? Well, because as you can see, this transformation transforms time into space and space into time in the two when I change reference frame. So it mixes space and time. So space and time must not be a separate object anymore, and is why we define a vector x mu like tx. More in general, in 4 dimensions, and also here, as you can see in normal physics, this t and this x have 2 different dimensions. So if we want to keep the normal units, here there should be a c, which is the speed of light, so that this object and this object has the same dimension. But in this case, we will work in the reference in the natural unit, in which c, which is the speed of light, is equal to 1. In this particular unit, t and x, so the time and the space, have the same dimension, and so we don't need to specify this c here. Now, if we are in 4 dimensions, what happens is that the Lorentz transformation, the lambda mu nu is equal to, is the same object, but a little bit more big, a little bit bigger, because it's like this. This is the Lorentz transformation in 4 dimensions, describing 2 different reference frames, one moving with respect to the other only in the z direction. So these 2 components, x and y, do not get mixed. Then we can define our usual 4 vector x mu as tx, in which x in this case is a vector and it encodes all 3 dimensions. So this will be something like t x, y, z. This is our notation. So this is in 2D, simple example. This is in 4D, full relativity. Then since we saw that the objects like x mu equal t component, for example, in this case will be t squared minus x squared. This is a invariant quantity, so it's the same in every reference frame. And here there is a minus. It is convenient to define not only this vector, which is called contravariant vector, but also this vector with the lower index, which is called covariant vector. This is very, very convenient, because if I do simply x mu times x mu, what I get is simply t squared plus x squared, which, as you can see, it's not covariant, it's not invariant. So this object here, if I compute it in a reference frame, then I change reference frame, this object, this number that I get is not the same number anymore. So to get the covariant, the invariant object, I define the covariant vector. So in this case we have a contravariant vector. Or 4 vector, which is x mu. I can define the same object, a vector, but covariant, which is called x mu. And in this case, let me erase this part. In this case, if the contravariant vector, I define it as t, the first component is space, is time, and then a 3 vector with space components, this vector here is defined as t minus x. And in this case, when I will do x mu times x mu, this will be equal to x mu with lower index times x mu with upper index. And this is a invariant vector, so this will also be equal to x prime mu, x prime mu. The generalization of this rule is that in this case we just defined the 4 vector of space-time 4 vector, but this is true for any scalar product between two 4 vectors. This is always Lorentz invariant. And what we are interested now in is to define other vectors that are contravariant or covariant, and in particular the vector of derivatives. For example, we have that we can derive what happens if we other stuff before the derivative vector. It's transformation in explicit way. Okay, explicit transformations, it's easy to see that, for example, if I want x prime 0, this will be t, okay, t prime. So the time in the reference frame prime in this case will be gamma t minus beta x, beta gamma x. So in this case will be gamma t, in this case x3, it's not equal to x anymore, but is equal to z, because it's the third component of the space vector. So this will be minus beta gamma z. Then x prime in the first reference frame will be, we are always using these transformations here, of course. So x prime mu equal mu nu x nu. So x prime in this case, since here there is a 1 in this matrix, this is simply equal to x, so x and x prime do not change. Y prime, which is also equal to x2 prime, is equal to y also, and then z prime, this is equal to gamma z, yes, minus beta gamma t. And these are the explicit Lorentz transformation between two reference frames in 4 dimensions, in which one of the two moves along the z-axis with a constant speed. With these explicit transformations, is useful to define also a 4 derivative. So we defined the 4 vector of space-time, and now we define the 4 vector of the 4 derivative vector, which we call demu. And this will contain the time derivative, so d over the t, and all the spatial derivative. Spatial derivative, which will be also, yes, we can define this vector as d over dx mu. So as we said, time derivative and space derivative, which is d over dx, d over dy, d over dz. All this we are defining because then we will have some solid knowledge about how to go and how to make calculations in our theories. This part here, as you can recognize already, it's also equal to the nabla operator. Nabla, how is it called? I think, yes, nabla operator, let's call it nabla. Yes. The name is not important. The fact that is that this operator here, it's derivative with respect to x, with respect to y, and with respect to z. So it's exactly this part here. So this we can also call it d over the t, and then this operator. Okay? Then we can define the... Okay, this is very important, very tricky. A lot of people fall here, but it's very important. This 4 vector here, we define it with a plus in this case and not a minus, but it is contravariant, it's not covariant. So it transforms with this matrix here. Because as you can imagine, the vector defined with the minus here will transform in an opposite way. Will not transform with this matrix here, but will transform with a matrix which is something like, and we call it, the convention is to call it mu nu. So the first index is low and the second index is high, as opposite to here, in which the first index is high and the second is low. And this will be a transformation in which it is exactly the same as this transformation, but here we have plus beta gamma, plus beta gamma. And this is just to take into account the fact that this minus sign is now defined in the vector part and not in the Lorentz transformation part. So just to be clear, let me erase a little bit and reorder everything so we can have a clear picture. So, recap. We defined the 4 vector contravariant form equal Tx. This is contravariant. Then we define the covariant form T minus x Okay. We define the Lorentz transformation in 4 dimensions, but let's see just how do they transform. This guy here transform, let's put only 2 dimensions since the velocity is only on the z-axis. These guys transform like equal to gamma minus beta gamma minus beta gamma gamma, so that a transformation of this vector here will be t prime x prime equal all this matrix here times tx. So now the covariant vector has this minus here. So in this case, we define the covariant vector as the same vector, the same column vector as this, but with a minus here. So if the minus goes here, this for it to transform in the proper way, this minus here must go away. So you see that the covariant vector, sorry, it transforms with another kind of transformation, and we define as notation this other kind of transformation with a lower index first and an upper index second, so mu nu, and this transformation is the same as before but with plus here, beta gamma, gamma, and you can convince yourself, as we define gamma and beta, that this transformation here times this transformation here is equal to 1, to unity. Okay? Not even... No, this is a sum. I don't want to sum them. I want just to do a matrix multiplication. This transformation is the opposite transformation of this one. So they are opposite transformation, and the multiplication between these two transformations gives me 1. Okay? Now we do the same thing with the derivative. So we define a derivative which is contravariant. No, sorry. Let's first define it and then understand who is contravariant and who's covariant. So the mu is equal to d over dx mu. This is an object which is defined like dt, so d over dt, and then this operator here with the plus here. This defined as the plus as the contravariant vector, but is not contravariant, but is covariant. It's very confusing. I know it's tricky, but that is what it is, and you can try to see how the derivatives transform using the explicit notation of x and t as we write them before, but we will not look into that, but this is something that we must pay attention to. So then we define the covariant derivative, which is, I mean, this guy here, no, sorry, this is covariant derivative, even though it has a plus here, and then this is the contravariant derivative, and is something like this, and this is derivative with respect to time, and minus this operator, so the derivative with respect to space, okay? And this object here transform with this matrix here, okay? So they are swapped in a sense. This transforms with lambda mu nu, and this transforms with lambda mu nu. Okay? Very good. We defined all this stuff here because now we want to define... another stuff we have to define first before going to the Maxwell equation is this operator, which is called the metric tensor. So we defined 4 vector space-time, 4 derivative, and now how do I pass from a vector which is covariant to a vector which is contravariant and vice versa? I simply do something like this. X mu is equal to eta mu nu x mu eta mu nu x nu. So in this case, when this index here is contracted, I multiply by this object eta mu nu, and I lower the index. So when I have a high index here, for lowering the index, that's it. So in this case, eta mu nu, since the vector, we already know which is the relationship between the covariant and the contravariant vector, we have a very easy time to define this object, and this object is equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Okay? In this way, these are the relationship that we want and we get. And this object here is called the metric tensor. So I can pass between covariant and contravariant vector multiplying by the metric tensor. Then I can do all sorts of computations. What I'm interested in is, again, we are interested in invariant quantities, so quantities in which I have a lower index multiplied by the same upper index and vice versa. And then we are interested in covariant formulas, covariant equation, because covariant equations are the things that describes our physical law in a good way. For example, Maxwell equations are covariant. And now we will go to see how Maxwell equations are covariant and see how Maxwell passed the test of relativity, which is a test that Schrödinger unfortunately will not pass. Chalk. Yes. So let's discover together if Maxwell equations pass the relativity exam. First of all, we write down Maxwell equations. We have 4 equations for electromagnetism. These usually a physics student or engineering students already know these equations, but let's call it. So we have divergence of the electric field is equal to rho, which is the density of charge over epsilon 0. This epsilon 0 is a constant, and in this case we'll have mu 0 equal epsilon 0 equal 1 in our notation. Now let's write them down for completeness, but then we will remove these two constant mu 0 and epsilon 0, so we don't care much about what they are. And also in there is this relation in which mu 0 epsilon 0 is equal 1 over c squared, but also in this case we put also c equal to 1. So they are separately equal to 1, and also c is equal to 1, so of course their multiplication will be equal to 1. Okay? So in this case we say that the source of the electric field is the charge, electric charge. Then we have the divergence, the curl, the curl of electric field minus the derivative with respect to time of the magnetic field is equal to 0. Then we have the divergence of the magnetic field is equal to 0. This means there is no source, there is no how do you call magnetic monopole, we can say, but there is no source of the electric of the magnetic field. But the magnetic field, the source of the magnetic field, it's moving current, moving charges, so currents. So we can say that the curl of the magnetic field minus or plus mu 0 epsilon 0, the derivative with respect to time of electric field is equal to mu 0 j. So in this case, rho is the charge density, j is the current density. So when I have a charge that goes with a certain speed, I have this j. When I have a charge which is still, I have this rho. Rho is the source of the electric field in a sense. J also in a sense is the source of magnetic field. That means that I have magnetic field only if charges are moving, only if charges are going around. And you see why this must pass the test of relativity. This must pass the test of relativity because if I have no charge, for example, if I have no current, I have no magnetic field. But then I start running, so I change reference frame in which I start go fast. But if I go fast, at this point, yes, I have a current, because what was first a still charge, a still electric charge, then it becomes a current. And then if I run, I see a magnetic field. So that means intuitively that magnetic field and electric field should be the same object. So we write this equation down in the relativity notation in such in a way that we can then define and test if these equations are or are not relativistic invariant, relativistic covariant, let's say, Lorentz covariant. I'm very starting to getting confused, but you get the point. This equation here now, we cannot say if they are covariant or not because we don't know. They are in a form in which it's not manifestly covariant, let's say. We have to write them down in a form which is manifestly covariant. And we have to build objects which are relativistic objects. The first thing we have to do is to put everything to 1. So in this case, this epsilon 0 go away, this mu 0 epsilon 0 go away, and this mu 0 go away. And we simplify already a lot Maxwell equations. And then we have to collect objects in relativity. So in relativity we know that we just built an object which is x mu, which contains time and space. And with this object, these two entities must be together in the same object, because we see that with a Lorentz transformation they get mixed. But what else get mixed in a Lorentz transformation? Well, first derivative, of course, this also we already defined, d over dt, and then spatial derivative. What else gets mixed? Of course, current, electric current and electric charge that gets mixed if I go fast. So we can define a 4 vector of current, which is ρ in the first component. So it has charge in the first component and current in the second component. And then what else gets mixed? Of course, electric field and magnetic field. But electric field and magnetic field, there is a huge problem, not so huge, but there is a little problem, that we cannot combine them in a 4 vector, because magnetic field, it's something like B equal explicitly bx, so a x component, a y component, and a z component. So it contains 3 elements. Electric field E is equal to Ex, B, Ey, Ez. So also electric field contains 3 components, and in total these two objects that should get mixed in relativity contain 6 components, and I cannot fit 6 components, as you can see, in a 4 vector. So we define these 3 objects here, and we have to define another object that has 6 components, and the smallest object in which I can fit 6 components is a 4x4 matrix. So I construct this 4x4 matrix, and not only a 4x4 antisymmetric matrix will have 6 degrees of freedom. And as you can see, we construct this object f mu nu, which is equal to, now let's see if I remember, 0 on the diagonal, minus Ex minus Ey minus Ez. Then we have Bx, By, Bz. Here there is a minus, 0, 0, 0. As you can see, now all the 6 components have been put inside this tensor here, which is a 2-index object, and then to have the same degree of information, I just re-put this 6 components in this part of the matrix, but changing the signs. So I have Ex, Ey, Ez, and here I have Bx, Bz, By, and in this case I change the sign like this, and in this case, so I have all my objects that I need to build relativistic Maxwell equations. So these are all objects that in some way are suitable for being put inside formulas which are relativistic. This f mu nu here is a very peculiar object. First of all, as we saw, is antisymmetric. So if I exchange the 2 indexes, f mu nu is equal to minus f nu mu. So if I pick this component, I know exactly what this component is. It's just the same component with a minus sign on top. But even more important is how do I transform this component in a reference frame. So in a reference frame, this component gets transformed like this. I put it here because it's very important, and I will keep it. F prime mu nu. This is equal to gamma lambda mu alpha, lambda nu alpha, f this beta, f alpha beta. So as you can see, it does not transform with a single Lorentz matrix, Lorentz transformation, but you have to multiply to this object, you have to combine this object with two Lorentz transformations. This object in particular is not a vector, but is a tensor with two indices. Okay, so we have this tensor now, we have space for vector, derivative for vector, current for vector, and in this case you can just verify by yourself that the Maxwell equation can be written in this form that I will now proceed to write. Okay, I have written a bit this tensor that we want to use and the Maxwell equation, and now you can verify by yourself that if I take the derivative, the fourth derivative of this tensor, the mu f mu nu, this, and I put this equal to j mu, where of course the fourth derivative we defined as derivative with respect to time, and then all the derivative with respect to space, and then we have j mu defined as rho, and then the electric current. We have that this equation here is in a form that describes the first Maxwell equation, so this one, and the the fourth Maxwell equation. This describes 1 and 4, which are the Maxwell equation which has a source. Okay. Then, if I want to describe this Maxwell equation here and this Maxwell equation here, the form, the way I describe them using these objects here is simply the mu f rho sigma plus the sigma f. Here I just making the indexes go around. Sigma mu rho plus the rho f sigma mu equal to 0. And this equation here describes the 2 and the 3. So this one is 1 and 4, this one is 2 and 3. So I can write Maxwell equation. These two objects here contain exactly the same information of these four equations here. They are just written in a way which is relativistic covariant. And in a moment we will see what does it mean that is covariant relativistically. So it's Lorentz covariant. But these two here contain the same information as these four here, are the Maxwell equations. Now, it's clever, before seeing the covariance of this object, to define something which is more fundamental than this f mu nu object, and something that we will use in particle physics and identify as the photon field. In particular, what one can do in electromagnetism is to define this object, or better, these two objects, one being the scalar potential and one being the vector potential, and then define electric field and magnetic field as function of these two objects. In particular, I can define the curl of A equal B. So if I take the curl of this object, I get the magnetic field, and if I take the divergence of the scalar field, the scalar potential, minus, I think, now I check, the derivative of the vector potential with respect to t, I get the electric field. Now it's time, the time has come. If you don't know what this object is, the curl is, haha, very, very bad, but no, I'm joking. We will now define what is the curl, even though we were talking about it a lot, but there is a little trick to calculate the curl of something, which is simply say something like x, y, z. Then I have here, I want the curl, so this is the x, the y, the z, and then I have ax, ay, az. If I want the b component of the x component, so this component of the magnetic field, so I will have bx. In this case, I have to take these two objects and do this times this minus this times this. So in this case, the x component of the magnetic field with respect to the vector potential will be the y a z minus the z a y. The same I can do with y component. With the y component, I have to take these two columns and do the z times the x, like this times this minus this times this. So I will have by equal to the z a, okay, the z a x minus the x a z. You can try the same with bz, but as you can see now we have three components of the magnetic field written in terms of the three components of the vector potential. Now in relativity, also vector potential and scalar potential get mixed. We can put them together in the same vector, which we call a mu. This is a vector field now and has as time component the scalar potential and as space component the vector potential. Now we define this vector potential and we want to see how this vector potential is related to this f mu nu object. This is super helpful because in this case we will have an object which is fundamental, which is this 4 vector, and we will not keep around a tensor which is not fundamental in this case. So the tensor, this tensor in 4x4 matrix is defined in terms of this vector, this 4 vector, as f mu nu equal to the mu a nu minus the nu a mu. As you can see, there is a very close similitude between this object here, which is the magnetic field in terms of the vector potential, and this object here, which is the tensor f mu nu in terms of this vector, this 4 vector potential. Okay, and in fact, if you can see, minus bx is this component here, which is f 32, and in fact b is equal y is the second component, so this will be the 2a3 minus the 3a2, but this is minus x, so this will be exactly this component, and we verified that in one specific case for bx this relation holds, and you can try to verify that this relation holds also for all the other components of this tensor. But now we have the tensor written in a form written as dependent by a four component vector, which is a fundamental object. What do we do with this fundamental object? Why we are interested? Well, because there is a super good plot twist, which is that this fundamental object, this 4 vector, will describe a 4 field when we will go in quantum field theory, which if we excite that 4 field, that 4 component vector field, we will obtain photons. And this object here will be the responsible for the electromagnetic interaction, and so it's super important. There is another advantage also that we see now. So now defining with this 4 component vector, we have a very huge advantage, which is that we can define this tensor as a function of this 4 component vector, so I don't have tensors going around, and what becomes fundamental, it's not anymore the electric field and the magnetic field, but this stuff A. This was called vector potential in electromagnetism. In quantum field theory, this will be a vector field in all its glory and will describe the photon field. So this is the fundamental object. And we have two advantages. First of all, since the mu, the nu, a rho, for example, is equal to, swapping these two indices, the nu, the mu, a rho, since this equation holds, the 2 and 3, yes, these two Maxwell equations are a direct consequence of this relation here. So there is no need to make a second equation very weird with indices swapped around that we saw before. That is called the Bianchi identity. So we from this we simply derive that the mu f nu rho, this is in compact notation, the huge formula that we described before, is 0, and this is called the Bianchi identity. So this is the first huge advantage. Then second huge advantage, we can just, since this is the Bianchi identity, then the electromagnetism equation becomes only 1. And so the big advantage is that for seeing how this equation behaves when I go and make a transformation, I just need to check this simple equation, this single equation, and we will do now. So what happens if I go to the reference frame sigma prime as before, where sigma and sigma prime are related with a Lorentz transformation? Well, simply I will have a new equation, which is the first mu f first mu nu equal to j first nu. And now to see if this equation is covariant, we see independently how these three parts transform. So we will see how this part transform, how this part transform, and how this part transform. Okay, we already saw how this part transformed before. This is very easy because it's a 4 vector, so it transforms exactly like the 4 coordinate vector. This also we already saw how it transforms, so simply we write them down. First part, how does it transform? Transform like this. The first mu is equal to mu nu, the nu, okay. Then we have the second component, f mu nu. F mu nu transforms like this. F first mu nu will be equal to lambda mu alpha lambda nu beta, f alpha beta. And the third component, which is this j, will be j first nu. This will be equal to lambda nu beta j beta. Okay, these are the transformation of the single components, and now we are interested to see if the equation, the Maxwell equation, transforms in a Lorentz way. So let's combine this single component in the full equation, and we will have that first component will be lambda mu nu j. No, sorry, this is not a j, but is a derivative. The nu. Then we'll have the second component, which will be these two times f. So alpha mu alpha nu beta f alpha beta equal to how this transforms. So tac nu beta j beta. Now, since this is a sum, when we contract indices we have sum, not multiplication. Here we don't need to know if the matrices are commutative or non-commutative like in quantum mechanics, but we can just take the term around. And so we can already see that this and these two guys, yes, if this I call, also another thing in relativity is that you can just rename the indices that are contracted. So this index here, which is nu, I rename it to be alpha. So alpha, alpha. Okay, and as you can see now, we have mu alpha and mu alpha. So these two guys here, when I go to make the transformation, this transformation and this transformation, they cancel out. So these two I can simply remove from my equation. And as you can see now, if I move a little bit the pieces, I do it in this little corner. No, I do it here because it's important. If I now move this object here, I move it here, what I get is that lambda nu beta d alpha f alpha beta is equal to lambda nu beta again j beta. As you can see, here we have a Lorentz transformation, another Lorentz transformation, and then what we get if we anti-transform, so we go back to the first reference frame, is exactly the Maxwell equation that we had before. So this Maxwell equation, it's very well behaved and it's relativistic for his nature, meaning that the right-hand side, which is this one, and the left-hand side transform in the same way, and not only in the same way, but in a Lorentz way. So everything is okay with this equation. We did all this Maxwell equation business not only to familiarize with relativity, but also because this stuff will be super useful when we go to particle physics. But now, as last thing for this relativity part, let's see why the Schrödinger equation is not good and it's not covariant, does not pass the test of relativity. With the Schrödinger equation, we will not do all these calculations, but just follow some logical argument and see that is not Lorentz covariant. Let's, for simplicity, take just the Schrödinger equation in the free particle and one dimension. So this will be minus h squared over 2m d over dx phi xt. So why does this equation why is not good for relativistic for describe relativistic physics? Well, first of all, as you can see, we have a second derivative with respect to x and a first derivative with respect to time. So in this equation, it's very clear that time and space are treated as two separate and different entities. So we cannot find a way, trust me, like try if you want, but you can't find a way of writing this equation in as a function of the mu and x mu. These two objects here are not suitable for this equation. You cannot write this equation using these two objects. And this is already a symptom that this equation does not behave well in a relativistic context. So this is the first reason. These two objects can't be used. The second reason, which is related to the first one, by the way, is that x is an operator. This is not only for Schrödinger equation, but in general for quantum mechanics. The x, it's not a dynamic variable, but is an operator. It's something that can act on the wave function. As, for example, what we saw for the energy operator, for the momentum operator, for the Hamiltonian operator. All these stuff are operators that modify the wave function, while t is a variable. So they are really two different things. X space is an operator, t it's a variable. Doesn't work. And the third reason for which we really, this third reason of which we could notice already before, is that if you remember, how did we construct the Schrödinger equation? For constructing the Schrödinger equation, we used energy like this. Energy was equal to pi squared over 2, not pi, sorry, momentum squared over 2m. This energy here is not good because it's not relativistic. This is classical energy. So no wonder that if we build Schrödinger equation starting from the classical kinetic energy, we find something which is not relativistic. So the first thing to try for building a Schrödinger equation version, so a quantum mechanics formula, which is relativistic, is to try to swap this energy here with the relativistic energy. And the next thing we will gonna do is to compute the relativistic energy. It's very simple, but it's a result that it's used everywhere in particle physics. Then we will try to put this relativistic energy and build a new Schrödinger equation cousin or something similar to Schrödinger equation, but using relativistic energy and not the classical energy. And let's see where we can get and if we can get something useful out of it. But now I'm very tired and this will be a topic of the next lecture. So, what happens with the relativistic energy? We saw that Schrödinger equation is not covariant, is not Lorentz covariant, because we constructed the Schrödinger equation with an energy which is E equal p squared over 2m, and this is non-relativistic. So first of all, I don't want to give you the formula simply for relativistic energy, but we will go and derive the formula of relativistic energy. This is super nice because it's very easy, it's like one line, and it makes you familiarize with relativity principles. So in relativity, we see that x move, for example, we can combine time component and space component. This we can do also with the momentum. So the momentum and the energy in relativity, when we go and change reference frame, mix. And so we can define a quadrimomentum vector, which is called p mu, in which the first component is the energy of the particle and the second component is the momentum of the particle. This, of course, always using c equal to 1. In a minute, we will talk and we will be more systematic about this natural unit, putting c equal 1, but for now, let's just use this momentum. And in this case, we know that every scalar product between two four vector, it is a Lorentz invariant quantity, so it's the same in every reference frame. We try then to compute p mu. We know that this quantity here is the same in every reference frame for a particle, and in this case this will be equal to E squared, the energy of the particle, minus p squared, the momentum of the particle. This, it's a vector, okay? So, but then when we square a vector, this is not anymore a vector, it's just a number. But now we ask ourselves, what happens if I go in the reference frame in which the particle has zero momentum? So in the reference frame in which I travel with the particle, well, in this case, we have that p mu in the reference frame in which I travel with the particle is simply equal to mc squared. Also here I put the c squared just because this you recognize probably, but then with c equal 1 this will also will only be equal to m, and 0. Of course the momentum of the particle is 0. So in that case, in that particular frame, I have that p mu let's call it a prime reference frame, so P mu prime, in which the particle is at rest. In this case will be equal to m squared, because it's the energy squared, but also but the energy is equal to the mass, and this is the famous, very famous relation E equal m. See, I put in blue because then we will put equal to, we will set equal to 1, but this is the very famous relationship that we used, and this is the energy of the particle if the momentum of the particle is 0. So we have these two things, that in a random reference frame, this is the quadrimomentum squared, and in a reference frame in which the particle is at rest, this is the quadrimomentum squared, or the scalar product between the Lorentz invariant product between two quadrimomentum. Now we know, since this is Lorentz invariant, this piece here and this piece here must be equal, because P mu is equal to P prime mu, and so we have that E squared minus P squared must be equal to m squared. And so the relativistic formulation of energy must respect this formula here, E squared equal P squared plus m squared, where P is the tree momentum of the particle and m is the mass of the particle. And this formula is the relativistic formula for the energy. Now we will use this formula instead of this to build an analogous of Schrödinger equation, and we will see what comes out from that. But first, let's familiarize with the the natural units. You have seen that by now we have used many times, especially in relativity, c equal to 1. So speed of light equal to 1. This is equivalent to rescaling our units to make a better set of units. And I will explain it to you with an example. Let's say that we are in relativity, and what we consider always is speeds that are close to the speed of light. So it doesn't make sense to talk about meters in the x-axis and seconds in the time axis, because if I have the speed of light, for example, a particle, a photon, what a photon would look like in this graph here, it's something like this, in which, and also this is exaggerated already, it's much more down here, with 1 meter here, or better, no, 1 second here. So when 1 second pass, 1 unit of time pass, 300,000 kilometers have passed, let's say, in the unit of meter. Okay, so 1 unit of time corresponds to 300,000 times, okay, 3 times 10 to the 9th unit of space. Okay. You see that this is not a convenient system of units for talking about stuff that goes near or close to the speed of light or are compatible with the speed of light. So what we do, and what we did already, and you saw that we did this, is to set the path that light follows as a 45-degree line. In this case, 1 unit of space corresponds to 1 unit of time, and what we change in this case is time. In this case, this axis here is not declared in seconds anymore, but in c times t. This means that, and then we set c equal to 1. This means that we rescale this axis completely in a way that when 1 unit of space is traveled by light, this is done in 1 unit of time. Okay, so 1 unit of time now will be 1 second over c, over the speed of light. So 1 unit of time, it's now a fraction of 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 a second. In this way, the two axes are compatible, and this we do setting the speed of light equal to 1. So in this case, if I set c equal to 1, this axis I can simply call time. And another advantage is that, we have two advantages. The first advantage is that I have a better set of units, so I can really describe space and time in a proper way. And the second advantage is that I had two advantages very clear in mind, but now I don't remember them anymore. Okay, for sure the second advantage is that I can describe everything with the same unit. So with c equal to 1, this is almost a philosophical question, because with c equal to 1, the space and time have the same unit, and the unit is length. So both of them have unit of length. The first advantage is that, yes, of course, first advantage is trivial, and I simplify my formulas. Okay, so these are the two advantages of setting a better system of units, and this system of units is called natural unit. Now, what if I do my formulas and I find a time of, I don't know, 1 in our relativity frame, so a time of 1, which has unit of length, so it will be a time of 1 meter, for example. Well, of course, for going back to my usual system of units, I have to do time divided by c. I mean, no, I have to multiply that by c. Let me think about it. Time is in meter now, so for having seconds, yeah, this is just a dimension argument. So if time is in meter now, to have second, I have to divide by meter over second. So I have to divide by a velocity. So I have to take my time in meters, divide it by c, and I get the time in seconds. Okay? So this is the conversion between meter and seconds. The conversion between natural units and normal units that we use every day. Now, in particle physics, we extremize this to the maximum level, because we don't set only c equal to 1, but we set c equal to 1, h bar equal to 1, epsilon 0 equal to 1, and mu 0 equal to 1. Let me write it down. And the second advantage will change, because it's not anymore that space and time are measured in length, but we use a new unit for measuring space, time, and multiple other things. So what we use in particle physics is c h bar epsilon 0 mu 0, and possibly others, but these are the one that comes to my mind now. C h epsilon 0 mu 0 is equal to 1, equal to 1, equal to 1, equal to 1. Okay, this holds the same advantage, the same first advantage, so we simplify the equations. And the second advantage in this case, it's always that we use the same units for a whole amount of quantities, and in this case the same units are giga electron volt. So same units, and the units are GeV. Okay, an electron volt is a unit of energy, so 1 electron volt is equal to the kinetic energy of an electron passing through a difference of potential of 1 volt. through, I always have doubts on how to write it. I hope it's correct. Let's say passing through a difference of potential, so delta V equal 1 volt. Okay, so an electron passing through 1 volt, it acquires or loses a certain amount of kinetic energy, and 1 electron volt is this amount of energy. Okay, what we use in particle physics usually is not electron volt but giga electron volt. Giga electron volt is simply 1 electron volt times so 1 GeV is equal to 10 to the 9th electron volt. And this is because with 1 giga electron volt we can do computation in particle physics. This is more natural unit than simply electron volt, which is very, very, very tiny amount of energy. Now let's make a nice table in which we describe every quantity that we use in particle physics, their measurement, their units in terms of these 3 plus electron volt, and then their units in electron volt. And for this I need the fantastic book in which the table is. So I have all this quantity that I can describe as power of the energy. Energy, of course. So as you can see, here we have a table. If I want to measure, for example, a momentum with h bar and c not set equal to 1, I have that a momentum is an energy divided by a velocity, by the speed of light. And then when I set c equal to 1, of course, this becomes just giga electron volt without the c. If I want to measure a mass, I have GeV over c squared, same thing. When I put c equal to 1, it becomes GeV. In this case, as you can see, time and length has the same relation as before. So one is h bar over GeV and one is h bar over GeV times c, which is the same as before. The length is equal to the time times the speed of light. Yes, but both of them are as power of GeV to the minus 1, so 1 over GeV. Now, if they say to you, I don't know, the top quark have a mass of 173 GeV, what you know is that this mass is in a unit of energy. Is the unit we use in particle physics, is in the natural unit, so it simplified the equation. It's convenient in a philosophical point of view because we describe mass with an energy unit. But if you want to know how is how much the top quark weight in kilos, then you just use this conversion and you know, oh, this is a mass. To have the right unit in the normal, in the conventional system, I have to divide this time by c squared. So I have this divided by c squared. We will become a certain mass which is called which is in these units, and then you can convert using this the value of c, the value of GeV in international system unit, so you can actually find the mass in kilos. And this you can really see because the energy in international units, so GeV, you can describe it as kilos times meters squared over second squared, and then you divide by c squared over by c squared, which is a velocity, so s squared over m squared, and you can find that actually this GeV over c squared has the right unit in the international system of measurements. And so indeed you can recover a mass. But for now we will set everything, from now on we will set everything equal to 1, and I will specify only when I will set not equal to 1 for some weird reason. Okay? Super nice. This simplifies things a lot. now that we have our new system of units, we are ready to go relativistic quantum mechanics. So we saw that first of all, the relativistic energy is equal to E squared equal p squared plus m squared, where p is the momentum and m is the mass of the particle. And then we have that second thing, we still assume that the solution that describe a free particle non-interacting, so without potential, will look something like this. Phi equal to a certain normalization factor, e to the I px minus et. As you can see here, we had a h bar I divided by h bar, but now h bar is 1, so we drop it. Perfect. Let's pay attention to this. This is just an assumption. So I don't know, I know that Schrödinger equation doesn't work anymore. I don't know which new equation will work, but I assume that the solution of this new equation can describe particles, at least in the reference frame in which I don't go like in the limit in which relativity is not needed. I know that the solution of this equation will look something like a plane wave. And this is just an assumption. So with this assumption, I also know that the energy operator and the momentum operator are the same as the one we described before. So these are the quantum mechanical operators. Setting h bar equal to 1, I have that energy is equal to, it should be minus I, no, plus I derivative with respect to time, and momentum p should be minus I derivative with respect to x, but then I do x, y, z, and so this nabla operator. Okay? Last thing, last operator, no, other operator I don't think we need, but in this case then simply instead of when we constructed Schrödinger equation, what we did was, so Schrödinger what we did was simply to apply energy and momentum. We knew that energy is equal p squared over 2m, so we said energy operator times wave function psi, let's put it in blue, is equal to p squared over 2m times, so it's not, this is not really times wave function, but this is the operator applied to the wave function phi. Okay, what we do now in the new equation that we will call Klein-Gordon equation is exactly the same logic, but in which instead of energy I will have energy squared, because this is the relativistic energy, and instead of p squared over 2m I will have p squared plus m squared. So I will go relativistic, and I say that the energy operator squared applied to the solution of this equation, this wave function that we assume to be a plane wave, will be equal to p squared plus m squared applied to this same solution. Okay, we will now move a little bit the terms and write e squared and p squared in terms of operators. So p squared, e squared will be equal to this stuff squared, I squared is equal to minus 1, and so I have minus d over dt squared phi equals to, in this case, minus I times minus I is always equals to minus 1, so minus this operator squared times psi, no, times phi, plus m squared times phi. And now I just move some term. For example, I can do this, move everything on the left hand side, and what I will get is minus, but no, wait, let me think. If I move everything to the left hand side, I will get this, but if I move this to the right hand side, what I get is that d over dt squared minus delta squared applied to phi is equal to plus m applied to phi. In this case, m is not applied because it's not an operator, so it's just m multiplied by phi, m squared multiplied by phi. This is equal to 0. Okay, we are almost there because now we know that this operator here, we encountered him already, because if we define the mu equal d over dt delta and nabla, the mu equal d over dt minus nabla, we can just say that this part here is equal to the mu. So the Lorentz invariant scalar product between these two derivatives. So we can write the Klein-Gordon equation now as, write it here instead of this middle one. This part here will just be the mu. And then I have plus m squared. Everything applied to this phi, which is the wave function, is equal to 0. And this, my friend, is called Klein-Gordon equation. The Klein-Gordon equation respects the relativistic energy. It's covariant, but has a huge problem because, okay, now the problem is always an illusionary problem, but was a problem at the time in which people were trying to describe wave function as solution of this Klein-Gordon equation. Because if I say this solution to the Klein-Gordon equation is a wave function that describes my particle moving without moving freely, what I get is that, first of all, the energy of this particle must obey this relation here. So E is equal to plus or minus p square over E is equal plus or minus square root of p squared plus m squared. And in this case, I have a positive solution for the energy and a negative solution for the energy. We will deep dive into that a little bit later, but the real problem here is that in quantum mechanics I cannot get rid by the negative from the negative energy solution. I cannot throw it away. And then, since this negative energy solution, this also applies to Dirac equation, but then Dirac equation, we will find a way of sorting out this. The real problem is that at some point we compute the probability density and probability current that we will put in a same vector, which is equal to rho j. In this case, this is not the same for current that we used in electromagnetism, but this is a probability density. So it's a density not of charge or current, not of charge, but of probability. And in this case, this probability density with this energy, with this form of the equation, can be negative. And this is something that in quantum mechanics we cannot interpret. We cannot say, oh yes, we have a negative probability and that's fine. So this implies having a negative probability density implies that this object here, the solution to the Klein-Gordon equation, cannot describe a particle, the wave function of a particle. So this guy here can't be an amplitude, or can't be can't be the description, but I have no space to write it, can't be the description of a single particle, a single quantum mechanics particle. Okay, because the probability density is negative. I say I put so much time and effort on explaining you this stuff because this equation is okay if this is a field. This equation is not okay if this is a wave function describing a single free particle. But it's just a matter of how I identify this solution to this equation. So the Klein-Gordon equation doesn't work for quantum mechanics and for relativistic quantum mechanics, and we have to find something else. This something else will be the famous Dirac equation that will change forever our perspective about particles. So Klein-Gordon equation is something like this. The object, the solution to the Klein-Gordon equation, cannot be used to describe the quantum mechanical particle. So Dirac thinks about it, and Dirac thinks, what if, since Klein-Gordon equation is something like p squared plus m squared times psi, like applied on phi, not psi, sorry, is equal to e squared phi. This is how we derived Klein-Gordon equation. Dirac thinks, what if I can find a new equation which also satisfies this equation? So this equation is satisfied, but what if exists a new element here, a new function, a new solution to a new equation that also satisfies the Klein-Gordon equation, so it's relativistic and the energy, I can recover the relativistic energy, but it's linear in the space and in the time derivative. This equation would look something like this. So I have the energy operator applied to some function psi. I call this solution in a different manner from this solution because there are two different objects, which is equal to some something, which could be a number, could be I don't know what. We have to find out. I call this something alpha times p plus beta times m. And this will be applied to psi. Okay, so the Dirac equation, it's different from the Schrödinger equation in the sense that, as you can see, it's not p squared plus m squared, but is p times something plus m times something is equal to e. So it's linear in the momentum, in the mass, and in the energy. And so Dirac wants something, some solution to this equation, but this solution must also satisfy Klein-Gordon equation. So in a sense, the solution to the Dirac equation are more constrained than the solution to the Klein-Gordon equation. And in this object, we will try to see if the probability density associated with this object is also negative, or it's something that works for describing a single particle in quantum mechanics. Okay, let's see the condition of this object that this object must satisfy to satisfy also this equation here. Well, the conditions are very simple. I first check what this e squared is, and for doing e squared applied to this object here must be equal to this part squared applied to this object here. So I make an assumption, or Dirac make an assumption, in which the Hamiltonian of Dirac, so the Dirac Hamiltonian, will be equal to this alpha times p. This is a scalar vector between these two vectors, or better, this is a vector, this we don't know what is it, plus beta times m, and this is the Dirac Hamiltonian. In this case, the energy squared will correspond to the Dirac Hamiltonian squared. So to recover Klein-Gordon equation, what we have to do is simply to make the square of this object, that I will write down in a more, let's say, a more expensive notation to use, but a more clear notation. The more clear notation is simply that, since this is a scalar product, I will have something like Okay, I will have alpha x px plus alpha y py plus alpha z pz plus beta m. This is also equal to this. Okay, so it's also equal to the Dirac Hamiltonian. Now, what we want to check if, like, we want to recover the Klein-Gordon equation. So to do this, we simply squared this side here and this side here. So what we get when we square the Dirac Hamiltonian, it's something like this. Let me write it down completely and then we'll discuss about it. So Dirac equation, but with this and this term squared, will become something like e squared. But okay, the e squared, please don't. I'm thinking on how to make it clear, the more clear possible. So yeah, let's just square this term. So we will write down what is this term square, and then we apply this term square to the solution of the Dirac equation. This term squared is simply this term here times itself. So times the same thing. Okay. This Dirac Hamiltonian squared is equal to this term, which is equal to this piece here times the same thing. So I put alpha x px, then we have alpha y, alpha z, this pz must be white, then we have beta, yes, okay, so this pz, okay. To have this squared, I just say I have the products between px and px, py and py, pz and pz, m and m. These are the simple one. So I have that Dirac Hamiltonian squared times psi will be equal to alpha x px px. So in this case, we'll have alpha x squared px squared. The same for alpha y, alpha z, beta. So we will write it down now. Yeah. Okay, this is the first piece, and then we have all the cross terms. So I can have px times py or px times py, so I can build it in two different ways. But since we apply this operator to the phi, we can simply say alpha x, alpha y, for example, is different, or we don't know what these elements are. So it could be different from alpha y, alpha x. So this could be different, we still don't know, from alpha y, alpha x. So for these cross terms, we have to write down something like this. So here there is a plus, there is something times px py plus, again, something times px pz. And this something, and then we'll have px py pz. And these are all the cross terms. And then we have the terms in which I have px times mass, py times mass, pz times mass. And these are other terms, px times mass, then I have py times mass, and then something else p z times mass. Okay, all of this applied to psi. So yes. What are these terms here? Well, these terms here are simply alpha x, alpha y plus alpha y, alpha x. And then here I have xz, so I will have alpha x, alpha z plus alpha z, alpha x. Now we simplify a bit the notation and we say that alpha I, alpha j between these two brackets is equal to alpha I, alpha j plus alpha j, alpha I. This is called the anticommutator. It's called anticommutator because the same thing with a minus here is called commutator. But in this case, so we will not write down alpha x, alpha y plus alpha y, alpha x, but we will simply write down the anticommutator between alpha y, alpha x. So in this case, we have py, pz, and here we will have anticommutator between alpha y and alpha z. Then here we will have anticommutator between alpha x and beta. Here we have anticommutator between alpha y and beta. And here we have anticommutator between alpha z and beta. Okay? Now we are ready. We are ready to compare these two equations. So if with this Dirac equation, squaring the two terms, I must recover Klein-Gordon equation, I simply need only the terms p squared and m squared. P squared, this is a vector squared, so it's px squared plus py squared plus pz squared, and then I need m squared. So the only thing I need is this part here. This one will be associated to p squared, this one will be associated to mass squared, and then you can see already that there is a very simple rule that our elements here, alpha x, alpha y, alpha z, and beta must follow, which is that all the anticommutator between different elements is 0. Because in the Dirac equation I don't have mixed terms, so this here must be 0, this here must be 0, this one must be 0, bam, bam, bam. Okay, you understood the point. So the rules for Dirac equation for these alpha elements and beta elements must be the following. First of all, if this must recover Klein-Gordon equation, this, and this must be all 1. So this must be 1, this must be 1, this must be 1, this must be 1. We don't know if they are numbers, so let's write this weird one which we call identity. So we know that alpha I, where I can be x, y, z, whatever, squared will be equal to the identity, and also beta squared will be equal to the identity. Then second relation that we found out is that the anticommutator between alpha y, alpha I, alpha j must be equal to 0. In this case, I must be different by j, otherwise the anticommutator will be 2. And you can, of course, find it by here. And also the anticommutator between alpha I and beta must be 0. Now, beta, we could have called beta also alpha, so that only these two rules apply. So if we call also beta, we call it alpha 4, for example, or alpha m, we will have simply two rules, which are alpha I square equal 1, and then alpha I, alpha j anticommutator equal to 0, okay? This is super important because this is called the algebra of the Dirac equation, and we are not really interested on what these elements are, so what these alpha and beta are, but the important part is that we find a set of 4 elements that respect these two properties. If we find a set of 4 elements that respect these two properties, we find a set of elements that's suitable for the Dirac equation. Now we go as investigators and we see what is this set of elements about, what characteristics this set of elements must have. Let's try. Recap. Dirac equation, we ask that this equation is true, and we ask ourselves what relation these two elements or these 4 elements must satisfy to also satisfy Klein-Gordon equation, and this is the set of rules that these 4 elements must satisfy. Now, from this set of rules, we don't need to identify a fixed set of 4 elements, but we just identify a class of sets of 4 elements. So any set of 4 elements that satisfy these rules is okay to put here on the Dirac equation. Let's see, this, first of all, you can try by yourself to find 4 numbers or 4 something that satisfy this rule, and you can already see that these 4 cannot be numbers, okay? Simple numbers cannot be, because otherwise you can find some number that squared is equal to 1, but then you multiply these two together and then you do plus the same thing but swapped and becomes equal to 0, because then at this point it means that either one of the two is equal to 0, and so it can't be that his square, like if you square it, it becomes equal to 1, and that's, so number, we exclude numbers, so these are not simple numbers. Bam, okay. What else they could be? They could be matrices. Okay? If they are matrices, what characteristics this matrix must follow? So the first characteristics is that the trace of this matrix must be 0. The trace is simply the sum of the element on the diagonal of the matrix. For example, this matrix here, 1, 0, 0, 1, S trace equal to 1, because it's the sum of this element plus the sum of this element. So the trace, if this I call matrix M, the trace of M is equal to the sum over I, M, I. So this guy here plus this guy here, and this is equal to 2. Okay, in this case the sum, the trace of these matrices must be 0, and it's very easy to prove, because if I take the trace of alpha I, then I can multiply here, since beta square equal beta is equal to 1, I can multiply here times beta. So I can do, this is equal to the trace of alpha I beta. Then there is, I'm doing all this because it's important to familiarize with this notation, the traces and the matrix. I could just say, okay, look, this is the set of 4 elements that respect Dirac equation, but no, we are doing all this investigation issue, this investigation exercise, because it's very, very important to familiarize also with what does it mean, the trace of a matrix? What are the properties that we are interested in when we talk about matrices? So this is a good property of the matrix, which is the cyclicity. Cyclicity means that I can take this matrix here and move it here, and the trace will not change. So the matrix, the multiplication between the matrix, etc., could change. So the result could change, but the trace of the total matrix doesn't change. So this is also equal to the trace of beta times alpha I times beta. Okay? Now there is another step which I always forget. Ah, yes, of course. Since now we use another property, another one of these two properties. So first we use this property. The second property we use is that these matrices, the anti-commutator between these matrices and beta is 0. So this guy here, since alpha I beta plus beta alpha I is equal 0, we know that alpha I beta is equal to minus beta alpha I. No? This means that this means that I can swap these two terms, putting a minus in front. Beta alpha I, and then this again is 1, and so this is equal to minus the trace of alpha I. So we follow all these steps. We just use the two rules here that we got, and we know that the trace of alpha I, this guy here, is equal to minus the trace of alpha I, but the trace is just a number. So if a number is equal to minus himself, the only number that is equal to minus himself is 0. So the first thing we get from this is that the trace of alpha I is equal to 0. This is the first rule that we get. Then, second rule that we get is that the eigenvalues of these matrices must be 1. And this is also easy to follow, because if we apply alpha I to a certain other matrix X, this must be lambda times X. This is the eigenvalue equation in which X is something. So we apply this operator to X, and this is equal to an eigenvalue over X. Then if I multiply here times alpha I, and also here times alpha I, of course this eigenvalue is just a number, so it can go there. This will be equal to lambda alpha I X, but alpha I X, we define it to be lambda X. So this, it's simply lambda X, which is equal to lambda square X. So we know that alpha squared X is equal to lambda square X, but we also know that alpha I squared is equal to 1. So we know that lambda squared, which is the eigenvalue of this eigenvalue equation, is equal to 1. And so we know that lambda is equal to plus or minus 1. Okay, so the eigenvalues in which, so eigenvalues means if the matrices that we are searching for are not diagonal matrices, so they don't have just elements on the diagonal, but they have elements everywhere, we can find an eigenstate, so this other element X, which diagonalizes the matrix. So we can find a form of this matrix which is diagonal. In this case, the eigenvalues of this matrix, so the things on the diagonal when the matrix is diagonalized, will be either plus 1 or minus 1. So this is the second rule that we find out about these matrices that we will put inside the Dirac equation. Third rule that we find out, it follows from the first and from the second. Third rule, very easy. Is that must be even dimension, and now I explain you why. So this matrix cannot be a 3 by 3 matrix or a 1 by 1 matrix, which is a number, or a 5 by 5 matrix. Can be only even. This is because the sum of the eigenvalues must be 0, because the trace is 0. But the eigenvalues can be only +1 and -1. And the only way of making 0 out of +1 and -1 is to have the same number of +1 and -1. And to have the same number of two elements, the complete set of elements must be must be even. And so this has even dimension. And the fourth, this applies only in this case when we write down the Dirac equation like this, and will not apply when we will write down the Dirac equation in another way, which is the common way of writing down the Dirac equation. But of course, this comes directly from quantum mechanics, and in quantum mechanics, when you have an operator that describes a physical observable, this operator must be Hermitian. Hermitian means that, for example, for the energy operator, which we will call in this case the Hamiltonian operator, Dirac Hamiltonian, must be Hermitian. This means that the complex conjugate, we first transpose the matrix and then we take the complex conjugate of the matrix, must be equal to the matrix itself. In this case, only in this case, the eigenvalue of the matrix are real, and this matrix describes an observable in quantum mechanics. If the eigenvalues, if the Dirac equation, if the Dirac Hamiltonian must be Hermitian, also the elements contained inside the Dirac Hamiltonian must be Hermitian. So we know that alpha I is equal to alpha I transpose and complex conjugate. So these two matrices are the same. So this is a set of rules then that our matrices must obey. And now we can find a set of matrices that obey this set of rules, a set of 4 matrices that obey this set of rules. And we will build this set of matrices starting from the Pauli matrices that we already encountered in quantum mechanics. In reality, we didn't encounter them in this course, but if you made a course, if you took a course on quantum mechanics, you encountered these Pauli matrices for sure. These 3 matrices are the Pauli matrices, but as you can see, they are 2 times 2 matrices. They could respect all these rules, etc., but they are not 4 matrices, they are only 3 matrices. And what we need are 4 matrices. So the smallest dimension in which we can be is not 3, because we cannot have, these matrices cannot have even the odd dimension, but it's 4. So our matrices, the one we are searching for, are 4 by 4 matrices. And we can see, we can verify that a set, we will not do it, otherwise we'll take all day, and we took already a lot of time for defining all the rules that these matrices must obey to, but you can check that these matrices here satisfy all these rules that we talked about. First of all, the beta matrix, the one close to the mass, must be equal to identity, 0, 0, minus identity, in which these 2 blocks here are 2 by 2 matrices. So in this case, 1, the identity, is equal to 1, 0, 0, 1. Okay? Then alpha I must be equal to 0, sigma I, 0. For example, if we want to know what is alpha x, this is an example, exemplium gratia. Alpha x, yes, the matrix alpha x, which is associated to the momentum, the x component of the momentum in the Dirac equation, will be something like this. It's a 4 by 4 matrix, 0, 0. Then we have here the x Pauli matrix, so 0, 1, 1, 0. Then also here we will have the X Pauli matrix, so 0, 1, 1, 0, and then everything else is 0. 0, 0, 0, 0, 0, 0. Nice. So these two guys here, or these four guys here, are the matrices that satisfy every rule for entering inside the Dirac equation. And this is crazy because now we can write down the Dirac equation in this form here, yes, but we also want to write down the Dirac equation in this same form here, so the covariant form of the Dirac equation in which we treat space and time in the same way. So first of all we do that, and then we will find out some mind-blowing result about this Dirac equation. The first mind-blowing result indeed is that this object here, so the solution to the Dirac equation, is not anymore a single complex number in every point in space, but is something which is made by 4 components. Because if these are 4 by 4 matrix, this is 4 by 4 matrix, this guy here must be something which has 4 elements. So psi will be equal to an object which contains psi 1, psi 2, psi 3, psi 4. Is this a relativistic 4 vector? Is it not a relativistic 4 vector? We will find out about this later, but spoiler, is an object that we never encountered up to now. Okay, now we have Klein-Gordon written in this form, Dirac written in this form, and we want Dirac more or less in this form, so covariant Dirac. We know what these matrices are, but we will define a new set of matrices which are suitable also for the Dirac equation, in which the first matrix beta we call gamma 0, and then beta times alpha I, we call it gamma I. Okay, very nice. And in this case, with this set of equation, this set of matrix, which is closely related to this other set of matrix that we already saw, we can just put the energy here. Yes, and remember the energy and momentum. How are they written in form of operators? So we have that. No, actually, we don't put the energy here, but we transfer this into this form here. So we have I d over the t. This is the energy operator, minus I delta. This is the momentum operator, but of course this cannot be just delta, but must be alpha matrix times delta. And this, of course, is always a vector product. Plus, then we have beta, no, minus, because we moved that here, minus beta m. This is applied to this solution to the Dirac equation, and this must be equal to 0. Okay? Now, as we said, we multiply beta here, so we have beta, here we have beta, and here we have beta. Beta times beta becomes simply 1. Beta times alpha becomes sigma e, sigma I, and beta becomes sigma 0. So now we have this equation, which is like gamma, this is a gamma, gamma 0 d over dt minus gamma I d over d, let's say, the xi, which is this guy here, times, let's say, gamma I call this a vector, so I remain consistent with the notation. So this vector gamma will simply be equal to gamma 1, gamma 2, gamma 3. Yes, so I'm consistent with the notation. This scalar product with this, yes, minus m applied to psi. Also, so complicated. This I must be inside here, otherwise I miss an I here. Okay, this is equal to 0. And now we can just redefine our scalar product between two Lorentz, like a Lorentz invariant quantity, and this Lorentz invariant quantity will be, which, pay attention, it's not, in the end, we have to check if it's a Lorentz invariant quantity, will be something like I gamma mu de mu. This seems like a vector product, a product between four vectors, but it's not, because this is a matrix, it's not a 4-vector. So we are not sure that this is an invariant quantity, and indeed I say that it's an invariant quantity, but I'm not sure, and I don't think it is. Minus m psi equal to 0. Boom. This is the Dirac equation that you probably have seen somewhere. This is the form that we normally use to describe Dirac equation. The matrices do not respect anymore this algebra here, but they have a new set of rules, which is closely related to this set of rules, but it's simply that also in this case, gamma I, gamma j, commutator is equal to 0 if I and j are different, and then we have that gamma I squared is equal to -1, and gamma 0 squared, so with I equal 1 to 3, gamma 0 squared is equal to +1. That's it, and we can compactify all this notation, all this algebra, into one single equation, which is this one, and I will place it somewhere. I have no space left. Everything in this blackboard, it's really, really important. I think the less important thing that we can cancel for now are these two matrices here. Yeah, my heart cries cancelling this, but let's cancel these two. And we can say that the algebra satisfied by these gamma matrices is something like this. The anticommutator between I and gamma j, with, in this case, I and j can be 0, 1, 2, 3, is equal to 2 times the metric tensor. Yeah, since I now and j are not anymore just space indices, but space-time indices, let's call them mu and nu. Gamma mu, gamma nu. This is equal to eta mu nu. Okay, this is just one formula that encodes all these relations here. I think a big difficulty in particle physics is that we have all this new notation, all these new ways of writing down formulas in a compact way, and in the end we lose all our understanding sometimes of what's going on really in our physics, because this formula here is a compact notation that contains all this information here. So now what I want to do is to take this Dirac equation, and once in your life you will see the Dirac equation expanded using these and these as matrices as they should be used. Let's do it. we saw that this is the covariant form of the Dirac equation with this gamma mu for 4x4 matrices that respect a lot of rules, and the algebra of these 4x4 matrices is described by this relation here, which is also called Clifford algebra. This is just naming, who cares about the names, but just remember that the set of rules that these elements must satisfy is this one. Then we can find any set of 4 elements that satisfy these rules here. But now the question remains, this is a compact notation. What does it mean? How do these gamma matrices work? What is this object here? So let's see the real face of the Dirac equation, because I feel like a lot of confusion in particle physics, it's always because we use compact forms to describe everything, and so we forgot what we are thinking about, what we are talking about. So first of all, let's define the 4 gamma matrices, and the 4 gamma matrices, as you remember, are gamma 0 equal to 1, 0, 0, minus 1, and gamma I, so gamma 1, gamma 2, gamma 3, are equal to 0, sigma I, minus sigma I, 0. Before, when we defined beta and alpha matrices, here, this guy here was plus sigma I. In this case here, it's minus sigma I. So now we have all the information to write down the Dirac equation in the whole, like, expanded form, not contracted, not compact form. Yeah, third ingredient that we need is that this guy here, which is some object, mysterious object for now, which will be the solution of the Dirac equation, it's some 4-component object. So psi is equal to some psi 1, psi 2, psi 3, psi 4. Ok. First things first, we find out what is sigma times the mu, but not sigma, I mean, not the mu, but the I, so only the spatial component. And this is something like this. Sigma I, the I, is something like, yeah, we can do it for sigma 1, sigma 2, sigma 3, and you can simply verify. Also, that puts I here, so this you can simply verify which that is the 3 minus the 3, where the 3 is the derivative with respect to z, and then we have here the 2, which will be, the 2 minus I, the 1 minus I, the 2, and here we have the 1 plus I, the 2, yes? Then when we go and multiply everything by I, this becomes I, the 3, this becomes plus, here I put the I, here I put the I, and here becomes minus the 2, and this becomes minus I, the 3, and so we remove the I from here. And in this case, and then it's very simple to verify that 1 times the time derivative will be simply time derivative on the diagonal. So that this now becomes a 4x4 matrix equation in which I will have I, let's write it down explicitly, I, gamma 0, the 0, so derivative with respect to time, plus I, gamma E, the I, minus m times a 4x4 unit matrix, psi equal to 0. Okay? This now, using this relation here, so I will have I, this in the diagonal and everything. I can build a 4x4 matrix in which I have all the terms of the Dirac equation. Let's make it very, very big. So the real face of Dirac equation, it's showing very, very slowly. huge 4x4 matrix that I multiply by a 4-component something, which I still don't know what is it. 1, 2, 3, 4. This will be equal to 0. Yes. Now I have, first of all, I d0 minus m took from this gamma 0 times d0 on the diagonal I have always, and then I have always minus m on the diagonal of this 4x4 matrix. So here I also have I d0 minus m. Here I have minus I d0 minus m. And here I have again minus I d0 minus m. Perfect. Now, these guys here on the diagonal, they have these 4x4 matrices on these two blocks here. So I will write these 4x4 matrices, in one case positive and in the other case negative, since this is negative. So the first one is, here I will have 0. This 4x4 matrix will be I d3, I d3, and here I will have I d1 plus d2. And here I will have minus I d1 minus, no, plus I d1 minus d2. So here this is the 2x2 matrix. Here I will also have 0, I guess. Here I will have 0, here I will have 0. And then I will have another time this block here. So, but in this case negative. So minus I d3 minus, no, plus, yes, this one is minus, so this one is plus I d3. And here I will have the same block but negative, so minus I d1 minus d2 and minus I d1 plus d2. But this now is the real face of the Dirac equation. If you want the Dirac equation written like this, so in the compact form, what it tells you is that there are 4 coupled differential equations for which the solution are these 4 components of this object, which we will now spoil. It is a Dirac spinor, whatever a spinor is, and we will find out more about this object now, checking if the Dirac equation is covariant on a relativistic point of view, so it's Lorentz covariant, and second, checking something that is very, very subtle, but will tell us a whole lot of things about this object here. So we continue our investigation work, discovering what this object here that we find as solution to the Dirac equation represents in our physics. Now it's the time in which we do a little recap of what we found out about the Dirac equation, because it's very, very important, and then we will see the plan for what's next. First of all, we saw that Dirac postulated this equation to explain and to solve the problem of the Klein-Gordon equation, namely that the energy of the Klein-Gordon equation was negative, and or at least the energy associated with solution to the Klein-Gordon equation, and even more importantly, the probability density of solution associated to Klein-Gordon equation was negative. So Dirac postulates this, and in the covariant or in the modern form, the Dirac equation becomes this object here. We wrote down explicitly some minutes ago the Dirac equation. So we see that these are really four differential equations, four coupled differential equations, and the solution to the Dirac equation, so both to this equation and to this equation, are four component objects, which are something like this and are called the Dirac Spinor. So this is something like psi1, psi2, psi3, psi4. Now, what is next? What we want to do in this next hour or minutes together about the Dirac equation? So first of all, it's to see how spin emerges from the Dirac equation, or at least it's not emerges from the Dirac equation, but it's necessary for the Dirac equation. So necessity of spin. Then, after we will see, so we know now that this equation describes one relativistic particle. So this equation is relativistic because we build it with relativistic laws and respects this law, E squared equal P squared plus m squared, which is the relativistic energy of a particle, so it describes a relativistic particle. 2, it describes a quantum mechanical particle, so it's built up on the law of quantum mechanics, not only on relativistic, so it has quantum mechanics embedded. 3, we also know that this is a free particle, because it's just a particle moving freely. We didn't introduce any potential in the Hamiltonian, and we see that we postulate a Dirac Hamiltonian, which is something like this. Because this operator applied to the wave function, to what we now interpret as a wave function, gives us the energy value associated to this particular solution of the Dirac equation. So we know that this particle is free. Free means non-interacting particle. And 4, we still don't know, but we want to know what is the spin of this particle. So does the Dirac equation describe any particle with any spin, or just some particle with some particular spin? And this is what we will see with the necessity of spin in the Dirac equation. Then we will see explicit solution to the Dirac equation. So what is psi in practice? How do I write psi? And then the last part of this piece of lecture about the Dirac equation will be interpretation. In particular, this interpretation part is something that will lead us directly to quantum field theory. And then we will see interpretation of quantum field theory in other, quantum field theory interpretation of particles in other kind of situations. So in which, in situation in which I don't have the Dirac equation, but I have other kind of particle and other kind of fields. Even though fields for now, it's just an empty word for you, but we will see exactly why the Dirac equation, the solution to the Dirac equations, are not really probability amplitudes, like in quantum mechanics, but are some superposition of creation and annihilation operator of fields. So, yeah, it's crazy, okay. We'll see all this kind of stuff, okay? But let's start with the necessity of spin. Okay, I kept this part because it's very, very important. In particular, now we will not see this equation here, but we will go back to the previous equation in which the alpha and beta matrix define completely the Dirac equation. And as you can recollect from the previous minutes, alpha I is equal to some matrix in which has 0 on the diagonal. This is a 4x4 matrix, and here has the Pauli matrices, sigma I, sigma I. And the beta matrix is something that has a 1 here, 0, 0, and then minus 1, where this weird one means a 2x2 matrix composed of 1 in the diagonal. Now, how do we see that spin is necessary for the Dirac equation, for these solutions to the Dirac equation? Or better, first of all, what is spin? Spin is something that in quantum mechanics we introduce because we see that there is this property that particles have, like electron, when we shot them inside this magnetic field, and probably you already saw the Stern-Gerlach experiment. I also have a video about that. Also, that video is in Italian, but maybe one day will be translated in English, so you can watch it. Back to us, spin is some property of the particle. And this property, like, I don't know, the electric charge is just something that the particle has in quantum mechanics. And it's some property that is equivalent to an angular momentum. So it's like an intrinsic angular momentum. The first assumption was that the particles spin on themselves, and so they generate an intrinsic angular momentum. But then Pauli showed that if the particles were balls spinning on themselves, for generating that value of spin, they would have to spin faster than light. So this interpretation didn't make sense of spin. So in quantum physics, we just say the spin is something that it's there, and we don't really know why, but particles have intrinsic angular momentum. In the Dirac equation, we can give a more sophisticated argument for spin. And this is the argument. In short, the angular momentum of a particle that respects the Dirac equation, it's not conserved. But we know that a free particle, this is a free particle, we know that something that's moving freely has to conserve the total angular momentum. So what we say is, oh, there is another component of the angular momentum that go and adds to the orbital angular momentum. So the normal angular momentum, it's something like this, L equal R vector product P. So it's the position of the particle vector product with the momentum of the particle. And we define, so this is the angular momentum operator, and then we define a total angular momentum operator that we call J, that will be L plus S. So it's the orbital angular momentum plus the spin angular momentum. And we see that in the Dirac equation, if this is the Hamiltonian of the system, the angular momentum itself, it's not conserved, but the total angular momentum is. So for making such that the total angular momentum will be conserved, that is something that we want because the particle is a free particle, so there is no interaction going on. Like, where does it go? If the angular momentum is not conserved, it means that the particle can change its angular momentum going around, but if it's not interacting with something, we want as a principle that the angular momentum is conserved. So, first of all, how do we see that the orbital angular momentum is not conserved? Well, we use the Heisenberg picture of quantum mechanics. Heisenberg picture is something like this. In quantum physics, we describe observables with some operator O, and the evolution of this operator in time, in the Heisenberg picture, is described by this equation. The derivative of the operator with respect to time is equal to the this mean value, average value of the how is it called in English? The commutator between the Hamiltonian of the system and the operator. I don't know if in this course we already defined this object here with these two brackets. This object is called the commutator. This will be super useful also for later. The commutator between these two objects, if you see that if this commutator is equal to 0, then also the evolution in time, so the derivative of the operator with respect to time, is equal to 0. And so we see, we know that the observable O is a constant, because its time derivative is equal to 0, so it's constant with respect to time. But we have to check it. I mean, an operator, an observable, is a constant, is something that doesn't change in time if and only if the commutator of this operator with the Hamiltonian of the system is 0. Now, what is the commutator? It's something like this, HO. So the commutator between two matrices or two number or two whatever you want, it's H multiplied by O. In this case, H and O are two operators. One is the Hamiltonian operator, one is the normal operator, is the sum observable, minus O multiplied by H. Since these two objects are matrix, it's not given that this operator and this operator, like the multiplication between O and H is the same as the multiplication between H and O. So only if this object is the same as this object, the operator commute with the Hamiltonian, and the operator or the observable O is a constant. Okay. Now we want to do what we want to do now is just check whether the angular momentum, in this case, in the case of the Dirac equation, commutes with the Dirac Hamiltonian. If there are two cases, so if this commutes with the Dirac Hamiltonian, so we take the Dirac Hamiltonian commutator with the angular momentum, and this is equal to 0, okay, angular momentum is conserved. If the Dirac Hamiltonian and the angular momentum do not commute, so this is different from 0, then there is an evolution in time of the angular momentum operator, and the angular momentum operator is not constant, so it's not conserved. So in this case, okay, now let's check in which of the two cases we are. We'll check with only one of the components of the angular momentum. We already defined the vector product, and in this case, so wait, this I also cancel, and also this I cancel, so we have space for doing all our computations. We already defined the vector product between two objects, so in this case the angular momentum has three components, Lx, Ly, Lz, but for now we will compute only Lx and see what is the commutator between the Dirac Hamiltonian and the x component of the angular momentum. So the x component will be Ry Pz minus Rz Py. This is the x component of the angular momentum. Now, let's see whether this commute with the Dirac Hamiltonian. This will be equal to, so the Dirac Hamiltonian will be alpha p plus beta m, but beta m always commutes with r and with p, because in quantum mechanics the canonical commutation, I don't know if canonical is the right term, but the commutation between the position operator r could also be x, but now we call it r. At some point we will call it x, but it's always the position. When we talk about r or x, we are talking about the position. The position operator and the momentum operator are not two things that commute, so this is equal to I. Okay, and this is important because now we can should continue to drop. Okay, this is important. Now this means that we have the commutator between alpha p plus beta m, and this Lx will be Ry pz minus Rz py. Okay, commutation between these two quantities, but since beta is a diagonal matrix, this part here goes away, and also we already know that m commutes with everything because the mass is just a number, so this part goes away. This we can divide into two pieces, so the commutator between alpha p and Ry px, alpha p minus the commutation between alpha p Rz py. Now, alpha p, these are 4x4 sorry. Yes. This alpha p will be, yes, this alpha p will be equal to something like alpha I, so alpha x px plus alpha y py plus alpha z pz. But as you can see, here we only have Ry, here we only have z. So the only important part here is alpha y py. The only important part here is alpha z pz, because what we want to do is this thing here. So the real commutator will be between p and r. So if here we have the y component, the only things that can give a commutator different by 0 with the y component is this alpha y py. So let's write it here. Alpha y py. And here the only thing that can give a commutator which is different with from 0 with this component here will be simply alpha z pz. So alpha z pz, yes. So this now I write it like alpha y yeah, I think it's right, but let's check. Alpha y, the commutator between py and ry, minus alpha z, the commutator between pz rz, py. And this will be equal to, now we see that this, we already write it here, r and p is equal to I, so p and r is equal to minus I. So this commutator here gives us minus I, this commutator here also gives us minus I, and this total thing here gives us alpha y, here I forgot a p, this was a pz, here I forgot a pz, yes, alpha y minus I collect it from here and from here, alpha y pz minus alpha z py, which is simply minus I, the x component of alpha vector product p. If I do the same with the y component of the angular momentum and with the z component of the angular momentum, what I find, I discovered that this Hamiltonian operator does not commute with the angular momentum, but is equal to, so the commutator between the Hamiltonian operator and the angular momentum is equal to minus I alpha vector product P. So let me write it in cubital characters in, somewhere. So this one is not the case. Angular momentum does not commute with the Hamiltonian. Angular momentum and Hamiltonian, like commutator between angular momentum and Hamiltonian, is equal to minus I alpha times P. Sorry, I was lost for a moment. So the result we found is that the Dirac Hamiltonian and the angular momentum operator do not commute, and the commutator between these two objects gives us minus I alpha vector product P, where alpha are the three matrices in front of P, and P are the three components of the momentum of the particle. What we want to do now is to say, okay, the angular momentum does not commute, but surely the total angular momentum commutes. So total angular momentum operator is J, which is equal to the orbital angular momentum plus some intrinsic angular momentum, which is the spin. And if this one commutes with the Hamiltonian, so request we require that H and J commute. Dirac Hamiltonian operator and total angular momentum operator commutation must be 0, so that the total angular momentum is conserved. Now what we do is just find out what is the matrix S that gives us this relation, and the matrix S that gives us this relation is one that such that the Dirac Hamiltonian, the commutator between the Dirac Hamiltonian and this matrix S must be equal to the opposite of this, so plus I alpha vector product P. Okay, and you can check, now we will not derive everything etc., but you can check that the S matrix, so the spin matrix, its spin operator equal to 1/2 sigma 0 0 sigma. This is the spin of the particle described by the Dirac equation. So this solution to the Dirac equation will represent a particle with these spin matrices, this spin operator. So what is the spin of this holy particle that comes out from the Dirac equation? Well, we know that if we do S squared applied to the wave function, so we find the eigenvalue of the spin S times S plus 1. I do S square and not simply S because not always the wave function, so the thing described by a certain equation, in this case by the Dirac equation, is an eigenstate of one of the components of the spin, but it's always, or at least it should be, an eigenstate of the squared angular momentum, the squared spin. So this operator squared, it's always some eigenvalue, yes. The solution of the Dirac equation should be an eigenvalue of this operator squared applied to the Dirac equation. So now it's just a matter of seeing how, what is this operator squared, and this operator squared, S squared, will be equal to Sx squared plus Sy squared plus Sz squared. And since every Pauli matrix square gives 1, this means this is 1/4, 1 1. It's something like this. It's 3 times because it's Sx, Sy, Sz. Every one of the 3 gives 1/4 times a unitary matrix. Okay. This is 3 times. So the eigenvalue of this eigenvalues equation gives us 3/4 times the wave function psi, and so we know that 3/4 is equal to the spin value times the spin value plus 1. This is just a very long, very long way of checking what is the spin of this of the particle described by the Dirac equation that I remind you. So once we have this eigenvalue equation, we can find the spin value, which is so s times s plus 1 is equal to 3/4, and we can check that 1/2 times 1/2 plus 1 is equal to 1/2 times 3/2, which is equal to 3/4. So s equal 1/2. This is so important. This is so important. The Dirac equation describes particles with spin s equal 1/2. Particles which do not have spin 1/2 do not obey to the Dirac equation. So Dirac equation only describes 3 spin 1/2 particles. And this is a very important result. But now we will see the second very important result of the Dirac equation, which is how the Dirac equation predicts antimatter. What we want to do now is to understand explicitly the solutions of the Dirac equation, and we will do this in 2 cases. So, first one in the case in which we are in the rest frame of the particle, so the momentum of the particle is equal to 0, and then second one in the case of p, the momentum of the particle is different by 0. And we'll see this time really explicitly what the 4 components of this Dirac vector, so psi1, psi2, psi3, psi4 are. And we will discover in searching, in trying to understand what these 4 components are, what is antimatter and why the Dirac equation not only requires that the spin of this particle described by the Dirac equation is 1/2, but also requires that there is not only particle solution but also antiparticle solution. And we will see this in the case of the rest frame, so when the momentum of the particle is equal to 0. So the Dirac equation, we'll write again it in a modern notation, so gamma mu, the mu minus m psi. Psi I put always in orange to say this is the solution of the Dirac equation. This must be equal to 0. Okay, in the rest frame of the particle, it's very easy, because if p is equal to 0, in this case, I will have that I gamma 0 energy E, since p mu is equal to E p. This is, sorry, p mu with an upper index. Then at some point, we will consider equal higher and like in some book upper index, lower index are considering the same. In this case I want still to do a distinction, and this is not the energy yet, but is the time derivative, so d0. D0 is the derivative with respect to time, minus I gamma I di, so di is the derivative with respect to space, minus m multiplied by psi, which is the solution to the Dirac equation, is equal to 0. And then the assumption we make is, so it's just an hypothesis, but is what we used to describe free particle of momentum p every time, is that the free particle is something like, so a solution of the Dirac equation, psi, one of these, psi1, psi2, psi3, psi4, is equal to a certain normalization factor, a certain, normalization factor, we put it inside the U, so a certain thing, a certain solution that depends on the quadri-momentum, p mu, times e to the minus I p mu x mu. So this is the plane wave solution that we already saw in quantum mechanics, and we already saw in the Klein-Gordon equation. And just to be super clear, p mu x mu is equal E t minus p x. So it's a scalar product between two four vector, the four momentum and the four space vector. And this is the extended notation. This notation we will use also, like for describing this thing, we will also use px without carrying around all these indices. So it will be a little bit simpler to write this as px. E to the minus I px means e to the minus I, parentheses, energy times time minus momentum times space. Okay, this is the extended, this is what we will write from now on. And this is ui. Okay, so we see that there are four independent solutions of the Dirac equation. Now we derive, so we put this psi I inside the Dirac equation, and we see that if the momentum is equal to 0, this is simply equal to e to the minus I et, because the momentum is equal to 0 in this case. So this part here, it's not inside the solution of the Dirac equation, and this is the solution that we will consider. So in this case, the derivative with respect to x, it's 0, because we don't have an x dependence inside our solution. So this part of the Dirac equation goes away, and this simplifies things a lot, because in this case the Dirac equation becomes E gamma 0, d0, e to the minus I, etc., etc. This will be derivative with respect to time, it's minus IE. Okay, minus IE minus m times this part here, ui, that depends on p. In this case, it depends only on energy and 0 momentum, times e to the minus I e t equal to 0. Since this is equal to 0, we can simply remove this term here and find a solution of the Dirac equation for this component here in momentum space, when always we are in the rest frame of the particle. So in this case, I times minus I is simply 1. So we have that gamma 0 times the energy minus the mass is equal times ui, that is dependent on p, is equal to 0. Okay, and in this case we find this is a 4x4 equation, so it's really 4 equation that gives us the 4 components of this vector here. Pay attention, here can be a little bit confusionary. These are not the same 4 components of this vector here. This vector here is a 4-component vector in which the solutions are 4 independent pieces, psi 1, psi 2, psi 3, psi 4. This is equation. Now, for example, we choose one of these, psi 1, we put it here, and now in this case, U1 will be one of the independent solution of this equation. So, for example, we can choose 4 independent solutions, which are U1 equal a certain normalization factor. So, okay, every UI, let's put it in this way. This U1 could be something like this. Gamma 0 A will be E minus E minus E. This is a 4x4 matrix. Then we have minus m, so minus m we just put it here. Minus m, minus m, minus m, minus m, times the component of this vector here, which we can call, for example, phi 1, phi 2, phi 3, phi 4. These are the component of the U1 vector in momentum space equal to 0. And now we will find, we have to find 4 independent of this vector, which will correspond to the 4 independent solution of the Dirac equation. And the simplest one that obey this equation here are U1, which is simply a certain normalization factor multiplied by 1, 0, 0, 0. So it's a 4 vector in which it just has 1 here and then all 0. Then U2, which is simply, again, a normalization factor 0, 1, 0, 0. And you already know, you can imagine already U3, which is equal to normalization factor 0, 0, 1, 0, and U4, which is again equal to normalization factor 0, 0, 0, 1. So these 4 are the 4 solutions to the Dirac equation that corresponds to this 4 psi here. If I want to construct psi, I just multiply times e to the minus e t. In this case is important because these 4 solutions here, so I have that psi 1, for example, if I want, just to make one example, if I want psi 1, I have to just multiply this times e to the minus e t. Okay? Now, this is important because the first two, U1 and U2, have energy equal to mass. The second two have energy equal to minus mass. This is very, very, very tricky. Let's do it carefully. So once we have the 4 solutions, let me erase here a little bit. Let's take 2 of the 4 solutions, for example, U1 of P equal normalization factor. U1 will be only of energy E, normalization factor 1, 0, 0, 0. Now if I plug this U1 inside the Dirac equation, I get that gamma 0 E minus m U1 equals 0. So it means that in this case I have that E U1 equal m U1. Try to obtain this result, but it's very easy because it just, yes, I make the matrix multiplication, maybe I should leave the matrix here. E minus m, E minus m, minus E minus m, minus E minus m. This is the 4 by 4 matrix. It's obvious that if I multiply this times 1, 0, 0, 0 equals 0, I get that this times this is the only term which is not 0, and so I get that E minus m U1 is equal to 0, and then E applied to U1 is equal to m U1. Okay, and this is like a little bit like an eigenvalue equations, in which the eigenvalue of the energy for this specific Dirac vector, the Dirac spinor, it's m plus m. But what happens if I use, instead of U1, I use U3? If I use U3, here I have 0, 0, 1, 0. The only component which is not 0 is this one, so the third row multiplied by the vector when I do the matrix multiplication. And what I obtain is that E plus m as an equation, E plus m applied to U3 is equal to 0, and then E applied to U3, so the operator E applied to the state, the third solution, let's say, of the Dirac equation is equal to minus the mass times the third solution of the Dirac equation. So for U3 and U4, I get that the energy operator is equal to minus m. So the eigenvalue of the energy operator is equal to minus the mass of the particle. So what I get now that I build my, my solution is that for U1 and U2, I have E equal plus m. And for U3 and U4, I have E equal minus m. Okay? This is so important because it's very, very puzzling as a result, because one says, what does it mean for this particle to have negative energy? These two solutions associated to negative energy, we will see that in reality there is no particle with negative energy. It's just the solution, the energy that pops out of my solution of the Dirac equation is the opposite of the physical energy of the particles, but this describes a particle which is not the same of this particle here. This is the antiparticle associated with the Dirac equation. So in a sense, so Dirac tried to explain this with the Dirac C, which is a view that can in some way explain it, but it's not physically correct in the end. But yeah, it's crazy. It's crazy because from this equation, it's not sufficient to have a solution with positive energy or two solutions with positive energy, but I also have two solutions with negative energy. Okay, so now we have a solution with positive energy that will be written as psi1 is associated to U1, then psi2 is associated to U2, psi3 is associated to U3, psi4 is associated to U4, and how are they associated? Just U2 times e to the minus m minus I m t. This is also e to the minus I m t. This is, no wait, okay, sorry, this is plus, because this is 3, this is plus I m t, because, why? Because this is the e to the minus I e t, but e is equal minus m, so this becomes plus m. This is always equal to minus e m t, and this is also e to the plus I m t. Okay, these are the four solutions to the Dirac equation in the case of the particle being in the rest frame. So in the case in which my reference frame moves together with the particle. This is important. It's important to see this solution in the rest frame because in this frame, in this particular frame, we have another property of these these four solutions. Let's see what is the other property, and we'll see that we didn't randomly introduce the spin operator for no reason. Okay, we found the four solutions. Now let's try something. Let's try to apply the spin, the z momentum, z component of the spin operator to these four solutions of the Dirac equation. So if I apply Sz, I remember you that Sz is 1/2 sigma z, but sigma z is equal 1, 0, 0, minus 1. This is the Pauli matrices, the Z Pauli matrices, Z Pauli matrix. So this is 1, minus 1, 1, minus 1. This is all 0, this is all 0. So it's a 4x4 matrix with all 0, but not on the diagonal. On the diagonal I have 1, minus 1, 1, minus 1, and this is the Z component of the spin operator for the solution of the Dirac equation. So let's try to apply this to our four independent solution of the Dirac equation. So if I apply Sz to psi1, what I get, since psi1 contains U1, and U1 is a 4 vector with only the first component not 0, I get 1, so 1/2. 1/2 psi1. Okay, if I do same as z psi 2, then I will apply to psi 3, then I will apply to psi 4. So Sz applied to psi 2 is equal to minus 1/2. And this you can just check plugging in psi 2 and multiplying it by this matrix. Sz applied to psi 3 is equal plus 1/2. Sz applied to psi 4 is equal minus 1/2 again. So in this particular frame, it's not the same in every frame. So if we start moving in a weird direction, the solution, if we are not moving in the z direction, the solutions are not anymore eigenvalues, eigenstates, sorry, of the spin operator, but in this case they are. It's crazy because psi 1 describe a particle which has spin 1/2 and positive energy, or the energy of this particle is equal the mass of the particle. Psi 2 describes a particle which has always positive energy, so the energy is the mass of the particle, but with minus 1/2, spin minus 1/2. Then this solution here, psi 3, describe energy which is minus the mass and spin plus 1/2, and this one, energy which is minus the mass and spin minus 1/2. So this solution is associated to a particle, and this is the spin up particle. This solution again is associated with a particle with this time spin down. This solution is associated with an antiparticle with spin up, and this is again antiparticle with spin down. Okay? In this particular frame is very visible. When we go fast, so when we are in a reference frame which does not move together with the particle, this is not, it's not very visible anymore. But we always have negative energy solution and spin solution. So we have two energies which are associated to particle and antiparticle, and two ways of polarizing the particle, up and down. Okay? And yes, this is the beauty of the Dirac equation. If you want to stop the video, stare at it for a little bit, but it's just how it is. This equation, the solution of this equation describes both particle, both antiparticle, and like both particle and antiparticle, and both spin up and spin down, all in the same equation, and I cannot just disentangle the particles. The equation requires that there is spin and there is particle-antiparticles. Otherwise it doesn't work. And this is one of the major achievements of theoretical physics and of this little equation that you see here. Now what we want to do is to see what happens when I go fast. Namely, when the momentum of the particle with respect to my reference frame is not zero anymore. In this case, the solution will be a little bit more complicated, but we will do it anyway because we want to see how the Dirac equation transforms from a reference frame to another one. Now we have to use a little bit of strategy because things can become very complicated. So let's try to make it as simple as possible. We want to get rid to the solutions in momentum space of Dirac equation that gives us that rises negative energy eigenvalues. So what do? We simply say this guy here has four solutions that we search of the type of U of p, e to the minus I px, and this will be associated with four solutions. We already saw in the case of momentum equal to 0 that we have psi 1, psi 2, psi 3, psi 4, but psi 3 and psi 4 are negative energy solution. But we cannot just throw them away as we do in classical physics, because in classical physics we have continuous variations of energy. So if we start with a positive energy, we cannot jump to a negative energy as nothing. So if we start on the branch of the positive energy solution, we will be sure that we always remain on positive energy solutions. But here we are in quantum mechanics, and in quantum mechanics we can just jump from an energy level to the other, and so we have to accept that there are solutions with negative energy, because from this level, from the positive energy level, we can just jump to the negative energy solution. So this we cannot just throw them away, etc. We have to accept that there are 4 independent solutions of the Dirac equation. But what we do is that we will search for other 4 solutions which are of the form like this: V dependent by P, e to the plus I P x. Also in this case here we will obtain 4 solutions, which we can call psi 1, psi 2, psi 3, psi 4. And in this case the first 2 solutions will be associated to negative energy solution when I am just looking at V, okay? And these 2 here will be associated with positive energy solution, as these 2 here will be associated to positive energy solutions. So what we do is just we obtain 4 solutions here, 4 solutions here. We throw away 2 solutions here and 2 solutions here, these 2 and these 2. So bam, and we only keep the solutions of the Dirac equation that gives us positive energy eigenstates, positive energy eigenvalues when I consider the momentum space solution of the Dirac equation. Okay, now let's make it clear and let's go to the momentum space. So the momentum space is simply the first 2 solutions that we call 1, and the second 2 solutions that we call 2. So the orange type solution are the one with the minus here. The blue type solution, this maybe it's better to do it in orange. The orange type solution have a minus here. The blue type solution have a plus here. That's the only difference. Okay. So the orange type solution will be something like this. Now gamma mu de mu, it's simply gamma mu, it becomes gamma mu p mu minus m psi, but psi is equal to u times e to the minus I p x is equal to 0. Okay, this is just, sorry, moment of distraction. Okay, this is in momentum space after deriving, and also after deriving this I goes away. Then we can, since we don't have anymore some x going around or some operator, some derivative, this part here we can just throw it away. And the second, this is the first type of solution, must obey to this equation. The second type of solution must obey always to this. So I gamma mu de mu minus m u e to the plus I p x equal to 0. But now I derive with respect to mu, and I obtain the same thing but with opposite sign here, because I get plus I p in this case here. So the mu applied to this object here gives me plus I p mu, and this means that this becomes minus gamma mu de mu, because plus I times I gives us minus 1, minus m, and this is not anymore a demo, but is a PMU, minus m with this solution, sorry, this is the second kind of solution, so it's a V, e to the IPX is equal to 0. So, also in this case, e to the IPX goes away, and now, if I collect this minus sign here, this is a plus sign, and this minus sign can go away. Okay, so we have now two kind of Schrödinger Dirac equation in momentum space. For this equation we will have 4 solutions. For this equation we will have 4 solutions, and we keep 2 solutions from this one and 2 solutions from this one, the one who have positive energy eigenvalues. Okay, let's solve this one, and then for the other one will be exactly the same procedure. Okay, for solving this one, first we need to understand what this gamma mu p mu thing is. So we have that gamma 0 E, since P0 is, of course, P mu is equal to E minus P. So we have gamma 0 E minus gamma I pi minus m u equal to 0. Now we do a little bit of computation. First of all, we divide this, since gamma 0 is equal to 1 on the first 2 and minus 1 in the second 2 entry, we just divide this into 2 by 2 matrices, which will be 1e minus m. Then we will have here minus 1e minus m. Okay, and then here we will have minus gamma ipi, and this we'll do it later. Yeah, this is multiplied by u plus another 2 by 2 matrix, which will be gamma I pi, it's 0 here, sigma I pi, but there is a minus here, so here we put a minus sign, and this here we put a plus sign. This will be sigma I pi. Here we put a plus sign because there was a minus here, but also a minus in the gamma matrix. This will be 0 as well, and this will be times u, and the total will be 0. Now, for keeping the positive energy solution, we will solve the first line, and in particular we will search for solutions which are of this kind. U equal to some bivector, some 2 component vector here, which we'll call, I don't know, psi A, and then something here. So I don't know, U1, U2. Okay, and we will choose psi A to be, or better, this is something like this, psi A, psi B, in which psi A and psi B are two component vectors, so in total will be 4 components. And the positive energy solution in this case will be associated with U1, which is equal to psi A being 1, 0, and then here we have to find out who psi B is, and then U2, which will be equal to 0, 1, and then we will find out if psi A is 0, 1, who psi B will be. So in our spirit of writing everything as a 2 by 2 object, we will write also this one as a 2 by 2 object, which will be psi A, psi B, and also this one as a 2 by 2 object, which will be psi A, psi B. Okay. Now we will just, okay, here all the other entries here and here are 0. Now we will divide this in this way here, okay. What we want to do here is to express psi A in terms of psi B and psi B in terms of psi A, but since we have psi A specified, which we will choose to be 1, 0 or 0, 1, what we want is psi B as a function of psi A. And the easiest way to do it is to solve just the bottom part, let's say, of this 4 by 4 matrix equation, which is this. So 0 multiplied by psi A is equal to 0, plus this multiplied by psi B, which will be minus E plus M psi B, where psi B is a 2 by 2 vector, is equal to, or let's do it piece by piece. Then we'll have plus sigma I pi psi A is equal to 0. And this specific part here gives me that psi B, you already know it, you can already see it. Let's erase this. This specific equation here gives me that psi B, or no, psi B is equal to sigma I pi over E plus M times psi A. So we have this relation. The other relation was psi A equal sigma I pi psi B divided by E minus M, but that was associated with the negative energy solution. So if we solve the top part of the 4 by 4 equation, we end up with the solution associated to the negative energy, and that is what we don't want. So that's what we have. And now if we choose psi A to be 1, 0, psi B will be sigma I pi, yes, sigma, what is sigma I pi? This is simply pz minus pz. This is multiplication between the matrix, Dirac Pauli matrices, and the momentum component. So this will be px minus I py, px plus I py. Okay. This means that if sigma A is 0, 1, let's try to do it. So let's try to find the two solutions, U1, U2. This is not important anymore. So the solution U1 to the Dirac equation will be associated with, so a certain normalization factor as always. First vector psi A to be 1, 0, and then if this is 1, 0, this part here will be, the first component will be pz over E plus M, and the second component will be let me think, this times this, and then this times this. Yes, the second component will be px plus E py over E plus M. Okay? U2, you can try yourself putting, instead of 1, 0 as CA, you put 0, 1. Okay? If you put 0, 1, you will obtain that U2 is equal to normalization factor 0, 1, it's our choice. Then if the first is 0, 1, this will be Px minus Ipy over E plus M. And then the second component will be minus Pz. You can try by yourself. These are the two solutions of the Dirac equation associated with this equation here. Then we have the two solutions associated with this equation here, which we will do in exactly the same way, with the only difference being that there is a plus sign here. And now I'll write you the two solutions without calculating everything, but you can just find the relation between Pb and Pca in the second case, and you will find these results that now I will write here. These are now the four independent solutions of the Dirac equation. These two associated with a positive frequency when we write e to the Ipx, and these two associated to a negative frequency when we write e to the plus Ipx. Now we will see, finally, the general solution of the Dirac equation and how do we interpret this general solution to the Dirac equation. Of course, this we will let here written as they are. No, before the general solution to the Dirac equation, I invite you to consider this, which is a very important matter. I can cancel everything. Before we see the general solution of the Dirac equation and how do we interpret the general solution of the Dirac equation, I want you to consider an important matter, which is when we are in p equal to 0, so rest frame of the particle, we have, for example, psi1, which is equal to normalization factor 1, 0, 0, 0, e to the I minus IMT, okay? And when we start going fast, so we find the particle which is not moving according to our together with our reference frame, we find that psi1 in this case will be equal to our U1 vector, but our U1 vector is equal to a certain normalization factor 1, 0, 1, 0, the first component. You see that is the same, and then Pz, let's consider just a particle moving in the reference, in the z-axis. So it's not that P is different by 0, but just Pz, the z component of the momentum is different from 0. So this part here we don't have. This is over E plus M, and this is 0. This one is the solution of a Dirac equation in the case of the particle moving in the z direction, and you see here, this is super important, that we cannot relate these two solutions with a Lorentz transformation. These are not related by a Lorentz transformation like this. So the Dirac spinor, it's a four-component object, but does not transform as a vector. So for example, when we saw Maxwell equation and electromagnetism, we saw that there is this object, mu, that when we want to change reference frame, a prime mu was equal to Lorentz transformation, lambda mu nu, a nu. So this object is a four-component object, a four-component something, that transform as a vector, okay? It's a covariant object. The Dirac spinor, psi prime, it's different. I mean, you cannot relate psi in a reference frame in which I'm moving fast, so in an inertial reference frame in which I have a momentum with the psi, in which I don't have a momentum with a Lorentz transformation. So this guy here, the transformation between psi and psi prime in another reference frame is related by a matrix which we will call S, which is not a Lorentz transformation. Okay, this is just something I want you to notice because it's important to understand why the Spinor field, what we will call later the Spinor field, it's not an object that transforms as a vector. So it's not a vector field, it's something different, okay? And up to now we saw three types of field. The Spinor field, which is this Dirac field, even though we didn't call them field. The vector field, which is this, the solution of the Maxwell equation, and the scalar field, which is the solution of the Klein-Gordon equation. And these three fields, these three types of field that transform in three different ways, will have an important, a fundamental role in what we will see later, because they represent three different kinds of particles. But no spoiler, we will see it in a moment. Now I just want to write down the general solution of the Dirac equation. We worked very hard up to now, and we are ready for the reward, which is the general solution of the Dirac equation, which is something very crazy. So we found two solutions, just to recap very fast, psi1 and psi2, which goes like u1 e to the minus I px and u2 e to the minus I px. So these 1 and 2, we can call them up and down, or we can call them, these are the polarization states or spin states or whatever you want them to call it. I mean, I don't like really to call them spin, even though most of the time in the general solution they are called spin states, but this is not in general an eigenstate, yes, an eigenstate of spin operator of Sz. So I don't really know how to call them, just let's call them 1 and 2. And then we found 3 and 4 that goes like v1 e to the plus I px and v1 and v2 e to the plus I px. Okay, these are four objects that compose, in a way, the Dirac equation. Are four independent solutions, and we wrote down a minute ago U1, U2, V1, V2 are four independent solutions of this very beautiful equation that I will put here not to forget about. So every one of these, psi1, psi2, psi3, psi4, is a solution of this equation here. Okay, there are four independent solutions, so I cannot build a solution starting from the other. But I can build a solution as a linear combination of these four independent solutions. So a general solution will be the sum, the weighted sum of these four independent solutions. And also another thing which is very important is that these solutions are solutions with fixed momentum p, as we were seeing with plane waves. A plane wave which occupies everything in space is just, it has a fixed value of momentum. But when I consider a particle sitting somewhere in space, it's not given that the momentum is exactly that momentum. So the general solution is something like this. Psi that depends on x. Here x is intended as x mu, so both x and t, is equal to, so the first two, 1 and 2, we call them US, where S represents 1 or 2, e to the minus I px, and these we call them VS, e to the plus IPX. So this will be let's put it in an ordered way, because there is a huge things to write. We have U1, or better, US, e to the minus IPX plus VS. VS and US depend by a single momentum P, e to the plus IPX. Okay. This, so we have the sum of these two solutions, but it's not said that this, or better, this 4 solution, because S can be 1 and 2. So we have to, first of all, sum over S. Okay, so we'll have U1 plus U2 plus V1 plus V2. But this 4 solution is not given that they weight the same. So I will add the sum operator here, which sorry, not sum operator yet, just some complex number, which I call B dagger S and A dagger S. No, sorry, and AS. Okay, so these are complex number, complex coefficient, and these are the, in a way, the eigenstates of this state, of this superposition of state. But then I say, wait, there is not only one momentum in our particle. I have to sum over all the momentum, just like I summed over all the polarization states, over all the spin states. So what I do is just to integrate over the 3 momentum, and then the convention here is to put a nice 2 pi to the third, and then 2 times the energy of the particle with momentum p. Okay, so this one is the general solution of the Dirac equation, and is important. What is very important here, unfortunately, is all attached. Maybe I could write it a little bit. Let me write it better to comment it. This is the general solution of the Dirac equation. As you can see, we have a ton of pieces, but every piece now you should just know where it comes from. So these 2 pieces, or these 4 pieces, because there is the index S, are just, okay, this was the blue solution of the Dirac equation, this was the orange solution of the Dirac equation. So 2 solutions here, 2 solutions here. These are 2 complex numbers associated with these 2 solutions, so I can build any kind of superposition of state with these 2 complex numbers in front of these 2 solutions. Here we didn't quantize yet, so it's just complex numbers. And then not only, this solution here accounts only for one state in momentum space, so only the particular state with momentum p. So what I do is to integrate over all possible momentum. And as you can see, this is the general solution of the Dirac equation, and these 2 terms are super important. This one and this one are crazy important terms, because after we will quantize the field, and we will quantize the field not just with the Dirac field, but with the scalar field, which is a little bit easier to understand conceptually, and we will build the formalism of fields and how to handle fields in the next hour or so with the Lagrangian mechanics. But these 2 objects here are fundamental, because once we quantized the Dirac equation, how do we interpret this is just like a field operator, and this has 2 operators, A and B. And in this case, then we can have another solution, like the conjugate of this solution, which in this case I have this solution, psi, that goes as A plus B dagger, and then I will have psi bar that will go as A dagger plus B. Okay, these two operators, we interpret them as operator that creates and annihilates particles and antiparticles, so creates and annihilates modes with momentum p. So specific modes within our quantum fields. And in this particular case, this B dagger, it's something that creates an antiparticle, so creates a mode with momentum p associated to a negative frequency, so it's an antiparticle. So this one creates antiparticle. We will see this a little bit more in detail when we go further, but I just want to fix this concept a little bit, and then we will re-look at this. And this guy here annihilates a particle. So what this superposition can do is to annihilate a particle and create an antiparticle. This field operator can do these two things. Then the conjugate of this field operator can do the opposite. That is, create a particle, so this guy here creates a particle, or annihilate an antiparticle. So this guy here annihilates an antiparticle. And this means that since charge must be conserved, creating an antiparticle, for example, if I am in the context of the electron, I am describing an electron, this field operator here creates a mode, so creates a plane wave with momentum p associated with an antiparticle, so increases the charge of my system of 1, so it adds 1 unit of charge, but can also annihilate a particle. So annihilating a particle, if the particle is an electron with negative charge, means removing from my system a negative charge, and so increasing the charge of my system of 1 unit. So these two objects makes, in a sense, they make the same thing, which is increasing the charge of 1 unit. This object does the opposite, so decreasing the charge of 1 unit, annihilating an antiparticle. So if I annihilate a positron which has positive charge, I am removing 1 unit of charge. If I am creating an electron which has negative charge, I am also removing, in a sense, 1 unit of charge. Okay? So this is a crazy result. Put it in your wall or somewhere. We didn't justify why this now becomes creation and annihilation operators, but just remember this and we will come to it later. Just remember that as a closing of this part of the lecture, this guy here adds a quantum of energy in the system with energy okay, and this removes a quantum of energy in the system with this same energy. Okay, this is another way of seeing it. So this guy can create an antiparticle with positive energy. You see that the energy of the antiparticle that gets created is positive. It's just the charges that is opposite between particle and antiparticle. And this guy here can remove a quantum of energy of this particular energy. So the energy that is created, the quantum of energy that is created or removed, is the energy of a particle of momentum p. Okay? We will see this not in the context of the Spinor field, but in the context of a scalar field, which is a bit simpler. But before seeing that, we have to develop our tools, which is one of the most important principles in physics, which is called the action principle, least action principle. And we will talk about this and about Lagrangian mechanics and about how to handle fields in a moment, in the next episode, let's say. In the last part about the Dirac equation, we saw that we do not interpret anymore the solution of the Dirac equation as a single particle wave function, so a solution representing the probability amplitude of a single particle going around, but as field operators. So these two objects here will be field operator. This object in particular, we build it from the first one, simply saying that is the first one dagger, so conjugate. This will be transposed vector plus conjugate times gamma 0. And in particular, these two objects are two conjugate objects that creates and annihilates particles and antiparticles. So this one, it depends from, as we saw last time, A and B dagger. So A annihilates a particle. So a particle is annihilated, and particles are the solution which were associated to what we wrote in orange, so the U parts of the wave function, let's say, so the wave that had positive frequency, and creates an antiparticle. This guy here instead annihilates an antiparticle and creates a particle. Because this guy here is the conjugate of this guy here. I can also write it explicitly. If this spinor here, psi, it's something like psi 1, psi 2, psi 3, psi 4, then this spinor is the transposed conjugate and multiplied by gamma 0. So this will be psi bar equal to, okay, first of all we transpose. So instead of being a column vector, now I also call it vector in the last lecture, but this is always a spinor. When I say vector, it's just to say that it has 4 components, so it's not just a number, but it's 4 complex numbers. I transpose them, psi 1, psi 2, psi 3, psi 4. Then I conjugate them, so this is the complex conjugate of psi 1, complex conjugate of psi 2, complex conjugate of psi 3, and complex conjugate of psi 4. And then I multiply by gamma 0, but gamma 0 is just a 4x4 matrix with 1 on the first 2 entries and minus 1 on the second 2, so this becomes minus, this becomes minus. So this is the conjugate of this one. This operator creates an antiparticle and annihilates a particle, so in total it increases the charge of my field of +1, so delta, we could say the difference of charge is +1, and this one decreases the, so this operator here creates a particle, so for example an electron, annihilates an antiparticle, and so it removes one unit of charge, so it changes the charge inside my field of -1. So now to understand how this thing work and how these operators, which are solution of the Dirac equation in this case, are described by our mathematics, we have to understand fields. And in particular, what is the plan for today? It's to, first of all, understand what fields are. So and we have 3 types of field. Scalar, we have vector field, and we have spinor field. Okay, then second thing we want to understand is the description, the mathematical description, mathematical tool which we use to describe our field, which will be super powerful, and this is we could we could say Lagrangian mechanics or Lagrangian mathematics or something like this. I put Lagrangian formulation. And we will discover that there is a single object which is the Lagrangian of the fields. The Lagrangian could be just the Lagrangian of one single field or one single type of field, scalar or vector or spinor. And from the Lagrangian of the field, we will derive the equation of motion. For example, the Dirac equation, which is the equation of motion of spinor field, free spinor field, or Klein-Gordon equation, which is the equation of motion of scalar field, yes, and then Maxwell equation in the free case, which is the equation of motion of a vector field. So you see that everything is connected, and we derive these three equations of motion separately, but we can derive everything just starting from a single Lagrangian that contains every field, or we can derive these three separately from three separate little Lagrangian that contains this field. And the Lagrangian formulation of particle physics, it's super strong, super powerful, because then we will define this big formula, which is the Lagrangian, and all the physics of our particle, all the dynamics of our particle, all the dynamics of our field, how our field behaves, and all this kind of stuff, it's all encoded inside the Lagrangian. So once we have the Lagrangian, we really have something that tells us how our field behaves. But from the Lagrangian to the equation of motion, it's always classical field theory. And then 3, we will see how to quantize the scalar field. This field quantization, we will just see how it works in a very simple case and skipping a lot of mathematics, because this is not a course in quantum field theory, just but it's nice to know, because a lot of particle physicists just have no idea about how to pass from the Lagrangian formulation to the quantization of field, and how to obtain this operator that creates, annihilates particles, antiparticles. And that is precisely what we will do after deriving the equation of motion. We will see that there are, in a sense, quantized solutions to this equation of motion. Well, let's start, because this is one of the most exciting lectures, I think. This is the most exciting part of this course, because let's start, it's so good. What are fields? This is something that many people doing field theory take a lot to understand what are fields. So now I want to be super clear. Fields are really not that difficult to understand conceptually. A field is just some mathematical structure that associates a value to every point in space and time. So in this case, I draw points to represent points in space and time. Then, of course, all these points are infinite, meaning that there is no, at least we don't know, but in principle there should not be a separation, a quantization of space-time, so there should not be a structure, a finite structure of space-time, and this should be a continuum. But a field, how we define it, is something that associates some value to every point in space and time. This mathematical value then can oscillate and create all sorts of modes, particles going around in fields, and all these particles, as we describe them, are just modes inside quantum fields. But what does it change? Because we saw that there are three types of field: scalar field, vector field, and spinor field. And these three types of field we already encountered, even though we didn't call them fields, in all the lecture that we were talking about, like in all the subjects we were talking about before. In particular, the difference between these three types of field is the way they change when I go and change my coordinate system. So a scalar field, what we will in practice, let's say, what we will talk about is not just a scalar field, but a complex scalar field. This guy here associates a complex number to every point in space and time. So for example, I don't know, it's just a number here, another number a little bit bigger here, another number here, another one here, tack, tack. So now I draw number just like big or small balls. It's just a representation of numbers. But the important part is that in every point in space, so this point, for example, I call it x mu. This is a space-time point. At this space-time point, there will be associated a scalar field, so a complex number, psi, associated to that x mu. Okay? Perfect. The way it changes, the scalar field changes when I change reference frame. So when I take x prime mu equal lambda mu nu x nu. So in this case, I start from x nu, so the point in space-time x nu becomes a new point in my new reference frame. But when this point in space-time becomes a new point, so x phi of x, it's equal to phi of x prime. You guessed it right. The scalar field does not change if I change my reference frame. So if this point at some point turns, because I start to change inertial frame and I go to x prime mu, so this point I change it to another reference frame, the number associated to this point does not change. And this holds for every number. So for every single point, every single number associated to every single point does not change. Okay? This is the way the scalar field behaves, and the scalar field is associated to the first equation that we see, that we saw, which is the Klein-Gordon equation. At least, no, it's not the first we saw. We first saw Maxwell, but okay. This is Klein-Gordon. So the scalar field is a solution to the Klein-Gordon equation. Okay, I write it down just for clarity. The mu plus m squared phi is equal to 0. Okay, this is the equation of motion of a scalar field. This equation defines a scalar field, and the scalar field is defined in this way here. It's a collection of complex numbers that do not change if I change my reference frame. Then the second field that we see is the vector field. The vector field, it's something that associates to every point not a complex scalar but a vector. So could be one here, someone smaller, somewhere larger. Every vector, as you see, as you know, the vectors have a direction, and in particular in this case, vector field, for example, AMU, is the solution of the Maxwell equation, okay? And AMU of x changes in this way, is equal to gamma mu nu anu of x prime. Okay, so you see that the scalar field, no, the vector field, sorry, does change if I change my reference frame. In particular, if I go to a new reference frame, the components of the vector field must change as a vector, because at every point in space-time, as I associate a vector, a 4 vector in particular. And since at every point in space-time I associate a 4 vector, the 4 vector, when I change my reference frame, must change exactly as vectors, okay? And in this case, an example of equation that governs a vector field, it's the Maxwell equation, which was also here for clarity, we'll write it down, the mu F mu nu, but F mu nu was the mu a nu minus the nu a mu. Okay, this should be equal to J nu, but in this case we are just interested in the free field equation, so free equation of motion, and so we will put the source equal to 0. As you can see, this is an equation for a vector field. Now we already you already understood that in the case of the Spinor field, the equation that describes the equation of motion that describes the Spinor field is the Dirac equation that we wrote multiple amount of times. Let's put it in another color. First time I use this red. Let's see. It seems like pink, but it's okay. So the Dirac field, the Spinor field is solution of the Dirac equation. And in the Spinor field, what we have is neither a complex number, neither a vector, but something that we call a spinor. So I will just draw it like this, just because, I don't know, it's impossible to find a classical analog of a spinor, and I will just draw like little circular arrow just to give a representation of the spinor. And the spinor, the way the spinor change under changes of my coordinate system, it's in a weird way, which is that psi of x will be equal to some matrix S times, of course this is, I always forgot the prime in this case here. So in this case, psi of x will be equal to psi prime of x prime. This will be equal to, yeah, this is the same, but okay, I should have put this matrix here in front of this vector here, but indeed is the same. It's just the way I define who is the prime reference frame and who is the non-prime reference frame. So doesn't change anything. But in this case, if I take the spinor prime evaluated in a new reference frame which is changed with the Lorentz transformation, the spinor does not change as a vector, does not change with the Lorentz transformation, but with this matrix S. So this psi of x. And S is a function of the Lorentz transformation that we use to change the reference frame, but it's not the Lorentz transformation that we use to change the reference frame. While here, this is exactly the Lorentz transformation that we use to change our reference frame. Okay, I hope it's clear. We didn't see explicitly what this S is, but in the end, who cares? Now, it's not something that we care just right now. The important thing is that the spinor and the vector field, even though they have both 4 components and 4 components associated to, so 4 complex components associated to 1 point in space, and also here 4 complex components associated to one point in space, but the way these 4 components change, so I take this point in space, just to be super clear, I take this point in space, I have in this point, so psi of x, this is the point x, I will have 4 components, psi 1, psi 2, psi 3, psi 4, okay? And the same applies with this one. I take this point x, at this point I will have 4 components, which is a vector. In this point I will have 4 components, which is a spinor. And the difference is that these 2 objects change in a different way when I go and change my reference frame. To do it also with the scalar field, if I take a point x, in this case I will have just 1 complex number associated to this point in x, okay? So 1 complex value. Now, we saw what are these three kind of fields. I also tell you that these three kind of fields are super important because practically, not even practically, like the standard model, so the description we give of particle, if we exclude the graviton, it's all based on these three kind of fields. So the scalar field, the only scalar field that we have is the Higgs boson. So only particle associated to scalar field Higgs boson. Particles associated with vector spin are the gauge particle, gauge vectors, which we will talk about in a moment. And these are the photon, which we call gamma, the gluons, which we call G, and then the massive vector gauge boson, which are called W plus minus and Z. Okay, and in the end we have the spinor. The spinor are the matter particles, so the one that has to obey to the Dirac equation and to the Pauli exclusion principle. So all spinor are also fermions, and in this case we have the electron, the muon, the tau, then the associated neutrinos, so electron neutrino, muon neutrino, and tau neutrino, and all the quarks. So these are called leptons, and then we have up, down, charm, strange, top, bottom, and these are all the quarks. So these are all the particles that are spinors, these are all the particles that are vector, these are all the particles, so only Higgs boson, that is a scalar field. Okay, this gives us practically a good picture of the standard model, and these are all the fundamental particles that we use to describe how nature works, without gravity, so strong interaction, weak interaction, and electromagnetic interaction. Okay, I hope now what is a field and which field is associated to which particle is clearer. Now that we know what is a field, we go and see what are the equations that govern our fields, so the Lagrangian equations. And we will explain that with a simple example. Okay. So we saw that we encountered three types of equation: the Klein-Gordon equation, the Maxwell equation, and the Dirac equation that describes the solution of this equation and describes three types of field. But we build up from the bottom the Dirac equation, we build up from the bottom the Maxwell equation, we build up from the bottom, in a sense, the Klein-Gordon equation. But there is a principle in physics that is arguably the most deep thing in physics, which is this least action principle. I forgot a T. Least action principle. The least action principle, it's really some deep mathematical truth, because from this one, so knowing just one thing about the system, which is the Lagrangian, I can derive the equation of motions, the equations of motion, so Dirac equation, Klein-Gordon equation, and Maxwell equation, and this is just for quantum field theory, but I can do the same in classical mechanics. If I know the Lagrangian of a ball moving, and we will see just that as an example, I can define the equation of motion of this ball moving, so I can define the behavior of this ball. So just knowing this thing about the system, the Lagrangian, I can build the action, then I will minimize the action and find out a whole amount of things about the system. Not only that, from the Lagrangian formulation of our system and from another theorem, which we will not cover in detail, but it's one of the most beautiful results of mathematics and physics together. From the another theorem, looking at the Lagrangian, I can find out what are the symmetries of the system and what are the conservation law of the system. For example, energy conservation, momentum conservation, angular momentum conservation, all come just from the nether theorem. So just looking at the Lagrangian of the system, I will know, I don't need anymore to say, oh, the energy is conserved as a principle, so it should be conserved because I don't know why, but I observed that it's conserved. No, from the Lagrangian I see, oh, there is this symmetry in the Lagrangian, so the energy is conserved. So this is the power of knowing the Lagrangian of the system. And this is precisely what we will do now, with an example, with a simple example of classical mechanics. So we will do Lagrangian physics or field theory in 0 plus 1 dimension. We will start with this and then move to field theory in 3 plus 1 dimension. That just means 0 spatial dimension and 1 time dimension. We will start with this, and this is classical mechanics. And then, as analogy, we will not derive everything that you can find in textbooks, but as an analogy, we will build the formalism in 3 plus 1 dimension. That is the number of dimensions that we use for particle physics. So 3 spatial dimension plus 1 time dimension, and this is particle physics. Okay? If the plan is clear, let's find out what is the Lagrangian of a system and the least action principle in a simple example in 0 plus 1 dimension. So assume that this is a classical problem. Assume that I have a ball here with mass m. Okay, I throw this ball with a certain initial speed, initial velocity, which will be vx, so a certain speed on the x-axis and a certain speed on the y-axis. And I want to know the trajectory of this ball. So I can divide this trajectory into two trajectories. The trajectory on the x-axis will be x of t, and the trajectory on the y-axis will be h of t, for example. So the height of the ball will do like this. Will go up and then will drop again. And in the x-axis, the ball will just go straight on. So h of t is the trajectory of the ball on the y-axis. So how do I find the trajectory of the ball on the x-axis and on the y-axis? Well, there are two methods of doing it. The first one is the Newtonian mechanics. So Newtonian mechanics is just that the force applied to the ball is equal to the mass of the ball times the acceleration of the ball. So I have two equations of motion. The force on the x-axis is just 0, because there is no force on the x-axis. I suppose there is gravity here, so g. So the force on the x-axis is 0. The equation of motion in the x-axis is that 0 force is equal to the mass times the acceleration on the x-axis. But the acceleration on the x-axis is just the second derivative with respect to time of x. That's it. Okay? The second equation of motion for the y-axis is force. Force on the y-axis will be minus m times g is equal to mass, again, times second derivative of the height of the ball with respect to time. So okay, so this is the equation of motion in the x-axis, this is the equation of motion in the y-axis. Now let's just consider this equation of motion. This is a very simple way of doing it, and then I need to specify, of course, the initial velocity on y, initial speed of the ball on the y-axis, and the initial position on the y-axis. And in this case I will just find h, this is the classical h of t will be equal to the initial position, so y0, which in this case will be 0, plus the velocity v on the y-axis times the time, minus 1/2 g t square. So this is the equation of motion of the particle, and this is the equation of motion. Solving this equation of motion, I get the trajectory, and this is simple problem, classical mechanics problem. But there is a second way, which is very, and there is a lot more to do in this second way, but it works exactly the same, and it gives us exactly the same solution, which is the Lagrangian mechanics. We could say analytical mechanics or Lagrangian mechanics or something like this. So we do this in this second way. First point, we write down the Lagrangian of the system. The Lagrangian is equal to the kinetic energy of the ball, T, minus the potential energy in which the ball is put. Okay, so in this case, the potential energy will be V equal plus mg times the height of the ball. Okay, this is just the potential energy in gravitational field on Earth. Okay, so this will be T minus V. Second, we write down the action of the system. So this is the Lagrangian of the system. This will be the action of the system. The action of the system is defined as T0 or T1, T2, where T1 is the moment in which the ball starts, and T2 is the moment in which the ball lands. Lagrangian with respect to time. So it's the integral with respect to time of the Lagrangian. Okay? And then 3, this is the principle. So this is where, so I defined a quantity, which is the Lagrangian. I defined a number, which is the integral of the Lagrangian with respect to time. And then here, I just make a choice. I say, let's try this principle. To understand what is the path x of t that my particle will follow, I just choose the path for which this number, this action is minimum, or at least who has okay, this is the principle. You try all the paths. This is very silly. It's just something that no one would never dream to do in normal physics, because this method is just so straightforward. This method is so, like, I do all kind of crazy stuff, but yeah, in particle physics is what we do. The principle is you try all the paths, okay, for example, this path here, or this other path here, or the ball maybe goes up a lot and then does this. You try all of them, and the path that the ball will follow, it's this orange path, which is also the path that has the least action associated to himself. Okay, let's try to make sense of this. So I choose the path x of t that minimizes the action. Okay, and I will find x of t equal v0 x, so the initial velocity in x times t, and I will find h of t equal this one. Okay, I will find exactly the same result if I follow these 3 steps. So if I define the action, if I define the Lagrangian, I compute the action starting from the Lagrangian, and then from all possible paths I find the one who extremize, could also be maximum action, but in this case, let's say who has the least action. Okay, let's try it. Let's try if it works, and let's demonstrate how do I find the equation of motion knowing the action of the system and knowing the Lagrangian of the system. I know it seems a very long path for arriving to particle physics, starting from a simple example, but trust me, if you understand this simple example, you will then understand, or at least get a flavor of what we are doing in particle physics when we extremize the action. Let's talk about just the path of the particle on one dimension, so the height of the particle with respect to the time that the particle moves. So we know from experience that if I launch a ball, let's try. Yeah. Or I launch it, this is not a ball, but we can approximate this as a ball. We do worse things in particle physics. So if I launch it straight up, this is the path that will follow. We'll go up, up, up for a certain time, up, 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 and then at some point it will stop here. So the velocity here is equal to 0, the y velocity, and then we'll go back until it reaches 0. So what do we do in Lagrangian mechanics is just to say, I know where the particle starts, where the bottle starts, or where the ball starts, or whatever I launch starts, and I know where the ball ends. These two points are very important, and we call them xa of t. So at t1, the ball is here. At t2, the ball or bottle or whatever it is, it's here. So at t1, in this case, per specific case, at t1 it was in the ground, or at this height in which I launch it. At t2, it is in the ground. Okay, so we know xa, which is the starting point, and xb, which is the landing point. Then I build the Lagrangian of the system. In this case, the Lagrangian is kinetic energy. So the kinetic energy of the bottle is mass of the bottle times speed of the bottle squared. So it will be mass divided by 2 times speed squared. But speed is also derivative with respect to t, okay, of the path that the bottle will follow. Let's call this path x, just to be consistent with the notation that we generally use in quantum physics, in Lagrangian mechanics to define a coordinate. So this one will be m divided by 2 times derivative of x with respect to time squared. This is the kinetic energy. And then we have minus the potential energy, mgx. Also in this case, the potential energy, I just write it like S. V of x. Okay, so the Lagrangian, it's some quantity which depends on x, my coordinate, and the derivative of x with respect to time, which I will call, to be consistent with all particle physics, the Tx. In Lagrangian mechanics, when you do a course in Lagrangian mechanics, the Tx is also called sometimes, or most of the time, x dot, just to abbreviate the thing. So this is kinetic energy, this potential energy. So now I have my Lagrangian. Then from the Lagrangian I build the action. S is equal to integral from t1 to t2. So I always know my starting point and my landing point, and this must be fixed, it's very important. t1 and t2. Lagrangian, that depends on x and derivative on time of x with respect to time. Perfect. Now, what I do? I try, for example, let's try 3 paths. This one I know that is the correct path. I call it h of t. So it will be the right path that the bottle will follow. Then I have another path, which I don't know. Maybe it goes up very fast and then it goes down. No, the contrary. Well, okay. Anyway, this is another path. And then I have a third path. Let's Let's make it like this. Okay, weirdest thing. It's like the first path is like the bottle goes up very fast and then it drops slowly. This path here is like the bottle goes up and then slows down and then goes down. I mean, it's crazy, crazy path that they are nowhere in nature. This I call x1 of t, and this red one I call it x2 of t. And I label the real path that I know that the bottle will follow h of t. So what I do now to minimize the action is just I have the action, and then I can just do a plot and say, okay, what is the action of the first path, x1 of t? x1 of t, I compute the Lagrangian. From the Lagrangian, I compute this integral, so the integral in time of the Lagrangian, if the particle follows this path, x1 of t, that will be s1, and I get this number, for example. So if the particle or the bottle or the ball or whatever you want to throw follows this path here, this will be the action associated to this path. Then I will try also for ht, which I know that is the real path. So if the particle follows the path ht, then maybe the action will be something like this. If the particle follows x2 of t, then same, I take x2, I build the Lagrangian that depends on x2, derivative on time of x2, then I compute the action. From the action I get a single number, and I get maybe something like this. Okay? From the tree, my principle, so the third step is to choose the path that minimizes the action. So from this tree, it's clear that I choose this one. Okay, so this one has the least action. The problem is that the particle or the bottle or whatever we want to throw can follow an infinite amount of path for going from point 1 to point 2. So what I have, it's an infinite amount of closed path from before x1, then from x1 to h, from h to x2, and then after x2. And so I can just, like for every one of these paths there is a Lagrangian. And for every one of these paths there is an action. So I have that, this is not right. Yes, for every one of these paths I will have an action. So the action in this case will look something like this. And the point I chose from the infinite amount of paths that the bottle could follow, so all the small variation of this, everyone, like here there is an infinite amount of paths. From the infinite amount of paths, so I get this curve, I have to choose the only one so that extremizes the action, so the one that has the least action possible. And to do this there is a trick, that is to notice that the variation of the action around this point, if I magnify this point, you could see that this is the point I want. The action have to go down and then go up again, if this is the minimum of the action. And you see that if I am close enough to this point, the variation of the action it's very thin. So this point is the point that has delta S equal to 0. Okay, this is the mathematical way of explaining, of finding out which one is the path that minimizes the action, knowing that the action is a functional, so it's a function of infinite functions. So it's not a simple problem like just minimizing a function of x. If I have f of x equal x squared, for example, to find the minimum of this curve here, I just derive with respect to x and then put it equal to 0, and then I find the minimum and the maximum of this curve here. In this case, S, the action, is not just a function of a single variable, but is a function of infinite functions. So the way I do it is just say I search for the point in the action in which the variation of the action is equal to 0. And now we go into the mathematics, so now we forget about the problem we are trying to deal with, and we go general, and try to solve this, having a general Lagrangian and a general action, we try to find a rule that can tell us how to select the path that extremizes the action. I hope it's clear. So now the goal, it's not anymore to find the minimum one, but in general, what is the rule that tells me which one is the path that extremizes the action? And I have to do it with a little bit of mathematics. Let's do it. Well, let's dive into the mathematics of this. So, I have a system, I write down the Lagrangian of the system, then from the Lagrangian I can compute the action, which is a number. The Lagrangian is some function, the action is just this will be function of t, this is just a number, integrate on t over t, and then I find the path from the infinite possible path, I find the one that extremizes the action. So, in which delta S is equal to 0. And to do this, now it's pretty simple, because delta S, I can write it like S that depends on x plus delta x, where x and x plus that, well, let's write it and then I comment, minus f S of x. This squared brackets is just to say that the action is a functional, so it's not just a function of a variable x, but is a function of functions. This delta S now is just the distance between the action of a path, S of x, and the action of a closed path, x plus delta x. Okay? These x and x plus delta x are two paths that start and end in the same position. So they start in xa and in xb. And then one is something like this, and the other one is something really close. Okay? Perfect. And then I find the action such that the distance between the action of these two paths is 0. Okay? So this I have to fix equal to 0. Now it's very easy to see that S of x plus delta x, this I do somewhat something like a Taylor expansion. This would be the integral between t1 and t2 of the Lagrangian of x plus delta x. But the Lagrangian of the x plus delta x I can just write it as the Lagrangian of x, because delta x is very small, plus the derivative of the Lagrangian with respect to x times delta x plus, let me think, yes, plus the derivative of the Lagrangian with respect to the other variable, the tx, with respect times delta dtx. Okay, this is the variation of the Lagrangian. Okay, I mean it's the Lagrangian evaluated not at x but at x plus delta x, and that is not precise, but is a goes like it's very close to this. Okay, this guy here it's very close to this. But now this guy here, like S of x plus delta x, will be just the integral of this Lagrangian here. So the integral of L of x, so Lagrangian evaluated in x, plus the variation of the Lagrangian with respect to x times delta x plus the variation of the Lagrangian with respect to derivative in time of x times the variation of the derivative on time of x. Okay, and this integrated over the time. So now, now it's done, because first of all, okay, it's not done. the most one of the conceptually difficult stuff has still to come, but we are almost there. Now I divide this term, so I do the integral over the t of this part here, plus the integral in the t of this other part here. Okay, and this, as you can see, is just the action evaluated at the point x. Okay, plus all this piece. So the action evaluated at x plus delta x is equal to the action evaluated at x plus this integral here from t1 to t2 of this object here. Okay, so when we do this guy minus s evaluated at x, what we get is just this object here. So let me write it down. So this guy here goes away when we subtract this part in this formula here. So we have that let me see if I remember it after cancelling. We have that, okay, this must be equal to 0, but this is also equal to the integral from t1 to t2 in the t of derivative of the action with respect to x times delta x. This I never remember if this is just a derivative written like this or a delta. Now I put a delta, but I think it's in the like it's just a notation fact. Plus derivative of the Lagrangian. This maybe I call it action, but it's the Lagrangian with respect to the tx times variation of the tx. Okay. Now we do a integral per part, EPP, integral by part. And we notice that if I derive d over dt, so if I derive with respect to time this object here, let's see what I have to derive. I have to derive with respect to time I need to obtain this guy here. Yes, so I have to derive okay. This is just, for now, it seems unrelated to this, but just try to derive this and you will find that this is a derivative with respect to time. This derivative with respect to time, I can just call it dt to follow our notation. So it will be derivative with respect to time of this part here, dl over the dtx, plus this part naked and derivative with respect to time of delta x, but this is just the L over the tx, yes, times delta the tx. And you see that now we just did that for comfort because this term here, it's exactly this term here. And I want to write this term here as if this part is equal to this plus this, I just move this object on the other side of this equal sign, and so it will become that this object here, derivative with respect to time of all this object minus derivative with respect to time of this guy here, it's equal to this guy here. Okay? Very good, because now instead of this guy here, in this formula, I can put this other guy here. So this blue one, I now put it instead of this red one, because they are the same thing. Okay? So if I put the blue one instead of the red one, what I get is that this must be equal to 0. So 0 must be equal to the derivative with respect to time of this guy here. But the derivative with respect to time of a derivative with, the integral with respect to time of a derivative with respect to time is just derivative and integral goes away. And so I get just dl over dtx, delta x, evaluated from t1 to t2. And this is so important because we have delta x evaluated at t1 will be delta x a. Delta x evaluated at t2 will be delta x b. But since we have our fixed, our condition that the path must start here and end here, delta x in this point, so delta x in the point A must be equal to 0. So the path cannot move in when evaluated inside in this precise point delta xa, so xa. And same goes for xb. Delta xb is equal to 0. The path cannot move when I am sitting in this precise point. So all this part here goes to 0. Because delta xb is equal to 0, delta xa is equal to 0. And then I remain with my big minus the integral from t1 to t2 dt. Yes, this part here, I already collected a minus sign here, so I will have derivative with respect to time, dl over dtx, then plus this part here. But since I collected a minus, here I have to put a minus sign, and then I will have minus derivative of the Lagrangian with respect to x, with respect to the path x that I am considering. I forgot something. Yes, this guy here has to be multiplied by a delta x, of course, because otherwise, yeah, this I forgot, and so also here I have to multiply this by a delta x minus, okay, minus dl over dx times delta x. Okay, of course, now I have that this quantity here must be equal to 0. So let me write it in the center of the blackboard, because this one is the central part of all this discussion about the least action principle, and is what we will also use in particle physics. Central part of the course, this is one of the most important things we will see. This applies to not only to field, as we see, now we are doing just for particle, so for a path that depends only on the variable t. So requiring that the action is minimal, so requiring that, yes, how can we say? Yes, let's say requiring that the action is in a minimum, so that the variation of the action is equal to 0, coincide to requiring this thing to be equal to 0. But since this must hold for every path, for every small variation, this integral being equal to 0 means just this part here being equal to 0. So from the least action principle, we obtain this formula here, which is super important and is called the Euler-Lagrange equation. Euler-Lagrange equation is this object here equal to 0. So let me write it down, and this also, it's something worth a picture, a screenshot, and then if you're crazy enough, attaching it to your wall. But it's one of the deepest finding of physics. So the Euler-Lagrange equation tells us that the derivative with respect to time of dl over dtx minus dl over dx is equal to 0. Okay, this is the Euler-Lagrange equation, and this is precisely the equation of motion. It's a general equation of motion. So the solution of this equation will be x, exactly the path that the bottle or the ball or the particle or whatever you want to put here will follow if it's in a system described by this Lagrangian. Okay, this is very profound. This is super profound. This, yeah, let's see that it works in our case that we wanted to check. So we wanted to find h of t. We know that the Lagrangian for this particular, so for the height of the bottle with respect to time is just L equal to mass of the bottle divided by 2 times the derivative of h with respect to time twice. Sorry, no. This is the derivative of h with respect to time, which is the velocity squared, minus v, and v is equal to mg times h. Okay, now for respecting our notation, the derivative with respect to time, we will call it dt. And this is the action of our system. Okay, this is the action of our system of the bottle thrown up. Knowing the action of our system and knowing the Euler-Lagrange equation, let's see what happens. I simply compute the derivative of the action with respect to the derivative on time of my path, and the derivative of with respect to time of my path is this one. So the derivative of the action with respect to dt h is equal to 2 times divided by 2 m, so is equal to m derivative with respect to time of my h, okay, of my my path. And then then I have this second term, which is the derivative of the Lagrangian with respect to the path, and the path in this case is just here. Okay, so the derivative of the Lagrangian with respect to the path that I want to find, h, is equal to minus m times g. Okay, now I put everything together, I derive in time this quantity minus this quantity, so I have that mass derivative 2 times derivative on time of h minus mg. Yes, let me think. Yes, minus mg, it becomes plus mg is equal to 0. This is the Euler-Lagrange equation applied to this specific Lagrangian. So with this example we saw we have a system that we want to describe. We compute the Lagrangian of the system, we write down the Lagrangian of the system, and then we use the Euler-Lagrange equation to find the equation of motion of this system. And incidentally, the equation of motion of this system are the same equation of motion that we wrote down in the Newtonian mechanics, because the derivative 2 times with respect to time, 2 times derivative with respect to time of this quantity h is just the acceleration in the y-axis. So mass times acceleration is equal to minus mass times g. Okay, and we found the Newtonian law, Newtonian equation of motion. So m derivative of h with respect to time is equal minus mg, where this is the force to which the particle is subject, and this is mass times acceleration. You see, bam, Newton equation. From just this principle of I associate a Lagrangian to my system, I compute the action of this Lagrangian, then I minimize the action, so I find the path in which the action is minimal, I find the Euler-Lagrange equation, and from Euler-Lagrange equation, bam, equation of motions, okay? And this we did for a simple system, but for more complex system, it's very easy to just find the Lagrangian, because once I have the Lagrangian, I have everything I need to describe the equation of motion and also how the system evolves in time. In this case, how the system evolves in time, in the quantum field theory case, so when I'm dealing with fields, I don't have anymore a certain variable that depends only on time, but I have a field that depends on time and x. And now it will be super easy to go to generalize this equation here to all the equations that we saw before and to the Euler-Lagrange equation, not for a single path in 0 plus 1 dimension, but for a field, okay? And that's what we will do now. Was a long ride, but it's very worth it. Perfect. We saw the case in 0 plus 1 dimension, so the Lagrangian mechanics in 0 plus 1 dimension, and this I remember to you that it's 0 plus 1, not just 1 dimension, because it's 0 spatial dimension and 1 time dimension. So the solution that we are searching for, it's the configuration of, for example, the bottle that drops in with respect to time. So this is something like x with respect to time. That depends only on one variable, and the variable is time. What do we do when we go in field theory? So 3 plus 1, this it's always will be field theory in 0 plus 1 dimension or field theory in 3 plus 1 dimension. Field theory in 0 plus 1 dimension is just classical mechanics or quantum mechanics when we want to formulate it with the Feynman path integral. It's just a path integral that depends on Lagrangian, for which solutions are things that just depend on t. What do we do when we go in quantum field theory? As we saw before, is to step from the trajectory of the particle that depends on t. For example, in quantum physics, x is an operator and time is a label, to a field. So we have a collection of field that we can call phi I. In this case, I call it phi I just to say, to denote that this could be a scalar field, a vector field, or a Spinor field. It's just phi I, and is a collection of field. So every I corresponds to a different field, which depends on x, so 3 spatial coordinates and 1 time coordinate. Okay, so the solutions to our motion equation will not be a trajectory anymore, but will be a field configuration. So what is the value of the field in every point in space and time, while this was what is the value of what is the position of the particle at every point in time. Okay, we saw that the Lagrangian in this case, it's something that looks like L equal kinetic energy minus potential energy. The Lagrangian just depends on the path x, so coordinate x, and derivative with respect to time of coordinate x. And in this case, when we go in 3+1 dimension, so when we have a field configuration as solution of these equations that we will write down, we have Lagrangian that I write with this funny L, just to remind us that it's not a Lagrangian anymore, but it's a Lagrangian density. We will anyway call it Lagrangian, and the difference is just the fact that this Lagrangian density, to obtain a Lagrangian, we have to integrate over space, over the three components of space. But for now, just consider the Lagrangian density as the same object of the Lagrangian here. The Lagrangian density will be something that depends on the field phi I, so the collection of the field that we have in our system, and the derivative not anymore in time, but in every component, so in every dimension that we are considering. So derivative demu of the field I, so the field collection I. Okay, and in this case, so we just swap the coordinates, the trajectory with field configuration, and we swapped the derivative in space with the four derivative. So in this case, what was depending on this object here is now depending on this object. I mean, what was this is now this. Okay. And now we also saw the Euler-Lagrange equation from the least action principle. So indeed, we can also write down the action before. Remember, the Lagrangian, it's some function, okay? The action is just a number. So action, in this case, is S, which depends of the path x, will be the time derivative, the integral over time of L of the various x. Okay, the integral over time of the Lagrangian. In this case, the action of the fields, so the action of a collection of fields phi I, will be equal to the integral over the 4x, so not anymore integral over time, but integral over all the components, space and time, so all the four components of the Lagrangian density that depends on my collection of field and my four derivatives of the collection of fields. Okay, and now we go to the important part, let's say, equation of motion, or also Euler-Lagrange equations. In this case, as we saw, was derivative with respect to time, dl over dt x minus dl over dx equal to 0. This was the Euler-Lagrange equation for 0 plus 1 dimension. When we go in 3 plus 1 dimension, as we did before, we change x and the t with field and derivative with respect to every component. So in this case, we will have the mu the L over the mu phi I. There is one Euler-Lagrange equation for every possible field I, which is contained in our Lagrangian, minus the L over the phi I is equal to 0. Okay, this one is, okay, we didn't prove it like formally, or we didn't do a lot of mathematics, we just saw the analogy between these two cases. We proved this, we don't prove this, but you can find it in every textbook about classical field theory, and you can also find a very good derivation of this Euler-Lagrange equation for quantum field theory in the quantum field theory and the standard model book. But this is not the point now. This is just to show you we derived this, and this is for the fields. And now, just as we did nothing. We did nothing yet. Now we will use this Euler-Lagrange equation to describe our field, our equation of motion, so the Dirac equation, the Maxwell equation, and the Klein-Gordon equation in terms of a Lagrangian. Because then knowing the Lagrangian of a system will lead us will simplify our lives a lot, because then we will just use the Lagrangian for doing particle physics. Okay, so most important result of this blackboard is this guy here, because from this guy here we will find the equation that we discussed up to now. Now it's super important, because we will talk about the Lagrangian of fields. So we have a Dirac Lagrangian, a Maxwell Lagrangian, and a Klein-Gordon Lagrangian. And this is something that we already saw. Now we saw the Klein-Gordon equation. Let's start with the simplest one, Klein-Gordon equation. In this case, this was the mu phi, no, sorry. I'm already writing down the Lagrangian. We have a Klein-Gordon equation, ANSI, yes, no. First of all, let's do something more systematic. Let's write it here. Let's write here the Euler-Lagrange equation. Which is okay. This we will keep it here. Perfect. Now we have our Euler-Lagrange equation for fields. Fields are the solution to the Euler-Lagrange equation, and knowing the Lagrangian of a field, we can derive the equation of motion of the fields. And the equation of motion of the fields that we want to derive are the Dirac equation, the Klein-Gordon equation, and Maxwell equation. So we will do this for Klein-Gordon. Maxwell. Before Dirac, and then Maxwell. I'm trying to not to cover everything while I write, but it's very difficult, as I do for your own commodity. Klein-Gordon equation, let's see. The Klein-Gordon equation was something like this. D mu plus m squared phi. Solution of the Klein-Gordon equation are complex scalar field is equal to 0. Okay. Now we want to ask ourselves, what is a Lagrangian that gives me this equation when I apply the Euler-Lagrange equation? So, if I write down a Lagrangian, which depends by the field phi, and also the complex conjugate, and the derivative of the field phi, and it's something like this, the mu, okay. Okay, this is the Lagrangian that describes a complex scalar field. And to prove this, we will derive the Klein-Gordon equation as an equation of motion of this Lagrangian here. So it's very simple. We just have to derive both of these pieces. So we have derivative of the Lagrangian with respect, in this case we will do it with respect to the complex conjugate of the field. So with respect to the mu phi dagger is equal to, okay, it's very easy. You see already that this piece here is the complex conjugate of the field, this one. So the derivative with respect to this is just d mu phi. D mu phi. Okay, then we can do the same for the second piece, which is derivative of the Lagrangian with respect to the field. In this case, we will do it with respect to the field, the complex conjugate of the field. dl over the phi dagger is equal to minus m squared phi. Okay, now we will combine these two pieces that we obtained. The Euler-Lagrange equation is derivative of this minus this. And so it's very easy because you see that the mu derivative of this minus m squared becomes plus m squared phi is equal to 0. And this is, if I collect phi, so phi, I write it only once here, this is exactly the Klein-Gordon equation. Boom! And we did it deriving with respect to the complex conjugate of the field. If we did it with respect to the field, so without this cross here, that will be the same, but we will have obtained the complex conjugate equation of the Klein-Gordon equation. So the Klein-Gordon equation for the conjugate of this field here, which is the same Klein-Gordon equation. Okay, so we proved, in a sense, that this is the Lagrangian governing a complex scalar field, because it gives us the Klein-Gordon equation when we use the Euler-Lagrange equation. Let's now write down the Dirac equation and find out the Dirac Lagrangian. This is very fun now. That is very easy also after all this trouble that we had. And I remind you that we want the Lagrangian because having the information about the Lagrangian of a field, it's having the deepest information possible about how the field behaves. So the Dirac equation, it's something like I gamma mu d mu minus m. We use the red, let's continue to use the red, psi is equal to 0. Okay? The Lagrangian, the Dirac Lagrangian will be Lagrangian that depends on Spinor field psi derivative of the Spinor field psi equal to psi bar that we defined before, I gamma mu d mu minus m psi. Ok. The Lagrangian also in this case depends both by the field and by the conjugate of the field. Okay. In this case, we do the same. We try the Euler-Lagrange equation and see if we can recover Dirac equation. And also in this case, we will derive with respect to the complex conjugate of the field. So with respect to d mu phi bar, psi bar, sorry, this is psi, not phi. This is simply equal to 0. As you can see, there is no derivative with respect to psi bar in the Lagrangian of the Dirac equation, in the Dirac Lagrangian. And then the second part, derivative of the Lagrangian with respect to this guy here, it's also, no, let me think, no, sorry, we are deriving with respect to psi bar. So derivative of the Lagrangian with respect to psi bar is equal to psi bar is here, so it's multiplied in a sense by this term here, so it's just equal to this term here. So it's equal to plus I gamma mu, the mu minus m psi. And as you can see, is exactly the Dirac equation. Then the Euler-Lagrange equation will be, no, sorry, it's not exactly the Dirac equation, it's just the left-hand side of the Dirac equation. Then the Euler-Lagrange will be minus this term is equal to 0, but if minus this is equal to 0, also plus this is equal to 0, and then we find from this Lagrangian we recover the Dirac equation, exactly as from this Lagrangian we recovered the Klein-Gordon equation. Now for Maxwell, the Maxwell equation, the relativistic Maxwell equation was the mu f mu nu equal j mu. We will just take the free equation, so the mu f mu nu is equal to 0. F mu nu contains a mu in his inside f mu nu there is a mu, there are this term here, and the Maxwell Lagrangian it's simply L Maxwell, which depends on A and the derivative of A, where A is this vector field, and it's equal to minus, this is free Lagrangian equation, free Maxwell Lagrangian, minus 1/4 f mu nu f mu nu, and then if we want to add source j mu, this will also be we will also add minus a mu j mu. But for now let's keep it free, and we will not check the Euler-Lagrange equation because there are a lot of indexing going on. It's something that is boring, but you can check by yourself or look into a book that this Lagrangian here, minus 1/4 f mu nu, gives us this equation of motion here if we use Euler-Lagrange equation. So now we have a general way of going from the Lagrangian of our field, the Lagrangian describing our field, to the equation of motion describing our field. And we have recovered with this technique, or we cheated a little bit because we wrote down the Lagrangian such as we recover the equation of motion that we studied before. But one could also just write down the Lagrangian which, from first principle that govern these fields, and these fields, and recover the equation of motion through the Euler-Lagrange equation. Okay, it's incredible. Okay, so from now on we will always work, or in most of the case we will work with the Lagrangians. These are all Lagrangian that describe free, non-interacting fields, but when we will go in the standard model, what we will do, this is the power of working with the Lagrangian, it's really, if you have information about the Lagrangian, we have information about, crazy information about the system, because when we go in the standard model, we will build an enormous Lagrangian starting from all these free Lagrangian. So Lagrangian of the standard model, it's something crazy that you probably have seen on mugs, on shirts, on magnets, everywhere, if you are a little bit a nerd about physics. And this contains inside Spinor field, scalar field, Spinor field, vector field, scalar field for Higgs boson, and then interactions. So it contains all terms, all sort of terms which are combination of scalar with vector, for example, or spinor with vector, etc., etc. So writing down a Lagrangian which has combination between field and not only one field corresponds to write down how the particles interact, and that is what we will do in the next part of this course. First, before going to see the Lagrangian of the simplest interacting theory, which is electromagnetism, we will also need to justify a little bit more how did we quantize the field and how this solution to the field work, because the solution now to the field equation that we have, to the equation of motion that we have, no one says to us that they are quantized, and in fact they are not quantized. Also, this solution we also can get in classical field theory. There is nothing quantum about this solution here. How do we quantize them? We will see that now. Well. Now we are ready to see in a more sophisticated way how to quantize a field, or how to quantize, would be better to say, how to quantize the solutions to the equation of motions for this field. And we will do it for the Klein-Gordon equation, so for the scalar field. This we will do it for scalar. Complex scalar. Complex means, scalar and complex means that at every point in space-time there is associated a complex number. So we saw that the Lagrangian of this field will be phi de mu phi, so it will depend by these two variables, let's say, is equal to the mu phi dagger de mu phi minus m squared phi dagger phi. Then we saw from this Lagrangian we can derive the equation of motion, which is simply the Klein-Gordon equation, the mu plus m squared equal to phi, times phi applied to phi is equal to 0. And from the Klein-Gordon equation we found out general solution, or we didn't do it, but it's exactly analogous to what we do for the electron. So for the Spinor field, we find that a general solution of this field here, it's something that goes as e to the minus I px. So this is just a plane wave describing a particle going around with momentum p, with fixed momentum p. But also general solution goes as e to the plus I px. These are both solutions to the Klein-Gordon equation, and so exactly how we did for the electron and for the Spinor field, we build a general solution basing on these two independent solutions, which is something like this. Phi, so the field at a certain position x will be equal to the integral over the 3p over 2 pi over 2 pi to the third. Then we also add here 2 times square root of 2 times the energy of the particle of momentum p, and all these terms are just a convention. This is constant, and it's a convention that simplifies our computations in quantum field theory, but we probably will not see all the computation that gets simplified by this convention, but we still use the convention. And then we have the superposition of the two possible solutions, so a possible solution with e to the minus I px, and another possible solution which is e to the plus I px. And of course we weight these two solutions with two complex numbers, which are a, write it like this, a depends on p, so it's some complex number that depends on the momentum p, and then we have b dagger, it's a complex number that depends also on a momentum p. So we have this superposition of two states and then integrate over all possible momentum p. all this convention here can be changed, so all these numbers, this constant can be changed, simply reabsorbing them inside A and B dagger. Okay, but the important part is that A and B dagger are now two complex numbers. We can also define a complex conjugate of this field, because as you can see inside the Lagrangian, there is not only this field but also his complex conjugate, and this is simply something that goes as okay, I will not write it down because it's very long and it's practically the same information, but the complex conjugate of this field is the same thing, but it goes like e to the IPX A dagger, and then e to the minus IPX here, and B without the dagger. So we complex conjugate these two numbers. So we have now some psi that it's proportional. It goes like, or it contains A and B dagger. Okay. This is what it contains. And then we have a psi dagger that contains A dagger and psi and B. Okay, this you should remind of these complex numbers from the general solution of the Dirac equation that we wrote down some time ago. Okay. Now, how to quantize this solution? First of all, what is quantized in quantum field theory? It's not the field or something weird, it's the solution of the equation of motion, which we can have in principle every possible solution. If this remains just complex number, which can be every number, the solution can be every possible solution. It's not quantum. The quantum part comes when these numbers cannot be any number, but it's just they become quantized, and we interpret them as creator and annihilator operator. And how do we do? So first of all, yes, let's keep it simple. For quantizing this, we use two principles. One from Lagrangian mechanics, or better say two results, than more than two principles. Lagrangian mechanics, and one result from quantum mechanics. Okay, the result we get from Lagrangian mechanics, if you remember, we have that the Lagrangian, let's say, what is the Lagrangian for a free particle in 0 plus 1 dimension? This is just the kinetic energy, will be kinetic minus potential energy, but free particle, it's not inside a potential, so we cancel this stuff. This is just a specific case of the general rule that we want to apply. Which is also equal to mass times divided by 2, derivative of x, so of the coordinate of the particle with respect to time, and then this guy here squared. Now, if we derive the Lagrangian with respect to dtx, what we get is, this is just m divided by 2 dtx squared. So if I derive this part here with respect to the tx, the 2 goes here, and I get m times the tx. Okay, but m times the tx is just mass times velocity, and so this is just momentum of the particle. Okay. So momentum and position in Lagrangian mechanics are said to be conjugate variables, I think. And what I get is that the momentum in Lagrangian mechanics is just the derivative of the Lagrangian with respect to the derivative in time of position. Okay? That is the result that we will use from Lagrangian mechanics. Then there is a result that we will use from quantum mechanics, and this is something that physicists are more who has a degree in physics and has done quantum physics in a good way is more familiar with, which is the thing we already talked about, and is the commutator between position and momentum. In particular, in quantum physics, position it's an operator, momentum is an operator, and the commutator between position and momentum is equal to I. Okay, this we already saw when we tried to solve something that I don't remember very well. Ah yes, this guy here, we saw it when we found out about the spin described in solution of the Dirac equation. Okay, but this is a result from quantum mechanics. Now we want to apply both of these results to quantum field theory in 3+1 dimension. This means that, first of all, the conjugate, since the x is just a field, let me think, yes, x is just a field, sorry, x in Lagrangian, in 3+1 dimension field theory becomes the field phi. So we can also define the conjugate field, which we call pi, which will be, so we can also find the analogous not only of x, but also of the conjugate variable of x. So p will become another field pi, and pi we define it in the style of Lagrangian mechanics. So pi is something that goes like derivative of our Lagrangian that will depend on phi with respect to the derivative, the time of the field phi. Okay, in this particular case, so this is general solution for every kind of field. In this particular case, in which the Lagrangian describes a scalar field, this you can try by yourself. The derivative with respect to time of this is just the complex conjugate of the field, but derivative with respect to time. So the conjugate of the field phi is the complex conjugate of the field, but derived with respect to time. And then we apply the second result, but in this case not anymore to momentum and position operator, but to this field operator. So we promote this in quantum mechanics, x and p to operator, and in quantum field theory we promote field to an operator and conjugate field to another operator, and then we apply the same commutation relation. So this leaks here and becomes that the commutation relation between the field phi evaluated in a certain position of space x commutator with the field pi evaluated in a certain position of space y, it becomes equal to, this is also some convention, 2 pi to the third delta 3 x minus y. This means, even if it's a little bit in disguise, but this relation here, this commutation relation between the two fields reflects perfectly this commutation relation here. This I get it wrong. Okay, I'm trying to do less calculation to speed up a little bit things, so without doing calculation it's easy to be wrong, because you have to remember in your mind what's going on. This is not 2 pi, but it's I times the 3 x minus y. Okay, this is what we impose to these two fields. So this commutation relation is just exactly the same of this. We just introduced this delta 3 to say that this commutator is 0 every time that the field phi and its conjugate pi are evaluated in two different positions in space. But when we evaluate the two fields, or the commutator of the two fields evaluated in the same point in space and time is already implicit also here, must be the same time, then the commutator gives us I exactly as the commutator in quantum mechanics for position and momentum operator. Okay, and this is something that we impose by hand. Okay, why we impose? Well, it's something that in theoretical physics a lot of time you just try to do something and then you see that this thing works, and I think this is the case. Maybe there is some deep reason to impose this, but I think that just the reason is it's like this in quantum mechanics. So we also want that this commutation relation holds in quantum field theory, because if quantum field theory is a generalization of quantum mechanics, then also the commutation relation that works in quantum mechanics must generalize to quantum field theory. I think this is the deepest, deep reason. But now it comes the catch. Also here, without doing too much calculation, once we impose this, we have a commutation relation also on this number that are inside phi and phi dagger. And let's see what is the commutation relation of these numbers inside phi and phi dagger. I cancel this. Let's just put okay. So we came to this commutation relation between the field and its conjugate, and we imposed this because we want the same laws that applies in quantum mechanics. So we impose this, and imposing this, you can try to check on, or you can read it in a book. Also in this case, I will not go through all the calculation because it's boring, and I don't think it adds something important to our discussion. But imposing this commutation relation between the field, and noticing that in the case of the scalar field that obeys this Lagrangian mechanics, the pi field is equal to, so pi field operator is equal to the derivative with respect to time of psi dagger. So in this case, the pi field operator will contain A dagger and B, and these are still numbers. But imposing this, we find, so this is finding, we find that the commutation relation between A and A dagger, and this we promote also to operators, it's the same of the commutation relation between B and B dagger, which are also promoted to B operator. Yes, this we evaluate in P and Q, but let's do a simple case. Let's suppose for a moment that this is evaluated on the exact momentum P, and also this. So all of them are evaluated in the same momentum. Okay, this commutation relation, it's 2 pi to the third. Okay, this is super important. You just can't see it yet. If I evaluate these two different momentum, so A evaluated in P and A dagger evaluated in Q, so where P and Q are different momenta, here we have 2 pi to the third delta 3 P minus Q. This is the same as before, to say that this delta here means that the commutation relation is 0 everywhere. It's just not 0 if we evaluate the same in the same momentum. If we evaluate them at the same momentum. Okay, and in this case, of course, you can see that these are evaluated in some momentum, not in some position as the field. Okay, this is super important, and this is, of course, this momentum argument holds also for B and B dagger. This is super important because these are commutation relations that we get in quantum mechanics for quantum harmonic oscillator. So for quantum harmonic oscillator, we have these commutation relations between A and A dagger, which is equal to 1, okay? And this has the same structure. There is this 2 pi to the third, which bothers a little bit, but it's just a real number, and also in this case it's just a real number. So the commutation relations between these two numbers are exactly the same commutation relation in quantum mechanics of the creator, this one, and annihilator operator of energy level in the quantum harmonic oscillator. So we jump to the conclusion that these two guys here that are contained in my solution of the field equation are two operators, A and B dagger, that creates and destroy something. Okay, as the operator in the quantum harmonic oscillator creates and destroys energy modes. In this case, they create and destroy not energy level in the quantum harmonic oscillator, but plane wave modes. So this guy here creates a plane wave with momentum p going in a certain direction, which is defined by the frequency. But anyway, this other one, it's destroying, so it's annihilating a mode with momentum p. In particular, this is annihilating an antiparticle, and this one is creating an antiparticle. To understand this creation-annihilation business, let's talk a little bit, like really 10 minutes, about the quantum harmonic oscillator, and then we will really see how this creates and annihilates particle, and that is the conclusion of this part of the lectures on how we quantize fields. So how this quantum harmonic oscillator works? We are describing a quantum mechanical system which is something that has this potential. V of x, it's something quadratic like this. So we have that the Hamiltonian of the harmonic oscillator, as you remember from classical quantum mechanics, the Hamiltonian of a system is something that describes the total energy of the system, and this is an operator. Hamiltonian operator will be the kinetic energy of the particle inside the harmonic oscillator, so p squared over 2m. This is also equal to 1/2 mv squared minus, and this is the potential, 1/2 mass of the particle, if we are talking about a particle, omega squared x squared. So the Hamiltonian, it's a function of the position of operator and momentum operator. But we can do a clever thing in this case and define creation and annihilation operator. So we define a certain operator A, which will be a function of p and x, which we will not see what is the function, we don't care now, and a certain operator A dagger, which will be another function, we will call it g, for example, of the two operator p and x. And the role of these two guys is to create, this one creates an excitation in the energy level in the quantum harmonic oscillator, and this guy here destroys an energy mode, or an energy, how do you say, a quantum of energy in the quantum harmonic oscillator. So the Hamiltonian applied to the wave function with n, let's say n energy excitations, will give us the energy En of the system times n. Okay, so this is simply the eigenvalue equation. Hamiltonian applied to the eigenstate of the energy, it's equal to of the energy of the state times the state. Okay, what happens if I apply A to the okay, we have two principles just to understand a little bit what happens if I apply A and A dagger. The first principle, or it's more like a mnemonic thing to remember how A and A dagger look like. A dagger A applied to the state with n energy excitation, so with n quantum of energy, gives us the number of the quantum of energy applied always to the state. So the eigenstate, like this is n is an eigenstate of this multiplication here that gives us the number of energy excitation in the system. Okay, the energy En of the system in the quantum harmonic oscillator is equal to h bar omega, where omega is the frequency, times 1/2 plus n. Okay, so we have a ground energy, and then we can add n excitations. Okay, so the Hamiltonian, in terms of the creation and annihilation operator, looks like this: h bar omega 1/2 plus A dagger A. Okay, so that the Hamiltonian applied to the state n gives us the energy of the state n. Okay, and this is the first one. And then we also know that A and A dagger alone, when we apply them alone to the energy state n, they create or destroy a quantum of energy. So for example, if I apply A to n, I will obtain something times n minus 1. If I apply this always operator, A dagger to n, I will obtain always something times n plus 1. Okay, this decreases the number of energy quanta in my system of 1, and this increases the number of energy quanta in my system of 1. The factor that I have to put here is just such that the multiplication of these two gives me n. So for example, we can choose, okay, it's not that we can choose, it's that's how it is. This is square root of n, and this is square root of n plus 1. Yes, so that we can see that if I apply A dagger A to n, I first apply A to n, so I apply the annihilation operator to an energy, a quantum state with n quantum of energy inside, n quanta of energy, and so I obtain A dagger. A applied to n is equal to square root of n times n minus 1. And then I apply A dagger to n minus 1. So this will be square root of n. A dagger applied to n minus 1 will give us square root of n minus 1 plus 1. So again, square root of n. And the state will be n minus 1 plus 1. So will be n. So we see that A dagger A applied to n gives us the number of energy quanta in the system times the wave function of the system. Okay? So this is mathematically how the creation and annihilation operator work in a quantum harmonic oscillator. And just the only thing that you have to remember is that when I apply A to my state with n quantum of energy, it removes one quantum of energy. If I apply A dagger to my state of n quanta of energy, it adds one quantum of energy. Okay, and this, since we found, okay, and of course that's the important part. We found that we can find, if I apply the commutation law, the commutator between p and x to the quantum harmonic oscillator, and to the function of x that these two guys are, I obtain that A dagger, so the commutator between these two operators, is equal to 1. And this is exactly analogous, it's structurally analogous to what we obtained in quantum field theory, which was that A dagger evaluated in the same place is equal to 2 pi to the third. These chalks are becoming very, very thin. Okay, so we found out in our quantum field theory formulation that these coefficients that are in front of the modes that are solution to my equation, my field equation, are just the creation and annihilation operator of quanta of energy. Every quanta of energy will correspond to a particle. Let's see how it works in a without doing too much math. Now we will have a lot of fun visualizing a little bit what happens when I apply A and A dagger and B dagger. So we can do this remembering that we have our three fields at our disposal. So scalar. Let's start with scalar. We found out that psi is equal to let's take psi as a field. This is a field operator, so it adds and removes particles or antiparticles. But let's do it in a fun way. Okay, here we have x. Here we have psi of x. In this case, psi of x is not anymore the operator, but it's just the value of the field in this case. So if we are in a state in which I have zero excitation, zero quanta of energy, I am in this state here that I call zero. Okay? What happens if I apply B dagger to this state? B dagger to this state 0. B dagger depends on a certain momentum p. So I can do B dagger of p, of a momentum p, apply to the state 0, exactly as in the case of the quantum harmonic oscillator, adds a quantum of energy. But in this case, B dagger is associated to this wave here. So it adds a plane wave, in this case, something like this. Okay? Everywhere, all throughout all the space. So the field that was completely flat was all 0. When I apply B dagger to this system, I see that the field starts oscillating with this plane wave. So it's just a mode of oscillation. What B dagger really does mathematically is introducing an oscillation in the field. Okay? What happens, for example, if now I add, so this one will be the state with one particle, one antiparticle in this case, because B dagger is associated to antiparticle, with momentum p. Okay. What happens if to this system now I add another antiparticle, for example, B dagger, but in this case of another momentum q. Okay. Another momentum q to this state which already have a particle with momentum p. But in this case, let's say also that q is larger than p. Okay? In this case, what I do is just introducing a new mode of vibration in the field. So the field not only vibrates with this blue mode, but also start vibrating with a red mode. Which, if you notice, I made it with smaller wavelength because the momentum of this mode it's bigger than the momentum of the blue mode. Okay, so now in my state there is a superposition in my field. There is a superposition between this blue mode and this red mode, which correspond to two particles. So that what it really corresponds is it's one particle, or better, one antiparticle with momentum p and one antiparticle with momentum q. Why they correspond to an antiparticle with momentum p plus an antiparticle with momentum q? Well, this is because every time I add one of these modes, I am adding a quantum of energy, which is E p. In this case, when I do B dagger p, I'm adding to the system, which had zero oscillation, an oscillation that corresponds to a quantum of energy of p squared plus m squared. So I'm adding the energy corresponding to a particle which moves with momentum p. When I add a particle or an antiparticle with momentum q, I'm adding a quantum of energy eq. So with energy q squared plus m squared. And I can play with this. If I want to remove, now I can just remove antiparticles, so I can just apply B of Q, for example, or B of P, because if I apply, for example, A, and I try to remove a particle from a system that has no particles, I get 0. So that's the rule, no? If I just try to remove something that is not there, I get 0, flat. Everything disappears, okay? But I can play with this system, so I can add particles, add antiparticles, or remove particles, remove antiparticles. And all of this, all this machinery here is encoded in the solutions of the Klein-Gordon equation in this case, but more in general is encoded in the solutions that I get, the general solution that I get of the equation of motion of the fields after quantizing the solutions. Okay, I hope this gives you a little bit of an intuition on what we are doing and where we are going, even though you can just do particle physics without even knowing this stuff about introducing a mode of oscillation inside my field, etc., because this is a big approximation. And when we do computation, we also need to know, like, yeah, this will come later, but when we do computation, we always use particles with definite momentum, because we always work in momentum space. But this means in coordinate space that the particle is nowhere, or it's everywhere, okay? So it has no precise position. The scalar, we had the solution of the scalar field that pops out of the Klein-Gordon equation, which in turn pops out from the Klein-Gordon Lagrangian, or the scalar field Lagrangian, and analogously we can have the solution of the Spinor field and the solution of the vector field. Let's just write them down for completeness. So this guy here, this solution comes from d mu plus m squared phi equal to 0. And then this is promoted to a field operator. If I have a spinor, the solution is, wait, spinor we did in red, let's make it in red again. The general solution in the case of the spinor of the Dirac equation, it's then of course I can also conjugate these various solutions to obtain the other creation and annihilation operator, but for now, who cares? Is equal to the 3p over as you can see, the structure is very, very similar. This is the solution, this is Spinor solution. It's a superposition of 4 different solutions, so we'll have not 2 operators but 4 operators. These always are operators that creates and annihilates particle and antiparticle, and in this case with a certain polarization state. And this comes from the Dirac equation. So or better, this comes to the Dirac equation, then we quantize, and we get these two operators that annihilate or create particle. And pay attention, the commutation relation between these two, which are in the Spinor field, are different from the commutation relation of these 2 operators that are in the scalar field. That is because of the Pauli's exclusion principle, and so we have that in this case the commutation operation that we instead of applying commutation, we apply anti-commutation, something like this. But yeah, it's not really relevant to our discussion now. But just know that we apply to our physical law some constraint that doesn't allow us to put more than one quantum of energy in a certain momentum P with a certain polarization state S, because Pauli exclusion principle doesn't allow two fermion for being in the same quantum state. Okay, and this general solution for the Spinor operator, come from the Dirac equation. Then last thing we see is the vector. In the case of the vector, I write it down, then I check if it's true. Solution of the vector is something like yes, and this of course is S. Okay. Yes, and this equation here, so the general solution for a vector field come from the Maxwell Lagrangian or Maxwell equation, which is the mu f mu no equals 0. This is the how do you call it? The free Maxwell equation. Okay, and this in turn. Okay, all these three equations, Klein-Gordon equation, Dirac equation, and Maxwell equation, all of them can be written down inside a Lagrangian. And so there is always our source of truth underneath, which is the Lagrangian. Two considerations on the vector field. In the vector field, you also see that there is a polarization state, and the polarization state for a massless vector fields, for example for the photon, can only have 2 degrees of freedom, and that is for gauge invariance. We will talk about gauge invariance later. For now, it's too long to introduce what does it mean, gauge invariance, and why the polarization state can be only 2. But this S represents 2 polarization states, and so we can have 2 of these vectors here. We can give a representation, for example, for a wave that's moving only on the z direction. We have epsilon mu 1, which will be equal to 0, 1, 0, 0, and epsilon mu 2, which is 0, 0, 1, 0. You see that this is a 4-component object, but only there are only 2 independent of this 4-component object, not 4 independent component objects, and not 4 independent 4-component objects. And the second remark on this vector solution, this vector field solution, is that in this case we didn't write down A and B like in the other two. Here we have A and B, A and B. In this case we have A and A dagger. This is because for the vector field, for example the photon, the particle coincides with the antiparticle. So we don't have a complex conjugate of this solution here, or at least the complex conjugate of this solution here corresponds to the exact same object. Okay, so the particle and antiparticle, the photon is the same as the antiphoton. That is what this formula is telling us. Okay, I think for this subject here we did a lot for now, and from now on we will practically almost forget about these 3 objects here and just work with the Lagrangian and work with symmetries in the Lagrangian to define how our particle interact, because this solution, and this solution are all solutions for free fields, so fields that are not interacting with anyone else. Now things becomes more complicated because we want to add interaction, and so we are smart enough not to talk about these explicit solutions anymore, but work at the level of the Lagrangian. By now we already know everything about the Lagrangian, and so it will be super easy to introduce the interaction between fields. Today is a joyful day because we will finally see the quantum electrodynamics Lagrangian and the theory of quantum electrodynamics, which is arguably the most successful quantum field theory in history. For doing this, I want to do a little recap very fast of what we have seen so far. This is the most concentrated summary of what we have seen so far. So what we did is starting with observations and observations of reality. This is also what physicists did, constructing and building these theories. So observations about reality lead us to quantum observations. So for example, double slit experiment, the fact that the hydrogen atom has quantized energy levels, all this kind of crazy stuff that can only happen in quantum mechanics. Then we had relativity, so observations that the speed of light is the same in every reference frame. That's something that led to relativity, so the formulation of Lorentz transformation and how a reference frame transforms if, or better, how can I transform and mix space and time when I start to go fast. And then we had a third class of observation, which is electromagnetic effects. So for example, Faraday law, Coulomb law, etc., that were all unified in Maxwell equation. So all these three parts, which look like independent part, quantum physics, we derived in quantum physics the Schrödinger equation, that is led by observation in quantum physics. Then from relativity, the observation led to Lorentz transformation and the mixing of space-time when we do calculation in relativity and all kind of crazy stuff. Electromagnetic observation led to Maxwell equations. So Maxwell could unify in a way all the crazy stuff that people were seeing, playing with electric field, magnetic field, and charge going around. So for example, charge generating electric field, moving charge generating magnetic field. All this information here about the observations in electromagnetism is encoded in Maxwell equation. Then we go a step deeper and we enter inside theories, because this is already theories, but these look like three separate theories. We did a step, we did another step, and we went unifying relativity and the Schrödinger equation, because Schrödinger equation doesn't work in relativity, and to unify this, this is wrong, no, yes, it's right. So we have relativity equation, so Lorentz transformation, that are incompatible with Schrödinger equation. We unified this into Dirac equation. So these two now are unified into Dirac equation, and then Maxwell equation were already compatible with relativity, but were not written in a manifestly covariant form. This is how you write electromagnetism, so Maxwell equation, in a manifestly covariant form. So also this now it's unified with relativity. From these two theories, which are Dirac equation and Maxwell equation in relativity, we found with a lot of mathematics, with a lot of principle, Dirac Lagrangian and Maxwell Lagrangian, which we called L Dirac and L Maxwell, for short, Maxwell. Okay? Now it's the time to unify also these two theories. So in unifying these two theories, we will use local gauge invariance, which we will see what this principle is. So we will use this principle for unifying these two theories. It's not the only way of doing it. One can also say, oh, I compute, I see what is the current here, which is the Noether conserved current, and I use that as the electromagnetic current. But okay, we will do it starting from this local gauge invariance principle. So we will require the gauge invariance to be local, and we will see in a moment what that means. But this will lead us to the most beautiful formula of all physics, which is the Lagrangian of quantum electrodynamics. It's the first Lagrangian of a complete quantum field theory which interacts, so with interaction turned on. And I beg you to learn and to understand as best as you can quantum electrodynamics, because then the standard model and all the particle physics will be a generalization of quantum electrodynamics, because in quantum electrodynamics is the simplest model of particle physics that we will see, because this is just electron or charged fermion interacting with light, so with photons. Then we will add new interaction, new symmetries, and new particles when we go to the Lagrangian of the standard model. But if you understand very well the logic of the Lagrangian of quantum electrodynamics, then you will also understand the logic of the interaction, of the new interaction, which will be strong interaction and weak interaction, and all the new particles that come out of that. The only new things that we will introduce, which is outside of the quantum electrodynamics Lagrangian, is the Higgs mechanism and the need of the Higgs boson, but we will talk about that. And then just to see that it's not that we are going further and further from reality, because reality is here. What we observe, it's here. Then we do this, and we obtain three separate theories. Then we unify these two and these two. Then we unify these two, and we obtain a complete new, or what it looks like, a complete new theory. But this is not farther from reality, because from this theory, so from the Lagrangian of quantum electrodynamics, we can derive the Feynman rule to explain these processes, so to explain the interaction between light and matter. And from the Feynman rule, we can derive cross-sections and decay rates. These are two examples of observables that we can actually measure, for example, inside particle accelerators. And these are, again, observations that are led directly by the prediction of quantum electrodynamics. So all the physics that we see here, all the theory that we see in this blackboard, is sort of pinched between observations here and observations here. So it's very well connected with reality. It's not some crazy theory that we go a step further, a step further, a step further, as a lot of people think when they just see the Lagrangian of quantum electrodynamics. They say, well, we derived this, but we are completely far from reality. No, we are really close to reality, because then directly from this Lagrangian we can do, we can compute physical observables. We will talk about the simplest symmetry in quantum physics, which is the phase shift. And then we will generalize this symmetry to quantum field theory. So we will use a generalization of this symmetry for constructing the quantum electrodynamic Lagrangian. This is very important, and it's very important to understand this symmetry in quantum physics. So let's start with a simple example, which is the same thing we saw in the beginning, which is the double slit experiment. So this will also serve as a recap of the rules for amplitudes, which will be super helpful after we introduce the Feynman diagrams, because the rules that apply to Feynman diagrams are the same rules that apply for amplitudes in quantum mechanics. Okay, we will see what this means in a while. So for the double slit experiment, I have a source, I have a detector of particle, and I have a certain point x to which I want to know what is the probability of the particle starting from the source and reaching this point x. The particle can go through slit 1 and land in x, or can go through slit 2 and land in x. What I do, if you remember from the beginning, I have a complex number, which is the amplitude of the particle going from the slit to the point x on the detector, which is the sum of the two possible ways, or the sum of the two complex numbers associated to the two possible ways that the particle can go in the point x. So an amplitude associated to the particle going to point x passing through slit 1, and this I call amplitude phi 1, plus an amplitude of the particle going to the point x passing through slit 2, and this I call phi 2. Okay, so this is the amplitude associated to the particle, to the event of the particle starting from here and landing here. I don't know, I don't see what happens in between because I don't measure in which slit the particle passes. Then if I want the probability for the particle going from here to here, what I do is simply squaring the amplitude. So I take the complex conjugate of the total amplitude times the total amplitude. This is because I take the complex conjugate because this is a complex number. What does it mean that this is a complex number, which is a sum of a complex amplitude plus another complex amplitude? Well, the complex number means that I can represent these two amplitudes as vectors in a two-dimensional space. In particular, if this axis is x, this axis is y, phi 1 can be, for example, this arrow here. And not only that, now we'll see why I'm talking about vectors. I'm talking about vectors because phase shifting is equivalent to rotate this vector in the complex plane. So that is why I'm representing the amplitudes now like vectors. And we will see what does it mean invariance under phase shifting. That is what we want to see. So for example, this is phi 1. And phi 1 I can also write it like rho 1, which is the length of this vector, okay, times e to the I alpha 1, let's call it, okay, where alpha y, it's alpha 1, sorry, it's the angle of this vector with respect to the x-axis, okay. Since this is the sum between alpha phi 1 and phi 2, I can also add phi 2 here, which will have a magnitude. So phi 2 will have a magnitude rho 2 and a phase e to the I alpha 2. The magnitude of phi 2 is the length of this vector, and the phase of this vector is the angle with respect to the x-axis. So this is alpha 2. Okay? Then the total amplitude will be the sum of these two vectors. So the total amplitude will be the vector that, exactly as you do with vector sum in classical physics, will be a vector that starts from the tail of the first one and reach the tip of the second one. So this one will be the total amplitude, and then in the end, when I want to compute the probability, I square the total amplitude. Squaring the total amplitude means that I lose every information that I have on the phase of the total amplitude. So I don't care anymore what is the inclination, what is the angle of this complex number in the complex way, in the complex plane, but I just care about the magnitude of the complex number in the complex plane. So I just care about the magnitude of the total amplitude. Okay? This reflects in an invariance. An invariance is I can change something in the description of my physical system without changing the system itself, without changing the physics. So what I can change here is the phase of these two objects here in the same way. So I cannot change the phase in a different way, but if I multiply everything by a phase factor, so I apply a phase shift, the total physics does not change. So if I multiply here e to the I theta, okay, this guy here, I call this phi prime, so I will have a new total amplitude, which is the same as before, but rotated by a certain angle pi. This is equivalent to rotate phi1 of a certain angle pi, sorry, not pi, certain angle theta. So rotating the total amplitude of a certain angle theta is the same as rotating both of the two components of the same angle theta. Okay? The important part is that the relative angle between these two, it's not changed. Okay, so if the relative angle between phi1 and phi2, it's not changed, as long as this angle is not changed, the physical result that I get changing phi1 and the orientation in the complex plane of phi1 and phi2 does not change my physics. Okay, this is important. This is, I think, the simplest example of symmetry in physics. So I have something that if I change this thing, the description of my physical law does not change. Another way of saying it is that phi and phi prime equal phi times e to the I theta describe the same physical system. Okay? They are two equivalent descriptions for my physics. This does not change because, of course, we already saw it. Why doesn't change? Because when I square it, when I take the absolute square of this number, what I care is just the length of the vector, not the orientation of the vector in the complex plane, but let's see it also mathematically. It does not change because if I do phi prime times phi prime, this conjugate, okay, this will be phi prime squared. This is also, okay, phi prime conjugate, it's phi prime, sorry, phi conjugate, so this conjugate, times e to the minus I theta, and then times phi, times phi prime, it's e to the plus I theta, phi prime, phi. Okay, this is phi prime conjugate, and this is phi prime. Okay, the probability computed with the new amplitude, the new total amplitude phi prime, it's equal to this object, but then we have a property in complex number when we do computation between complex number, that is e to the minus I theta times e to the plus I theta is simply equal to 1. So this object here is equal to 1. And so this is also equal to phi star phi, which is also equal to phi square. So you see that phi prime squared, absolute square of phi prime, it's the same object. It's exactly the same as absolute square of phi. Okay, I repeat it another time. Changing the phase, the total phase, changing the phase of the total amplitude result in an equivalent, in a completely equivalent description of my physical system. So does not change the underlying physics. And this is called asymmetry. So it's called to have a symmetry in my system. And symmetries are very important, are all that is in quantum field theory, because now we will see that this symmetry generalizes also with the Dirac Lagrangian. So let's try. Of course, asymmetry is a symmetry if the Lagrangian of the system is symmetric under that transformation. Let's see what does it mean. So now we want to answer to the question, it's the Dirac equation, it's the physics described by the Dirac equation symmetric under global phase shift? Well, let's see. If the physics is symmetric under global phase shift, and I write down a Lagrangian, so let's do a recap. Dirac equation was I gamma mu d mu minus m times phi psi equals 0, where this is a Dirac spinor. This is the equation of motion from the Euler-Lagrange equation from this L Dirac. So this equation here has a Lagrangian associated to it, which is psi bar I gamma mu de mu minus m psi. Okay. Now, if the system, it's of course the Dirac Lagrangian we build it from quantum mechanics, and if in quantum mechanics every physical observation does not depend by a global phase shift, then also the Dirac equation must describe something, must describe some physics which is not dependent under global phase shifting. How do I check this? Well, this is the power of the Lagrangian again, because we will work in the we will work with Lagrangians now because they are super powerful. Because they are super powerful because if I want to check if my physical laws are invariant under this transformation here, so under this is called U1 transformation in jargon. We call this U1 transformation a phase shifting. So U1 takes a certain object, in this case the Dirac spinor, and sends this object into psi prime equal e to the I theta psi. So to see if our physics is invariant under this transformation, what we check is if the Lagrangian describing my physics, it's exactly the same as the Lagrangian when I do this phase shift. Okay, if this happens, then my physics is invariant under this transformation. So let's see if this Lagrangian, this Dirac Lagrangian, is invariant under global phase shifting. I say global, but we will see what does it mean when we will introduce local phase shifting. So, is the Dirac Lagrangian invariant under global phase shifting? Well, it's very easy to check. Let's do something. Let's put this guy here in white and this guy here, psi prime, in red, so that we can distinguish when we are when we are describing a physical system with a local phase shift and without the local phase shift. No, sorry, with the global phase shift or without the global phase shift. So in this case, L prime, I will call it L prime in red. This is just a color code to understand at site where we are. Okay, Lagrangian of Dirac, it's something like this. Yes, we have it already here. Let's write the red Lagrangian. So in the first, okay, the red Lagrangian is equal to psi prime bar I gamma mu de mu minus m psi prime. Okay, so psi prime and psi are related by a global phase shift. And now we will also write it shifting the phase. So we will write explicitly. And this is, no, this is in white this time, psi bar. Psi bar transforms as e to the minus I theta. So times e to the minus I theta. Let's put theta in red, just to understand that this is what causes the thing to become red, in a sense. I gamma mu de mu minus m, and then also this I will write it explicitly, so e to the I theta psi, and that's it. Okay, now theta is a constant. It is a constant. That means that I can filter theta through all these operators here, which is a derivative operator, but the derivative of a constant is just 0, so I don't need to derive this, and I will just put it here. But of course, if I put e to the I theta close to the e to the minus I theta. These two annihilate and it becomes 1. So e to the I theta times e to the minus I theta is equal to 1. And so we can simplify this term with this term. And then we have psi bar I gamma mu the mu minus m psi, which is the Dirac Lagrangian, as you can see here clearly. Okay, so we prove that the Lagrangian of Dirac Lagrangian is the same if I change the phase of my Dirac spinor. So the physics is invariant under global phase transformation. Also, when I'm considering the Dirac Lagrangian. Now we do what will lead us to the unification of quantum mechanics. So yeah, practically from quantum mechanics to electromagnetism, or more generally the unification, or no, more specifically to the unification between the Dirac equation and the Maxwell equation, and will be amazing. Okay, and this is an assumption. The assumption is, or a question that we want to answer. The question that we want to answer is, what if the phase is local? Local means that theta is not a constant anymore, but depends point by point in the space-time. So theta is something that depends from the point we are in space-time. E to the I theta that depend on x, where x is equal x mu. Okay? So what happens if instead of having a constant phase, I have a not constant phase, but a phase that depends on the point I am sitting in space-time? Is my physical law still invariant under this transformation or not? Well, this is precisely what we will check now. If the Dirac Lagrangian is still invariant under local phase transformation. So the difference between local phase transformation and global phase transformation, it's, now we can talk about this, local, it's phase transformation of the type theta that depend on x. Global, it's simply theta, which is a constant and does not depend on x. So I shift every point in the same way. Let's see what happens in this case. So what happens to the Dirac Lagrangian under local gauge transformation? In particular, what happens to the Dirac Lagrangian under this particular local gauge transformation, which we call U1, which corresponds to a phase shift. It's exactly the same thing as a phase shift. How does, so we write here the Dirac Lagrangian equal to psi bar yes. How does the local gauge transformation U1 work? It simply takes the spinor, the Dirac spinor, and it transforms it as psi prime equal to e to the I. Let's modify it. It will be, respecting our notation, it will be theta that depend on x, but actually we want also to explicitly define the electric charge, or yes, the electric charge associated to the spinor field, and we want to put it here. So let's rescale our gauge transformation and call theta of x, theta dependent on x, we call it q times alpha that depend on X. This is just rescaling our gauge transformation and factoring out a charge. So this becomes e to the I q alpha that depend on X. This is the only things that changes between local gauge transformation and global gauge transformation. It's that now the phase factor depends on the position of the space-time, okay? And this times psi. So what happens to the Dirac Lagrangian when I apply this local transformation? Let's see. First of all, it's convenient to separate the mass term and the kinetic term. So the Dirac Lagrangian, it's something like, we can write it like psi bar I gamma mu de mu psi minus m psi bar psi. Okay, this guy here we call kinetic term, and this guy here we call it mass term. Okay, for very obvious reasons, this has the mass, but in general, in any Lagrangian that we will see in quantum field theories, when we have the field multiplied by himself, so when the term which is squared in the field, it's always associated to the mass. And this is the reason of this, without going too much into detail, but can be seen as a unit reason. So this term here has has the right unit to be associated with a mass term, and is the only one who has the right unit. But okay, let's not dive too deep into that. Just know that this is the mass term because it has associated a mass to it, and this is the kinetic term because it's squared on the fields, but there is derivative inside. Okay, so it's not the same unit of this term here, but okay, parenthesis closed. What happens to these two terms? Well, let's do first the mass term. So the mass term under this gauge transformation, we put this in blue. So m times psi dagger, psi bar prime, psi prime. You can check by yourself, but this is, oh no, let's do it properly. M psi dagger psi, and then here there is e to the I minus I q alpha of X, e to the plus I q alpha of X, and so this and this goes away, and the mass term, when I change the phase, even though I change the phase locally, point by point in space-time, I change the phase in a different way, the mass term remains invariant under local gauge transformation. So this term here is invariant. Now the troubles come, because we try to see if also the kinetic term is invariant. Let's see. So kinetic term, it's something like this. Let's put it in the... in my mind there is always this word, let's put it in this reference frame, but this is not a reference frame. This is just, let's put it in this gauge, we could say, yes. Let's sit in this gauge here in which we are in the blue gauge, let's call it. So psi dagger prime, in the blue gauge only the things are blue because the other one remains unchanged. I gamma mu de mu psi. Okay, what changes here? It's simply that let's see explicitly. This will be psi bar e to the minus I q alpha of X times I gamma mu de mu, then parenthesis is important. The derivative operator is applied to everything. So to this psi blue, psi prime, sorry, this psi prime, which is e to the I q alpha that depend on x psi. So the derivative operator, it's applied both to this and this, okay? Every term is trivial except for the derivative operator, because now we have to derive, and deriving this part here is not trivial. In particular, we can use that, so we will do now derivative of e to the I q alpha with respect to x, the alpha that depends on x, times psi. Also psi depends on x. Okay, so we have the derivative of this term times this term plus the derivative of this term times this term. Okay, so this will be derivative demu e to the I q alpha that depend on x times, so this term here by itself, times psi that depend on x, plus e to the I q alpha that depend on x, derivative demu psi that depend on x. Okay, how to do this derivative? Well, just remember that the mu it's actually d over dx mu, but this depends on alpha that in turns depend on x. So this we can also write as derivative of derivative of alpha with respect to x mu times the derivative with respect to alpha. Okay, this is just simple chain rule is called, I don't know. So this will be the mu alpha of x times the derivative with respect to alpha of the object inside. So times derivative with respect to alpha, which is a bit weird written like that, but d over the alpha. Okay, so now this term here will be the derivative with respect of alpha is simply iq e to the iq alpha of x times the mu alpha with respect to x times psi. Yes, and this is the first term, plus the second term, we will write it like as it is, but as it is, it's we can factor, okay, but okay, this is, yes, e to the iq alpha of x, derivative with respect to the various x psi that depend on x. Okay, so this is the derivative of this term, and you see that is not trivial at all. Chalk always down. Perfect. So now we can write down this kinetic term using this definition of the derivative of the term in the gauge, in the new gauge. Let's see what happens. Using this derivative here. So using this derivative here, we have that this will be equal to psi prime, sorry, not psi prime, psi bar, e to the minus I q alpha of x. Now, yeah, no, let's do it one step at a time, otherwise we will do it wrong for sure. I gamma mu, and then there is the mu, this time this guy here, but the mu, this guy here, we calculated before, and let's see what we can collect. We can collect this term here and this term here, even though in this case we apply the derivative to this term, but we see the common term are this and this, and also in this case this and this. So we factor out e to the iq alpha of x, and then we move this term before, so the mu, This will be the term. This I write after everything, after the parentheses. And then I have plus IQ plus IQ. As I already put, derivative with respect to the various x, the space-time coordinates, alpha of x. And then this is multiplied times psi. Okay, you can see that this guy here now it's free, can filter here, and it goes to 1 with these two. So these two annihilate again. And this becomes, yeah, this term here becomes psi bar I gamma mu, now I multiply, so now I do all the multiplication of this parenthesis, gamma mu the mu psi, and then I have I times I, which is minus 1, gamma mu the mu, so minus I q, gamma mu, I also have this term here, which I forgot, so it's psi bar gamma mu psi times the mu alpha. Okay, this I put in parentheses because it's important. You see that the kinetic term in the first gauge, so after I change my gauge, after the gauge transformation, it's the same as the kinetic term minus a part. So the Dirac Lagrangian, it's not invariant under local gauge transformation. This is the claim. This is the final claim of this calculation. Dirac Lagrangian, it's not invariant under local gauge transformation. We checked the kinetic term, which is not invariant, as you can see, the mass term, which is invariant. So putting these two together, the mass term plus the kinetic term, we discovered that this I keep here. This one is the kinetic term in the after gauge transformation, so it's prime I gamma mu the mu prime, yes. Okay. So putting together mass term and kinetic term, I discovered this. Let's see what I discover. I discovered that if I apply a local U1 transformation to the Dirac Lagrangian, this takes the Dirac Lagrangian, sends it to a Dirac Lagrangian in the new gauge, which is equal to, as you can see, mass term invariant, first part of the kinetic term I recover it, so it's equal to the old Dirac Lagrangian, but the old Dirac Lagrangian minus one piece, minus q psi bar gamma mu psi d mu alpha. And this accounts for the local gauge transformation. Do you see already also that if this alpha of x does not depend on x, so it's a constant, the derivative with respect to the space-time coordinates of this object here is 0, so all the new piece is 0. So we recover also the information that we had before, that the Dirac Lagrangian is invariant under global gauge transformation. So if I do a global phase shift, Dirac Lagrangian does not change. But it changes if I do a local gauge transformation. How to fix this? I mean, it's not something that it needs to be fixed per se, so it's not a problem per se. It's not that there is some deep reason why we want the Dirac Lagrangian to be invariant under local gauge transformation, but it turns out that if I try to fix this, I can describe and I can unify electromagnetism so Maxwell equation and Dirac equation. Let's see how it works, and there is another hint that I want to show you, which is this term here that I always put in between the parentheses, in between the brackets, which is the J mu term. I call it J mu, I call it a current term because this is a current, because hi, yes. Sorry, moment of distraction again. There is people entering the room while I record. And yeah, this term here, we can associate this term to a current. We didn't see explicitly the Noether theorem, but the Noether theorem just tells you that if there is a symmetry associated to your Lagrangian, then there is also a conserved current. And in this case, this is the conserved current, so this combination of fields with the gamma mu is the conserved current associated with the global symmetry in the Dirac Lagrangian that we just saw. So the symmetry associated to this factor here being a constant. This is a strong hint to associate this current here to the electromagnetic current in the Maxwell Lagrangian, and so unifying the two Lagrangian. This is not how we will do it. We will do it just now introducing a new piece, and we will see, but this is another way of unifying Dirac Lagrangian and Maxwell Lagrangian. So what we will do instead is to introduce a new piece in our Lagrangian, and this new piece that we will call L interacting must transform under this U1 local symmetry exactly in the opposite way than the Dirac Lagrangian transforms. So this new symmetry will be something like this new piece in the Lagrangian will be something like L prime int, so interacting Lagrangian in the new gauge, equal to L int. In this case, the same term, but with a plus. So plus Q psi gamma mu psi d mu alpha. Okay, perfect. This under the U1 global symmetry. So in this case, if we write down a Lagrangian which is L Dirac plus L interacting, this Lagrangian will remain exactly the same in the new gauge. So this will be L prime Dirac plus L prime interacting. Okay, this is so important because the two terms, this will be just a big Lagrangian that we can call L. It's not yet the quantum electrodynamics Lagrangian because we are missing a piece. But if we find a new piece of the Lagrangian that changes exactly in this way here, then we can write down a Lagrangian which is the sum of the Dirac Lagrangian and this new piece of the Lagrangian that we didn't find yet, that remains invariant under local gauge transformation. How does this piece look like? Well, we have an hint, strong hint, by how the Dirac Lagrangian transforms under local gauge transformation, local U1 gauge transformation, which is that to the Dirac Lagrangian we sum a piece which is dependent by the derivative with space-time coordinate of an object. And this reminds us the way that the vector potential field transforms, or the gauge transformation of the vector potential field in electromagnetism. This is something we didn't talk about, but we will talk about now. How does the photon field, in this case, transform under gauge transformation? We know from Maxwell equation and electromagnetic, like electromagnetic field, etc., that if I take the vector potential and scalar potential field and transform this field in a certain way, my physics remains invariant. So there is an invariance of my physics, in particular of Maxwell equations, under this transformation to the field A mu. A mu goes to A prime mu plus the derivative with respect to space-time of a certain field chi. Okay, we see that the structure is the same. We have the derivative with respect to space-time of a certain object, and the physics of electromagnetism is left invariant under this transformation of the vector field that in our theory will be associated to the photon field. And this is the perfect occasion for putting together the two theories, and in particular you can check, and we will check, that this piece here, the interacting Lagrangian, must be something like, if I take in this case a field A mu that changes like minus q, derivative with respect to space-time coordinates of the same local transformation that I apply to my Spinor field, then I can choose a piece. I can choose a new an interacting Lagrangian, an interacting piece of the Lagrangian, which is L interacting equal minus I don't remember if the I is there. No, it's not there. Minus q psi gamma mu psi A mu. Okay. Let's see if the new Lagrangian, so I can have a new Lagrangian, which will be yeah, let's cancel a little bit of things. These two I cancel. So the interacting piece is this, and this is the piece that I have to add to the Dirac Lagrangian. So the new Lagrangian, L, will be Dirac Lagrangian, so psi I gamma mu the mu minus m psi minus this piece here, minus q psi gamma mu psi A mu. This Lagrangian here is invariant under local gauge transformation, given that the field A mu transform under U1 transformation as A mu goes to A prime mu equal A mu minus minus q d mu alpha. Okay, so this Lagrangian here is invariant under local gauge transformation, and we will write it here. Local U1 transformation. Given that the two fields that are involved in this Lagrangian, which are the Spinor field psi and the vector field A mu, transform in a very particular way, in this way and in this way. So, given that the two fields transform in these two ways, then the Lagrangian is invariant. The Lagrangian is invariant means that if I apply a U1 transformation to this Lagrangian it's sent, so applying a U1 transformation to this Lagrangian means applying this U1 local transformation to the pieces inside the Lagrangian in this particular way. Then the Lagrangian becomes, goes to L prime, which is also equal to L. So is left invariant under this transformation. Left invariant under this transformation, Lagrangian invariant, means that the physics described by my Lagrangian, it's invariant under this transformation. The two Lagrangian describe exactly the same physics, and I have a degree of freedom, freedom of choice of choosing this particular, like my physics is independent by the choice I make of this factor here that depends on the space-time points. Okay, this is not yet the QED Lagrangian, but for coming to the quantum electrodynamics Lagrangian, it's very, very easy. And in particular, it's not yet the quantum electrodynamics Lagrangian because we miss a kinetic term for the photon. Let's see how it works for going from this invariant Lagrangian to the QED Lagrangian. So we have this Lagrangian, which is invariant under local gauge transformation of U1 local gauge transformation. So invariant under this kind of transformation. How can we now go to the quantum electrodynamics Lagrangian? Well, simply, first of all, let's expand this Lagrangian. So we have I gamma mu de mu psi psi minus q Okay, how to go to the quantum electrodynamics Lagrangian? Well, first of all, we have three terms in this Lagrangian, which are this one, and this one. We saw already what these three terms are. This one is the kinetic term for the Spinor field. This one is the mass term for the Spinor field. And this one is the interaction term. So this term will describe in our Feynman diagram that we will see short after this Lagrangian, the interaction between the Spinor field and the scalar field AMU. Okay. What we want to do now is to understand what term is missing. Well, what term is missing? It's simple. It's very simple because what could be missing is, since we introduce a new field, which is a vector field, it's missing the kinetic term for this field AMU, but could also be missing the mass term. I say could because there is a very important disclaimer. Mass term always for this field AMU. So to have a complete Lagrangian, I miss a mass term for this field and a kinetic term for this field. Well, for the mass term, the problem is it solves himself because photons are massless. So the mass term, it's not needed. We already know that this vector field describes photon. If the mass was needed, it will be a mess because adding a mass term for this field here breaks the gauge invariance, and this is exactly what happens with weak interaction, where the gauge boson, which are the analogous of the photon in this case, are massive. So massive gauge boson break gauge invariance, and we have to come up with the Higgs mechanism to maintain gauge invariance in our Lagrangian. But in this case, the problem is not there because the mass term is not there. Then we have a kinetic term for AMU. But we notice that this is simply Dirac Lagrangian plus or minus Q a certain J mu times AMU. This guy here, we remember this term from the Maxwell Lagrangian. The Maxwell Lagrangian was something like minus 1/4 F mu nu, F mu nu. minus J mu A mu. Well, if we rescale J mu here, the current, putting a charge, an electric charge here, then you see that this term in the Maxwell Lagrangian is exactly like this term in the invariant Lagrangian we built, and the Maxwell Lagrangian has already a kinetic term. So this term here is the kinetic term in the Maxwell Lagrangian that we are searching, kinetic term for A mu. I write it here also, mu nu is equal to the mu A nu time minus the nu A mu. Of course, this term here, F mu nu, it's or minus 1/4 F mu nu, it's invariant under the gauge transformation of A mu. So if I send A mu to, this is something that you can easily check, A prime mu minus equal A mu minus Q d mu alpha. This guy here remains the same. So if I put A prime mu inside F mu nu and I build F prime mu nu, F prime mu nu will be the same as F mu nu. Or but I now I didn't check explicitly, but I think this term would be the same. But for if this term is not the same, I would have to check. This term is the same for sure. Okay, so this kinetic term, it's very good because it preserves our gauge invariance, and so this is the kinetic term that we add inside the quantum electrodynamics Lagrangian. So now finally we'll write down the quantum electrodynamics Lagrangian, which is, let's make it colored. I just realized after some minutes of explanation that I had put an I too much in the QED Lagrangian, so I will redo the part of the QED Lagrangian. This is the correct, this time, quantum electrodynamics Lagrangian. This is a beautiful equation and is the simplest gauge theory. Let me do it straight. It is the simplest gauge theory that we will gonna see. So then things generalize in other gauge theories, but in this case we have a very beautiful theory. This is a beautiful equation. This is the quantum electrodynamics Lagrangian and written explicitly. So every term is written explicitly. You probably have seen more compact version of this Lagrangian, but we will comment it now and then see more compact version. If we have only the free part for the photon, what we recover is the free Maxwell Lagrangian. If we have only these two parts here, which are the kinetic and the mass term for the electron, or in general for the spinor field, we recover the Dirac Lagrangian. And this is the interaction between the spinor and the photon. So this term here, when we will see Feynman diagrams, we will not compute mathematically, like we will not derive explicitly the Feynman rules from quantum field theory, because this is not a quantum field theory course, but we will see that this free term for the photon, so this kinetic term for the photon, will give us the photon propagator, for who knows a little bit about Feynman diagrams. If you don't know what I'm talking about, no problem, we will see it later. This part here, which is associated to the Dirac Lagrangian in the quantum electrodynamics Lagrangian, gives us the electron propagator, or in general the Spinor field propagator, and this term here, which is the interaction between the Spinor and the scalar field, the Spinor and the vector field, or the photon, gives us the vertex. So this is a vertex with that describes interaction between a photon and the electron, or in general the Spinor. Okay, so from the quantum electrodynamics Lagrangian, we will derive the Feynman rule. We will not derive them, we will enunciate the Feynman rules, and from the Feynman rules, once you have the Feynman rules, you can compute physical observables, which are, for example, cross-sections and decay rates, and we can do a lot of physics knowing the Feynman rules. But we have to keep in mind that the Feynman rules that we will derive in briefly are given by the Lagrangian of the theory. That is why we give so much importance to the Lagrangian of a theory. Sometimes you find the quantum electrodynamics Lagrangian written in a more compact term with something called a gauge covariant derivative. What is a gauge covariant derivative? Let's see. The gauge covariant derivative is an operator that will simplify a little bit the notation of the quantum electrodynamics Lagrangian. I don't like it very much because it compactifies everything, so you cannot really see anymore where the photon lies, where the interaction terms lies, etc., etc. But it's something that is useful when we will go to more complex gauge theories, because then we will have a prescription which tells us that you simply swap the derivative operator with a gauge covariant derivative operator. So in this case, the gauge covariant derivative for quantum electrodynamics, it's something that tells you that this term that I had, so the kinetic term of the Spinor plus the interactive term, I gamma mu the mu psi minus q psi gamma mu psi a mu. So these two terms can be condensed in a way in the covariant derivative term. So simply I gamma mu, instead of having the derivative, I have a covariant derivative that accounts for the piece that I add to my Lagrangian to make the interaction piece to make my Lagrangian invariant under local phase transformation. So, psi. So the gauge derivative in this case must be something like this guy here must be the same as this guy here, so it must be something like I gamma mu times d mu plus I q a mu psi, so that this is I times plus I, which becomes minus 1. So all this part here will be psi, psi. Then we have I times I, it gives minus. Then we have gamma mu, that gives gamma mu. Then I have the other side that gives psi, and then I have q a mu that gives q a mu. So this is the gauge covariant derivative. Is equal to d mu plus I q a mu. With this prescription here, the quantum electrodynamics Lagrangian can be compactified a bit in a form that you are probably more familiar with if you already saw some quantum field theory, because usually they always use the compact form, even though it's less clear in my opinion. Lagrangian quantum electrodynamics in the compactified form, it's again minus 1/4 f mu nu plus an equivalent of the Dirac Lagrangian, but with the covariant derivative. gamma mu d mu minus m psi. This is the quantum electrodynamics Lagrangian, just written in a more compact way. Okay? It's something that, as I said, is a little bit less clear, but it will be useful when we generalize the quantum electrodynamics Lagrangian to the standard model Lagrangian. Last thing that we will see now, or in the next minutes together, will be how to derive, at least a sense, a flavor of how to derive the Feynman rules from the quantum electrodynamics Lagrangian, and how to use Feynman rules to calculate physical cross-section and physical processes. So how to relate the quantum electrodynamics Lagrangian to real physics that's going on in the world. Quantum electrodynamics and physical processes. Now we have the quantum electrodynamics Lagrangian. We have this object that depends on three fields, two Spinor fields, one Spinor, one anti-Spinor, let's say, and one vector field, which is the photon. How do we use this object here to compute physical stuff? How do we relate this object to physics that can happen? The big advantage of quantum field theory over quantum mechanics is that not only it's relativistic, but also can describe processes in which the final state particle, the number of final state particles is different from the number of initial state particles. That doesn't happen for quantum mechanics, in which, for example, we have always a number of fixed particles that our system, our physics can describe. So we can use quantum field theory for describing effectively, like very well, interactions between particles. Particles bouncing off each other, in a sense, particles decaying and producing other particles, or also particles bouncing off each other and annihilating, and in this annihilation process create new particles with the energy which is available in the after annihilation process. Okay, so this is what we can describe with quantum electrodynamics and in general with quantum field theory. Now, what is the simplest process for making an example in quantum electrodynamics? Well, the simplest process is something like an electron and a muon scattering. So we have muon electron that goes to muon electron. How this happens? Well, simply in a classical point, from a classical point of view, the muon and the electron are two negatively charged particles, so they repel each other. So if I shot a muon and an electron, one against the other, they tend to bounce off each other. This is in a classical sense. What happens? So, how do I describe my process using the quantum electrodynamics Lagrangian? Well, I have a muon here with momentum p1 and an electron here with momentum p2. The muon and the electron are both particles described by Spinor field. That is why I'm putting them in blue, because the Spinor field inside the Lagrangian is in blue. Then I shot one against the other. Then in between, I don't know what happens, so an interaction happens. Interaction. And then what I see is that in my final state, I have a muon with a different momentum. Before it started with momentum p1, now has momentum p3, and an electron, which also exits from this process, with momentum p4. So in this interaction here, which I don't know what happens in between, but I just know that there was an exchange of momentum between the electron and the muon. The exchange of momentum must be such that P1 plus P2, this of course it's not just momentum, but it's quadri-momentum. So every time I write P, I'm saying P mu, which includes energy. So its energy momentum must be equal to P3 plus P4. This is energy and momentum must be conserved in the process, in the total process. But what happens here? The quantum electrodynamics Lagrangian and quantum field theory comes into play when it comes to describe what happens at a fundamental level when the electron and the muon interact. And the way the electron and the muon can interact is encoded in the quantum electrodynamics Lagrangian, if we only have electromagnetism turned on. Otherwise, we have other terms which are added by other kind of interaction, in particular by the weak interaction. But in this case, we consider only the electromagnetic interaction, and one of the possible way of this process happening, it's represented by this Feynman diagram. So let's start from the beginning. What I see in my experiment is just an electron with momentum P2 and a muon with momentum P1, so initial state. And then I see final state. I don't see what happens in between, what happens in the interaction. And the initial state in quantum field theory, so the assumption we make, it's just a plane wave with momentum P2 and a plane wave in another field with momentum P1. So the initial state is described as plane waves. So we can say a plane wave for the electron, so a plane wave in a Spinor field with momentum P2, and another plane wave in another Spinor field, which represent the muon, with a momentum P1. So we have plane waves. Or another way of saying it, always in the quantum field theory language, it's free particles. Then in the final state, what I see again are plane waves. In this case, the plane waves have momentum P1 and P2. This is always for momentum. In the final state, I also see free particles, so non-interacting. Which are described in my quantum field theories by plane waves. Are described by plane waves because we know the momentum of these particles. And this is very, very useful for calculations, because when we are in momentum space, we say nothing about the position in which the interaction happens or the position in which the particles are, because we can't, because the particle is everywhere when it's a plane wave, as we saw. But it's very useful because it's a very useful approximation, because we can make calculation very, very easily in momentum space. And we will see that the Feynman rules in momentum space are very easy to write down. So the particle in the final state, it's always also a plane wave. So I see in the final state what I represent with my theories. With my P theory is plane wave with two plane waves, one with momentum P3, one with momentum P4, one representing the final state muon and one representing the final state electron. Okay, what happens? So final state, initial state I can measure, final state I can measure. What happens in between I can't see. Okay, so it's a quantum mechanical process. This is a quantum mechanical process described by this matrix element that I call minus IM, which is an amplitude. The probability of the interaction happening, it's the square module of this amplitude. Exactly as in quantum mechanics, the probability of the particle reaching the screen was the square modulus of the amplitude, so the absolute square of the amplitude going of the particle going to the screen. And the amplitude in quantum mechanics, I was building that using all possible ways in which the particle could reach the screen. And here it's the same thing. To every possible way in which the particles can interact, I have a Feynman diagram associated to that way. I have a Feynman diagram associated to each possible way in which this interaction can happen. Each Feynman diagram has this amplitude associated, so I can compute this amplitude, and then the total amplitude of the process happening will be minus I, all the possible ways, so m1 plus m2 plus all the, I would say, I say it, then we will see what does it mean, the infinite possible way in which this particle can interact. And all the infinite possible ways in which the particle can interact have an amplitude associated to them, which can be computed using the Feynman rules and the Feynman diagram. Let's make an example of one of the infinite possible ways in which this interaction can happen. So, example. So this is how my theory describes interaction. Describes interaction saying the interaction happens in every possible way. To every possible way, I associate a Feynman diagram which has an amplitude. I would also add, let's write it down. So what happens here in the interaction? The probability of this interaction happening is equal to this m element squared. M is an amplitude for the interaction. And m, it's the sum of all the possible amplitudes associated to all the possible way in which this interaction can occur. For example, one possible way, it's represented by this Feynman diagram. The muon, it's here, the electron is here, and they exchange a virtual photon. Also in this case, if I fix the momentum of the muon and the electron, etc., so this has momentum p1, this is momentum p2, p3, no, this was p4, p3. Yes, if I fix the momentum of this two initial state particle, two final state particle, what I'm really saying, these are plane waves interacting. So it's not this photon, this interaction here does not happen in a certain point in space, but happens everywhere. It's like we have two plane waves in the initial state. These two plane waves excite in some way the photon field, and since both of them are coupled to the photon field, so for both of the plane wave, for both of the spinor field, there is one interaction term. So the muon field is coupled with the photon field, the electron field is coupled with the photon field, and so they produce an excitation in the photon field, which corresponds to a photon traveling from here to here, or to here to here. Both of the cases are included in this diagram. And the excitation in the photon field, in turn, produce an excitation in the electron field. Okay, so this is how these two electrons interact. These two spinor interact. They interact not directly, but through an excitation in the photon field. For example, this term here, this Feynman diagram here, in which they just bounce off each other, it's not present. Why it's not present? Well, because this is encoded in my Lagrangian. There is no term in this Lagrangian which has 4 Spinor fields. So with no 4 Spinor field, there is no vertex in this Lagrangian in which the particles, the electron and the muon, can interact directly. So I have to build all the possible ways they interact using an interaction between a Spinor field and a vector field. Okay, I hope that makes a little bit of sense. So, for example, to go further with this reasoning, to this Feynman diagram, which represents one way in which the interaction can happen, I associate minus I m. So I associate an amplitude. Then I find out all the infinite possible Feynman diagram associated to this interaction, and I sum all the possible amplitude. So this amplitude here, the total amplitude, let's call it m tot, it's equal to m, the amplitude of the process happening, let's call it m1, in the first way, plus the amplitude of the process happening in the second way, which we didn't see yet, plus all the possible, the process happening in the nth way, and all the infinite way of this process happening. Okay? This is quantum mechanics. It's crazy, but that is what it is. And now we will see how to associate an amplitude actually to this Feynman diagram, like particularly this Feynman diagram, through the Feynman rules for quantum electrodynamics. So once we know the reasoning, once we know that we have a possible, infinite possible ways of this interaction happening, and to every one of these infinite possible ways there is an amplitude associated to, how to compute this amplitude, which will be, once we fix the initial and final momentum, this amplitude will just be a complex number. How to compute this complex number? Well, this is done through the Feynman rules for quantum electrodynamics, and now we will see the logic of the Feynman rules for quantum electrodynamics. So let's talk about the Feynman rules and Feynman diagrams in quantum electrodynamics. What do we need for discussing the Feynman rules and Feynman diagram? Well, first of all, we need the quantum electrodynamics Lagrangian, which is here, and I let it here. From the quantum electrodynamics Lagrangian and from the diagram that we wrote before, we can infer that we have three, let's say, let me think. I think three basic ingredients. The first ingredient is propagators. The propagators are associated to particles being exchanged in the process. For example, let's put down the process that we saw before. Mu1 electron and photon, virtual photon being exchanged here. In this case, the propagators are associated to particles being exchanged. So in this case, this guy here, it's a propagator. In particular, since we have two fields in the quantum electrodynamics Lagrangian, the propagator can be a photon propagator. So here there is a vertex that we will see later. So this is the propagator of the photon, or an electron propagator, or in general a Spinor propagator. Okay. I put this little thing here and here. This will be Spinor, 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 Spinor. Just to say, this guy here, it's between two vertices, always. Otherwise, it's not a propagator. Then the second thing we need are external legs. External legs are associated not to exchanged particles, so not to virtual particles, but to initial state and final state particles. So everything which does not end or begin with a vertex is an external leg. So in this case, we can have the Spinor external leg, something like this, and then here there is a little vertex. Or we can have a photon external leg. So a photon incoming, and then here there is a little vertex. Okay? The external legs can be of two types: initial state particles, so the particle enters and then there is a vertex, and final state particles. So for example, the particle in this case, there is a vertex here, and then we have the particle in the final state, and same for the photon. They are different objects, and we will see later what they are associated to. Here there is another little vertex, which we will not consider here. And then these are the final state particles. So these guys here are initial state. And these guys here are final state. And then the third ingredient in the Feynman diagram, which it's the most important, arguably. It's not that these are not important, but this ingredient here tells us which interaction can happen and which interaction cannot happen, and this is the vertex. In general, we can have more than one vertex, but in this case, in the quantum electrodynamics Lagrangian, we only have one vertex. And the vertex is what kind of interaction can happen. In particular, what kind of interaction can happen, it's given by the interacting term of our Lagrangian. As you can see here, we have psi bar, psi, and amu. So an interaction can happen in a vertex in which I have a photon, a spinor, and an antispinor. So a photon, particle, and antiparticle. So in the vertex, there is always a photon, and then particle and antiparticle. Okay? Perfect. To every one of these ingredients, we will then associate some number or some function. We will then put all together to generate every possible Feynman diagrams. And then, so there is a function associated to this, there is a function associated to all this, there is a function associated to all possible vertices. And then this function, these various functions will be multiplied when we go and construct Feynman diagrams. Any possible Feynman diagrams can be built out of these 1, 2, and 3 ingredients. Okay, let's see how it works, and let's see what are the functions associated to these 3 ingredients. So these are the ingredients that we will use to derive our Feynman rule. We will not derive them formally because this is not a course in quantum field theory, but we will give an idea on how this Feynman rule go out from the process, because I know that a lot of people just know how to compute Feynman diagrams and get the final result, but they don't actually know, at least intuitively, where the Feynman rule comes from. But we did a lot of work up to now, and we saw the free spinor solution, the free photon solution, the interaction that comes out from the quantum electrodynamics Lagrangian. So we have all the instruments to understand at least intuitively where the Feynman rules come from. I put this down just to for your convenience, because you have to remember that this guy here, which is the Spinor field, can, or the Spinor field operator, I didn't put the operator sign everywhere, but they should be there. The Spinor field operator can annihilate a particle with this term here, or create an antiparticle with this term here. The anti-Spinor field can create a particle with this a dagger here, which is a creation operator, or annihilate an antiparticle with this guy here. Okay. Same thing goes for the photon field. He can create a photon with this operator here, which is a creation. This can annihilate a photon with this operator here, which is an annihilation operator, or create an antiphoton with this operator here, which is a creation operator. You could find a possible inconsistency with what we called before a free photon field, in which we had this vector here, this polarization vector, which was common for both photon and sorry, I don't know if I said create an antiphoton, but this is not true if I say that, because okay, this is create a photon, this annihilate a photon. An antiphoton is the same thing as a photon, so that's why we have only one of the field operator for photons and two field operator for spinors, because spinor we have particle and antiparticle. For photons, the particle is equivalent to its own antiparticle. Back to us. Last time we defined this object here with a single polarization vector in the end. In this case, in a more general case, the polarization vector can be an imaginary, can have imaginary number entries, and in particular, in this case is associated a certain polarization vector, and in this case is associated the complex conjugate of that polarization vector. So in this case we distinguish between the two cases, and this will be useful when we construct the Feynman diagrams using the Feynman rules. Good. Once we have this, yes, and also I define this sum and integral together, just not to write every time this big object here, which is the sum over, like every time you see this integral together with the sum, I'm implicitly saying sum over polarization state or spin, so spin for the electron, for the spinor, and polarization state for the photon, sum over this, then integration over the 3 momentum over 2 pi to the third over 2 times the energy of the particle under the square root. So not to write every time this, I just simplify this symbol using this compact notation. Also because it's not important for what we have to discuss now. Very good. So let's start. We saw that we have 3 ingredients in the Feynman diagrams. The first ingredient, let's start with the interaction vertex. So one interaction or vertex. The Feynman rule for the vertex is that every time we see a vertex of the type, so there is a photon and then a particle and antiparticle, every time we have a vertex, we associate to this vertex a factor minus q gamma mu, and that's it. Yes. Wait. No, minus I, yes. Minus I, something was missing. Q gamma mu. Okay. Every time we see a vertex. And the vertex describes many types of interaction, because now with the free spinor and free photon field operators, we can see that this vertex can have can describe many type of processes. For example, it can describe an antiparticle being created and a particle being annihilated and a photon being created. This will be this case here. Particle comes in, antiparticle comes in. In this case, every time we have an antiparticle, the convention is that in the Feynman diagram, if the momentum of the antiparticle is in this direction here, we put the arrow in the other direction. This comes from the fact that physical antiparticle with physical positive energy are associated or are mathematically equivalent to particles with negative energy going backward in time. So if time goes in this direction, when we write the antiparticle, we always write it with an arrow which points in the opposite direction with respect to the direction of the antiparticle. This is just something that remains in our convention. It's very confusing, but at least it can tell us who in the diagram is an antiparticle and who in the diagram is a particle. So if we have time going to this direction, I already know that in this diagram, for example, if this is an electron, this will be a positron. And this positron will travel in this direction here. Then, what does it mean? What does it mean to travel in this direction? In this case, we are in momentum space when we'll see the Feynman diagrams, so nothing will mean nothing traveling in a certain direction. So we have an antiparticle, a particle entering here. In this point, the particle gets annihilated. The particle gets annihilated by this operator here. And in the same point, an antiparticle gets annihilated, and the antiparticle gets annihilated by this operator here. And in the same point, a photon is emitted. And the photon is emitted by this operator here. So it's created by this operator here. Another kind of event that we can describe always with this interaction vertex, and we can see it, what happens under the hood here, is, for example, a photon gets annihilated. So an initial state photon from this operator here gets annihilated by this component here. And then I create a particle and an antiparticle. So also in this case, it's something like this. The antiparticle with momentum p will go in this way, the particle will go in this way, and the interaction vertex describes both these cases in which we have a particle-antiparticle annihilation and the creation of a photon, or the photon that goes and creates a particle and antiparticle couple. So this is annihilation, this is creation process, and then we can have other kind of processes in which, for example, I have a particle that goes and at some point emits a photon. And this is in the interaction vertex. If we read it off from the interaction vertex, it's just the case in which I use this operator here to create a particle. So in this point in space, I use this operator to create a particle. This operator to annihilate a particle. So annihilate this one and recreate it. And then I use this operator to create a photon. Okay, so all these kind of processes have all of them, all the vertices which describe annihilation, creation, scattering, etc. In this case, not scattering. This will be an emission of a photon from an electron or an anti-electron. The equivalent with an anti-electron will be something like this. Just since it's an antiparticle, the convention is putting it traveling backward in time, but this will be an absorption of a photon, or we can have an emission of a photon, which is something like this. All of this, it's equivalent, and all of these vertices have associated to them a number, a function which is minus I, the charge of the spinor field, times gamma mu. Okay, so this is the rule from the vertex, and we read it from the interaction vertex inside the QED Lagrangian. This is the same process that we will use to describe Feynman rule for other type of Lagrangian, for example, for the standard model Lagrangian and other type of interaction, for example, weak interaction and strong interaction. But, so the vertex, we have the vertex, we saw all the possible cases which are described by the vertex. And now let's talk about a more difficult object, which is the propagator. As we saw, the propagator is just a particle, which can be a photon or an electron, traveling from a vertex to another. So this is the photon propagator, and the Spinor propagator, we represent the photon propagator with a wavy line and the Spinor propagator by a straight line, something like this. Okay, how do I compute this? I will not show you the computation, but it's simply like in space-time. So the propagator of a photon from a point x to a point y in space-time is computed like this. 0 time order product between a mu x, a nu y, 0. Okay, this is the object associated, which I have to compute to get the propagator from a point to another point in space-time of the photon. And what this object is saying, as you can see, it's something like I create a photon in a certain point in space, and then in a later time I annihilate a photon in another point in space. So this object tells me the amplitude for a photon to travel from a point to another point in space-time. This guy here, it's computed in space-time coordinates, so from x to y as 0 time-ordered product. The time-ordered product simply orders who comes first. So it orders the fields in a way that they respect who is first in time. So in this case I have a spinor in x. You see that is practically the same object. Also in this case we will not compute this object, but the idea is what is the amplitude of a fermion to be produced in a certain point in space-time and propagate and be detected or be found in another point in space-time. Okay? If we compute this object, we find a function of space-time, so we find the propagator of as a function of the distance between these 2 points, and then we transform and we go in coordinate space, in phase space. So we go in momentum space because, as we saw, we always measure momentum of final particle and initial state particle, so we want to work in momentum space. And in momentum space, the propagator becomes very simple, because this propagator here, when it's in momentum space, so it's not anymore from a point x in space-time to another point y in space-time, becomes, so whenever I see a photon propagator, I associate to the photon propagator a minus I g mu nu, but we call it eta mu nu before, so let's call it eta mu nu, where eta mu nu is the metric tensor, over p squared plus I epsilon. P squared, P is the quadrimomentum of the photon, so I have a photon with quadrimomentum P. I epsilon, it's simply a term for avoiding a pole when I do my integral. Just trust me and put this term here. But the reason why this term is here is also encoded in quantum field theory and in the fact that I have to do an integral actually, and there is a pole. In this case, the pole is when the momentum is equal to 0. For the fermion propagator, what I have is minus I p slash plus m over p squared minus m squared. This is the fermion propagator in momentum space. And also in this case, this is the propagator associated to a fermion with momentum p. What does it mean p slash? P slash simply means gamma mu p mu. So it's the contraction between the gamma matrices and the form momentum of the spinor. Okay? Perfect. A simple trick to remember, I don't know if to say this, but yes, I think it's interesting. A simple trick to remember, at least, of course, here I put also in this case there is a pole when I do my integral in coordinate space. Also here I'm not anymore in coordinate space, so I remove x and y. It's not anymore a propagator, a particle propagating from a point in space-time to another point in space-time, but it's just the amplitude associated to having a particle with momentum p within my diagram. Also in this case, when I'm in momentum, when I'm in space-time coordinates, I have an integral, and for not having a pole when the momentum is equal to mass, I have to add this I epsilon term. Epsilon, also here, it's a very, very, very small constant, and also here it's a very, very, very small constant. You can also think of the propagator without this guy here. An interesting thing on remembering the shape of the propagator is that in momentum space, the propagator is proportional to the inverse of the operator in the free equation of motion. For example, in the case of Dirac equation, we have I gamma mu d mu minus m associated to our spinor field psi. So this operator as applied to psi is equal to 0. This is the free equation of motion of the spinor field, so it's the Dirac equation. I go in momentum space, so for example I take psi to be u e to the minus I px. I solve this. When I'm in momentum space, the derivative with respect to the space coordinates, it becomes simply minus ip. So in this case, this guy here becomes minus ip times I, which is plus 1. So it becomes gamma mu p mu minus m times psi equals 0. This is the free equation of motion in momentum space, and the propagator, so I have an operator which I apply to my wave function or to my field operator. The propagator in momentum space is the inverse of this operator. It's proportional to the inverse of this operator. In fact, as you can see here, we have minus I over p squared minus m squared. Doesn't look like the inverse of this element, but I show you that indeed it is the inverse of that element, or at least proportional to the inverse of that element. So propagator of the spinor field, it's proportional to 1 over gamma mu p mu. We follow our new notation and we call it p slashed minus m. Why we wrote it in another way here? Well, simply because we can also multiply and divide this times p plus m over p plus m. So the denominator becomes p squared minus m squared. And the numerator remains p slash plus m. And then for avoiding the pole, I again add this small complex constant here in the denominator. So you see that there is a minus I factor missing, but this is proportional to the inverse of the operator that I have in the free equation of motion. The same thing applies also to the photon propagator, in which the free equation of motion is the Maxwell equation, but we will not see that. It's just a curiosity and just to check that your propagator is correct when you have some doubt. Also, this photon propagator here, I wrote it like this, but this is in a particular gauge which is called the Feynman gauge, but it's practically what you use in the end for calculation in most of the cases. Third ingredient in the Feynman rule are the external legs. And these are the simplest object to read off from the free photon and free spinor solution. Because, so whenever we have an external leg, if it's a initial state, so we have two cases, initial state and final state. Okay, and then we have spinor. so particle or antiparticle, or photon. So, let's put it a bit. Okay. So, for example, an initial state spinor. Who creates an initial state spinor? In this free Spinor equation, the initial state spinor is created by this guy here, psi bar. And the initial state spinor in particular is with momentum p is created by this creation operator, which is associated no. Sorry, yes, I was confused for a moment. There is another little complication. Let's put here the diagram that also, or the electron-positron annihilation, for example. So let's write here a diagram for you to understand my point here. This is another kind of diagram in which, for example, an electron and a positron annihilate, so disappear in this vertex. Then we have a photon propagator, and then an electron and a positron emerge, so get created from the photon. Okay, in this case, who are the initial state particle, antiparticle, etc.? Initial state particles are the electron and the positron. So, if I have an initial state particle, the particle in the diagram needs to be annihilated. So I search in the free Spinor solution the term who annihilate a particle. The term who annihilate a particle is this term here. Okay, so this term here, this operator here, annihilate a particle and is associated to this guy here. Okay, so an initial state spinor, an initial state particle is associated with U of p. So this is an initial, every time I have an initial state particle of momentum p, I associate this guy here to the Feynman diagram. If I have an initial state antiparticle, in this case the positron that goes here, also the I need to choose the element that annihilates an antiparticle. Who does annihilate an antiparticle? This guy here. So this annihilate antiparticle, in particular this operator here, which is associated to this guy here, to this spinor. So I associate a V bar of momentum p. This is the guy who annihilates an initial state antispinor. So for final state spinor, I need to create a particle. Who creates a particle? This guy here. So to a final state particle, I associate this spinor here, UP. So every time I have in my Feynman diagram a final state particle, I associate this guy here, a final state particle with momentum p. Every time that I have a final state antiparticle, I need to create a final state antiparticle. So who creates a final state antiparticle? This guy here. This guy here, because this operator creates a final state creates an antiparticle. Who cares who is in the final state? The fact is that it needs to be created if it's in the final state. So who creates an antiparticle is this guy here, who is associated to this spinor here. So in this case, to a final state antiparticle, I associate a spinor V of p. Okay? For the photon, an initial state photon needs to be annihilated. So I associate to him this polarization vector, epsilon mu, momentum p. This is always a final initial state particle gets annihilated and has momentum p. And to a final state photon, it needs to be created. So I need to use this operator here to create it. And so I associate this, this polarization vector. Okay? These are the Feynman rules that allow me to write down the amplitude associated to any Feynman diagrams at tree level, so without loop. We will see the exception with the loops in a moment, but now let's familiarize a little bit with these Feynman rules, writing down a process. So I will cancel this part here and put it here while keeping these Feynman rules in the right side of the blackboard. Now we will familiarize a bit with these Feynman rules, writing down the expression associated to some Feynman diagrams. What I want to mention is that once you have the Feynman rules, you can write down the expression associated to a certain Feynman diagram without knowing nothing anymore about the Lagrangian or the underlying theories. Once you have the Feynman rule, you have a defined procedure for computing scattering amplitudes, for computing amplitude associated to certain process happening. I will make you an example about this. Suppose you want to solve this equation. I don't know, 3x minus 2 equal 5x plus 1. Okay? There is an idea under this equation. So the idea or the logic is I have to find x. So it's very, very simple. The logic is I have to find x such that this equation is satisfied, such that if I put x inside here, I get one number equal another number. So the logic, it's easy. Okay? I need to find x. Then there is a procedure. And the procedure, it's something that you can do without knowing nothing about the logic. You can just put all the x, everything associated with an x in this side and every number in this side. So you have step 1, do this, so it will become 3x minus 5x equal 2 plus 1. Then step 2, do the computation. So 3x minus 5x will be minus 2x equal 3. Then step 3, divide by minus 2. So divide by the factor that there is in front of x. So x equals 3 divided by minus 2, which is minus 3/2. Okay, I hope it's right, otherwise. So we have a logic, which is very simple. And then we have a procedure that we can follow to find x, which has nothing to do with the logic. We can do blindly the procedure and finding x. With the Feynman diagrams, is the same thing. Once we have the Feynman rule, we can forget about the logic and the idea that particles are excitation within quantum fields and quantum field theory and how the interaction work, and just do the procedure. And the procedure is very useful because this maybe one can also do with logic, but at some point the equation becomes so difficult that you need a procedure to solve it and to find x blindly without thinking about the logic that is behind. So Feynman diagrams and Feynman rules are the thing you use for it's the procedure that you use to find out the actual number that are related to our physics and to what we observe in the world. Okay, but you can follow blindly Feynman rules without knowing the underlying logic. Okay, what we did was at least a hint on what is the underlying logic, which is quantum field theory. And now we will do the first step of the procedure, which is associating a certain function, a certain mathematical expression to the amplitude associated to a certain diagram. That is the first step of the procedure for the Feynman rule, and then you can do computation with Feynman diagrams using many tricks about gamma matrices, about spinors going ultra-relativistic to simplify equation, etc., etc. We will not see all the procedure, so we will not see how to get a number out of a Feynman diagram and how to compute actually a cross-section for some event, because the procedure is something that they teach everywhere, I think, but a lot of time they lack about the logic, because the procedure is very easy. You get Feynman diagrams, you associate to every piece of your Feynman diagram, you associate one of these objects, and then you compute. So let's see the first step of this procedure. All of this to say, my goal here is to explain to you the logic which is behind Feynman diagrams. But now we will see a step of the procedure, just to have a flavor of what a particle physicist do and what are the calculations that one encounters in particle physics. So let's take the process we had before, electron-muon scattering. by photon exchange. So how does it work here? For associating an amplitude to this process here, the amplitude minus I am associated to the process electron-muon scattering happening in this particular way. It's something like this. This one is P1, this one is P2. Both of them are particle, so the arrow goes in the same direction as the momentum of the particle, and also both final state are particles, so the arrow again goes in the same direction in which the particle goes. We have two vertices. We label this vertex, for example, mu. This vertex, we label it nu. And then let's see what happens in the first vertex. Here is P3 and here is P4. Okay. The way we label the momenta will be important for how we write down the mathematical function associated to this Feynman diagram, but we can label these momenta arbitrarily. So I can call this P1, P2, P3, P4, or the important stuff is that we remember how did we label the momentum, and we are consistent when we compute other kind of Feynman diagram which are associated to this. But in this case, for electron-muon scattering, so if this is a muon and this is an electron, this is the only Feynman diagram that enters, so the only way of this process happening at tree level, so with two vertices. There are other ways of this process happening with more than two vertices, but we will see that later. So what is the amplitude associated to this Feynman diagram? Well, we use Feynman rules. First of all, we have a vertex and external legs. So in this vertex here, we have an external leg entering, which is an initial state particle, and then we have a final state particle. What we put before, it's always a final state particle, so it's always the thing with the bar. This is because, it makes sense to put always the thing with the bar before, because the thing with the bar is a row vector, and the thing without the bar is a column vector, which is not a vector, it's a spinor, but it's a column object. So if I multiply this by this, I get a number. If instead I put the one without the bar before, I get a matrix. And the matrix is something I don't want, because the final amplitude is just a complex number if I specify the momenta. So as a rule, always put before the thing with the bar. Okay. So we have final state particle with momentum P4. Then we have the vertex, which is minus I q gamma mu. No, this vertex I call it nu, so let's be consistent. This I call it gamma nu. Then we have the initial state particle. So U of momentum P2. Then we have times, I go in the other line, the propagator. This is a photon propagator. So photon propagator, it's this object here. If it was an electron propagator, it would be this object here, but in this case it's a photon propagator, so minus I eta mu nu over the momentum of this particle, but the momentum of this particle, we can call it Q. The momentum of the photon, it's defined by the conservation for momentum. So this momentum can be, for example, P2 minus P4, because you see that this momentum enters and this momentum exits. So in this vertex here we have one momentum going in, one momentum going out, and one momentum of the photon. So this momentum here can, if this is P2 and this is P4, this momentum here it's P2 minus P4. So the momentum in this case of the internal particle of the propagator, it's completely defined by the momenta of the external legs. So in this case, instead of putting P squared, which will be the momentum of the photon, I put P2 minus P4 squared. Plus I epsilon. And then, so propagator done. This momentum here, it's equal to P2 minus P4. and it's also equal to P3 minus P1. No. P3 is equal to Q plus P1, so yes, okay. It's I'm not sure. It should be P3 minus P1, but I didn't. Okay, I don't want to check. And then we have the other vertex here. So the other vertex is associated to an initial state particle, final state particle. So we put final state particle before U. That depends on P3. Then we have minus I Q, the vertex, gamma mu. And then we have initial state particle, U of P1. Okay, so this guy here, once I specify the values of P1, P2, P3, and P4, this guy here is a complex number. So after I do all the calculation, which we will not see, gives me a complex number which is associated, it is the amplitude of this process happening in this particular way. Okay, I can simplify this a little bit, for example, using U, in this case I call U4 the final state particle with momentum P4. So if I collect minus IQ, let's do it a little bit better. I collect minus IQ times minus IQ, that becomes minus Q squared, and then I put this I outside. So this becomes plus I Q squared. And then I have U bar 4. I contract this eta mu nu with this gamma nu, so I will have gamma mu U2. Then we have propagator, so 1 over P2 minus P4 squared plus I epsilon. And then we have the last part, which is U3 gamma mu U1. Okay, this is in a more compact way, and this is equal to minus I epsilon. No, minus I m. Okay, so this minus I can go, minus I plus I can go, and m it's equal to minus this object here. This minus here is a convention because anyway we'll have m squared. So in the end, the probability of the process happening in this particular way, if this was the only possible way of this process happening, the probability would be exactly the element squared. So this amplitude here squared. If I have other way in which this process can happen, the probability is the sum of all the possible amplitudes squared. Okay, let's see a case in which we have two ways of the process happening. For example, if these two guys are, this guy it's an electron and also this guy here it's an electron. So instead of having a muon scattering, I have electron-electron scattering. What I get here is that the initial momentum and final momentum, we label it in the same way, but the way in which this process can happen change. Like I have one more way in which this process can happen. So I have this interaction, but then in the end, the electron that goes to be of momentum P3, okay, I write it down and then I comment. Okay. Here, this is not an this is not a vertex. It's something that just something like this. Okay, this is important. This one is not a vertex. It's just particle crossing, but without interacting. So I have these two processes in this case. If I have two electrons interacting, electron-electron scattering, I have two processes because I cannot distinguish when I measure two final state electrons, one electron with momentum p4 and one electron with momentum p3, which one of the electrons, let's put it like this. I have this scattering here. I measure two electrons, this one and this one in the final state, but I could also have measured the fact that I don't know if the electron that I measure here with momentum p3 and this is momentum p4, I don't know if the electron that I measure with momentum p3 was the electron which started with momentum p2 or was the electron which started with momentum p1. So there is another situation in which this electron here starts with momentum p1 and then bam becomes the electron with momentum p2, or there is and equivalently, I mean in the same process this happens. So the momentum p2 electron becomes the momentum p4 electron and the momentum p1 electron becomes the momentum p3 electron, or as we saw before, the momentum p2 electron becomes the momentum p3 electron and the momentum p1 electron becomes the momentum p4 electron. These two situations are indistinguishable, so I have to add and to sum both contributions. Okay, so I use my Feynman rules to compute minus I m1 and minus I m2, which are the two ways in which this process can happen. I sum the two, so the total amplitude m will be minus m1 plus m2. There are other Feynman's rules that account for the fact that when I swap fermion lines, I have to put minus sign inside the diagrams, but we will skip this part. It's just conceptually. So remember that we are talking about the logic and not about the procedure, or we are not being so precise about the procedure. But the important part of the logic is that in this case here, the total amplitude of this process happening, an electron scattering and like two electron scattering, is given by two contributions, this one and this one. So the total amplitude is the sum of two complex numbers, and the probability, what I will measure in the end, will be the square, the absolute square of the total amplitude, not the absolute square of the amplitude separate. Okay, separately. Very well. So this was the case of electron-electron scattering. Another case in which, for example, other contribution can be added to the Feynman diagrams is where we have loops inside the diagram. What does it mean having loops inside the diagram? Now we made an example on how to write down a mathematical equation, a mathematical structure, a mathematical function associated to a Feynman diagram. So all these Feynman rules, we can cancel them. We will not use them anymore. But we will talk about the concept of adding amplitudes together. Every diagram we saw before, every Feynman diagram was at 3 levels, but there are infinite possible ways of a process happening. What does it mean and why we can still do physical prediction with infinite possible Feynman diagrams associated to a certain process. We have to talk now about loop diagrams and 3-level diagrams. Okay, what is a 3-level? For example, let's take an example as an event as an example, and the event we will take is electron-positron annihilation. So positron plus electron that goes to again positron plus electron. This is called the Baba scattering, if I'm not mistaken, and it goes something like this. So we can have 3-level contributions which is, first case, we have an electron and an anti-electron, so a positron, A minus, A plus. They annihilate and produce a photon, and then the photon decays into, again, E plus, E minus. Okay, this is the first contribution at tree level. But there is another indistinguishable way in which this process can happen at tree level, so with only two vertices in the diagram. And the other indistinguishable way, it's something like this. Okay, so if I want to compute a Feynman, the amplitude of this process happening at tree level, I have to sum the amplitude associated to this diagram with the amplitude associated to this diagram, and minus I m, so the total amplitude of this process happening at tree level, so considering only these two diagrams, will be the sum of these two amplitudes. Okay, so this is tree level. But if you think about, these are, I told you multiple times already that there are infinite ways of the process happening. So which one are the other way of the process happening? The other way of the process happening, it's with loops inside the diagrams. And here is where the things become very, very complicated. Loops. And in particular, we will see the case of one loop. See the case of one loop inside the diagram. So if you think about, there are other contributions which look like, for example, electron-positron annihilation. Then we have a photon here. The photon produces again an electron-positron couple, but this electron-positron couple re-annihilates and then recreate another photon, and then bam, in the end I have electron-positron. Okay, so here I have initial state particle, an electron and a positron, an electron and a positron, and final state particle, an electron and a positron. Also here I have initial state particle, electron, positron, and positron, electron, final state particle. So this guy here is indistinguishable from our instruments when we do measurement from this guy here, because we have the same final state and initial state particle with the same momenta. So I don't know if the process happened like this or happened like this. Other examples of one loop diagrams are, for example, something like this. Yes. So there is a photon exchange, and then there is another photon exchange. So this is called the box diagram. And also in this case, I have electron-positron in the initial state, electron-positron in the final state, and something happens in between, which is physically undistinguishable from all the other cases. So at one loop, I have to take these diagrams, all the possible variants of these diagrams, plus all the possible variants of these diagrams, plus all the possible variant of this other guy here. Which is called, this one is called the vertex correction, this one is called the photon polarization, vacuum polarization, this guy is called the box diagram, and then we have at least another one of these kind of diagrams, which is, now I don't remember anymore, yes, there is the self-energy of the electron, which is something like this. So I also have to account for all the possible diagrams that have this structure here. So at some point, an electron or a positron emits a photon and then recaptures the photon. But in the final state, this is again indistinguishable from all the other possible cases. So you see that if we go to one loop, we have much more diagrams than we have at 3 level. If we go at 2 loop, so we count all the processes that can have, in this case at 1 loop are all the processes that can have 1, 2, 3, 4 vertices. So every one of these at 1 loop, if you count the number of vertices, you will find 4 vertices. Then you can have more vertices going to 2 loops, 3 loops, etc., 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 and you can go at any number of loops that you want. So you really see now that you have an infinity of diagrams that can contribute to your amplitude, to your total amplitude. So how do we sort out this problem? Because if the total amplitude is the sum of all the possible ways in which a process can happen, but all the possible ways are infinite, I cannot stay there, I cannot sit down and calculate all the infinite diagrams that are associated to a certain process. Fortunately, the coupling in the quantum electrodynamics, so in quantum electrodynamics we have a coupling which is minus q psi bar gamma mu psi mu. So this is the interaction vertex in quantum electrodynamics, and fortunately, very fortunately, the coupling constant, which is not a constant, but let's say the coupling between the photon field and the fermion field and the Dirac Spinor field, it's small. So this coupling, it's smaller than 1. So every time that we introduce new vertices, the process gets suppressed. So the amplitude, the magnitude of this amplitude gets suppressed. This process is at 3 level. In this case, we have an electric charge here, a factor of an electric charge here, and 1 here. So at every vertex we have the coupling, and also here, let's call it Q so we don't confuse it with the electron. So in this case we have a Q, in this case we have a Q, so we have 2Q. So the amplitude at 3 level, let me cancel something like this. The amplitude of all the processes at 3 level, it's proportional, or it's in the order of magnitude of Q square. The expansion parameter that we use is actually alpha, yes, where alpha is equal to E square over 4 pi, I think, and E is the electron charge. The electron charge, it's smaller than 1, and alpha equal E squared over 4 pi, it's 1 over 137. So this is the expansion parameter. So every couple of time, every couple of vertices has associated an alpha to it. So every time I have 2 vertices, for every diagram that I have that includes 2 vertices, it's in the order of alpha. And alpha is small. When I go to 1 loop, every diagram has 4 vertices. So I have a coupling constant here, coupling constant here, coupling here, coupling here. So this is order of q to the 4th, but since alpha is E squared over 4 pi, in the expansion parameter alpha, this is of order alpha to the 2nd. Okay, so all the diagrams at 1 loop are of the order of magnitude of alpha to the 2nd, alpha squared, but alpha it's 1 over 137. So all the contribution that I have to my total amplitude at 1 loop are much smaller than all the contribution that I have to my total amplitude at 3 level. If I go at 2 loops, all the contribution that I have at 2 loops are much smaller than all the contribution that I have at 1 loop, and so on and so forth. So at every loop, every time I add a loop, the contribution to the amplitude is smaller. So if I want a very precise measurement, a very precise prediction on the amplitude associated to a certain process, I have to introduce many loops. For example, I go to 3 loops if I want to be very precise on the number that I get on the amplitude. But if I want less precision, and if I'm okay with a rough estimate, I can just compute the amplitudes at 3 level, since all the other contribution, all the other terms will contribute less. So we'll change the amplitude a little bit, but not so much, okay? So yes, there are infinite diagrams in quantum electrodynamics that can contribute to a process, but I can stop computing diagrams at a certain order. If I stop at 3 level, for example, I only have 2 diagrams that contribute. So if I want to compute the cross-section of a certain process at 3 level, yes, by the way, let's write down the formula of the cross-section. The sigma, this is the differential cross-section, the infinitesimal element of cross-section, something that goes like, I just write down the formula to show you how the final amplitude is associated to something that we can physically measure in experiments. Okay, it's a nasty formula, we didn't derive it, but it's how to relate what we can compute with Feynman diagrams to what we can measure and what we can observe, so that we can compare the theory against the experiments. And where do Feynman diagrams and quantum electrodynamics enter in this physical process? It's all in this element here, in this amplitude. And this amplitude, for example, if you want to compute the cross-section at 3 level, in this amplitude there are only contributions from 3 level diagrams. So this amplitude will be the sum of the amplitude associated to this diagram plus the amplitude associated to this diagram here. If I want to be more precise on my physical prediction, so more precise on computing what I expect from my observable, I will also introduce all the diagram at 1 loop, sorry. And we saw 4 types of them. If I want to be more precise, I will introduce inside this element here all the diagrams at 2 loop and then at 3 loop and so on, okay? All the other factors are just something that I can measure. So 2 times the energy of the particle 1, 2 times the energy of the particle 2, the difference of velocity between the 2 particles interacting, and then this d pi ellipse, this is the Lorentz invariant space, Lorentz invariance phase ellipse, Lorentz invariant phase space, should be. Yes, Lorentz invariance phase space, which contains the information of all the final state Pj particle momenta, and it contains delta 4 sum over all the initial state particle momenta minus all the final state particle momenta. This means simply this is a condition that tells us energy must be conserved. So this formula here for the cross-section is very, very badly commented by myself, but I will put here the reference. You can find it, I think, in chapter 8 of the book Quantum Field Theory and the Standard Model, or chapter 8 or chapter 5. Last thing we see, it's a problem, an enormous problem that emerges when we introduce loop diagrams without seeing the solution, because it's something that is like you can dedicate an entire course on the solution to this problem. But I think you must be aware about this problem. So there is a very huge problem when we go and introduce loops inside Feynman diagrams. And the problem is that there are momenta which are not fixed in Feynman diagrams. Let's see what that means. When we are at 3 level, see before the 3 level case, for example, this diagram here at tree level, once we fix the external momenta, the momentum of this particle here, which we can call k, now let's put it in white, the momentum of this particle here, k, it's fixed by the condition that momentum must be conserved and by the fact that I have the knowledge about the momenta of the external particle. So if this is P1 and this is P2, I know for sure that the momentum of the internal particle, so of the exchanged particle, k, is equal to P1 plus P2. Okay, let's see an example of a one-loop diagram, for example, the box diagram, something like this. Oh, let's do it big so we can really write the momenta in a huge scale. This will introduce a new Feynman rule, by the way. So, what happens in this diagram? Let's fix first of all the four momentum. So we have, for example, P1 here, P2 here, and then the outgoing momenta, P3 and P4. Let's see, for example, what happens is this if we define this photon here to have momentum k. Okay, if this photon here has momentum k, this particle here, the flow of momentum inside the loop, we can put it as we wish, it's not important. But this particle here, if this momentum is k, this particle here, it has momentum P1 minus k. Okay, then we have this particle here, which has momentum P2 plus k, because both of them enter here and then goes here. So this particle has momentum P2 minus k, no, sorry, P2 plus k. And of course, all the particles that are associated to propagators are not real particles, but are virtual particles. That means that there is an excitation in the field with momentum p. And momentum, in this case, the momentum of the excitation is fixed to P1 minus k, here P2 plus k. Here we have P2 plus k, then a part exit here, P4. So this momentum here must be P2 plus k minus P4. And then these two match, so they connect at this vertex, and so we have that P3 must be equal to this momentum plus this momentum, P1 minus k, which comes from here. Then we have plus P2 plus k minus P4, plus P2 plus k minus P4. As you can see, this guy here, k, can go away. So I can just simplify minus k and plus k. That means that k, it's not defined specifying our external momentum, our external momenta. K can be everything. Really, if k is plus infinite, here we have infinite momentum that goes here, but then this infinite momentum cancels with this minus infinite momentum, and in the end, the conservation of four momentum is preserved. So you see that with this, in this case here, if I put P4 in this way, in this side of the equal sign, we have P3 plus P4 is equal to P1 minus P2. P1 plus P2. This is the conservation of four momentum. The conservation of four momentum is respected without any constraint on k. So k has no constraint from the conservation of four momentum, and k can be infinite inside the loop. Okay, the Feynman rule associated to this undefined momentum. So if we have a new Feynman rule that I can call the fourth Feynman rule, which is associating, which is when there is an indefinite momentum or non-fixed momentum, okay, what I do is to integrate over the 4k pi to the fourth. So I add this to my expression describing the amplitude associated to this Feynman diagram. But if I add this to my expression related to the amplitude associated to this Feynman diagram, and I integrate from on every possible momentum going to infinite here, then in some case the amplitude associated to this Feynman diagram in particular can explode and can give an infinite amount, like an infinite value. What to do now? This was really a major struggle for the theories until someone came up with the idea of renormalization. And renormalization is the idea of taking the infinities that emerges from our computation and hide these infinities inside parameters that are not measurable. So the infinites are still there in a way, but they do not influence our physics, and everything that we can measure, so the mass of the particles, the coupling constants, everything that we can observe physically does not depend by this infinite here. And it's a hard process. I am in this moment in a room which is called the Feldman Center, and I see Feldman right there. Not the real person, just, how do you call it, the face, the sculpture. And Feldman, together with his PhD student Toft, won the Nobel Prize because he proved that Young-Mill theories, which we will see in a bit, are renormalizable. So we can apply this procedure of renormalization to Young-Mill's theory. That is a hint that like, can make you understand how this renormalization business is not an easy business. Okay, so this last part of this lecture is just to show you that there is a problem in loop diagrams, and the problem is that the momentum inside the loop can go to infinity. How do we solve this problem? It's not something that we will discuss, but just be aware that there is a solution to this problem called renormalization of a theory. And quantum electrodynamics is renormalizable. So we can sleep. This is the Veltman's face, by the way. We talked about the quantum electrodynamics Lagrangian, and the quantum electrodynamics Lagrangian can describe any interaction that involves electromagnetism. So for example, we saw as an example a Feynman diagram, how to write down the Feynman amplitude related to this particular process here in which an electron and a muon interact. What I didn't tell you, not to complicate too much the things, is that actually this Lagrangian here is not good enough for describing this process because we only have one fermion field. So one fermion field coupled with one photon field cannot describe a process in which we have an electron and a muon, because the electron and the muon are two different fermion fields. So what we actually should do is to sum over two fermion fields in the Lagrangian describing this process. So we should have the sum over electron muon, and then this mass I, for example, so this should be I equal electron or muon, and then this should be fermion I, fermion I, fermion I, fermion I, so that in this case we have this term that accounts once for the particle, once for the first particle, which is the electron, and once for the second particle, which is the mu1. Okay, but so just to simplify a little bit the things, we didn't talk about this sum here, and we didn't talk about the fact that these two terms here should be doubled. Okay, but now we introduce a new type of interaction. And how do we introduce a new type of interaction, which will be weak interaction? Well, we just observe the world. So at some point, people observing the world found these beta decays, nuclear beta decays, in which we have a decay of two types. First of all, we can have a neutron inside an atomic nucleus that decays into a proton, and this comes with the emission of an electron. Okay, so people started observing at some point atomic nuclei could change one of their neutron into a proton, emitting an electron. Then measurements were done in which there was this mystery of missing energy between, like, the sum of the total energy of the final state was not the same as the energy of the initial state. And so Pauli, I think, postulated this new particle, which then Fermi called neutrino, that is involved in the interaction. So Pauli tells us, no, wait, there is missing energy, there must be a new particle, which is the neutrino. So if the neutrino should be described by this Lagrangian, I should also add a term related to the field, which describe which excitation of these fields are neutrinos. In modern terms, what Pauli was calling a neutrino, we now call an antineutrino, in a way that the lepton number is conserved between the initial state and the final state, but it's just really a convention on what you call antineutrino and what you call neutrino. And then you have a second type of beta decay, which can be somewhat the opposite process. So a proton decays into a neutron, so a proton transforms into a neutron, emitting a positron. How do I know that emits a positron in this case and an electron in this case? Well, because also charge must be conserved. So in this case, the initial state charge is 0, because the neutron has 0 electric charge. The final state charge is the charge of the proton plus the charge of the electron plus the charge of the neutrino. So this one must be +1 in charge, and this is -1 in charge. So in this case, the initial charge is +1, and the final charge, this one has charge 0, this one has charge +1, and so this, also in this case, this one has charge 0, this charge +1, this -1. So the antineutrino must have charge 0, and also in this process here, we have a neutrino, in this case, which also has charge 0. So this little number here that I wrote is the electric charge. So people, Fermi, tried to describe these two processes using a Lagrangian, which was analogous to the quantum electrodynamics Lagrangian, and he came up with what we now call an effective field theory. So a vertex in which these four particles are involved. But we also see that this effective field theory works, so the Fermi Lagrangian, for who knows what I'm talking about, works only at low energy, so when the exchange momentum between the particles is small. When we go and see reaction in which the exchange momentum between the neutron, the proton, and the final state is large, then this vertex here doesn't work anymore, and we see this in modern terms, so in full physics, as an interaction of this type. A neutron and a proton in the final state, they emit some particle, so there is some mediator, exactly analogous to the photon in this case here. And then there is this guy here decays into a neutrino, an antineutrino and an electron. So antineutrino, electron and antineutrino. This second process here, also in modern terms, it's seen as a proton that becomes a neutron, yes, and then we have a mediator particle here which then in turn decays into a positron and a neutrino. Okay? Of course, in modern terms, also the neutron and the proton are not fundamental particles, but they are composed by quarks. But for now, forget about quarks. We are just talking about this vertex here. So what we are interested in, it's a Lagrangian that describes this vertex here. What is the characteristic of this exchanged particle? Can we use the photon for, for describing this exchanged particle? Let's see. Well, first of all, we have two problems, which I will write down here. So the spoiler is, no, we cannot use the proton, and no, we cannot use the quantum electrodynamics Lagrangian for describing the interaction between these particles here, and in particular, we cannot use the quantum electrodynamic Lagrangian and this vertex here to describe this vertex and this vertex here. And there are two main reasons, let's say. First reason is that this interaction is extremely short range. Extremely short range interaction means that the exchanged particle, we didn't see why, but trust me, and you can ask some AI why, but an extremely short range interaction means that the exchanged particle is massive and the photon is massless. So this particle here, it's massive. So in the weak interaction, this interaction that we see, we don't know what this particle is, but we know that it must be massive. Otherwise, the interaction will be long range, and we will see something different, not a vertex like this at low energy. Then we have the second issue, which is easier, I think, to understand, is that this particle here must be charged, must be electrically charged, while the photon is it's neutral. So the exchanged particle must be okay. So why must be electrically charged? Well, for the same reason that we saw before. So for example, in this case here, we start with a state with zero electric charge. So in this case, the neutron has zero electric charge, and the proton becomes +1 electric charge. This means that this interaction here, these particles must carry an electric charge of -1. Okay? And then this particle decays into an electron, which has electric charge -1, and a neutrino that has electric charge 0. Okay, so this intermediated particle must have electric charge -1. This guy here also, -1, it's always in unit of the electric charge of the absolute electric charge of the electron. This particle here, if the proton is +1 as electric charge, the neutron is 0. So for conservation of charge in this vertex here, this particle that is exchanged must have an electric charge of +1 unit of electric charge. And then this, when this particle decays, becomes +1 in the positron and 0 in the neutrino. Okay, so not only this particle must be massless, must be massive, and so cannot be the photon because the photon is massless, but also must have an electric charge. So cannot be the photon because the photon is not electrically charged. And third thing is that I have two types of particle, one with electric charge +1 and one with electric charge one -1 and one +1, which can be also one the antiparticle of the other. But now we will see how this interaction can go out of a Lagrangian, okay? And which kind of Lagrangian do we need? So if the quantum electrodynamics Lagrangian cannot describe these two processes, how can we describe these two processes? How can we describe this interaction that we now call weak interaction? We will see now a simplified version of the weak interaction. So we will try to do the same thing we did with the electromagnetic interaction, namely start with a Lagrangian, which is a Dirac Lagrangian for some Spinor field, and then find the symmetries inside this Lagrangian and then make these symmetries local. Okay, which kind of Lagrangian we can use for describing this interaction? What is the starting point? Well, the starting point is to first of all forget about neutron and proton because they are made of quarks. So for now we just forget about this part and just talk about this interaction vertex here. In this interaction vertex here, there is a neutrino, an electron, and some particles which is not well identified yet. So we already know that the electron is a Dirac fermion. It's a fermion. So it's described by a Spinor field. We imagine that also the neutrino is described by a Spinor field. So let's write down the Dirac Lagrangian for a free electron and a free neutrino, which was the thing that we did for coming to electromagnets, to quantum electrodynamics, because we started by the free Dirac Lagrangian for one Spinor field. Now we have free Dirac Lagrangian for two Spinor fields, the electron and the neutrino. I will call the field associated to the electron simply E, and the field associated to neutrino simply nu. This is just for being faster, but don't confuse the field associated to a neutrino with a neutrino. So when I write in the Lagrangian nu, this doesn't mean a neutrino as a particle. When I write down in the Lagrangian nu, this means nu of x, which is a field operator which can generate, so create an antineutrino or annihilate a neutrino. Okay, so when you see in the Lagrangian nu and E and nu, these are not the particles, but are field operator inside the Lagrangian. So let's write down the Dirac Lagrangian for these two free particles. First of all, we have Dirac Lagrangian describing the free electron, which is E I gamma mu de mu minus the mass of the electron times electron field. And then we have plus the same thing, but for the neutrino. So nu bar I gamma mu de mu minus mass of the neutrino times neutrino field. Okay? This is the free Dirac Lagrangian for two generic fermion fields, and we label these two fermion fields electron and neutrino. Now, let's make an assumption that it looks like it doesn't make sense, but it will make sense because we will see later that there was a moment in the universe, in the very, very, very early universe, in which this assumption holds. And the assumption is, well, first of all, the mass of the neutrino is approximately zero, also the measured mass of the neutrino, so this we can just, in the standard model, set it to be zero. But the mass of the electron, we know that the mass of the electron is not zero. But we assume for now, so the first hypothesis we do is that the mass of the electron is zero. And this is precisely because we already know where we want to go. We want to have a Dirac Lagrangian which has some sort of symmetry inside. And if we put the mass of the electron and the mass of the neutrino exactly the same and exactly equal to zero, we will have a symmetry inside the Lagrangian, and this symmetry is simply like this. It goes like, this Lagrangian becomes electron I gamma mu de mu electron plus neutrino I gamma mu de mu neutrino. Okay. These two processes now we can cancel, but remember that we are doing all this, all the crazy stuff you will see now, we are doing them just because we want to explain how these two processes work. Okay, so this becomes our Lagrangian with the mass set to 0, and now you can already see a symmetry. You can see that this part is exactly the same as this part, the only thing that changes are the fields. And so you should also see that if we were to redefine our fields in a certain way, and we redefine the electron not anymore as the electron, but as a mix of the neutrino and the electron field, and the same we do with the neutrino, in a way that in the end, we have a unitary transformation between these two fields, the Lagrangian remains the same. This formally is known as an SU2 global invariance. But let's see it in a more sophisticated way. So first of all, we can organize the electron and the neutrino in a doublet. So we will write now D as doublet equal to neutrino electron. This is just a way of writing down the Lagrangian in a more compact way for now. It's nothing like nothing fundamental for now. And of course the conjugate of this doublet, so the D bar will be neutrino bar, electron bar. So that if I write down the Lagrangian in this way here, this is very important to understand. I'm spending a bit of time here because this usually it's skipped by the professor. They just, okay, now we can write down the doublet and the Lagrangian in terms of a doublet. Yes, but I want you to see that the Lagrangian in terms of the doublet is exactly the same of the Lagrangian without the doublets. Then we will impose symmetries, global symmetries, local symmetry, etc., and so we will see that there is something fundamental in organizing this neutrino and electron inside the doublet. But for now, it's just a way of rewriting down the Lagrangian. So I write D bar I gamma mu de mu D. And you see that if I substitute this row vector and this column vector inside the Lagrangian, then we have I do the various multiplication and I find exactly this Lagrangian here. So these two, this Lagrangian here for two free fermion fields, and this Lagrangian here that also describes in a more compact way two Spinor fields, two free Spinor fields, are exactly the same. Okay? But now we notice indeed that there is a symmetry in this Lagrangian, and the symmetry is called SU2 symmetry. So when we had the Lagrangian, this we proceed in complete analogy. When we had the Dirac Lagrangian for just one Spinor, this was invariant under U1 symmetry. So we were multiplying the field by a phase, so shifting the field by a complex phase. And in this case, the Dirac Lagrangian, so this Dirac Lagrangian in particular, with the mass equal to each other, etc., this guy here has a global SU2 symmetry. Now we will see what that means. These two are global. Okay? Making the symmetry, the U1 symmetry, local, forces us to introduce the photon field, and so forces us to introduce the interaction for the quantum electrodynamics Lagrangian. And we are hoping now that we have this symmetry, making it local will force us to introduce new interaction term that describes what we want to describe, so the beta decay. Okay, perfect. What does it mean to have an SU2 symmetry? Let's first see how the SU2 transformation acts on the field that we want to transform, so on the doublet, and then we will see if the Lagrangian is invariant under global SU2 transformation. Okay, so how does it act on the doublet? It's simply SU2, I'm talking about the global transformation, takes the doublet D and sends it to D prime, that I will put in orange, d prime equal to e to the I g, where g is coupling constant that we will see about, between the Spinor field and the new field that will come out. So this is just a constant that I put here now, times T alpha, and now we will see what T alpha are, D. Okay, this is the SU2 transformation. What are the various pieces? First of all, in this case, the transformation is on a doublet. So, and the doublet is made of two components. So this transformation must be a 2 by 2 matrix, must be described by a 2 by 2 matrix. And in practice, T are three matrices, T1, T2, T3, that are proportional to the Pauli matrices, the Pauli spin matrices. So Ti is equal to 1/2 sigma I, where sigma I are the three Pauli matrices. Pauli matrices sigma x, sigma y, and sigma z that we saw, for example, inside the gamma matrices. So these matrices are very, very important, and these are called the generators of the SU2 group. This is just terminology, but it's interesting to know, or maybe you have background in group theory, so you can relate the two things. These are called the generator of SU2. In a way, these are three basic transformation of SU2. So you can write any SU2 transformation on a doublet, that acts on a doublet, using these three generators here. Okay, so you can decompose any transformation. Then alpha, in this case, has the same role that in a U1 transformation alpha had, but in this case it's not just a single number, but are three numbers, so that T times alpha, this I say alpha and I put sigma, okay, not so good, T times alpha, it's really T1 alpha 1 plus T2 alpha 2 plus T3 alpha 3, okay? Let's write it down in a matrix form, since T are 1/2 the Pauli matrices. Then T alpha, it will be something like this. If I have three parameters, three numbers, T alpha will be something like 1/2 the sum of alpha times sigma Pauli matrices. So I will have here alpha 3, here I will have alpha 1 plus I, minus I alpha 2. Here we'll have alpha 1 plus I alpha 2, and here I will have minus alpha 3. So you see that this element here, T times alpha, it's really a 2 by 2 matrix that describes a transformation, an SU2 transformation. And the SU2 transformation is described by these three parameters, alpha 1, alpha 2, and alpha 3. It's like they are weights, and each weight, it's like each Pauli matrix, it's weighted by a certain parameter alpha, alpha 1, alpha 2, alpha 3, that tells us exactly how the transformation take place. Okay? Now, this is at exponent, so I have a 2 by 2 matrix in the exponent of this function here. So how does this really act on the doublet? Well, what we will consider, it's an infinitesimal SU2 transformation. What is an infinitesimal SU2 transformation? It's simply a transformation in which alpha, it's very, very, very small. Okay, so alpha 1, alpha 2, alpha 3 are very, very small, and then I can the reason why we will consider an infinitesimal transformation is that then we can compose any possible SU2 transformation as an infinity of infinitesimal SU2 transformation. So I just need to check that the Lagrangian is invariant under infinitesimal SU2 transformation. So what we want to check now is the Lagrangian invariant for infinitesimal global SU2 transformation. This I didn't put transformation because it doesn't fit, but is the Lagrangian invariant for under infinitesimal global SU2 transformations? Okay, let's see how an infinitesimal SU2 transformation looks like. So this is an SO2 transformation. So I start from a certain gauge, then I change my gauge using this transformation here. And an infinitesimal transformation, since this is a 2 by 2 matrix but is an exponent, I write it down as an infinitesimal SU2 transformation. An infinitesimal SU2 transformation, it's something that takes D and sends it to D prime equal to 1 plus I g T alpha. So the transformation is encoded in this guy here times D. This means if I write down D prime and D as doublets, that physically a little part of the electron field component go into the how is it called? The neutrino field component, and a little part of the neutrino field component goes into the electron field component. So after an infinitesimal SU2 transformation, the Lagrangian in the new gauge, it's not anymore written in terms of the electron field and the spinor field as fundamental object, but is written in terms of an electron field with a little bit of the spinor field, the neutrino field inside as fundamental object, and a neutrino field with a little bit of electron field inside as a fundamental object. So the fundamental fields in which I write the Lagrangian in the new gauge are a mix between the original neutrino and electron field. This means making an SU2 transformation. We check that the Lagrangian is invariant under an infinitesimal transformation, because then I can build any transformation as a consequence, as a, how do you say, as a multiplication of infinitesimal transformations. So what happens to the Lagrangian under this infinitesimal SU2 transformation? Infinitesimal, by the way, means that alpha it's very, very small. It goes to 0. So let's see, L prime is equal to D bar prime I gamma mu the mu D. Now let's write D bar prime and D prime explicitly with the gauge transformation inside. So the first one will be D bar. Remember that D bar is the conjugate of this one with a row vector that multiplies, in this case, the opposite transformation, so not 1 plus Ig, but 1 minus Ig, 1 minus Ig T alpha. And remember always that T alpha is a 2 by 2 matrix that depends on the 3 Pauli matrices, times this operator here, I gamma mu the mu, and then times, doesn't fit here, I go in the other line, again 1 plus I g T alpha. I always put T alpha in orange so to keep track on where the transformation is, times D. Okay, so now equal, I go here, What happens in this case? Well, in this case it's very simple. Since alpha does not depend on x, this means that it is a global transformation. I can simply filter all this part here. So all the transformation applied to D, I can filter it through the derivative operator. That is to say that d mu d prime is equal to the operator that applies an SU2 transformation to dply get filtered outside of the derivative. So 1 plus I g d alpha d mu d. Okay, so this operator goes through the derivative without being changed. So if this operator goes through the derivative, this function, this Dirac Lagrangian here becomes d bar y minus 1 minus I g t alpha times 1 plus I g t alpha, and then I have I gamma mu d mu d, which in this case here 1 minus IGT alpha times 1 plus IGT alpha, this simply becomes 1 squared, so 1 minus this guy here squared, so minus or plus g squared t alpha squared. But so this is something like 1 plus something of the order of alpha squared, but this is in an infinitesimal transformation, so we neglect everything that is order of alpha squared because it's like 0 squared, like it's much smaller than anything of order of alpha. So this part here we neglect, and this is just 1, okay? Exactly as in the case for an U1 transformation, we were putting e to the I theta times e to the minus I theta, we were putting that to 1. In this case also the transformation applied to the anti-doublet and to the doublet becomes 1. Okay, so all this part here, I put it to 1. And also, and in this case now it's easy to see that if this part here is 1, neglecting an order of alpha squared, where alpha, pay attention, it's not anymore the expansion parameter that we were talking last time about in the Feynman diagrams. This is just alpha, it's a small number. And so in this case I have d bar I gamma mu d mu d, which is exactly the same as the starting Lagrangian. So after a gauge transformation, the first Lagrangian is exactly the same as the second Lagrangian, as the Lagrangian with the gauge transformed fields. So we proved that the Lagrangian, the Dirac Lagrangian, including an electron field and a neutrino field, is a free electron field and neutrino field, is invariant under global U2 transformations. Okay, and this is very good because now we can try to make this transformation local, exactly as we did for quantum electrodynamics, and see what happens. So for a local SU2 transformation, the only thing it changes is that this parameter here, alpha, which is it has 3 numbers inside, alpha 1, alpha 2, alpha 3, becomes dependent on the exact point in space-time in which I'm sitting in. So the transformation, it's different. It's not anymore a global transformation in which I transform this doublet in the same way in every point in space-time, but I transform this doublet, so I mix the neutrino field and the electron field in different ways in every point in space-time. Okay, this is what a local transformation means. We will use the same strategy that we used in making the Dirac Lagrangian invariant under local U1 transformation. And in particular, we saw that introducing a covariant derivative in the U1 case equal to d mu plus I q a mu, with this a mu changing in this particular way, a prime mu equal a mu minus d mu alpha of x, introducing this covariant derivative inside the Dirac Lagrangian makes the Dirac Lagrangian invariant. And the reason why this makes the Dirac Lagrangian invariant is that the covariant derivative applies to the field. When I transform this object here, it transforms exactly as the field transforms. So it transforms like e to the I q alpha of x d mu psi. You can verify this. We didn't do it in this way, we just did it in a more physical way, let's say, without postulating a covariant derivative and putting it inside and requiring that this field transform in a certain way. But you can also do it like this. You do a prescription introducing the covariant derivative with this field inside the covariant derivative, and then you check how this field must transform in a way that the Lagrangian is invariant under local U1 transformation, and this gives you electromagnetism or quantum electrodynamics. Okay, we will do the same. So we will introduce a covariant derivative d mu such that when I transform d mu doublet, so the covariant derivative applied to the doublet, but in which the doublet is transformed. So I have these two objects in the new gauge. This, I require this to be 1 plus I g t alpha, the covariant derivative times the doublet. Okay? So the covariant derivative applied to the field transforms in a locally in the same way as the field itself transforms. Okay, let's see how can we enforce this. And so first of all, we have to define the covariant derivative. So covariant derivative, we define it like d mu is equal to d mu plus I g t w mu. Okay, so in this case the covariant derivative is really a 2 by 2 matrix in which we have the generator of the SU2 group applied to these three fields. So in this case w mu includes three fields, w1, w2 and w3. Okay, so in this case it's not anymore like in the case of quantum electrodynamics, in which we only include one field, which is the photon field, but we are including three fields, W1, W2 and W3, that enters inside the covariant derivative. And this field will transform in a way that, okay, let's see first of all the Lagrangian written down with the covariant derivative and see that this Lagrangian is invariant under local SU2 transformation. So if I define my Lagrangian to be d bar I gamma mu covariant derivative psi, d, okay, and then I transform this. So I transform in the new gauge. This would be d prime, d bar prime I gamma mu, and then we have d mu d prime. But wait, also the mu must transform because the mu contains these fields here which transform under gauge transformation. So d mu prime d prime, okay, and then I assumed that, so I require, now it's not written here anymore, but I require that the covariant derivative and the field together transform in the same way as the field alone transforms. So this becomes d bar, let me write it more here so we have space. Here we have d bar 1 minus I g t alpha, this time alpha depends on x, and then I have, yes, then I have this guy here, which transform, in which way transform? This guy here, I require that this guy here, I will define my covariant derivative, and in particular the transformation of the field inside the covariant derivative. So I need to define the transformation of this object here such that this object will become 1 plus I g t alpha covariant derivative of the doublet d in the first gauge, in the original gauge. Okay, so in this case this will be I gamma mu, and then this piece here that can already filter outside, so I will already put it outside, so times 1 plus I g t alpha of x, and then the mu d. Okay, so that for the same reason as before, this one is 1 plus order of alpha squared, and so neglecting the order of alpha squared, this Lagrangian in the new gauge is exactly the same as the Lagrangian in the old gauge. Okay, so this is equal to this. Okay, so the thing, the Dirac Lagrangian, it's invariant under local SU2 transformation if we introduce the covariant derivative with this field inside. This field is really a triplet of field, so it's not only one field as in the case of quantum electrodynamics, but are three fields. And now we have to see how this field must transform under local SU2 transformation in a way that the covariant derivative respects our requirement, our request. Let's put it down as simply as possible. I require that this characteristic is true. Okay? If this is true, then the covariant derivative, then the Dirac equation written down with the covariant derivative, it's locally invariant under SU2 transformation. It's invariant under local SU2 transformations. Okay? Now, how do these two pieces transform? Well, d prime mu transforms as, since the mu it's the mu plus I g t w mu, I have a field here that must transform. So this field here must be w prime mu in the new gauge. And this field, remember, that is made of three components, but w prime mu, I can just call it w mu prime equal to the old w prime, so the old gauge field, plus a delta w. Okay. So in this case, the transformation of this operator here, of this covariant derivative, will be d mu plus IGT w mu plus IGT delta w. Okay? This is how the covariant derivatives transform. Now, if to this operator here I apply d mu, so this guy here. No, sorry, the not the mu, the doublet prime. So in the first reference frame, which is 1 plus I g t alpha d. Okay, if I take this object here and I multiply it by this object here, and I want that this piece here filters through all these three objects and give me something, I must require that the field W mu transforms in a very particular way. So the thing is that I want to do is determine how W mu transforms in such a way that reabsorb all the terms that goes out from filtering this object here through this operator here, okay, through this part here of the operator, okay, because when I apply, when I do this multiplication here, I can filter this object out of this, but I will get additional pieces. So W mu must transform in this way. W prime mu must be equal to W mu minus d mu alpha. Okay, and this is the same prescription that we applied, exactly analogous to A prime mu equal A mu minus d mu alpha in the case of local U1 invariance. But in this case, for this object here, I must add a new piece, okay? A new piece given by the fact that this group here, it's not abelian. Non-abelian group means that I cannot apply, I mean, to subsequent transformation, like the order of the transformation of this group matters. Let's see what it means. So we will have the same structure as the vector field that we get out from local U1 transformation, which is this, plus another piece that reabsorbs the term in which, for which we want to filter this piece through this piece here. You can check that the additional term that we have to place here, it's the term that cancels when this object here filters through this object here. So let's try to do it. The fact is that I will have at some point, when I do this multiplication here, I will have at some point and I invite you to try at home, I g t W mu multiplied by I g t alpha, and then times d. Okay. For making such that all this operator gets in front of the covariant derivative, I must filter this piece here, IGT alpha, through this piece here. So what I want to get, it's these two guys swapped. But this guy here is a transformation, is a SU2 transformation, and this guy here, it's another SU2 transformation. And these two transformations, if I apply first this transformation, T W mu, and then I apply this transformation, T alpha, since SU2 is a non-abelian group, it's not the same as applying first T alpha and then apply TW mu. Okay? So for filtering out this object and putting it in this part here, I need to understand how this works. So first of all, I just say commutator between this transformation here and this second transformation, T alpha, must be equal as definition of the commutator. So it must be this times this minus this times this. So I will have equal these two pieces here, T W minus T alpha Tw times T alpha minus T alpha times Tw. So that, in this case, the sequence of the transformation is first Tw and then T alpha. But first Tw and then T alpha, if I take this relation here, it's exactly commutator plus this piece here. So commutator between Tw and T alpha, or let's put this first. So T alpha times Tw mu plus the commutator of these two objects, which I will write as minus the commutator of the object swapped. So minus commutator between. Let's also put T alpha in orange just for keeping track of where the pieces go. T alpha, okay, and in this case I have commutator between T alpha, which is one transformation, and W mu, Tw mu, which is another transformation. Okay, so this piece here must be Ig, but Ig it's simply minus 1g squared, because I have 2 times g, that multiplies, let's see, multiplies T alpha Tw, T alpha times Tw mu, and this is actually the operator filtered out. Okay, so I have it. Also in this case, let's just keep it like Ig, so it's exactly the term I wanted, but then I add a new piece, and the new piece it's minus Ig, or better, yeah, it will be minus I times minus I, which is minus 1, so here I have a plus, if I'm not mistaken with the signs, plus the commutator between T alpha and Tw. Okay. But this I also can write it in components. So, okay, the thing I must remove from this guy here, and also, okay, here I also have a g squared. And then I can use this formula to show that the formula is that some sigma matrix times an object A multiplied by sigma matrix times object B is equal to AB minus, no, plus I sigma matrix A vector product B. So that I know that the object that I must add here to cancel this term that gets out of my of filtering this piece in this way here, it's super confusing. I'm very sorry for this part. It's very confusing, but I hope the concept remains, and in the end you will only have to understand how this field transforms. But the piece that I have to add here, it's simply minus G times alpha vector product W mu. Okay, so now the field W mu must transform, or must also mix its components, but must transform in this particular way in order to maintain, in order to have this relation here, and this relation here in turn will give this relation here will give SU2 local invariance. To the Lagrangian made like this. D bar I gamma mu covariant derivative Okay. With this covariant derivative prescription, putting it into the Dirac Lagrangian for this doublet, and with the fields that we put inside our covariant derivative, which are these ones, W mu, which will be 3 fields, transforming in this particular way, we recover local gauge invariance for this Lagrangian here. What does it mean in practice for the interactions inside this Lagrangian here? Do neutrino and electron in this case interact or not? Because that is precisely why we are doing all this. We found a Lagrangian which is invariant under local SU2 transformation if I define my covariant derivative like this, and I define my field inside the covariant derivative, which is really 3 fields, to transform in this way here. Okay? This is not the same way of the photon field transforming, because the photon field transforming only had these 2 pieces here. In this case, I have another piece given by the fact that the group is not abelian. Okay? And this other piece mixes the 3 fields, the 3 basic objects of W mu field. But we will not go too deep into that. Now, I cancel this transformation because it's not what we need now. What I want to do now is to check that in this Lagrangian here we have the vertices to explain our beta decay in which we started this and we introduced this Lagrangian for. So let's see. First of all, in this case here I will have a kinetic term, so d bar I gamma mu d mu, simply writing the covariant derivative explicitly, d plus ig, but plus I times I, it becomes minus 1, so minus g d bar gamma mu, then I have t w mu. Also here write W mu in orange so that we know that orange it's vector fields times d. Okay, so this will be the kinetic term for the Dirac field, for the Spinor field, and this will be the interactions of our simplified, it's not here anymore, but this is again simplified weak interaction. We still miss kinetic terms for this W field, which we will introduce in a moment. But let's focus for now in the interaction term and let's see if it can explain our vertices for weak interaction. Let's write down things explicitly. First of all, what is TW mu? Well, this is simply, since T are the generators of the SU2 group, this is equal 1/2 sigma matrices. So TW mu, it's simply 1/2, then we have this 2x2 matrix in which I put the third component of W here, minus W mu 3. Okay, so I have W mu 3 and minus W mu 3 in the diagonal. This is just a multiplication between the sigma matrices and W1, W2, W3. So it will be sigma 1 W1 plus sigma 2 W2 plus sigma 3 W3. And of course these are all vector fields, so 4 vectors. Okay, but let's write it as a 2x2 matrix. So here I have W1 minus I W, so W mu 1 minus I W mu 2, and here I have W mu 1 plus I W mu 2. Okay, and this is our matrix that encodes our interactions. Our interactions are not perfectly the interactions that we have in nature, really, because we started by the assumption that the electron is massless. We started by, okay, we didn't talk about the fact that in nature only left-handed component of the spinor interact. This we will talk about it later, but for now this is just a simplified version of the interaction, but it can tell us much about the interaction. So this term here, how it works? It works like this. I have minus g. Now I write explicitly the doublets. Nu bar, E bar. So this is the doublet conjugate. Gamma mu. Then I have this huge matrix here. So 1/2. Let me put here a minus g over square root of 2, and we will see why. So here the 1/2 becomes W3 mu over square root of 2. Then it becomes 1 over square root of 2 W mu 1 plus, minus I W mu 2, and it becomes here minus, let's put it here, minus 1 over square root of 2 W3 mu, and here I have 1 over square root of 2 W1 plus I W mu 2. Okay. And then I have the second part of the doublet, or I mean the second doublet, so neutrino and electron here. Okay, this is the interactions interaction term in this Lagrangian. As you can see, it's much more difficult, more complicated than the simple interaction term, in which we only had one interaction term in the quantum electrodynamics Lagrangian. Here we have 4 interaction terms. Okay, so let's modify first of all this part here. This guy here, we call it W mu plus, and this guy here, we call it W mu minus. Okay, so that in our definition we have W mu plus minus equal 1 over square root of 2 W mu 1 minus plus W mu 2. Okay, this is a 1, not a prime. Very good. So that I can rewrite this matrix a little bit better and see what kind of interaction come out. So this will be W3 mu over square root of 2, and I have W plus mu, W minus mu, and minus W3 mu over square root of 2, and then doublet nu e. Now if I do all the multiplications here, this times this, etc., what I get, it's, first of all, let's do this multiplication between this matrix and this doublet here. So I get minus g over square root of 2, which is not anti-neutrino, it's just conjugate neutrino operator field, conjugate electron field, and then we will have this guy times this guy. So I will do this multiplication, this times this, and I will get the first row of a 2-column vector. The first row of a column vector of 2 rows, which will be W3 mu times neutrino over square root of 2 plus W mu plus times electron. Okay, and the second column, second row of this column vector, it's W mu minus times neutrino plus or minus W mu 3 over square root of 2 times electron. Now if I go to make this multiplication here, so between this vector and this vector, so it will be this term times this term plus this term times this term here, I will get four kind of interaction. Okay, let's see which interaction. And in particular, I'm interested not in the interaction between neutrino and electron, but I'm interested in the mixed interaction, because that is precisely what we get in the weak interaction and what we want to explain, or at least what we would like to get out of this little Lagrangian, which is not so little. Okay, let me cancel a little bit here. So from this Lagrangian here, the first interaction I get, it's nu coupled with electron. Let's see what is that. First interaction, it's so I have a term which is minus g over square root of 2. Neutrino. Here of course there is a gamma mu that I forgot, which I will write it here. Okay, so neutrino, gamma mu, then I have W mu plus electron. Okay, and this is this guy here, neutrino, times this guy here, electron. Then I can have, I'm only interested now in mixed terms, then I can have electron times this guy here, which is neutrino. So I also have another term, which is minus g over square root of 2 electron gamma mu W minus mu neutrino. Okay. Can these two vertices, these two interactions, and of course you see that they are very similar to the vertices that we get minus, minus q psi bar gamma mu psi a mu, okay, in which the role of a mu in this QED vertex is now played by two fields which are W plus mu and W minus mu. Okay, you see that the structure of the vertices is exactly the same, and in this case we have a vertex that couples electron neutrino through this W plus field, and another vertex that couples electron and neutrino through this W minus vertex. Okay, let's see what these two vertices represent. So I have, first of all, this vertex here. This vertex here can represent, let's put it like this way. So I have conjugate field, conjugate neutrino field. If you remember from previous lectures, conjugate field can generate particles or annihilate antiparticles. In this case, let's say that he generates a neutrino. So we have a neutrino in the final state. In this case, we have then a Spinor field. The Spinor field can create antiparticles. If creates a particle, it's correct. If it creates a particle, I get a particle in the final state. This guy here can annihilate particle or create antiparticles. So in this case, I will, if I have the initial state free, so in this case I have a particle that must be annihilated in the vertex. So I have an electron in the initial state and a neutrino in the final state. And then of course, this guy here, if I want to emit a particle, so create a particle, for charge conservation, this particle must be a W minus. So a W boson which carry a minus one electric charge. So we know that, or another way of doing it, it's, so this vertex here destroys an electron, creates a neutrino, and creates a W plus. But I can also do the same vertex with a W, this creates a W minus. But I can do the same vertex with a W plus in the initial state. This also is for charge conservation. So this guy here has charge -1, this has charge +1. So in the initial state I have charge 0, and in the final state I must have charge 0 as well. So W minus, it's a field, W minus mu, which is different by W minus and W plus particle. This is a field that creates it's in this vertex we have W plus field. So W plus field creates W minus boson, because I can have W minus in the final state, and destroys or annihilates W plus bosons. Okay. Okay, now let's see the second vertex. What can the second vertex describe? So we have still an initial state particle, a final state particle, and we need to understand who these particles are. These particles are, first of all, this guy here can create create an electron. So for example, in this case I have an electron in the final state, or it can also annihilate a positron. So I could also have a positron in the initial state, but let's make it with an electron in the final state. And this guy here, the new field, can create an antineutrino or annihilate a neutrino. So let's annihilate a neutrino. Yes. And in this case, if I annihilate a neutrino which has charge 0 and I get an electron here, this guy here must have charge plus. Okay, so this particle here must be a W plus in the final state. So this W mu minus field can create a W plus particle, or same way I can annihilate a W minus to get the same initial and final state charges. So this guy can also annihilate a W minus. Okay. So we saw that this Lagrangian here, with the covariant derivative defined in a certain way, with these three fields inside, can describe what we wanted to describe, that is the weak interaction. Of course, there are various caveats. First of all is that electron and neutrino today have different masses. So why did we put the electron and neutrino mass the same to make the global SU2 invariance in this Lagrangian? It's still a mystery that we will solve in another lecture. And then second stuff is that in this case we are considering all the fields interacting, but actually in the weak interaction only one component, the left-handed component of the fields, participates. But we will solve all these mysteries. Last part of this lecture is to figure out what is the kinetic term of these fields here, W. So we define the transformation properties of this field. We can also write down the transformation properties of the field component by component. So we have the kth component of the field W mu transforms in this way here, where epsilon ijk are the structure constant of the SU2 group. So in particular are numbers that come out from the commutation relation between the generator of the group. I believe it's Ti, Tj. So if Ti, Tj is the commutator of the elements of the generator of the group, this is equal to I epsilon I j k t k. Okay. In this case we call it epsilon because we are talking about SU2 group. So epsilon is also a function which it's +1 or -1 depending on how do you put these indexes here. Okay, but never mind. You just have to remember that this one relation here, it's written component by component, while this is just a vector, so it has all three components inside. But what I want to do now is to create a proper kinetic term in the Lagrangian for the W field, because we saw that the Dirac Lagrangian, it's simply doublet I gamma mu covariant derivative and then doublet again, but we miss the kinetic term for the W field, and we will define this exactly as we defined the kinetic term of the photon field. And in particular we call the kinetic term, or better, we introduce a term in the Lagrangian which is, we can call it LW, so the term in the Lagrangian that depends only on the fields W, it's equal to minus 1/4 W mu nu, W mu nu. Okay, but there is a but. If I define W mu nu to be, as in the case of F mu nu, d mu W nu minus d nu W mu, this term here, it's not gauge invariant under local SU2 transformations. What we have to do is to add to this term here a minus g epsilon I j k W mu I W mu k. Okay, and in this case this will be the kth component of this W mu nu. I will have k component, and this will be kth component. Okay, so the k goes here. Okay, this is written in components again. Okay, if I define W mu nu to be this object here, then this object minus 1/4 W mu nu will be gauge covariant. Okay, so also in this case I introduce new pieces because I have, let's write it in this way, minus 1/4. I don't write now all the indices, I just write down the structure of this, which will be, I also don't, okay, so let's write it as more or less equal to, this will be W mu nu squared. So if I do W mu nu squared, what I get, now the only thing I want you to see is that if I square this term here, W mu nu, what I get is a kinetic term, exactly how I got it for the photon field. So we'll have a kinetic term which is minus 1/4 d mu w nu minus d nu w mu times again d nu w mu minus d mu opposite d mu w nu times d nu w mu. So this is the kinetic term, and then I will have plus other terms which are this guy here who contains two W fields times this guy here. So it will be a term which has some term, more than one term, that has so this is just the kinetic field, kinetic part, sorry, of the Lagrangian. Okay, so this instead is the total Lagrangian that only depends on W prime on W. We'll have a kinetic field which is analogous to the kinetic field of the photon, but we'll have terms which are combination of 3W, so something times W, 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 and then I will have another term which is the multiplication between this piece here with himself. So I will have 4 W fields plus again something W, 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 W. Okay, this is just to say that the non-abelian structure of this SU2 group not only gives us all the interactions that are weird, let's say, but also gives us, so not weird interaction, I wanted to say, not only gives us a weird transformation of this W field, but also gives us interaction of the W fields, which because are 3 fields, with themselves. Okay, so it gives us new vertices in which we have interaction between 3 W fields, 3 W bosons, and 4 W bosons. So putting all the pieces that we discussed together for this toy weak interaction model, remember that it's a toy because we just start assuming that the neutrino mass and the electron masses are the same, but we will have that this is the Lagrangian that we get from it. Okay, so we saw a toy model for the weak interaction, and we get this Lagrangian. We started by this guy here, which was SU2 globally invariant. So was invariant under SU2 global transformations, which is the Dirac Lagrangian for two Spinor fields. And we get all this Lagrangian here, introducing this W mu field that describes our interactions. Now I've wrote it in an extensive way, in a way that we can comment it. First of all, we have the kinetic term for the electrons and the neutrinos. Then we have the interaction terms between electron neutrinos and these W mu fields, and in particular we have neutrino electron vertex, so vertices that mix neutrinos and electron with these W plus or W minus fields inside these vertices. And then we found, and we didn't comment, but in the vertices, so in these structures here, we have other vertices which do not mix electron and neutrino. So for example, we have neutrino-neutrino interaction with this W3 boson. We didn't talk about this vertex specifically because one is tempted to identify this vertex as the Z boson, which is it's a particle that we observe in the standard model, but this vertex here, it's not the Z boson. We will then identify the Z boson and the photon in an extension of this toy model in which we only have an SU2 local invariance, but that we will see in a moment. So we have an interaction term that tells us the interaction between electron and neutrino and this charged boson. Then we have a kinetic term for the electron and a kinetic term of the neutrino that are encoded in this piece of the Lagrangian. And then we have this piece of the Lagrangian here that only depends on the gauge bosons. And in particular, since we are making a local invariance of a non-abelian group, we have that, in this case, we have kinetic term for W, which will be the mu W nu minus the nu W mu squared, in a sense, okay, so proportional to this guy here squared, just not to write crazy amount of stuff, which is exactly the same as the kinetic term that we got for the photon in the Lagrangian for the quantum electrodynamics. But then, since this is a non-abelian theory, we also get terms inside this guy here, which encode the interaction between these W bosons. And in particular, we have one term in which we have a vertex with 4 W bosons, and one term in which we have a vertex with 3 W bosons. Okay, these vertices here also exist in the standard model with the W boson and Z boson and photon that we have in the standard model, although they are a little bit different because the fields that are involved in some cases are different. Okay, but these are now, we saw that from a non-abelian gauge theory we have this kind of interaction here with multiple gauge boson, not only one, which was the photon in the quantum electrodynamics theory, and we have interaction of the boson with himself. While in the quantum electrodynamics Lagrangian, we do not have interaction of the photon with himself. Okay, now we will do an extension of this model to also to explain the particles that we see in the standard model, because we still have 3 problems in this model here, 2 or 3. Let me count them. First problem. Introducing a mass term for the bosons, so mass of W plus minus breaks gauge invariance. Second problem that we would like to explain. The mass of the electron, of course, is not 0, but we came to this model assuming that the mass of the electron was 0. So how to solve this problem? We don't know yet. And third problem is that Z is not W3. So the Z interaction, the Z particle that we observe in the standard model, so in our interaction, so we really observe this in our physics, but this is not the W3 boson that is in this theory. So we would like to have some mechanism, something for identifying how the W3 boson in this theory here relates to the Z boson. And in particular, with electroweak unification, we will find that this W3 is a piece of Z and a piece of the photon, but we will talk about this later. And these 2 problems of the mass will be solved by the Higgs mechanism. So this exciting piece of physics is what is next. This was a tough one. So what we did up to now was to, first of all, making a U1 local invariance to the Dirac Lagrangian only for a Spinor field and obtaining the quantum electrodynamics Lagrangian, introducing a new field, a gauge field A mu, one single gauge field, for making this symmetry local. And we obtained the electromagnetic interaction. Then we tried the same mechanism using electron and neutrino and an SU2 symmetry that we made local. So for introducing this local SU2 symmetry in the Dirac Lagrangian for electron and neutrino doublet, we introduced three fields, WMU1, WMU2, and WMU3, okay? Which are the three fields associated to the generators of the SU2 group, which are, so the ith generator is 1/2 sigma I, where sigma are the Pauli matrices. Now, the plan for today is, first of all, explaining the structure of the weak interaction. And explaining, for doing this, we will explain what is the left-handed, so we will explore the concept of left and right-handed, so left-handed and right-handed chiral states. And we will see what does it mean that only left-handed chiral states participate in the weak interaction when it comes to exchange W- and W+ boson, which I remind you that are a combination of these WMU1 and WMU2 bosons. And then two, after seeing the structure of the weak interaction and the left-handed and right-handed, a little discussion about left-handed and right-handed chiral state, we go to electroweak unification. Okay, for making this electroweak unification, what we ask is, okay, we have now two separate theories. One that can explain partially the weak interaction, so the exchange of charge boson in the weak interaction, and one that can correctly explain electromagnetism. We derive these theories from two distinct local invariance principles, so trying to make invariant under local gauge transformation two distinct Lagrangian, but can we in a way put them together? And we will see that for doing this we will need to use another symmetry, which will be SU2 left. This left here has to do with the fact that only left-handed chiral states participate in the weak interaction, which we will see what does it mean in a moment, times U1 hypercharge. This U1 symmetry that we will impose to our new Dirac Lagrangian that we will write with electron and neutrinos, it's not the same symmetry as the U1 electromagnetic symmetry. So this one we will label U1 electromagnetism, and this one is U1 hypercharge. Okay, they are two different symmetries with two different fields associated to them. So this symmetry will have the same fields associated with this SU2 Lagrangian, which same gauge bosons, which are WMU+, WMU-, which are combination of these two. Okay, then we also have WMU3, and this symmetry here will be associated with another field which is called BMU. This is a photon-like field, but it's not the photon field AMU. We will find out that the photon field, after electroweak symmetry breaking and Higgs mechanism, that these two fields mix to create the physical fields of which particle, which are excitation of this field we observe, which are Z, so a Z massive boson field, and AMU, which is the photon field. Okay, so Z and AMU, which are the field that we physically observe, the particle that we physically observe, are mixing of these two fields. Okay, one it comes from the SU2 symmetry, and a part of that comes from the U1 hypercharge symmetry. Okay, so it's different than saying this AMU field comes from the electromagnetic U1 symmetry. It's a different stuff. This is the plan. It's just 2 points, but we will have very much fun on exploring these 2 points. Let's start with the structure of the weak interaction. Okay, we are in a point in which we talked about two theories. One is the quantum electrodynamics theory, in which we have a local U1 symmetry, and we obtain this interaction term in the Lagrangian. So an interaction term in the Lagrangian in which the electron field is coupled with the photon field. Okay, and in this case, the Lagrangian describes only an electron. Then we made an assumption in which we have a neutrino and an electron which behave in the same way, so they are both free fermion. We built the Dirac Lagrangian, and then we made this Dirac Lagrangian invariant under global SU2 transformation, and we find this interaction term here. Okay, this is not yet the interaction term of the weak interaction Lagrangian, because we have these fields here which are not quite right, and now we will see why. But the structure of the interaction is the same, it's exactly the same, so imposing an SU2 local invariance, what we found is this interaction term here, so the doublet neutrino-electron, which we called D, it's coupled with three gauge fields, which we will call W1, W2, and W3. Then W1 and W2 mix to form this W mu plus and W mu minus, and W3 remains on the diagonal term. What we are interested now is in talking about the structure of the weak interaction, because at some point we will see that measurements show that only the left-handed chiral state of these doublets participate in the weak interaction, and in a moment we will see what does it mean. But first, let's write down the electromagnetic currents. So what are currents? Let's define the various currents. So from the interaction Lagrangian from quantum electromagnetic, we can find that we have a term which is coupled to our photon field, which is this term here. So we can call the electromagnetic current J mu electromagnetic simply equal Q, where Q is the electric charge of the particle we are considering, in this case is the electron, but this can be any spinor field. Also in this case I remind you that E does not mean the electron as a particle, but is just a field operator that creates and annihilates electron and anti-electron, depending on if it's E bar or E. So this electromagnetic current is something like this: E bar gamma mu E, and that's it. Then from this Lagrangian here, we will only talk about the charge current, so weak charged current. I'm talking about these currents because in any book about particle physics and in which you do actual calculations, there are always these currents around, and I had very, very hard time as a student understanding what these currents were. But okay, charge current. in this case, charge means that it's the current associated, as in in quantum electrodynamics, the electromagnetic current is associated with the photon field. In weak interaction, the charged current is associated with the charge field, so with the W plus and W minus bosons. And in this case, with this field here, W mu plus, which I remind you, he creates a W minus boson and annihilates a W plus boson, and vice versa, this one creates a W plus and annihilates a W minus. So what are the currents associated to these particles, to these fields here? Well, simply, I can extend the interaction Lagrangian and take only the charged, so let's call it CC interaction. So the piece of the interaction which contain charge currents are the piece that have to do with these two fields here. So if I expand this term, as we did it already, W mu, for example, I do this product here, so the first row of this matrix multiply this column, and I get W mu 3 times neutrino, and then W mu plus times electron, and I'm only interested in W mu plus. So this coupled with the electron, and it's upstairs in the vector that I will get, and so this couples with the neutrino. So in this case we have G, or minus G, over square root of 2, then I have antineutrino, gamma mu, electron, and then I have W mu plus, and you can try to do the same with the W mu minus, but it becomes something like this, G over square root of 2. In this case I couple anti-electron, which is not anti-electron, but it's anti-spinor field associated to the electron, E bar, gamma mu, neutrino field, and this I couple it with W minus. So now, exactly as in electromagnetism, as in quantum electrodynamics, I can call this term here and this term here the currents. So in this case I have J, the mu goes on top, yes, J mu plus, and in this case I have J mu minus. But what we find out, so now let me just keep these currents here, and I write them here, so J mu plus. Okay, let me copy these currents here and then we will discuss. I copied the two currents, leaving a blank space here because we will need to add something here when we are describing actual physics, the actual physics of the weak interaction. What do we have to add? Well, we discover at some point, and in particular with the experiment of Madame Wu, which I will not expose because I think it's confusing in the way we are talking about physics, but we discover with the experiment of Madame Wu, and by the way, I think, as many other physicists think, that she should have won the Nobel Prize, but she didn't, unfortunately. But okay, anyway, in her experiments, she proved that the weak interaction violates parity, and this mathematically reflects to a statement which is that only the left chiral state, only left-handed chiral state. Now we will see what it means. Participate in participate in these two terms here, okay? This does not hold for the weak neutral current, so the terms in the diagonal. Actually, it's more complicated than that, because the term in the diagonal, after the electroweak symmetry breaking that we will talk about later, they will mix with another field, so it's a little bit more complicated. So that is why we only talk about the weak charged current and not the weak neutral current, but only left-handed chiral states participate in the weak charged current. What is a left-handed chiral state? Well, let's say that we have a spinor, psi. I can divide this spinor in psi L, where psi L is the left-hand component, chiral component of the spinor, plus psi R. Let me write it in another color, like this. Okay? I can decompose any spinor, so in this case the neutrino, the electron, also in this case the electron, I can decompose them in a left-handed component and a right-handed component. The characteristics of these components are the following. We define a matrix, gamma 5, which is equal to I, gamma 0, gamma 1, gamma 2, gamma 3, where gamma 0, 1, 2, 3 are the Dirac matrices that we used all along. So these gamma mu are just all the various gamma matrices multiplied and then multiplying times I. And this matrix here, so will be a 4x4 matrix that is used to select the left-handed or right-handed chiral state when I have a full spinor. Okay, let's see how it works. If I apply this gamma 5 matrix and I multiply it for a left-handed spinor, so a spinor which is only left-handed, I get -1 times the left-handed spinor. So it's a little bit like saying the left-handed spinor is an eigenstate of this gamma 5 operator with eigenvalue -1. And the same goes, or very similarly goes, for the right-handed spinor. So if I apply this operator gamma phi on the right-handed component, only the right-handed component of the spinor, what I get is plus psi r. Okay? So that is how it works. So I can identify a left-handed chiral state with this gamma 5 matrix, and I can identify a right-handed gamma chiral state with this gamma 5 matrix. Now, if I have a state which is a mix, is a superposition between left-handed and right-handed, like in this case, and I want to select the left-handed or right-handed component, I can, now I delete this one. How it works if I want to select a left-handed component. It works like this. I define some projector. I call PL the operator that takes my spinor, which is a superposition of left and right-handed chiral components, and gives me the left-handed component of the spinor. Okay, so we will define this operator here that takes the whole spinor and gives me only the left-handed part. Then I can also define PR, which is an operator which, when I apply it to my spinor, it gives me the right-handed component of the spinor. Okay, and these two operators are defined as follow. Of course, we use the gamma 5 matrices for defining these operators. PL is 1/2 1 minus gamma 5, and PR it's 1/2 1 plus gamma 5. Okay, so when I apply this operator here to the full spinor, I get the left-handed chiral component. When I apply this operator here to the whole spinor, I get the right-handed chiral component. is there a physical intuition to understand what does it mean to have a left-handed spinor or right-handed spinor? There is only in a particular case, which is the case of massless particles. In the case of massless particles, what I get is that the chirality of the particle, so for massless particle, chirality is the same thing of helicity. Now, what is helicity? Helicity is a concept in physics which is very much, it's much easier to understand than chirality, and is the same thing as chirality in the case in which the particle we are considering has zero mass. Helicity is an operator defined like this. Sorry, I put h bar as a reflex. Also, we don't even put the formula, just an intuition for it. If the particle is moving along this direction, so his momentum is this one, and the spin of the particle, the total spin of the particle, it's, for example, something like this, the helicity, so we have momentum operator, then we have spin operator, then we have helicity operator is the projection of the spin operator on the direction of the momentum operator, okay? So if the spin of the particle is aligned in a way, so it points in the same direction as the momentum, so as the direction of motion of the particle, then this one has right-handed helicity. Very confusing that before I called left-handed stuff in orange and now I'm calling right-handed stuff in orange, so that's just this spinor here as right-handed helicity, so RH helicity. Okay. If it's in the opposite direction, so if I have the momentum P in this direction, so the particle is moving in this direction, and the spin of the particle points in the opposite direction, in this case the projection of the spin of the particle goes in the opposite direction of the momentum of the particle, so in this case I have negative helicity, and in this case it's said that the particle have left-handed helicity. Okay, this is just an intuition for what chirality is in the case of massless particle. This is not the same in the case of massive particle because, of course, when I have a massive particle, I can always travel faster than the particle. And so I can get a reference frame in which I go faster than the particle and the momentum of the particle starts pointing in the opposite direction. That doesn't hold for the spin of the particle. So if I go fast enough, I can make such that the momentum of the particle for a massive particle points in the opposite direction. The spin of the particle keeps pointing in the same direction, and I have a particle which in a reference frame has right-handed helicity and in another reference frame has left-handed helicity. So this concept of helicity, it's not Lorentz invariant. This does not hold for massless particle because massless particle all travel to the speed of light, so I cannot go faster than the particle and I cannot invert their helicity. And so it's a Lorentz invariant concept only in the case of massless particles. Very good, but this helicity part is just for having a physical intuition of what's going on in this case and what is a left-handed chiral state, at least for massless particle. But in this case we have the electron, which is not massless, and also the neutrino, even though in the standard model is considered to be massless. Measurements show that the neutrino, it's not massless. So it's chirality what we really want. And now, if we want, if we measure this, that only left-handed chiral states participate in the weak charged current, what we do in our vertex that we had, so for weak interaction, now I call this weak and not SU2 anymore, the interaction part of the Lagrangian will be the same as minus GW, where W is the weak interaction term, times a doublet that is not anymore D, but I call it L. Okay, let me just think about this. L gamma mu T okay, yes, this should be the right one. So when I go to weak interaction, so not anymore SU2 total, I changed the doublet, which was a composition of neutrino and electron, with this left-handed doublet, which simply only selects the left-handed neutrino and the left-handed electron. So I will change my fields in, so the fields that I had before, which are neutrino and electron field, now are left neutrino, left-handed chiral state of the neutrino field, and left-handed chiral state of the electron field. And these are the only two fields that participate in the weak interaction. That means that a vertex like this and a current like this, let's do it for J mu plus, and then for J mu minus it will be the same thing. The vertices become like something like, in this case I will have J mu plus, which will be equal to GW in this case, because we have the the coupling constant for weak interaction, or for W bosons, over square root of 2, only left-handed component of the neutrino, then I have gamma mu, then I have only left-handed component of the electron. Okay, if I want to use my projector here in this current, what I write is that the anti-spinor field left-handed is equal to, in this case, one does the calculation using that nu bar is equal to nu dagger times gamma 0, and you get that this is equal to nu, so the total spinor field, anti-spinor field, times the right-handed component projector, okay, so PR, while EL, so the left-handed component of this spinor field here, is equal to simply PL, so projector left times the total spinor field. So once we introduce this, instead of writing down, this is just a rewriting of the vertex. After this rewriting of the charged current, we will just put the label L here in both cases, and we will be happy like this, so without any more talking about these projectors. But I wanted to show you this projector and how they enter in the weak charged current, because because it's very confusing to me why there is only once. Let's see. So yes, instead of putting nu bar L, I put here nu bar times PR. Then I put here, instead of EL, I put E times PL. Okay, or better leave a space here, PL. Now we use another relation, which is PL, or better, PR times gamma mu is the same as gamma mu times PL. These are all the relations that you can figure out also by yourself, just remembering the definition of gamma 5 and all the gamma matrices. And you will see that this holds. It's okay, it's difficult to see because they are 4x4 matrices, so it's very boring and very difficult. But trust me, this is the thing, and it's not difficult in principle to see it. It's long and boring, the calculation, but it's not difficult to show it. So this holds, so we can filter PR in the other side of gamma mu, so here, and it becomes PL. Okay, so I remove it from here, and it becomes PL. And then I use another relation, which is that PL squared is also equal to PL. So in this case, PL, I can just keep it once, and it's exactly the same. So this is PL. Okay, so you see that the plus component of the weak charged current, it's this object here. So what we do in practice, it's exactly the same component that we get by our SU2 Lagrangian, but with a PL here, projector left, and with a PL here. Okay. The thing I found always very confusing when I was studying is why there is only one time this PL operator. So it looks like only the electron part of the vertex, it's left-handed, but the neutrino part is not left-handed. So what happens, etc., etc. Okay, this is just because of all these relations here and all this simplification that we can write down in the projector operators. So this is the vertex that was verified experimentally, which is not the vertex, because the vertex will be coupled with the W plus and W minus boson. But just for you to know that the vertex, the charge current looked like this. And we, in our case, we defined it like the analogous of the electromagnetic current. But of course, you can dig much, much deeper into this, and we will not follow this direction of the currents. Now we will see how to unify the two theories that we got up to this point, which are quantum electrodynamics and this weak interaction theory. Finally, the electroweak unification, which is also called the Glashow-Weinberg-Salam model. Model. Okay, very good, very good. Let's assume. Let's start with an assumption. The assumption is, since we explored already the electromagnetic interaction and we explored that only left-handed chiral states participate in the charged weak interaction, the assumption we make is that we have, as before, a universe in which we only have electron, okay, and neutrinos. Now, the electron can be written as right component of the electron plus left component of the electron, and only this left component will participate in the weak interaction. Then, neutrino can be written as right-handed neutrino plus left-handed neutrino. But the right-handed neutrino in our standard model does not participate in any kind of interaction, so we will have a theory in which the right-handed neutrino does not exist. This is an assumption we make. We really don't know if it's true or not, but it's an assumption that we make that will in the end, we'll explain the physics that we see, so it's an assumption that is well made, let's say. So the neutrino part, it's only left-handed, and not only that, the left-handed component of the neutrino, of course, does not participate in the electromagnetic interaction because it's not electromagnetically charged. So this guy here only participates in the weak interaction. Okay? So we will now decompose the Lagrangian that we have written before, which was the Dirac Lagrangian. And also another. So the first assumption that we make is this: we only have these particles here, and then the second assumption that we make is that the mass of the electron and the mass of the neutrinos are all set to 0. This is also a crazy assumption. It is also a crazy assumption, it seems, but we see that with the Higgs mechanism, we have a way of saying that this assumption here was true at the beginning of the universe, like in the first 10 to the minus 12 seconds of the universe, of the early universe, every particle was massless. Then they gain mass through the electroweak symmetry breaking and the Higgs mechanism, which we will explore after all this discussion about the electroweak unification. Third assumption that we make, which is implicit in these two, no other particles. So we will we know that in the standard model all the fermions are up quark, down quark, neutrinos and electrons, okay, plus all the other families. So in this case we have charm and strange, top and bottom, and here we have mu1 neutrino, muon neutrino and tau neutrino in the standard model. So we also have all these other particles here. We are now not considering all these other particles because the Lagrangian of all the standard model with all the particles inserted inside is just an extension of the same Lagrangian that we have only for this one, with more complication in the quark sectors, which we will gladly skip for now, because otherwise it becomes not particle physics in, I don't know, 20 hours it will be now, but it will become particle physics in 100 hours, that I want to avoid. So now all these particles here, all these fermions, we will simply ignore them, knowing that if we learn this electroweak unification mechanism for these two particles, so in a universe in which only these two particles are there, then we have very, very easy times to understand the extension of the Lagrangian, in which we introduce also the other families and the other, so the quarks and also the other families of quarks and leptons. Okay, so just to be clear that in this case we only talk about electron and neutrino, but there are other particles around in the standard model. So how do we write down the Lagrangian? First of all, we start with a free field Lagrangian, so a Dirac Lagrangian for these three fields. So we will have electron left, which participate both in weak and electromagnetic interaction, I gamma mu de mu. Of course, this is electron left bar, electron left. Then we have the same term with electron right, which only participate in the weak interaction. Only participate in electromagnetic interaction, not in the weak interaction. Something this chalk, okay. And then we have neutrino left, which is the only component of the neutrino that participates in the physics of we are considering. Neutrino left. Neutrino left. So this is just a Dirac Lagrangian describing a free left-handed chiral state for the electron, a free right-handed chiral state for the electron, and a free left-handed chiral state for the neutrino. Free means no interaction, no electromagnetic interaction, no weak interaction, no electroweak interaction. Okay. Now, how can we write down this Lagrangian in a more compact way? Well, always using some triplet in this case, because we have three kinds of particles, three kinds of fields. So let me write down this triplet in this way here with this bar to distinguish it from the Spinor field that we were using in the electromagnetic Lagrangian, in the quantum electrodynamics Lagrangian. And I will just write it like neutrino left, electron right. Okay. So using this triplet here, the Dirac Lagrangian can be compactified in a way. L Dirac is equal to triplet bar, then I gamma mu de mu triplet. Okay. This is just if I extend all the components, I get this exact same Lagrangian. Now to the symmetries, because as we did for electromagnetism, as we did for the simplified weak interaction, we used this Lagrangian here. We searched for a global symmetries, and then we made the symmetry local. In this case, the symmetry that we impose is this one, an U1 symmetry let's call every field in this triplet a fermion field. So any one of these, it's just F. F meaning fermion field. Okay. So how the U1 hypercharged symmetry? We know that we want an SU2 left times U1 Y symmetry. How does U1 Y symmetry affect the fermions inside this triplet here? Well, it's very easy. The U1 symmetry, or let's talk before the SU2 left, or not. No, let's do U1, which is easier. U1 symmetry hypercharge. It simply take the fermion, sends it to a F prime. So all of these components, like one by one, F prime, equal to e to the I y, now we see what this y is, over 2 g prime times beta of x times the fermion. So it takes the fermion and it shifts the phase of this fermion by this component here. This y, etc., we will see what is that. This is different from the electromagnetic U1 symmetry. So U1 in electromagnetism, just to make it clear, takes a fermion field, in this case only the electron field, not this guy here, and sends it to F prime equal to e to the I q alpha of x F. Okay, so this is the difference between the electromagnetic U1 symmetry and the hypercharged U1 symmetry. Not only that, I can write down the charge of the particle that I'm considering as a big Q times the charge of the electron, or the absolute value of the charge of the electron. So in this case, the big Q will be how many units of the unit charge the particle that I'm considering carries around. So in this case, I can, instead of Q here in the transformation of the fermion field, I write down big Q times E, and big Q I put it in orange. Okay, because it will be important. F. Of course also, the transformation I forgot. So a phase that depends on space-time, as we discussed before, F. Okay? You see that the same role that is played by this Q here, which is the number of unit of charge carried by the particle we are considering, is now played by this hypercharge here. So the hypercharge is the number of unit of this coupling that the particle we are considering, and the particle will be neutrino left, electron right, carry around with respect to this U1 symmetry. Okay, this is a quantum number associated to the conserved charge and conserved current that we get by Noether theorem when we have when we apply this local symmetry to the Lagrangian. So in this case, the Lagrangian will have this local symmetry. We can shift any field by this amount, and we get, using Noether theorem, a conserved current. The quantum number associated to this conserved current is this hypercharge here. Okay? Now to SU2 left. For SU2 left, no, let me write it up here. These are all global invariances that are local, that are global in this Lagrangian here, and we want to make, I don't know if I said local or global, but let me rephrase. These two symmetries, not this one. This symmetry here is a global symmetry of this Lagrangian here that we want to make it, so it's global only when this does not depend on x. Now we ask how to make it local. So this symmetry starts to depend on the point in space-time in which this transformation starts to depend on the point in space-time in which I'm sitting. Then I have the SU2 left symmetry, which takes not f in this case, but only the first two components of the triplet. So the triplet is equal to nu left, e right, and I can also write it down as left-handed doublet and right-handed particle. So this R is just this R here is just the right-handed component of the electron field, and this L here is what we before called a doublet. Okay, so in this case the SU2 left symmetry only takes this doublet and transforms only elements of this doublet, mix only elements between this inside that doublet. So it takes the doublet L and sends it to L prime equal to, let's put it this way. We have a global symmetry which takes this and shifts it to e to the I, as we already saw, g w t w mu, no, sorry, t alpha times L. Okay, so it makes the doublet in this way here. This is a global symmetry that we have in our Lagrangian, written like this or as a triplet Lagrangian. And now we ask how to make this symmetry local. So the parameter alpha will depend on x. Okay? So we have these transformations here. For making this symmetry local, we will not go through all the way again, but we will just introduce a covariant derivative which we can apply to this Dirac Lagrangian that will make the symmetry local. So the symmetry under these two transformations local, and we'll introduce new fields that keep this symmetry local. Or better, that keep the Lagrangian invariant under these local gauge transformations. So we have this Dirac Lagrangian, which is invariant under global transformation, or under global gauge transformation with respect to this particular transformation here, SU2L times U1I. We want to make it local, so invariant under local gauge transformation. And for making this, we switch the derivative term inside the Lagrangian to a covariant derivative term. How to define this covariant derivative term? Well, this covariant derivative term will depend on the values of the hypercharge and isospin of the various particles inside the Lagrangian. So let's talk for a moment about hypercharge and isospin. We have our triplet here, which is neutrino left, electron left, electron right. Okay, this is our triplet. Then we have an SU2 left symmetry. When we talk about an SU2 left symmetry, we have a quantum number associated to this, which we call isospin, I. Okay, the isospin is something like this. Since we have a doublet, when we talk about SU2L symmetry, which is neutrino left, electron left, I can define a weak isospin, which is exactly analogous to the spin symmetry. So when we have a particle in quantum mechanics that can be, we have a spin part, a spinor, or how do you call it, a fermion that can have spin up and spin down, we say that the total spin of this particle is equal 1/2, and then the z component of the spin of this particle can be in two quantum states, the state plus 1/2 and then the state minus 1/2. exactly analogously to this, for historical reasons, we call this symmetry here isospin, like the quantum number associated to this symmetry here, isospin quantum number. We say that this doublet here, the particles inside this doublet here, carry isospin equal 1/2, and the component of this doublet here carry in turn the third component of isospin, which is exactly the same as saying the z component of the spin in quantum mechanics. Now, just remember the numbers. Even though if you don't remember all this reasoning, etc., we didn't go too much deep into that, so just remember the numbers, but this is the reasoning behind it. So exactly analogously to the case in quantum mechanics where I have a particle which can be in two states, spin up or spin down, in this case I can have a state, a field, let's call it, that can be in two states, the neutrino state or the electron state, left-handed chiral neutrino or left-handed chiral electron. So I group these two states in the doublet. The doublet will have, the two states in the doublet will both have isospin, total isospin equal 1/2, but third component of the isospin for the first component it's equal plus 1/2. For the second component, the third component of isospin will be minus 1/2. Okay, so in this case, isospin of this particle, it's always, let's do this. I have SU2 left, then I have U1 hypercharge, and then I have U1 electromagnetism. Okay, I hope it's clear. The symmetry associated to this guy here, the quantum number associated to this symmetry here, it's the isospin, and we can also talk about the third component of the isospin, and in particular, neutrino left and electron left have 1/2 isospin in the third component, 1/2 total isospin, and for the third component, this guy here it's plus 1/2, and this guy here is minus 1/2. Okay, the electron right does not participate in the weak interaction, so it's not part of a doublet, and it has, so electron right, it has third component of isospin as well as the total isospin equal to 0. Okay, so in this case we'll have third component of isospin equal to 0, both third component and total isospin equal to 0. Okay, so the isospin is the quantum number associated to the SU2 symmetry. Then we have associated to, let's do electromagnetic quantum number first. So we have U1 electromagnetic, and then we have U1 hypercharge. So the quantum number associated with the electromagnetic U1, it's the electric charge, Q. Electric charge is easy because the neutrino left does not couple with quantum electrodynamic interaction, so it does not couple with the photon field. So the number, as you remember, you see that here we see a pattern. The number of unit of electric charge carried by the neutrino, since he does not participate in the electromagnetic interaction, it's 0. Okay, the number of unit electric charge carried by the right component of the electron is -1, because the electron has electric charge -1, and then the number of electric charge unit carried by the right-handed component of the electron, it's always -1, because of course these are just two faces of the same particle when they interact electromagnetically. So these are the quantum numbers associated with this symmetry here, and then one can find out a formula for understanding the quantum number associated to U1 hypercharged symmetry. So in this case, the quantum number associated to U1, it's how many, in this case, it's divided by 2. So the, the hypercharge would be how many half unit of this coupling the particle we are considering carries around. For finding out the answer to this question, there is a whole reasoning that one can do with the weak charged current, the weak neutral current, and the electromagnetic current, combining everything and finding in the end this formula here, that the charge of a particle is equal to the third component isospin of a particle plus 1/2 the isospin, the hypercharge of the particle. So in this case, if I want the neutrino left to have electric charge 0, or carrying 0 unit of electric charge, I must have an hypercharge of -1. Because, of course, if I put 1/2 here for the neutrino, no? This will be 1/2 plus 1/2 times -1 equals 0. So I get the right electric charge for the neutrino, and so I deduce that the hypercharge of the neutrino must be -1. Same goes for the electron. This must be -1 because the third component of isospin it's -1/2. Then I have plus 1/2, and I multiply by -1, and this gives me -1, which is the right electric charge for the electron. And then for getting the right electric charge for the right component of the electron, since it has a third component of isospin 0, I must have hypercharge -2. Okay? Perfect. We talked about these quantum numbers because we need them to define the covariant derivative for making this Lagrangian invariant under local gauge transformation of this type. So if you recall, when we had the Dirac Lagrangian for just one field, one Spinor field, for making it invariant under local U1 transformations, in which we talked about U1 electromagnetic transformation, and for obtaining the quantum electrodynamic Lagrangian, we introduced a covariant derivative, demu, which was equal to demu plus iq a mu. So in this case, for making the covariant derivative, the Dirac Lagrangian invariant under U1 hypercharge gauge transformation, what we do is to add to the covariant derivative, so introduce a covariant derivative which is demu plus I, and in this case Q is substituted, we substitute Q with our hypercharge divided by 2, so the hypercharge of the particle we are considering, and the particle we are considering is always an element inside this triplet here, hypercharge divided by 2 times G prime, which is the coupling constant of this hypercharge interaction. Yeah, let's call it hypercharge interaction, or this QED-like interaction, and then the field associated to this symmetry. So the field that must vary in a certain way, exactly as this guy here varies, for keeping the Lagrangian invariant under local U1 isospin, U1 hypercharge transformations. So to make this Lagrangian invariant under only this part of the transformation, we take the derivative and we swap it with a covariant derivative in which this piece here it's added. So plus I hypercharge divided by 2 G prime b mu. Then we have another symmetry group which is SU2 left, and if you remember, with SU2, for making the Lagrangian with the doublet that we defined in the simplified weak model, we used a covariant derivative which was equal to the mu plus I g plus I g t w mu. Okay, we can rewrite this term for SU2 left of only the doublet. So in this case, here we have a triplet, but SU2 left, it's only the only acts on the doublet, so in the first two components of these triplets, and we can use a smart way of describing this interaction, simply making it dependent by the isospin of the particle we are considering, in such a way that since the electron right has isospin equal to 0, we can just turn off this term when we are talking about the right component of the electron field. So in this case, T are the generator of the SU2 group, and we can call it simply sigma matrices divided by 2. Okay, and this, in this case, this is the transformation that we have to add if it's SU2 left, and this is GW, because only left-handed chiral states are participating in this interaction. And then I can simply use this fact that I have a 1/2 term here. So write this 1/2 term instead of with the sigma matrix. I write it in the front of it, and I just say that this is the isospin of the particle that we are considering. So not the third component of the isospin, but the total isospin of the particle. So that this symmetry here, so this Lagrangian here, has this symmetry. The covariant derivative defined it in this way only when we are talking about the first two components, which have an isospin. Okay, so instead of writing here 1/2, I write isospin of the particle that I am considering. Okay, so that for the right-handed component of the electron field, since there is no SU2 global symmetry, also I don't need to make the symmetry local, and I don't need this piece here in the covariance derivative. But so we have a derivative that shifts to a total covariant derivative in which I add a field associated to the U1 hypercharge interaction, hypercharge symmetry, and then plus I and another symmetry, so I isospin GW associated to these fields here, so associated to the SU2 left global local symmetry. Okay, so in this case I take this Dirac Lagrangian and it becomes a new Lagrangian with the covariant derivative, in which I have the triplet. Let me write it explicitly. Neutrino left. Actually, this becomes a... Okay, no, let's not write it explicitly, because then this becomes a row vector and then it doesn't fit anymore in the blackboard. Just remember that the triplet, it's neutrino left, electron right. And then we will rewrite this term a little bit. So this guy here will be the triplet conjugate. Then we have I gamma mu covariant derivative, in which this covariant derivative that we added contains 4 new gauge fields. Okay, it's exactly these covariant derivatives here. It contains 3 gauge fields associated to the SU2 left symmetry, and 1 gauge field, which is a photon-like field, which is not the photon field, but it's exactly analogous to the photon field, associated to the U1 hypercharge symmetry. Okay, and then times psi. Okay, this is the Lagrangian now invariant under local gauge transformation of this type. Okay, to get the electroweak Lagrangian, so the unified Lagrangian, we also need to add a piece which counts for the kinetic term for the photon-like field. So in this case I will call it minus 1/4. Let's call it G mu nu G mu nu. And a field, not a field, a term, minus 1/4 W mu nu W mu nu, which accounts for the kinetic term of these W fields here, plus some interaction terms of these W fields, so self-interaction term of the W bosons. This term, self-interaction terms emerge, as we saw last time, because the SU2 group, it's a non-abelian gauge symmetry. So the element of this transformation do not commute, and so we have interaction between the bosons associated to this, the vector bosons associated to these fields here. Okay, so this one now it's the total Electroweak Lagrangian before symmetry breaking, so before the Higgs mechanism and everything else. Now we can rewrite it a little bit better, but just to repeat myself another time, but it's very important. As you can see, the covariant derivative here, it's this covariant derivative with 4 new fields, but when I'm considering only the right-handed electron field, the right-handed chiral state of the electron field, I only have this component in the covariant derivative because its isospin is 0. So this term here gets turned off. Okay, I can now divide this Lagrangian described as a triplet with doublets in the fields, just to show a little bit more how it works. Okay, just to express it a little bit more clearly, I can divide this triplet here into a left-handed doublet and a right-handed singlet, so that L is our usual nu E left, and R it's simply our electron right. Okay, and then we have now that the covariant derivative applied to the left-handed doublet, it's equal to d mu plus I, the hypercharge of the doublet, it's always -1, -1. So in this case I will have minus I G first divided by 2 B mu. And then the isospin associated to the doublet, the total isospin associated to the doublet is always 1/2. So I will have plus I divided by 2 GW, and then I will have sigma. What did I do? I forgot here to write down the generator of the group. So in this case it's not just, this is sigma times W mu. Okay, otherwise it doesn't make sense. Okay, perfect. This, it's sigma times the field W mu. The tax on the left-handed component. Okay, if I apply the covariant derivative to the right-handed component, so this will be applying the right-handed the covariant derivative just to this part here, electron right, or right-handed. Okay, we get it, is equal to d mu minus I G first B mu. R. Okay, it's not G first divided by 2 because the hypercharge of the right-handed chiral component of the electron field, it's -2. Okay, so the covariant derivative, the point that I want to make is that the covariant derivative that I write here in such an elegant way, it really depends by which component of the Electroweak Lagrangian I am considering, which field of the Electroweak Lagrangian I am considering, so that this interaction here with the W bosons, it's only turned on when I'm considering the fields which are placed in the doublet, the left-handed doublet. They are not turned on when I'm considering the fields put in the right-handed singlet, which in this case is only one field. Okay. We now have in front of us the Electroweak Lagrangian before symmetry breaking. As you can see here, I defined a little bit better every piece that is inside this Lagrangian. So this piece here will contain kinetic term for this W boson plus an interaction term made of 3 or 4 of this W boson, as we saw last time. This term here contains kinetic term for the B mu, so for the electron, the photon-like field. This term here, the left-handed term, contains interaction of this type, in which we have interactions between fermion and the gauge bosons, so the field that exit for making this symmetry local, which are hidden in this term and in this term. And in particular, this piece here gives us interaction which are of the kind electron left, neutrino left, and other kind of combination of these two particles and antiparticles, coupled with the W plus mu or the W minus mu fields. So this can either be a W plus mu or W minus mu field, and the coupling in this vertex here is proportional to the GW. This is the strength of this coupling here. Another kind of coupling in this term here, it's something of the type electron left, or even neutrino left, neutrino left. Okay, so this particle can be, let's divide it into two pieces. Neutrino left, neutrino left. So in one case we have the exchange of a W mu3 field, which we will see it's not a physical field, it's not associated to some particle that we can measure. With the coupling, again, GW. And then we have another kind of interaction, which can be the coupling between electron left, and another field, which is B mu, okay, which is associated to the U1 symmetry, with coupling G prime. Okay. Same thing goes for the coupling between neutrino left and neutrino left. They can be coupled with a field W mu 3, coupling with constant GW, or they can be coupled through a field which is B mu and coupling constant G prime. Okay. Last thing in this is much simpler because it's just one electron right, anti-spinor representing the left-handed chiral state of the right-handed chiral state of the electron, and the right-handed chiral state of the electron also here. And the coupling, it's always only right-handed electron coupled through this B mu field. Okay? And of course the strength of the coupling is proportional to G prime. So when you go and write down Feynman diagrams for these processes, which of course we will not go through all the Feynman rules for the Electroweak Lagrangian, but it's something that you can just find listed in a book. This coupling here is associated with a strength G prime. Now, the last point I want to mention is this. You see that in this case, for the Electroweak Lagrangian, before symmetry breaking, so without masses of the fermions and without masses of the W boson and the B boson, we have interaction through four kind of particles: W mu plus, W mu minus, B mu, and W mu 3. So this can be W mu 3. So, but the real particles that we measure are Z bosons, which we will say, when we say these fields here are not physical field, what I really mean is that the particle that we can measure are not generated, created and destroyed by this field here, but by combination, by combination of these fields here. And in particular, the particles that I can measure are generated and destroyed by these two, so these two are okay, and by Z mu and A mu. A mu can generate and destroy photon, so massless boson. Z mu can generate and destroy Z bosons, okay? And these two are mixed in a very specific way after electroweak symmetry breaking, and they are mixed using this matrix here and this angle. So we define an angle which we call Weinberg angle, which depends on the ratio of these two couplings, GW and G prime. This is just a definition that now I take out of the blue, but can be seen if we go and match the electromagnetic current and the neutral current in this electroweak interaction, but it's something that we will not gonna do. But in this case, the tangent of this angle here is equal to G prime over GW. And then we will see in electroweak symmetry breaking, so using the Higgs mechanism, all the particles, so the fermions and the gauge bosons, or most of the gauge bosons, not the photon, acquire a mass, and the Z boson, or the field that generates and destroys Z boson, and the field that generates and destroys photons are a combination of W mu 3 and B mu in this particular way. Cosine theta Weinberg minus sine theta Weinberg sine theta Weinberg cosine theta Weinberg, and here we have W mu 3 and B mu. Okay? How to read this? For example, if you want to know what is the combination of these two fields which are associated to the generators of the SU2 group and U1 group, couple and combine to generate this field here, you just read this matrix, you do this matrix multiplication, and it becomes that Z mu is equal to cosine of this angle, this weak mixing angle, times W mu 3 minus sine of this weak mixing angle, B mu. You can find, try the same exercise with A mu, and you find that A mu is this combination here. Cosine theta Weinberg B mu plus sine theta Weinberg W3 mu. Okay? We will see how this combination occurs with the Higgs mechanism. Nice curiosity, today I'm recording this lecture the 4th of July, and is the anniversary of the discovery, of the announcement of the discovery of the Higgs boson. So it's the perfect day to launch a lecture about the Higgs mechanism and how can we give mass to these particles. Because now in the Electroweak Lagrangian, all the particles that are described by this Lagrangian work very well to describe our interactions, so they can reproduce in a way the interaction that we see in nature, but this remains gauge invariant only if all the particles are massless. But we observe that this particle here, these particles here, associated to this field, this particle here at least, and this particle here, which I don't have anymore, but inside this, they are all massive. So how do we give mass to these particles without breaking the gauge invariance of this Lagrangian? This is precisely what the electroweak symmetry breaking will do and the Higgs mechanism will do. So this is the hook for the next lecture, and this hook is made on the 4th of July, which is the anniversary of the Higgs boson discovery. Several days have passed from the 4th of July, and finally we are here talking about the Higgs mechanism. What we saw in the last lecture was that we have a Lagrangian in which I have some doublet inside the Lagrangian or triplet, and we apply to this Lagrangian a symmetry group, which is SU2 left times U1 hypercharge. Applying a symmetry group means that we require that this Lagrangian becomes invariant under local gauge transformations of this symmetry group. And using this, so applying this one here local, so requiring that the Lagrangian is invariant under local transformation of this type, we get W plus, W minus, W3 and B mu as gauge fields. So we have these gauge fields. But these gauge fields are massless. Because introducing a mass term for these gauge fields inside the Lagrangian breaks the gauge invariance. So we want, at the same time that the gauge invariance is present, and we want mass for the gauge fields. So these fields here, in particular, we will see that they have mass. Not all of them, like the mix of these two that we saw that it was Z boson plus photon, has mass only in one case, which is the Z boson, and not in the case of the photon. But we also want that, like we experimentally, these are massive. So we need a mechanism which allow us to give mass to the gauge boson without breaking the gauge symmetry. Okay, and this mechanism is the Higgs mechanism. So for explaining the Higgs mechanism, which is pretty complicated for the standard model, so in the Lagrangian of the standard model, the Higgs mechanism is pretty complicated. So what we will do is to explain it in a simplest case, in a simpler case, and then generalize it to the standard model Higgs. So the thing we will see now, it's not the standard model Higgs, but it's something simpler than the standard model Higgs. But the mathematics and the principle that is behind is exactly the same. So we will then, my suggestion is, as always, as everything we did in this course, to understand very well the simpler case, understand very well the mathematics and the logic that is behind, and then the generalization will become very naturally, okay? Will be very natural for you. So, what do we need for understanding the Higgs mechanism? We need two principles. The first one, which we already saw, is local gauge transformation. So I will not repeat again all the discussion about local gauge transformations, but remember that this one will be crucial in the Higgs mechanism. And then the second phenomena or second principle or whatever you want to call is the spontaneous symmetry breaking. Okay, so with these two, with the knowledge of how these two mechanisms work, we will build the Higgs mechanism. In particular, we will build the Higgs mechanism in a simple case, so for phi, which is a complex scalar. So we will build this mechanism for this field here. And then for the standard model, we don't have a single complex scalar field, but the standard model Higgs is something like this. Standard model. It's a doublet, because of course the standard model Higgs must be associated to this symmetry group, so cannot be a single complex scalar field, as we will see in the simplest case, but is a doublet in which we have a field here, phi plus, and another field here, phi 0, and both of these fields here, both of these fields are complex scalar fields. Okay, so this is the second step. We will start by seeing the mechanism of spontaneous symmetry breaking and how it works. Then we will see the Higgs mechanism in a simplest case, so the complex scalar for a complex scalar field. And then once you understand very well this part here, we will jump to the standard model Higgs and see how the Higgs mechanism works in the standard model, so with real physics. Okay, very exciting stuff ahead. Let's start. For introducing the mechanism of spontaneous symmetry breaking, we will go back to a Lagrangian that we didn't see in a while. Because if you remember, everything we did in particle physics, in which we were talking about real particle, was also with only with vector fields and Spinor fields. We never talked about scalar fields. That is precisely the reason of this is that the only scalar field, the only particle associated to a scalar field in the standard model is the Higgs boson. So now is the time to introduce again a Lagrangian that we didn't see in a while, which is the Klein-Gordon Lagrangian. If you remember, the Klein-Gordon equation was something like this. Klein-Gordon demu plus m squared phi equal to 0. So it's an equation of motion for a free scalar field, and it has an associated Lagrangian, which we derived knowing that the Euler-Lagrange equation gives back the Klein-Gordon equation, which is the following. The Lagrangian is demu phi dagger demu phi minus m squared phi dagger phi. Yes, this is the Klein-Gordon Lagrangian, and this Lagrangian describes a free field, a free scalar field, and now we add a term to this Klein-Gordon Lagrangian, which is an interaction term, which is, we can say something like minus lambda times phi dagger phi to the second. So in this case we have a kinetic term. This one is kinetic. This one is a mass term, because remember that the mass term in every Lagrangian is always associated to the part quadratic in the fields. So this is a parameter that describes the mass of this complex scalar field. So this term here is mass. And then this term here is interaction term. This is not anymore the Klein-Gordon Lagrangian, because the Klein-Gordon Lagrangian is the part without the interaction. In this case, we add an interaction with no other particles. So in this case, the complex scalar field interact with himself. So it's something like this. The interaction are phi phi to phi phi, and the vertex looks something like this. Is a 4-point vertex, so 4-particle vertex. Okay. I introduced this Lagrangian and I put it here just because this is one of the simplest Lagrangian that you can imagine, and it's usually used in quantum field theory. In an introductory course in quantum field theory, usually this is the first Lagrangian you see. Oh, there is a simpler one, which is the case in which the field is not complex but is real. So a real scalar field, but anyway, this is one of the simpler Lagrangian that you can say. You can derive Feynman rules for this Lagrangian, and you can compute amplitudes associated to process in this Lagrangian here. So it's really useful to study the framework of quantum field theories. We just skipped this Lagrangian because we were talking about real particles, and real particles usually, before the Higgs boson, are always or either spinor or vector fields. But okay, now we need to modify a little bit this Lagrangian here, and in particular to modify this Lagrangian here, we use, instead of this mass squared, we use a parameter which we call mu squared, which is not anymore a mass, because what we want to do, even though it looks like it has no sense, no logical sense what we are doing, I introduce here a parameter that I call mu squared, which is not a mass, and I say what happens, I ask to myself, what happens if mu squared is negative? Okay, so if this parameter is such that mu squared is negative, what happens to my Lagrangian? Well, to my Lagrangian, the following happens. First of all, I subdivide the terms a little bit, and in particular, I keep this as a kinetic term, and then I call this term here, let's collect this minus sign, this becomes a plus sign, and this term here, I call it a potential, V of phi. Okay, so it's just a Lagrangian, which is a kinetic part minus a potential part. And the thing that happens if this parameter here is less than 0, by the way, lambda must be always less than 0, otherwise the potential has no minimum, but so lambda is always less than 0. The thing that happens is that the potential, so this part here of the Lagrangian, acquires this form here, in which, now I will also describe a little bit what all these fields are explicitly. But the potential, V of phi, which is in this z-axis in this case, acquires a form like this. Okay, probably you recognize it as the Higgs potential. What is in the axis of this plot here? First of all, we need to define very well what is this field here. So phi, it's a field which we define as, since it's complex, any complex number can be defined as a superposition. It's not a superposition, but let's call it superposition between two real numbers. So I have phi 1 plus I phi 2. So a complex number has 2 degrees of freedom, which are associated to two real numbers. So it can be identified as phi 1 plus I phi 2. And in this case, if I go to plot the potential as a function of phi 1 and phi 2, so in this case the x-axis and y-axis are the 2 degrees of freedom of the complex number, well, the potential has this shape here. So the minimum of the potential, it's not in zero anymore, as in the case if this was the mass and this parameter here, mu squared, was positive, the minimum of the potential would be in zero, because the potential would have this shape here, okay, like a parabola potential. But in this case, no. In this case, the potential has this shape here, which is called, someone calls it the Mexican head potential, someone calls it the bottom of the bottle wine. How do you say it in English? I have no idea. Someone calls simply the Higgs potential, but okay, this is the shape of the potential. And now you can see that the minimum of the potential is here, here, and in all the circle that is defined by something that we will now define better. So the potential, of course, has a rotational symmetry, and it's something like this, of course. Okay, so this circle here defines the minimum of the potential as a function of phi 1 and phi 2. Now, let's change a little bit the perspective and see it from above. And if I look at it from above, I see that I have something like this. I always have my 2 degrees of freedom, which are phi 1 and phi 2. I have the potential that is coming outside from the blackboard, and the minimum of the potential is in a circle like this. How do I define this circle? Why the minimum of the potential is in this circle here? Well, let's look at it. The reason is really, really simple, and it's just a little computation that we can do in calculus, as we did in calculus 1. And let me just rewrite a little bit the Lagrangian, or not. No, let the Lagrangian like this, it's okay. But just know that this is the potential, V of phi, this one that is underlined. So if I do, if I want to find the minimum of the potential with respect to a variable which is not phi, but is phi dagger phi, and in particular phi dagger phi will be also equal to 1/2 phi 1 squared plus phi 2 squared, try by yourself, we have that the derivative for finding the minimum, or better, finding the points that extremize the potential, so the minimum and the maximum, I have that dv that depends on phi over, so derived with respect to phi dagger phi, is equal to 0. This condition, like if I find phi dagger phi which respect this condition, I found phi dagger phi that are the minimum of the potential. So let's do it, and it's super easy, because I just simply have mu squared plus lambda phi dagger phi plus 2 times lambda phi dagger phi is equal to 0. And of course, I want to find phi dagger phi such that the potential is at a minimum, and then I find that phi dagger phi it's equal to minus mu squared over 2 lambda. Okay, and phi dagger phi it's also phi 1 squared plus phi 2 squared over 2. So we have that phi 1 squared plus phi 2 squared is equal to something. Okay, this is the minimum of the potential, and phi1 squared plus phi2 squared is the equation of a circle. When I have x squared plus y squared, I have a circle. Sorry, very confusionally, but this you will recognize as the equation of a circle. If I plot here the equation, phi1 squared plus phi2 squared is equal v squared, where v squared is equal minus mu squared over lambda. This is simply the equation of a circle with radius v. Okay, so the minimum of the potential is in a circle with radius v. Okay. Why this is important? Well, this is important because I know that if the minimum of the potential is not in 0, in phi equals 0, but is in phi that meets this condition, at some point when the field is in the ground state, so when the system is in the ground state, the Lagrangian will be written in terms of the vacuum state. The vacuum state is simply the field not centered in 0, but centered in one of these infinite points inside these circles. Let's rewrite a little bit the things and see how this is important. So, little recap, we have this Lagrangian with this potential here. The potential has mu squared as a parameter, which is negative, and if the potential has a parameter mu squared, which is negative, the minima of the potential, I don't have a single minimum in the potential, but I have infinite minima, which are all the points that respect this condition. Phi, all the points in which phi, so the fields, the complex scalar fields that I have in my Lagrangian respect this condition. Phi1 squared plus phi2 squared is equal v squared. Okay, every one of these points is in a minimum of the potential. So the minimum energy state of this system, it's in every single point of phi, so in every single value of phi that respect this condition. This means that there is, now we are coming to the spontaneous symmetry breaking, because we can choose one of these infinite points in which the state phi is as a, like, you can always almost say that is like any system in physics tend to go toward the minimum energy, and in this case phi tend to stay in a value which minimizes the energy, so it minimizes the potential, but the states that minimize the potential are infinite, and it can only be in one of these infinite states. So we just choose one of the infinite states in this circle, and in particular we choose one vacuum state. What the thing is called the vacuum state. So the vacuum state, it's any point that respects this condition here, but we choose one. We choose, so it's a choice. Choice, yes. We choose the vacuum state such that phi is equal to is here in this particular point here. So this is phi 1, this is phi 2. So we choose a vacuum state in which phi 1 is equal to v and phi 2 is equal to 0. So that phi 1 squared plus phi 2 squared is equal to v squared. So in this case, phi will be equal to 1 over square root of 2. Phi 1 will be equal to v. V is just a number. Plus phi 2 will be equal to 0. So plus I times 0, just to be explicit on what we are doing. Okay. This is a vacuum state that we choose, and is one of the infinite possible vacuum states in which my system can be. Okay? Once we choose this vacuum state, the Lagrangian is not symmetric anymore. Okay? This what does it mean, spontaneous symmetry breaking? But it simply means that this Lagrangian here has a symmetry, which is a U1 global symmetry. So, U1 global symmetry, it simply takes the field phi and sends it to phi prime equal e to the I, let's say, ig chi phi. Okay, if I do this transformation, the Lagrangian remains invariant. But yes, but not in the vacuum state. Once I choose the vacuum state, so in this case the vacuum state will be equal to V over square root of 2. This is one of the infinitely many possible choices. Once I choose the vacuum state, the Lagrangian is not symmetric anymore under this kind of transformation here. But this is very, very confusionary because this is not the last step. So the last step is not choosing a vacuum state. The last step is choosing a vacuum state and expanding about the vacuum. Okay, so now the Lagrangian will not be anymore this, written in terms of this field phi, but will be the Lagrangian of a field expanded around this vacuum state, this minimum energy state. So it's almost like, or it's like the field, I choose a vacuum state and then I expand. So the first thing to do is choose a vacuum state. I choose one that is convenient, and in particular I choose this one. In this case, the symmetry is broken. Okay, but then I restore the symmetry with the second step, which is expansion around the vacuum. Once I expand this, the symmetry restored. Now we will see what does it mean, this part here. The symmetry is restored when I expand around the vacuum, but is not explicit, so not visible. Okay, so the symmetry is actually never broken. The symmetry is always there, but it's just broken in a moment in which I choose the vacuum state, but this vacuum state is not the final field in terms of which I write my Lagrangian, because the final fields in the term of which I describe my Lagrangian are the expansions around the vacuum state. Let's see what that means. First of all, what does it mean to expand around the vacuum state? Well, simply is that the field is not centered in zero anymore. If I had this parameter positive, the minimum of the energy will be here, and then I will have the field. I would have the fields that are excitations around this minimum energy state in which phi is equal to 0. In this particular case, I have the field phi of x, which is a vacuum state. So the ground state of the field is in this particular point, which is v over square root of 2 over square root of 2, and then I have an expansion around the vacuum. In particular, I have two modes in which this field can be expanded. One mode along the real direction, and I call this expansion, this excitation around the real direction, eta of x, so a new field eta of x plus eta of x, and then I have a direction of expansion along the imaginary component. So I can also expand the field in this direction here, and this direction I call psi of x. So the field will be plus, let me factorize the square root of 2. So the field was 1 over square root of 2 V, which is the vacuum state, and is just a constant, plus eta of x. As you can see, this is not a constant anymore. This is a proper field, plus I psi of x. So I have a component, an expansion around the direction, the real direction, and an expansion around the imaginary direction. Okay, so this is the field after expanding around the vacuum state, in which the vacuum state is this one. Okay, so the field will become, just to rewrite it, something phi, and of course this I do it point by point in space-time. So phi of x becomes 1 over square root of 2 times V. Let me put the vacuum state in orange so that we know that this is the vacuum state and it's not a field, this is just a value, plus a field which is eta of x, which is an excitation in the real direction, plus I psi of x, which is an excitation around the imaginary direction. Okay? So we started by a field phi. We saw that the vacuum state of this field phi is not in 0, but is in this point here. And then we expanded the field around the vacuum state. Okay? Now, what we do now is to write down the Lagrangian, rewrite the Lagrangian with the exact same form, exact same potential, but not as a function of phi, but as a function of phi expanded around the vacuum state. And we will see what happens. Yeah, now the conceptual part is really done, because we saw that, so just to recap very fast. One, we saw that the minimum of the potential is in phi 1 squared plus phi 2 squared equal v squared. Two, we choose a vacuum. Choose a vacuum state which was phi 1 equal to v, phi 2 equal to 0, and then 3, we expand around the vacuum, which is this part here. So we find exactly this expression here for our original field. Okay, so 3 expand. Okay, these are the conceptual step. Now there is nothing conceptual anymore, because we just take this field here and we replace inside the Lagrangian, instead of this field here, we put the expression for this field here. So let's compute a little bit of things that are useful for our replacement. First of all, I want to compute what is phi dagger phi, because you see that inside the Lagrangian, and in particular inside the potential, the combination phi dagger phi is the important part. So phi dagger phi, using this expression here, it's simply equal to 1 over 2 v plus eta. I also put here v in orange and eta in green to understand that v is just a number, it's just the vacuum state, and eta, it's a new field, which is the expansion around the vacuum state. So in this case I will have v plus eta, and this is squared, and then I will have plus psi squared. In this case, it's just an imaginary number, so it's a real component squared plus imaginary component squared. And this is the imaginary number, complex squared. Okay. Now, using this relation here, it's very easy to see, to swap inside the Lagrangian. And without going through all the computation, I just write here what is the result. But it's really easy to see. Like you put you also have to square this one to compute this term here. Having phi dagger phi, you have already this term here, and then you just make the derivative, remembering that the derivative of v is 0 because v is just a constant. So what you find after exchanging phi with this expression here inside the Lagrangian is the following. So after a while, after computing everything, but it's just mathematics, it's not conceptually difficult. You just take this part here, you place it inside the Lagrangian, and you remember that mu squared is equal minus lambda times v squared. You obtain this expression for the Lagrangian. And as you can see, the field phi of x is not in the Lagrangian anymore, of course, because we write it, or better, it's implicitly in the Lagrangian, but not explicitly anymore, because we write it as an expansion, as a function of v, eta, and psi, which are two new fields plus a vacuum state. And as you can see, we have a kinetic term for eta, a kinetic term for psi. So this Lagrangian describes a particle associated to eta, a particle associated to psi. Then we have interaction terms. All this part here accounts for interactions. For example, if you see eta to the third, you will have an interaction made like this, in which I have a vertex with three particles associated to this eta field. If I see eta to the fourth, I will have an interaction like this, in which I have a vertex with 4 particles associated to the eta field, and the same for psi. Or, for example, in this case, eta psi to the second, I will have, for example, psi eta. Okay, so all this piece here accounts for interactions between these two new fields that we introduced, and the part that we are most interested in, it's not the interactive part, so this part here, the interacting part, we just ignore that for now, but is this one here. This one here, as you can see, it is quadratic in the eta field, and so it's a mass term for the eta field. And in particular, the Lagrangian, this will be associated to minus 1/2 mass of eta squared times eta squared. So the mass of the particles associated to this field eta will be eta equal to, if this is minus 1/2, etc., etc., this should be m squared. Wait, let me just do the equation very fast. 1/2 m eta squared is equal lambda v squared, so that m eta is equal square root of 2 lambda v. Yes, so m eta is square root of 2 lambda v. Yes. So this part here is very important, because we have now a Lagrangian which describes two new particles, eta and psi, in which one of the two has acquired a mass. Has acquired a mass due to the spontaneous symmetry breaking of this Lagrangian. And the other particle has not acquired a mass, so this has m psi equal to 0, because there is no part in the Lagrangian which is associated to psi squared. Okay, there is this part here, but as you can see, there is another field here. So this is actually an interaction between eta and psi, and is not a mass term for psi. And so this boson here, it's a massless boson, and it's called a Goldstone boson. what the spontaneous symmetry breaking did, it simply introduced two new fields and hide this original field, and of these two new fields, one of the two acquired a mass term. A mass term which is the following, which depends by the vacuum state of the field, of the original field, okay? And the other does not acquire a mass, is just a massless field inside our theory, and is called the Goldstone boson. Now let's see from the spontaneous symmetry breaking how to go to the Higgs mechanism, because now, after understanding the spontaneous symmetry breaking, we will introduce and we will use the concept that we already know of the local gauge symmetry for talking about the Higgs mechanism. The Higgs mechanism, it's when we have a spontaneous symmetry breaking, but we have a step before the spontaneous symmetry breaking. As you noticed before, with the spontaneous symmetry breaking, we pass from a field which is phi, which is in our Lagrangian, to two new fields which are eta of x, which is massive, so this one has a mass, and mass different from 0, and psi, which is called the Goldstone boson, which has mass equal to 0. Okay, but we do not have our gauge fields inside the Lagrangian, and our gauge fields are precisely the reason why we were doing all this trouble of the spontaneous symmetry breaking. We want to give mass not to these new fields which we don't care about, but to the gauge fields, which comes from making this symmetry here, which is global in the Lagrangian, local. So the step before, the Higgs mechanism comes when we have spontaneous symmetry breaking in a theory which is locally gauge invariance. So we have local gauge invariance, and once we have local gauge invariance in a theory, which means introducing gauge fields for making this global symmetry local, we spontaneously break the symmetry of this theory. And in this case, we will have the Higgs mechanism that gives mass to the gauge boson that comes from the local gauge invariance. So let's see how it works. We simply take the step that we did before, but we add a step before doing this. So how do I make this theory invariant under local gauge transformation? This is very simple because we saw it already. And also a little remark, in this case we are talking about a U1 global invariance, but this is not the standard model Higgs. This is just a simplified toy model that allows us to understand the Higgs mechanism. For the standard model Higgs, we have something which is a little bit more complex, but we will talk about this later. So, how do I make this symmetry local? Well, we saw it in every possible way. We simply say this is no longer global, it is local, which means that the phase here depends on every point by point in space-time. For making this local, I simply apply the prescription, which is take the derivative and swap it with a covariant derivative, which is equal to the derivative plus I g b mu. So I add a new field b mu. This is a photon-like field, is associated to this U1 symmetry. And in this case, when I do this transformation here, this becomes local. so a local U1 invariance, and this field here must transform in a precise way. I write it here even though now it's not necessary for the discussion. This must transform in this way. B prime mu is equal to B mu minus the mu chi of x. Okay, this now is not relevant for our discussion, but just remember that when we introduce the covariant derivative, this gauge field here must transform in a precise way. Okay, so now for making the Lagrangian invariant under local gauge transformations, I simply change this d mu with the covariant derivative in both sizes, in both cases. So I have d mu phi dagger. In this case, everything is complex conjugate, and d mu phi. And that's it. We made this Lagrangian invariant under local gauge transformations, introducing a gauge field. So this guy here, it's a gauge field. Okay. Now, let's go to the spontaneous symmetry breaking. This we already discussed, so I have this Lagrangian. We discussed that we have a minimum of the potential for every time that phi dagger phi is equal to v squared. We choose one minimum, so for the spontaneous symmetry breaking, first we choose a vacuum state, which is the same vacuum state as before. So I choose phi to be equal to v over square root of 2. In this case, I change again the color of v, so that I distinguish it from the gauge field, the scalar field, and v is the vacuum state, so it's just a constant. So this is how the symmetry breaking is realized. So this is the vacuum state, and then I expand around the vacuum. Expanding around the vacuum means that phi of x, the scalar field, becomes equal to, I rewrite this because now there is an important catch, 1 over square root of 2 multiplied by v, which is the vacuum state, plus eta of x plus I psi of x. Now, I could simply start by replacing this phi here inside the Lagrangian. Since I have now the covariant derivative, I also have interaction between the scalar field and the gauge boson field. But I want to do a simplification more, which is going to the unitary gauge, and in particular, as we like, how to say it. This degree of freedom here, it's a little bit problematic. This degree of freedom associated to this excitation, and I want to get rid of it. How do I get rid of it? Well, it's very easy, because now I have a local gauge transformation, and my Lagrangian is invariant under local gauge transformation. So I can choose to sit inside a gauge in which I have phi prime, which I will then call phi, just not to confuse it, phi prime of x. So in this case, I apply a gauge transformation, and I go to a new gauge in which phi prime is equal to 1 over square root of 2 v plus a real part, which now I call h of x, plus 0. So I apply a gauge transformation in which the imaginary part of this field here is 0. I can do this because the Lagrangian is invariant under local gauge transformations. And this gauge here is called unitary gauge. It's super important to go in the unitary gauge, because if we don't go in the unitary gauge, this degree of freedom, it's a little bit problematic. But when we go in the unitary gauge, this degree of freedom associated to the Goldstone boson goes away and becomes a degree of freedom inside the gauge field. And it's precisely the thing that gives the mass to the gauge field. We don't see it in detail. We just swap and go to the unitary gauge right away without seeing what happens if I stay in this gauge here. But this is what someone tell about when they, okay, everyone always talks about, oh, the Goldstone boson got eaten in the Higgs mechanism and gives mass to the gauge field. That is the way, let's say, the popularization way of saying that I go in the unitary gauge, and this degree of freedom associated to the Goldstone boson now becomes a degree of freedom associated, a new degree of freedom associated to the gauge field, which gives mass to the gauge fields. Because the gauge field, when they are massless, they only have two polarization states. When they are massive, they have three polarization states. So the polarization state, the new polarization state of the massive gauge field is the same degree of freedom that comes from the Goldstone boson. Okay, just to say. But now we will use then, we will use right away the unitary gauge without worrying anymore about the Goldstone boson. Okay, so what we do now, which is different from before, is to swapping this field here, phi, with this expression here. Also in this case, all the conceptual part is already done, and let's do the math. So for the first part, we just compute what is the mu phi. Let's see. Mu phi, first of all, I write down the mu. The mu is the mu plus I g b mu. And then phi, I choose the vacuum state and then I expand around the vacuum, so I obtain this thing here. So this is 1 over square root of 2 multiplied by v plus h of x. By the way, h of x will be the field of which excitations are the Higgs bosons. Another thing I wanted to say, oh yes, in this case I believe that it's not necessary to expand this potential here, but we will find the mass of the BMU field, so the term quadratic in the BMU field, only looking at this part of the Lagrangian. So in this case I will not look at this part of the Lagrangian. This is necessary because otherwise, if we don't have this potential here, we don't have asymmetry breaking, we don't have a minimum of the potential which is non-zero. But in this case here, I will just care about this part of the Lagrangian, and we will leave out all the interaction between these fields here. So let's see what happens. So the mu phi is also equal to the mu h, or better, yeah. No, let's write down directly also what is the mu phi dagger. The mu phi dagger is exactly the same thing, but I write it down so then we can do the multiplication, but with a minus I instead of a plus I. So minus Ig b mu, and then we have again 1 over square root of 2 v plus h. Very good. Now we do this part here. So I multiply this part times this part. Of course, this guy here has a higher index, so this index will be up. But I simply have, so I obtain that the Lagrangian, it's, or at least the first part of the Lagrangian, it's yes. Okay, I stopped here because the only part I'm interested in is this specific term here. So I started doing the computation of this. Now I come to this part here, which is the part that is associated to the mass of the gauge field. Of course, here I also added a part in the Lagrangian, which is this part here, which is the kinetic term associated to the gauge field, which in turn is associated to the local U1 invariance. This is just for completeness. So this is the full Lagrangian. Now we are doing, we are inserting inside the full Lagrangian this term here, the field phi, the scalar field, as a function of V, which is the vacuum state, plus H, which is an excitation around the vacuum state, and we obtain something like this, in which we have this term here. If there is only one thing that you have to remember about this Lagrangian, that then we will write down in full, it's this term here. Because of this term here, it's also equal to 1/2 the mass of the B squared times B mu. And so that you can figure that the mass of the field B, of the particle associated to the field B, it's G times V. So it depends by the vacuum state of this field associated to this scalar field here, and the coupling constant between the field phi and the gauge field B. Okay, now without doing all the calculation, let's write down explicitly this Lagrangian to see what are the interactions that comes out of this Lagrangian and what are the particles involved, who has mass, who doesn't have mass. This is the full expanded Lagrangian in terms of this field here in the unitary gauge and adding the kinetic part of associated to the gauge field. And as you can see now, we have a kinetic part for the Higgs boson. Then we have a kinetic part for the gauge field. Then we have a mass part for the Higgs boson, which is this one, so that the mass of the Higgs boson will be equal to square root of 2 lambda times V. So it depends by the vacuum state, and this mass of the Higgs boson comes from the Higgs potential. Then we have, very, very important, a mass associated to the gauge field, and the mass associated to the gauge field MB, as we saw before, it's equal to G times V. So it's the coupling constant between gauge field and this scalar field and the vacuum state of the scalar field. And then we have interaction terms. All of this part here, it's interaction between the Higgs boson and the gauge field, and this part here, it's interaction between gauge boson and himself. These two parts come partially from here and partially from here. In this case here, you see that we have B mu H, so we will have a vertex which is a Higgs boson interacting with two gauge fields. So these are particles associated to B mu. Here we have B mu H squared, so we have two Higgs bosons associated to two gauge fields. And then we have interaction between 3 Higgs boson and 4 Higgs bosons. So this theory has these kind of interactions. And these are all the vertices that we can build with Feynman rules. Like we can derive Feynman rules for every one of these vertex for this specific theory, which is a simplified, a Higgs mechanism, but which is not the standard model Higgs mechanism. So we found a solution to our problems, because in this case we just introduce a Lagrangian which describes a scalar field, then we make this Lagrangian invariant under local gauge transformation, and we saw that after symmetry breaking, the field associated to the local gauge transformation acquire a mass. So now we will use exactly this mechanism, exactly this procedure, but with fields, and we will add this piece to our Lagrangian, for making such that the fields that we know experimentally they have mass, for making them acquire a mass through the Higgs mechanism. Time to see the standard model Higgs. We saw the Higgs mechanism, so we saw that how the Higgs mechanism can give mass to a gauge boson in the case of the U1 local symmetry, but is not what we want in the standard model. In the standard model, and last time, before seeing the Higgs mechanism, we came up to this with this Lagrangian here. And this Lagrangian here is the Electroweak Lagrangian before introducing the Higgs mechanism and before symmetry breaking. So it's the Electroweak Lagrangian that contains one electron and one neutrino before, in the first instant in the universe. And without recommenting all the Lagrangian, just very fast, here we have the kinetic term of the W boson plus some interaction between the W and himself. Here we have the kinetic term of this B mu boson, which is associated to the U1 hypercharged symmetry and is a photon-like field. And then we have the fermionic part of the Lagrangian. We have left part and right part, or better, left-handed chiral states, which is this doublet here, composed by left-handed chiral state of the neutrino and left-handed chiral state of the electron. And then we have right-handed chiral state, which is a singlet. It's composed only of one field, which is the right-handed electron. And here, of course, this is R bar. Okay. What is missing in this Lagrangian? Of course, another thing which is important is the covariant derivative. Introducing the covariant derivative in these parts here, we made the symmetry SU2 times U1 hypercharge local. And the covariant derivative depends on the particular particle that we are considering. For example, in this case, the covariant derivative doesn't have this piece because, of course, also here, in the covariant derivative, this is not G prime, but this is GW. Okay, because these two are two different coupling constants, but okay. In the covariant derivative, in this case here, this piece doesn't exist because the electron right, or the right-handed component of the electron field has isospin equal to 0, while this guy here, the left-handed component, left-handed doublet, has isospin equal to 1/2, so this piece exists. So both these pieces depend on the isospin and the hypercharge. And this will be important because also the Higgs boson will have an isospin and an hypercharge, and so the covariant derivative associated to the Higgs boson will depend, or the coupling between, or better, not the coupling, like the pieces that we have to add, or the magnitude of the pieces that we have to add to the covariant derivative for the Higgs boson, when we will see it in few minutes, will depend by the isospin and hypercharge of the Higgs boson. Very good. Now, what is missing in this L0 Lagrangian? Well, we said it multiple times, but let me write it down once for all. What we have missing is Fermion Masses, in this case, the only fermion that we introduced in this Lagrangian is the electron. So a mass for E. Or better, there is also the neutrino fermion, but the neutrino fermion in the standard model doesn't have a mass, and this term, it's something like, if you remember from the Dirac Lagrangian, the fermion masses were something like this. Psi, psi, m, psi. Okay, so in our case, in which we only have the electron, the term that we have to add in some way, which describe the electron, the electron mass, should be done in a way like this: E, m, where m, E is the mass of the electron, E, and if you divide the electron in the way we divided it for constructing this Lagrangian, so we have a right and a left-handed component, E r plus E left. You can do the computation with the projector operator that we discussed a few times ago, and you will find out that this mass here, this mass term here, must be equal to also this. Here there is a minus, if you remember from the Dirac Lagrangian. This mass term here must be equal to minus something, yeah, minus mass of the electron times, we have a coupling between electron, like anti-electron right, which is not anti-electron, this will be anti-Spinor field right-handed component, and EL plus EL bar ER. Okay, so if you try to make this calculation, you can try by yourself, substituting ER plus EL inside E, and then using the projector operator, you will see that the only terms that survive in this mass term are the one which couple electron right, electron left, electron left, electron right, in this way here, okay? And this holds for every fermion which have mass. So we will try to find a term, try to activate a term like this using the Higgs mechanism and the Higgs boson after symmetry breaking. And then the second part that it's missing in this Lagrangian, part number 2, is the thing that concerns us the most, because we cannot introduce this mass by hand, and is the mass of the gauge bosons. So, gauge boson mass. And in particular, in our Lagrangian, we have 4 types of gauge bosons, which are W1, W2, W3, and B, okay? But the one for which we want a mass are these kind of superpositions, W plus and W minus, which are equal 1 over square root of 2 W1 mu plus minus. But also, no, this kind of superposition, I don't write it down because also the particles who have mass are W plus and W minus, but the superposition of W, let me write it down in this way, W I, and also here it's minus plus. Okay, without getting too much distracted. Okay, and this is W mu. So this is not the particle that have mass, but is the field, or are the 2 fields that generate and annihilate the massive particles in the standard model. And the massive particle in the standard model are the W plus and the W minus. Okay, so yes, this is the superposition that we are searching for, but the particles associated to these superpositions are simply called W plus and W minus without any index. So particles that have mass and that we want to give them mass with the standard model Higgs are W plus, W minus, and Z, while the photon have no mass. So only 3 out of 4 of this degree of freedom must acquire a mass. Okay, and in particular, this mass here will be given by a mechanism which is exactly analogous to the Higgs mechanism that we already saw in the previous case, and this mass here will be given by a term which is called the Yukawa term in the Lagrangian for historical reasons, and we will introduce it by hand, but we will also involve the Higgs boson. Okay, so let's see how to give mass. First of all, let's see how to give the fermion masses. So fermion masses, we just add a term, which is this, L Yukawa equal to minus GE. GE is a coupling between the Higgs boson and the electron, and then we have big parenthesis L bar phi, where phi it's the Higgs boson, or better, it's the field which after symmetry breaking contains the Higgs boson, and then we have R plus same thing, R bar phi dagger R L, sorry. Then of course we cannot just introduce this part. Now we will see how this Higgs boson, or it's not even the Higgs boson, this is the field that after symmetry breaking contains Higgs boson, but now we will see how this looks like. But we cannot just introduce this part alone, because this part must work together with the symmetry breaking that is exactly analogous on how we saw the symmetry breaking before. So the other term that we have to introduce to the Lagrangian, which accounts for gauge boson masses, is the following, which is something like the Lagrangian that we saw before. Let me call it Higgs Lagrangian, but it's just the name. The mu phi dagger, the mu phi minus V of phi. Okay, and then this part here of the Lagrangian, the symmetry, which is SU2 times U1, SU2 left times U1 hypercharge, must become a local symmetry. So we swap this, the mu and the mu, with covariant derivatives. So this part becomes the mu phi dagger. Then we have the mu phi, and then minus V of phi. Okay, so this term here in the Lagrangian will give, added to this Lagrangian, will give fermion masses. This term here with the covariant derivative and the Higgs potential added to the Lagrangian will give us the gauge boson masses. Now we will see how it works, because, okay, now we just add pieces to the Lagrangian, but how this mechanism works? Actually, once I tell you what this vector field, sorry, this scalar field looks like, my words are not working anymore. Once I tell you how this scalar field looks like, you could be already able to see how this Higgs mechanism works, both for Yukawa term and for this term here in the Lagrangian, but let's see it explicitly. So first of all, what we do for introducing these two masses to the Lagrangian is to take Lagrangian L0 and to add these two pieces. Let me write it here, and let me keep this part here because we need it. So let's see what I write it down, and then we comment. Okay. So to give fermion masses and gauge boson masses, we take this Lagrangian here, L0, and we just add these two pieces. Then I will show you exactly how this scalar field looks like. It is this is a doublet, so it's not exactly the same as the scalar field that we were seeing before with the Higgs boson. But after seeing how this scalar field looks like, you should already be able alone to derive how the Higgs mechanism works in this case. But we will see it explicitly. So just to say, the Electroweak Lagrangian will be equal to this L0 Lagrangian, which I now cancel, plus this term here. Let me write it down. Yeah. Okay, now we just rewritten what I already told you by word. Just to repeat myself another time, this piece here will give mass to the gauge bosons. This piece here, which is also called the Yukawa Lagrangian, will give mass to the fermion. In this case, the only fermion that we have in this Electroweak Lagrangian is the electron. How does it work, the covariant derivative? Because the covariant derivative for the Higgs depends on the quantum number of the Higgs boson. So now it's the time of seeing how is made this field, this scalar field, in the standard model Lagrangian. And in particular, this scalar field phi, it's made as following. This is a doublet, since as you saw in the Electroweak Lagrangian, L is a doublet. This covariant derivative here is made of 2 by 2 matrices, so this must be a doublet. And the doublet is made of two complex scalar field, one that we call phi plus and one that we call phi 0. And since both of these are complex scalar, both of them have 2 degrees of freedom. So we can say that phi plus is equal to 1 over square root of 2 phi 1 plus I phi 2. And then phi 0 plus and 0 are charges. So this complex scalar will be associated with particles which have charges plus 1, and so this is not a phi dagger, but this is a plus. A bit confusing. And this phi 0 will be associated to particles which have charge 0. But then, of course, after symmetry breaking, these will not be particles in the standard model. We'll see what, these particles here, or the particle associated to this field and this field, are not there, and we have just a particle associated to the Higgs boson that is introduced by this scalar field. This will be phi 3 plus I phi 4. Okay, so this is the doublet that we introduce for realizing the Higgs mechanism in the standard model, and this whole Lagrangian here, as we defined it with the covariant derivative, of course is invariant under this transformation, S U2 left times U1 hypercharge, okay, local. Local because of the covariant derivative. And in this case, so the covariant derivative associated to this doublet here will depend on the quantum numbers of the doublet. So in this particular case, the mu phi, where phi is the doublet associated to the scalar field, it's equal to the mu plus, in this case, the isospin of this doublet here, since this is a weak isospin doublet. This has isospin equal 1/2. And in particular, the first component will have third component of isospin equal plus 1/2. And this guy here will be third component equal minus 1/2. So in this case, I will have plus IGW sigma divided by 2, because this is the isospin of the Higgs which is not the Higgs. I continue calling this the Higgs, but this is not the Higgs. This is a scalar field, and after electroweak symmetry breaking and expansion around the vacuum, this will contain the Higgs, but this is not the Higgs yet. But allow me to call it the Higgs, and forgive me if I call it the Higgs. So this times W mu, and then we have plus I, in this case, hypercharge for both of them. If you make the calculation using that, the charge of a particle is equal his third component of isospin plus 1/2 his hypercharge, you will find that since this has charge +1, this has charge 0, the hypercharge for both of them it's +1. So hypercharge of both components on the doublet is +1. So in the covariant derivative, this will be I g first divided by 2 b mu. And then, of course, this is applied to the Higgs doublet. Let me cancel now this. So this is explicitly with the isospin and hypercharge of this doublet here. So I can cancel this part here. And there is another thing that I wanted to show you, but I don't remember. Ah, yes, of course. With this covariant derivative here, I have the Lagrangian, which is invariant under local symmetry, under this local symmetry here. And now we do the usual steps. So first of all, spontaneous symmetry breaking, or choosing a vacuum state. So for choosing a vacuum, since the potential is exactly the same as before, V of phi is equal to mu squared phi dagger phi plus lambda phi dagger phi to the second. Choosing a vacuum is exactly the same case as before. I can choose one of the infinite possible vacuum state for the field, and the vacuum state that I choose is the following: phi equal 1 over square root of 2. In this case I use phi 1 equal to 0, phi 2 equal to 0, and phi 4 equal to 0, and phi 3 equal to V. So in this case the vacuum is 0 V. Okay? And then after choosing a vacuum, I do the second step that we did already before, which is expanding around the vacuum. About vacuum. And in this case, I already sit in the unitary gauge. So that we don't have to make again all the reasoning about putting to 0 the imaginary component of the expansion around the vacuum. So in this case, after expanding about the vacuum, we have that phi of x, which was a doublet made like this, becomes very, very simple, 1 over square root of 2, 0 in the first component of the doublet, and v plus h of x in the second component of the doublet. And finally we have our field associated to the Higgs boson. So this one here is the field associated to the Higgs boson, not this one here. Okay, even though this one contains, after symmetry breaking and expansion, the field associated to the Higgs boson. So now what we will do is to check that this term here, so we want to check this one term and this one term, we will check that they give mass to the gauge boson, in this case here, and to the fermion, in this case here, after symmetry breaking, so using this expression for the doublet. So let's start by the simplest term, which is this one. We want to recover this term here, which was the mass term in a Dirac Lagrangian for the fermion, after symmetry breaking, so using the Higgs mechanism. Now, this is really, really simple because we have simply that we insert in this piece of the Lagrangian, so in the Yukawa Lagrangian, the broken, the symmetry broken scalar field. So we have that. This will be minus GE. Then we have over square root of 2. Left component, or L bar, will be equal to nu left bar, electron left bar. Then we have phi, but phi is simply equal to 0 v plus h over square root of 2, and I already collected the square root of 2. So this will be 0 v plus h. And then we have right component of the electron field, so we have ER. And then we have the same thing, which is, but with the right component. So we have ER bar. This one here, complex conjugate, so in this case it's simply 0 v plus h. And then the doublet, which is nu L E L. You see that making all the multiplications, we will have minus G minus GE over square root of 2 times V. Okay, and then we have nu L, every piece associated to nu L, so to the neutrino part, goes to 0, because it's always associated to the first element of this Higgs boson doublet. But the first element of this doublet after symmetry breaking is always 0. So this correctly predicts that the mass of the neutrino is 0. And we only are left with the mass of the electron, which is EL ER plus ER EL. And then, of course, there is another term which couples this part here not to V but to H. So in this case we will have a coupling between the fermion, which is in this case the electron, and the Higgs boson. GE over square root of 2 Okay, so this term here will be a term that couples the electron and the Higgs boson, and this term here, it's the term we are searching for, which gives us the mass of the electron. And in particular, you can see that the mass of the electron, it is equal to the coupling constant between the Higgs boson and the electron, which I call GE, V over square root of 2. Okay, and this is the first mass of the fermion. As you can see, the mass of the fermion depends on the interaction between the fermion and the Higgs boson, so this coupling here, and the vacuum value of the Higgs boson. So we have now a mechanism that gives us the mass of the fermions. In this case, the only fermion that we have is the electron, so we stop here with the mass of the fermions. But we do not have, or we have it already, but we didn't see explicitly, the mechanism that gives mass to the gauge fields. And let's see how it works. This is a little bit more tricky. But of course, we will not go through all the calculation, otherwise we end tomorrow morning. without going through every single calculation and every single term inside this piece here, I just wrote down the three pieces that we are really interested in, which are the pieces that give mass to the gauge bosons. As you see here in the Lagrangian, after electroweak symmetry breaking, we have these two terms, and in particular this term here is associated to a term which is 1/2 the mass of the W boson squared times WW. As you can see, this is quadratic in W1 and W2 and gives us the mass term for W plus and W minus, which are linear combination of W1 and W2. And so in particular, if this is associated to a term which is quadratic in the W and the mass enters in this way here, we can infer that the mass of the W is equal to 1/2 GV. So we have that. We already had mass of the electron, which I write down in blue, so that, okay, also, let me just do one thing. This piece here, I wrote it down just to show you the whole phase of the covariant derivative, which is a 2x2 matrix, and then if you want to make this calculation here, the mu, you just take this, you take the complex conjugate of this object here, and then you multiply it by this object here, and you get these two pieces plus other pieces. Now this piece here, it's not necessary anymore, so let me cancel this piece here, and let me discuss about the mass of W and etc. etc. We get we already got that from the standard model from the Yukawa Lagrangian. We get that the mass of the electron is equal to minus the coupling with the electron and Higgs boson times V over square root of 2, and this is the mass of the electron. Then we get that the mass of the W, since we are searching the terms quadratic in the fields, it's MW equal to 1/2 GWV. Yes. Okay. Where GW, it's not the coupling between the W and the Higgs boson, but is the coupling which appears in the Electroweak Lagrangian already before symmetry breaking. And then we have the mass of the Z. The mass of the Z is a bit more tricky, because as you can see here in this Lagrangian, and in particular in this piece here, do not appear like the term W3, so the term quadratic in W3 and the term quadratic in B mu do not appear, okay? What appears in this Lagrangian is a combination, so it's something quadratic in a linear combination of W3 and B mu, okay? And the linear combination is the following, this one, okay? So we can define a new boson which is defined with this linear combination of fields, which appears quadratically. So that means that in the standard model, what physically have a mass, so the particles that we can measure, of which we can measure the mass, are this linear combination of these two fields that exit from the Electroweak Lagrangian. So in particular, we can define a field which we call Z mu, which is this linear combination that appears quadratically in the standard model Lagrangian. So we'll define it as GW, W mu 3, plus, no, minus G first, W, no, sorry, minus G first, B mu. Then we also write it with a normalization factor. The normalization factor is the following: GW squared plus G first squared. under a square root. And so this field here now we can rewrite the Lagrangian in terms of this field here, and in particular this term, all this 1/8 v squared, etc., will be written as, let me see, this part here will be 1/8 v squared gw squared times plus g prime squared z mu. So now we have a term in the Lagrangian which is quadratic in the field z mu, and the mass term associated to this 1/8, I can also write it as 1/2 times 1/4. So, okay, because this is the mass term squared of the Z boson. So the mass squared, mz squared, is equal to this part here, so that mz will be equal to v over 2 times gw squared plus g prime squared under a square root. Okay, so now we have mass of the electron that comes from the Yukawa piece of the Lagrangian, mass of the W and mass of the Z that come from the covariant derivative associated to the Higgs boson. This is the Higgs mechanism at work. Of course, we are skipping a lot of pieces, and in particular all the pieces that are in this piece here and in this piece here, that gives first of all mass to the Higgs boson, and second interaction between Higgs boson and gauge fields, and then there is a piece here that gives interaction between the Higgs boson and electron fields. All these pieces here, we are not commenting them, but if you have like 1 or 2 hours of time, you can try to expand every one of these terms, and you will see every single interaction between Higgs and Fermion, Higgs and himself, Higgs and vector bosons, and everything else. But now let's just comment very briefly this mz and the combination of W mu and B mu that does not appear in this Lagrangian. The other linear combination of the field W mu 3 and B mu that does not appear as a quadratic term in the Lagrangian, so that we infer that this is a piece that associated to particles that are massless, it's A mu. We define it as A mu equal to, and we can define it because it's an orthogonal linear combination with respect to this. And it's simply the same with a plus and with these two swapped. So we have G prime W mu 3 minus or plus GW B mu over the same thing, so the same normalization factor, GW squared plus G prime squared under a square root. Okay, as you can see, this linear combination of the W mu and B mu field does not appear as a quadratic term in the Lagrangian. You can really try to expand every single piece, and we will see that this combination here does not appear. So we have that the mass of the boson associated to this field, which is the mass of the photon, it's equal to 0. Now we have every single mass of every single particle in this Lagrangian, except for the Higgs boson mass. Oh no, this I didn't want to cancel, because I want to comment it. So from this very, very simple Lagrangian, introducing the Higgs mechanism after electroweak symmetry breaking, or the mechanism is actually electroweak symmetry breaking and then expanding around the vacuum, we predict correctly all the mass of every particle which are included in this Lagrangian. I didn't write down the mass of the Higgs boson, but we can also get the mass of the Higgs, which depends by the parameters inside the Higgs potential and comes from expanding this term here. The mass of the Higgs in particular, it's 2 times lambda v squared, where lambda and v squared are the parameters that enters in the Higgs potential. So now we have a prediction for every mass of every particle except for the neutrino inside of this Lagrangian here, and this is really, really striking. We have the prediction that the mass of the photon is 0, as it is in reality. We have the prediction that the mass of the Z and the mass of the W are related, and let's see in which way are related in particular. Particularly if I define, as we did in the previous lecture, G prime over GW to be the tangent of a certain angle that I call theta Weinberg, the mass of the W and the mass of the Z are related in this way. MW over MZ is equal cosine of this angle theta Weinberg. And also, of course, we can use this theta Weinberg angle to define Z mu and A mu as function of cosine and sine of this theta Weinberg angle, as we did it in the previous lecture. We could stay here and comment this Lagrangian and the interaction that comes out from this Lagrangian and the relation between all the particles and all the fields in this Lagrangian for a week, but I will stop here with the relation that are present in this Lagrangian here, and just be aware that this is almost the full standard model Lagrangian, because here, okay, we have only an electron and an electron neutrino, but we can add new fermions simply adding pieces in the Lagrangian, and that so we can just sum other pieces in the Lagrangian for adding new fermions, for example, the tau and the mu and the quark. But then there is another problem, which is that the quark and the strong interaction between the quark would not be described by this Lagrangian. And in particular, for that, we need to modify the covariant derivative, and that is precisely what we will talk about. Once we introduce in this Lagrangian quarks and strong interaction, we practically have the standard model Lagrangian and the most advanced theory in particle physics and in physics in general. We know that the standard model Lagrangian is not perfect. We know that it doesn't describe everything in reality, but it's really, really, really a well-made theory, and it's striking how many predictions can make on the reality that surrounds us. So now it's time to complete this Lagrangian to get the standard model Lagrangian. This is probably the last lecture in this huge course about basic particle physics, and in the last 16 hours or 15 hours, I don't even know how many hours have passed, we came across this Lagrangian here. We built from scratch this Lagrangian here. This is the Electroweak Lagrangian with the Higgs boson incorporated inside, so we have also a mechanism to give mass to the gauge boson and to the fermion inside this Lagrangian. And don't worry if you still have doubts about every piece, because in the end of this lecture we will comment out every one of these pieces, piece by piece, and we will see which are the interactions associated to every one of these pieces. So now we will not comment it, but we also commented before. But what I want to do today, which is the last lecture, is to ask the question, what is missing in this Lagrangian, and complete this Lagrangian to get the standard model, the full standard model of particle physics. let's see what is missing in this Lagrangian. Also, answering to this question, we will came across something that we have been avoiding for all this time, which are quarks and quantum chromodynamics. But we will see it in a very natural way. Let's see first of all how did we build this Lagrangian here, and what is the content in particles inside this Lagrangian, and how we compare it to the standard model, because this is important to understand why we are doing the thing we will be doing today. So first of all, this Lagrangian, we built this Lagrangian, if you remember, starting from a single doublet of particles, which are the neutrino, so neutrino left, but in this case I will just write down neutrino, electronic neutrino, and electron. So these are the only two particles that we assumed to be there in the Dirac Lagrangian that describes free fermion when we started building this Lagrangian. Then in building this Lagrangian, we had to make this SU2 symmetry local, so we introduced gauge field, and the gauge field in the end, so the content in field in this piece here, it's simply, we have the photon, we have W plus and W minus, which are two fields, and we have the Z boson. So these are all gauge bosons that we activated for making the symmetry inside this Lagrangian, which was the SU1 hypercharge times SU2 left symmetry. We make this symmetry local and we get these three gauge bosons. Then we had a problem, we had another problem, which was the gauge bosons are not massive, and also the fermion are not massive, because if we introduce by hand a mass term for the gauge boson, we break gauge invariance and the Lagrangian doesn't hold anymore. So we introduced an important particle, which is the only, okay, yes, it's here, yes. We introduced an important particle, which is the only spin zero particle. Spin zero means that is associated to a scalar field, which is the Higgs boson. So in the standard model, the only spin zero particle that we know exists is the Higgs boson. So this is the content of particle inside this Lagrangian here. As you can see, in the standard model, we have many more particles. We have 1, 2, 3, 4, 5 more couples of particles, so 10 more particles that are not described in this Lagrangian, plus another gauge boson, or better, 8 gauge bosons, but that we consider just one particle, 8 gauge bosons which are associated to a new symmetry, which is the symmetry associated with quantum chromodynamics that we will talk today about. Fear not, because it looks like we only have 2 particles out of 12 fermion, but now the bridge from this Lagrangian to the standard model Lagrangian, which contains every single particles in the standard model, it's very easy, because all the conceptual part that we discussed in the previous lecture we will be used again in this lecture to build the Lagrangian for everyone else in a very straightforward way. So what we will do today is, number 1, discuss quarks, and quantum chromodynamics. So how will we do this? We will simply consider this same Lagrangian, this exact same Lagrangian, but not for a neutrino and an electron, but for the first family of quark, which is up quark and down quark. Okay, so discussing this Lagrangian, this will be the part of the lecture that will take more time, because discussing this Lagrangian, we will introduce a new symmetry, which is the SU3 color symmetry, which acts only on quarks and not on fermions. So that is why this Lagrangian, it's not invariant under this SU3 color symmetry. And then the second part of the lecture will be to, so second thing that we will do, it's introducing the other families. So the other 2 families of quark and the other 2 families of lepton. This we can say as, of course, sorry, there is a missing piece, of course, introducing up and down. and making this symmetry group, or better, making the Lagrangian invariant under this transformation local, forces us to introduce a new gauge field, which is the gluon. In particular, there are 8 gauge fields associated to 8 gluons, 8 versions of the gluon, but they are practically all the same. We can just, like when you see this scheme in particles, you just see 1 particle here, not 8 particles. Then we have, once we have the gluon, etc., we are only missing the other families of fermions, so other 2 families of quark. By the way, yes, these 3 here are called quarks. And these 3 here, so these 3 families here, are called leptons. The difference between quarks and leptons is that quark interact strongly, so they are subject to the strong interaction, and lepton are not. And this is a huge difference, because then quarks are confined and we cannot find quark along freely going around, but we only find quarks inside hadrons. So they are only inside composite particles. We will comment on this anyway. And then we'll see other families or generation. Introducing other families will mean expanding the Lagrangian that we will get to include also muon neutrino and the muon, the tau neutrino and the tau. Then we have the up quark, down quark. Here we have charm quark, strange quark, top quark and bottom quark. Once we extend this Lagrangian to include also all these particles here, we have the full standard model Lagrangian that we will then comment, and we will understand the interaction that come out from the standard model. We will end this lecture with an animation that I made a few months ago for visualizing all these particles and all their quantum numbers, because it's very in a course on particle physics, you always talk about particles, mass of the particles, etc., but you never actually, or at least I never actually told you which are the numbers associated to this mass. So you don't have really a sense of how huge, for example, the W boson is with respect to an up and a down quark. How huge is the Higgs boson with respect to these two? More in mass terms, so more or less it's the same order of magnitude. But instead of giving you a boring list of numbers in which this is the mass of the Higgs, this is the mass of the W, this is the mass of the Z, these are the quantum numbers, etc., I want to show you an animation that I made, animated particles. This animation is not intended as visualizing the particle as they really are, because of course it's not how the particle looks like, but in this animation will be encoded all the quantum numbers of all the particles in the standard model. So in the animation will be encoded mass of the particle, spin of the particle, charge of the particle, let's call it Q, and then whether the particle have or doesn't have a color charge. Color charge we didn't comment yet, but is associated to the strong interaction. Okay? So this is the plan for this lecture. Let's go. So for transitioning from the first family of leptons, which are described in this Lagrangian. So let's go back to what is described in this Lagrangian. In this Lagrangian is just described the first family of lepton. But for transitioning from lepton to quarks, we will ask, what if instead of having the first family of leptons, this Lagrangian describes the first family of quarks? Let's see what happens. So instead of having neutrino, electronic neutrino and electron, we now have in this Lagrangian up and down. Up and down are a doublet, are an isospin doublet. Better to say up left and down left is an isospin doublet, and acts in exactly the same way as neutrino left and electron left when it comes to weak interaction. But the complication of quarks is that we cannot find free quarks around. We can find a free electron, we can detect a free electron flying around, we can also detect a free neutrino flying around, but we can never detect a free up quark flying around. We can never detect a free down quark flying around. And that is because the strong interaction is there, and because of a thing called confinement. But let's say we skip all this part, we just assume that we already know that composite particles, which are called hadron, by the way, hadrons, are made of quarks. We skip all the historical struggle that has gone, how do you say, the historical trouble that people had figuring out that hadrons that they were measuring are made of quark, and we start from the knowledge that there are composite particles made up of quarks. And in particular, we now consider a Lagrangian that tries to describe only the up quark and down quark. So how do I have to change this Lagrangian if I want this Lagrangian to describe only up and down quarks, knowing that up and down quarks cannot be found freely flying around? Well, first of all, the gauge field part and this Higgs boson part remains exactly the same as in the Electroweak Lagrangian for neutrino and electron neutrino, except for the fact that we will introduce a new gauge field, but it's not the time yet. So for now, let's focus only on this part here of the Lagrangian, and in this part here that gives mass to the electron in the Lagrangian. So these two parts allow me to cancel these two parts. And let me just keep the fermionic part of this Lagrangian. Let's call it F, just to have a label that tells us this is only the part that involves fermions in this Lagrangian. Okay. Now, how I have to modify it? Well, first of all, I don't have anymore a electron right, and I don't have a doublet anymore. This doublet, I remind you that it's L equal neutrino left, electron left. I change this doublet to a doublet made of quarks. So in exact analogy with this doublet, neutrino left, electron left, I define a new doublet that I call big QL, which is up quark left and down quark left. Okay? Up quark left and down quark left, of course, means the left-handed chiral state of the field associated to the up quark, which is a fermion field, exactly as the electron field, and the down left-handed chiral component of the field associated to the down quark, which is also a fermion field, exactly as the neutrino and the electron. Okay, so these are Spinor fields. We spin 1/2 and have exactly the same properties of these two fields. The only difference, as I repeated already multiple times, is that they also interact strongly. Okay, but for everything else, they are exactly the same field. With respect to the weak interaction, okay, there are complications, for example, the mixing of flavor, etc. But for now, for the case we are seeing, for the weak interaction and for the electromagnetic interaction, they are exactly analogous to this field here. So, what do? We just change, instead of putting here the left-handed doublet, which contains two leptons, we put the left-handed doublet, which contains two quarks. Okay, so here we substitute Q bar L. Here we substitute Q bar L. Of course, this I wrote it like this. If you don't remember what this piece is, go to see the last lecture. The only difference between this piece here and the last lecture is that here we have this Hermitian conjugate term. This Hermitian conjugate means simply, it's simply a shorthand for not writing down the other part that we defined last time, which was ER phi dagger left. Okay, so the full piece that describes this Yukawa interaction in the for the electron. It's this piece plus this piece multiplied by minus GE, which is the coupling between the electron and the Higgs boson. And this piece here describes the mass of the electron. Now, let's say that we only have the mass of the down quark. In this case, we have this piece will be described by GD, which is the coupling between the Higgs boson and the down quark. Then instead of having this left-handed doublet that contains leptons, I will have the left-handed doublet that contains quark. And instead of having the electron right, I will have the down quark right, so right-handed component of the down quark. Of course, here I didn't change this, so I also have to put QL. In this case, if only the down quark is massive, instead of electron right, sorry, this is not only the down quark massive. If only the down quark participate in the electromagnetic interaction, in analogy of this, in which the neutrino does not participate in the electromagnetic interaction, what I do here is to add the down quark. Is to add down quark right, so right-handed component of the down quark, which is a single isospin singlet, and then right-handed component of the down quark. Of course, this is not complete, and this does not describe anymore the mass of the electron, but describes the mass of the down quark. Of course, this is not complete, because we know that for quarks, another characteristic, another difference between quarks and this doublet here is that the first component of this doublet, which is the up quark, participate in the electromagnetic interaction, while the neutrino does not participate in the electromagnetic interaction, and have a mass. So the mass of the up quark is not zero. So we have to add new pieces in this Lagrangian, because of course with the neutrino having a mass equal to 0, we don't need this piece for the neutrino, and with the neutrino not participating in the electromagnetic interaction, we don't need this piece here for the neutrino. There's not the right-handed component of the neutrino does not exist, at least in the in the standard model, in the Lagrangian that we commented before. Okay, but now for this quark here, those pieces must exist. So we will add a piece exactly analogous to this, but with up quark. So you are I gamma mu the mu you are, and then we add a mass term for the up quark. Let's comment how a mass term for the up quark looks like. Okay, the instinct, let's say the first instinct is that I just put minus G up, in which G up is the coupling of between the up quark and the Higgs boson. Then I put exactly the same structure as before, QL bar phi, where phi is the scalar field before symmetry breaking, and then after symmetry breaking it contains the Higgs boson field, and then I have up quark right plus Hermitian conjugate. But I have a problem, and the problem is that this field here, after symmetry breaking, let's see what this piece here does after symmetry breaking. Well, QL will be up L down L bar, okay? Then this piece here, after symmetry breaking, will just be 0 on the up floor and V plus H 1 over square root of 2 on the down floor, and then UR. And you see that this piece here gives us 0, because UL, or better, no, it doesn't give us 0. It gives us something which couples the down quark, the left-handed component of the down quark with the up quark. So it's a wrong piece, because what we need in the mass term for the up quark is something like this: up L something, so mass of up, and then up R plus the Hermitian conjugate of this piece here. So this guy here, it's not good for describing the mass of the up quark, but the change is very easy, because a term which is good to describe the mass of the up quark is simply the same term in which this V plus H, so the perturbation of the vacuum state of the scalar field, is not downstairs but is upstairs. So we have here V plus H. So we define a new field, which is it's not a new field, a transformation of this field here, which we call phi bar, and this phi bar is defined as I sigma 2, where sigma 2 is the Pauli matrix, phi star. Okay, you can check by yourself that with this field here, after symmetry breaking, so after deciding a vacuum for this field and then expanding around this vacuum, adding this new field here, we will have that we have this field here in which the non-zero part is on the upper component of the doublet. So in this case, if this is phi bar, I have a right term for the mass of the up quark. Okay? So this is the mass term for the up quark. And that's it. We changed the Electroweak Lagrangian from a Lagrangian describing this doublet here, which was nu left E, or better, nu electron, electron, describing both right-handed and left-handed, because of course this piece here describes like right-handed, to a Lagrangian, an Electroweak Lagrangian describing the doublet composed of up and down quark. Okay, that's it. Let's add back the terms associated to the gauge fields, and then let's discuss the complication of the strong interaction. Okay, if we add back the gauge fields, we have minus 1/4 the gauge fields associated with the SU1 hypercharge. It's B mu no, B mu no, or better, this is the kinetic field, kinetic part associated to this gauge field. Then we have minus 1/4 W mu no, W mu no. In this case, I'm not putting here indices. Okay, this doesn't need indices. This should need an A index, because this we have W mu no 1, W mu no 2, W mu no 3. So here we should need an index, but we always define it without an index. So I will not put it here. And this is the field, the kinetic part plus the interacting part of the field associated with the SU2 left symmetry. Then we have all the quark content of the Lagrangian, so all the fermion content, in which we only describe this doublet here. We have interactions between the gauge fields and the quarks. Then we have massive terms for the quarks. And of course, we need the Higgs boson part of the Lagrangian, which is the following. Okay, this is minus this term, and then we have plus the mu phi dagger, the mu phi minus v phi. This is the Electroweak Lagrangian with the Higgs mechanism included, describing a doublet of quarks without the strong interaction. Because now we will notice something. And this something will lead us to quantum chromodynamics. Well, this Lagrangian describes the up and down quarks, so the first family of quarks, but does not describe why quarks are confined. Why quarks can only be found inside hadrons, and in particular does not describe the existence of some kind of hadrons. You see, now we will skip all the glorious history of particle physics, and we will skip also the way in which people understood that hadrons, which are composite particles, for example, the neutron and the proton, are made of quarks. But so we will start by the assumption that we already know that hadrons are made of quarks, and we will try to and we will discover a new hadron which cannot be explained by this Lagrangian here. Let me write it here. So hadrons are particles that are composed and are made of quarks. So inside hadrons there are quarks, and people at some point understood that inside hadrons there are quarks and started classifying all the hadrons. It's very there was a moment in history in particle physics that people really were making new hadrons, and they started classifying these hadrons. We will just do two examples, the simplest ones. First of all, the proton, P, and the neutron, N, are hadrons. So these are the constituents of the atomic nucleus, and they are made of quarks. How do we classify these hadrons? For example, if we have the proton and the neutron, we can classify them as, so proton, neutron, we can classify them as using their electric charge, so Q. We can classify them using their spin, and from the electric charge and spin, we can understand their quark content. It's not as simple as that, but yes, more or less it is like that. So the proton has, let's just consider also the case, in this case we consider only up and down and no other quarks in nature. This of course is not true. There are hadrons that are made of other quarks which are not up and down, but for now let's just consider these two. So the proton has a charge of +1. We already know from chemists in high school, no? +1. This is the charge of the proton. The spin of the proton, people don't know it because they don't teach it at chemists, but it's +1/2. Okay? And it's made of 3 quarks. Now we know that the charge of the up quarks, the up quark have charge +2/3 and spin 1/2 because it's a fermion. The down quark have charge minus, so Q minus 1/3 and spin 1/2 because it's a fermion as well. So the difference in charge between this and this is 1 unit of charge, but they are not, as in the case of neutrino and electron, one charge 0 and one charge -1, but they are scaled up a little bit. This one has charge +2/3 and this one has charge -1/3, but the difference is always 1 unit of charge, as in the case of the electron and the neutrino. So if this proton has charge +1 and spin +1, the quark content must be 2 up quark, up, and 1 down quark, because the sum of +2/3 -1/3 gives me 1 unit of charge. The spin content of this hadron, so this hadron is a state made of up, down, with spin, will be a superposition, so we can assign spin as we want, and then it will be a quantum superposition of the various states. But one of the possible states, for example, is an up quark with spin up, another up quark with spin up, and the down quark, let's mix it a little bit for making it more fun, an up quark with spin down. So the composite spin of this state here is 0, because one is up, one is down, and this one has spin up, for example. Okay, this is one of the possible internal state of the proton, and as you can see, the sum of the spins of the quarks inside the proton gives us plus 1/2. So we get right the charge of the proton and the spin of the proton. Now let's go to the neutron. The neutron has charge 0, has spin 1/2, and so one of the possible internal state of the neutron is one up quark, two down quark. This is to get the charge right, and then the spin of this are distributed in the same way. So, for example, one up, and one down. Of course, up means plus 1/2, down means minus 1/2. Okay, just to be clear. So in this case, and of course, if a quark has total spin component, I just realized that we didn't discuss spin so much in these lectures because it's a knowledge that one should know from quantum mechanics, but we didn't talk about it in quantum mechanics. So if you have a spin 1/2 as the total spin of the particle, then the z component of the spin can be either 1/2, so plus 1/2, or minus 1/2. In this case, if the spin is bigger, then we can have other component of the z component of the spin. But in this case, we have one quark which is which third component of spin it's up, one is down, and one up, and then in total we'll have a particle which has a total spin of 1/2. In this case, we have up, up, down, and the particle has the particle composed of these quarks have total spin 1/2. Okay. Now let's do a third example of an hadron. Of course, we will not see all the hadrons and how are they classified, even though it's very interesting, but we will also, of course, skip all this discussion. But at some point they measured this hadron here, which is called delta plus plus, which has charge plus 2, which has spin plus 3/2, wait, let me think, 3/2, yes. Okay, this is a very weird hadron. How can I compose this hadron? Well, you can try to figure it out by yourself, but if I use one up quark, another up quark, and another up quark, I get the right charge, because I have 3 plus 3 plus 3 divided by 2, which is, wait, let me try, 2/3, no, yes, 2/3. 2/3 plus 2/3 plus 2/3. Okay, yes. The total charge of these three quarks is plus 2. Then I have a spin state. If I have to have 3/2, I have 1/2 plus 1/2 plus 1/2. So all the spin must be aligned up, up, up. Okay, as you can see, this hadron here must be made of 3 identical particles with identical spin, and I say, and also in the identical location, because they are composing the same hadron. I didn't say identical randomly. I say identical because this is against one of the deepest principles in quantum mechanics, and the principle is the Pauli exclusion principle. Because you see, these 3 particles are fermion, and the Pauli exclusion principle tells us that there is no reason, or there is no possibility for 2 particles, 2 fermions, to be in the same quantum state. In this case, we not only have 2 fermions, but we have 3 fermions in the same quantum state. So, how can we explain this? How can we explain the fact that there is an hadron? This hadron exists because we measure it, but it has to be made of 3 fermions that stay in the same quantum state, and this is not possible for the Pauli exclusion principle. Well, people came up with a reason why this is possible, and the reason is that there is a new additional internal degree of freedom in quarks. So these 3 particles are not the same particle, but they come in 3 different versions. Okay, so there is a new quantum number that can take 3 values, 3 different values, or let's say the quantum number associated, how can I put it? is not that the new quantum number has 3 basis states, as the spin quantum number has 2 basis states, up and down, but then the spin of a particle can really be a superposition of up and down. In this case, this new quantum number will have 3 basis states, and the quantum number associated to a particle is always a superposition of these 3 basis states. Okay? And this quantum number, we call it color. Okay? The color of a particle, of a quark, can be a superposition of 3 basis states, which are green, red, and blue. Okay? These are 3 states analogous to the 2 states of spin up and down. It's just naming. Calling them green, red, and blue, it's just a name. Of course, it's not that there is a red quark or a blue quark or a green quark, really like green colored as green quark. But having this new degree of freedom, we can tell that inside this hadron, this delta plus plus, the quarks are, one is red, one is green, and one is blue. This will also explain laterally, let's say, the confinement of quarks, because there is also this rule that every combination of quark must be always colorless, which means that we don't macroscopically observe this color quantum number. So a particle made up of quark must be in a superposition of color such as the total color is white. That means that the color quantum number becomes 0, or becomes like they cancel each other. So this is the reason why we cannot observe a quark alone, because of course a quark alone is in a particular state of color and cannot be colorless. Only a combination of quarks can be colorless. This also laterally explains why quarks are confined and we cannot find them outside of hadrons. But now we have a new quantum number, so we have not only one version of these quarks that we introduced in the standard model Lagrangian, so we don't have just one version of this doublet, we don't have just one version of this singlet, we don't have just one version of this singlet, but we have 3 versions of everything. So how can we modify this Lagrangian, this Electroweak Lagrangian for quarks to account for the fact that we have not really one version of these particles, but 3 versions, one for every color. To do this, we will cancel everything and keep only this piece here, but know that the modification that we will be making apply also to this piece here, because it also contains the quarks. Quantum chromodynamics, which is the dynamic of quarks. We discussed that, okay, first of all, I put this Electroweak Lagrangian including only this sector here, in which there are interactions between the up and down quarks and the gauge boson associated to the SU2 times U1 symmetry. And I labeled this Lagrangian with this Q, just to distinguish it from the full Electroweak Lagrangian. So in this Lagrangian, I remind you that QL is equal to a doublet, which is up quark, down quark. And of course, this doublet, it's the left-handed chiral component of these 2 fields. And then we have a up right and a down right quarks. Let me write them in a column so we can modify them. Okay, so we have these objects here in the Lagrangian. Up R, which is the right-handed chiral component of the up field, and then the R, which is the right-handed chiral component of the down field. Now, these guys here come in 3 possible basic Scalar states. So we have that this one okay, let's say this QL can be associated to 3 copies. One which is in the blue color state, then we have another copy which I do in red just for fun. Up, down, of course both of them are left-handed chiral state, and this is in the red color state, and then we have the same in the green color state. So up, down, both of them in the left-handed chiral state, and green. So I don't have anymore just one isospin doublet, but I have 3 isospin doublets. Then up R can come now in 3 combinations, or 3 versions, and also down right can come in 3 versions. So of course we have up right blue, up right red, and upright green, and then down right same thing, down right blue, down right red, down right green. How do I include all of this in the Lagrangian? Well, simply I need to take this Lagrangian and to make times 3. So I have an index here that I can say that this guy here is, for example, UR blue. So I have here an index in which it's a color index C, 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 where C can be red, green, or blue. So R or can be green, or can be blue. You will now see why I'm doing all this. And this one I call it QL with a color index. So also QL can be QL blue, QL red, or QL green. So also in this case I add this color index, and the Lagrangian that describes 3 copies of these quarks, it's simply the sum over the colors. So I sum over the color index. So it means that I have a Lagrangian which is blue, then a Lagrangian, the same stuff for the red doublet and the red singlet, and then the same stuff for the green doublet and the green singlets. Now, why I did this? I don't write it extensively, just because I don't have... it's very long, but it would be very fun to write it extensively and then accumulate everything together. But if I want to get rid of this sum here, of course the sum is over not only the first piece, but all the pieces are summed. If I want to get rid of this sum here, I do exactly the same thing that we did with the when we were talking about the Lagrangian, the Dirac Lagrangian associated to neutrino and electron, which was, if you remind, it was something like this. We had a Lagrangian in which we had a neutrino piece plus an electron piece separated, and then we built a doublet made of neutrino and electron. We call this doublet D. Okay, let's say also these are left-handed, so we can call this doublet L, and not confusing too much the ideas, but originally we call it D. And then we made a Lagrangian which is only a combination of this, like it's written in terms of this doublet L, I, gamma mu, d mu, L. While this Lagrangian here, I didn't write everything, but it's in terms of neutrino electron separately, okay? In this case, we want to do the same. Now, we define, instead of a doublet, we define a triplet made of these color states, okay? So, for example, we will have a triplet UR, which is simply made of UR blue, UR red, and UR green. Okay. The same thing I can do with DR. Okay, I can build a triplet made of these 3 basic color states, and then I can do this. This is just for educational purposes. Usually it's not made like this, but I build a triplet made of doublets. This is just for making you understand how do we build this kind of stuff. But I have no space for this triplet made of doublets, so allow me to write it somewhere else. Yes, I write it here. I call QL equal to, I will have the first doublet, then I will have the second doublet, and then I will have the third doublet. One is red, one is green, and one is blue. Yes, with these two objects, or better, three objects, let me also write the other one. Okay, perfect. With these three objects I defined, I can simply remove the sum and remove the color index. So now we will write the Lagrangian in terms of these three objects, and you will see now why we are doing this stuff. But it's exactly analogous on how we did, how we wrote down the Lagrangian when we were talking about the SU2 symmetry. In this case, we have not doublets but triplets, so you can already imagine what is the symmetry associated to this new Lagrangian. So if the Lagrangian, if I define three triplets like this, I can then write the Lagrangian without these indices, and now this guy here is a triplet, this guy here is a triplet, this guy here is a triplet, this is a triplet, this one is a triplet of doublets, and this one as well is a triplet of doublets. Okay, so the sum now is implicit in the calculation we make when we expand these terms made of triplets. Why I did this? Well, I did this because now the Lagrangian is invariant under a transformation which is called SU3 global. But let's do one step at a time. So we have that, I also remind you that this guy here, which is the covariant derivative, this, and this, since we already have a symmetry which is SU2 left times U1 hypercharge, and this symmetry is local. We made it local talking about electroweak theory, and if you don't remember how we made it, it's very, very important that you learn this, or even better, you learn it in quantum electrodynamics, which is the simplest case possible, and then you come back, because now the reasoning that we will do for making the symmetry associated to this triplet local is exactly the same. So we will not redo all the calculation and all the reasoning, but we will just jump to the conclusion. But this symmetry is local. For making this symmetry local, we introduce this covariant derivative, which is defined as follows. The mu equal to the normal derivative, then we have plus I GW isospin number. This guy here, I, stands for isospin. Then we have sigma matrices time W mu, which this is sigma times W mu means sigma 1 times W mu 1, sigma 2 times W mu 2, sigma 3 times W mu 3. So this is a 2 by 2 matrix. And then we had plus I G first, so this is associated with the SU2 left symmetry, and then we have IG first, hypercharge of particles divided by 2, and this, of course, this quantum number of isospin and this quantum number of hypercharge are there just to say to us, for example, the strength of the coupling between the various pieces, or better, the coupling will be proportional, the strength of the coupling will be proportional to this number here, to this quantum number. So for example, the particles that have isospin equal to 0, which are the right-handed chiral states, will not interact at all with these W particles, okay? Anyway, then we have I, G first, B, mo. And this piece here is associated to the U1 local symmetry. Now, what do we observe in this Lagrangian? We observe in this Lagrangian that if I change the internal color state of quarks in a certain way that now I will describe, the Lagrangian remains the same. So I have an invariance in this Lagrangian, which is a global invariance with respect to the SU3 symmetry group. So I have an SU3 transformation. If I define an SU3 transformation of the color quantum number, which is something like this. I take my my doublet, my triplet, for example, UR, let's say, UR, and I send this triplet to UR first, equal to exactly the same structure that we saw for the weak interaction, so for the SU2 symmetry group, which is something like e to the I GS, where GS has the exact same role that GW and G first have. So it's the strength of the coupling. In this case, it will be associated to the strength of the strong coupling times chi. Okay. In this case, chi does not depend on the coordinates in space-time. So chi, it's a global transformation. Times let's erase chi and call it alpha as we call it before, otherwise we get confused. But the important part is this. We have this set of matrices, lambda A divided by 2. Lambda A are called the Gell-Mann matrices, and they are 3 times 3 matrices. And then we have alpha A. So alpha, it's a parameter, it's just a number, but actually we have 8 numbers associated to 8 of these lambda matrices, and then of course times UR. So under the SU3 transformation, this UR field, so these UR triplets, get sent, like how do you say it in English, becomes this triplet here, which has mixed components. So the SU3 transformation, what the SU3 transformation does is to take this component and mix them, okay? Perfect. And this is a global transformation, meaning that, first of all, lambda A are 8 3 by 3 matrices. So they are 3-dimensional, like 3 row and 3 column in the matrix. So 8 3 by 3 matrices. Exactly in an analogous case in which the sigma matrix, sigma I, are 4 2 by 2 matrix, which are the Pauli matrices. But anyway, 4, no, they are 3, sorry. The sigma I, this is analogous to sigma I being 3 2 times 2 matrices. And we defined, when we were talking about the SU2 transformation, we defined the generators of the SU2 transformation as 1/2 sigma I. And in this case, the generator of the SU3 transformation will be this 1/2 lambda A. Okay, so lambda A are 8 matrices that define an SU3 transformation. Okay, an SU3 global transformation is something like this, that mixes the color states of the quarks in the triplet and the Lagrangian, the Electroweak Lagrangian. No, sorry, this is not the Electroweak Lagrangian anymore, but this Lagrangian here written in terms of the quark, which has inside the Electroweak symmetry because it's already invariant under this local transformation. It's invariant under global transformation of this type. Okay, so if you apply a global transformation in one of these triplets, the Lagrangian does not change. This is super, super important because the Lagrangian, so we have an SU3 color symmetry which is global. Now, exactly as in the case of the SU2 left, exactly as in the case of the U1 hypercharge, exactly as in the case of U1 of electromagnetism that we all discussed, we want to ask ourselves, what happens if I want to make this transformation local? So, is the Lagrangian also invariant under local gauge transformation? What happens? How can I make my Lagrangian invariant under local SU3 color transformation? And making it local means that this parameter here, which are 8 numbers, becomes dependent on x, on the position in space-time I'm sitting on. So this is a local SU3 color gauge transformation. Of course, this applies not only to U right, but also to D right and to Q left. Okay? Let's see what happens and how can I make this transformation local. Well, for making this transformation local, it's actually very easy because, as I told you, it's exactly the same reasoning we went through for making the SU2 transformation local. And for making it local, given this transformation, so given this SU3 transformation, we just add a piece to the covariant derivative, which is plus, and the piece has exactly the same structure of these two pieces here. In particular, it is plus I GS, where GS is the strong coupling. Instead of having sigma times W mu, in which sigma times W mu means sigma, this could be sigma A W mu A, which means sigma 1 W mu 1, sigma 2 W mu 2, sigma 3 W mu 3. So we have 3 matrices associated to the SU2 group, and we introduce 3 new gauge fields. In this case, we have 8 matrices, so we have lambda A over 2. These are 8 matrices associated to the SU3 symmetry groups. These are the generator of the SU3 symmetry group. So we have to introduce, sorry, not 3, 8 matrices associated to the SU3 symmetry group, and we have to add 8 new gauge fields associated for making this SU3 color symmetry local, which we call GA mu. These 8 fields here will be the gluon fields. So we have 8 gauge fields which are associated to gluons. Okay? The gluons are to the strong interaction what the photons are for the electromagnetic interactions. Okay, so the gluons are the mediator of the strong interaction that happens only between quarks. So this term here in the covariant derivative means that this covariant derivative now it's changed. It has a new piece, and this Lagrangian now is invariant under local SU3 transformation, given that this field here transforms in a very particular way that now I will proceed to write down. So, for this symmetry to be local, for the SU3 symmetry to be local, the gauge field must transform in this way. SU3 of color must take G mu and send it to G first mu, or let's do it component by component. So G mu A, the 8th component of this G mu field, send it to G prime A mu equal to, first of all, G mu A. Then we have a piece which is analogous to the one in the electromagnetic interaction, so simply minus derivative of this parameter here, which acts, which we don't have it anymore, but it's derivative of alpha A. Yes, that depends on x. Alpha A of x, it's the term in the SU3 transformation that gives the SU3 transformation. So the term associated to the generator of the SU3 symmetry group. Let me write the transformation somewhere. No, okay. You go some second ago, and the SU3 transformation is defined for the quark fields. This guy here comes from there. Okay, and then we have another piece which is minus I GS. I'm not sure about this I. Then I will check. Multiplied by F ABC. Let's call it A, B, C, G, mu, B, times alpha, so G mu, let's call it, okay, yes, times alpha C, that depends on x. I checked, and this I here, it's not there, okay? So this is the way the field G mu A, so the eighth component of this collection of 8 fields must transform under SU3 transformations is the following, where FABC is the structure function of the group that we already defined in the case of the SU2 transformation, but I will write you here how you define it, and it's simply these are simply the constants, so the number that come up in this relation here. If I take TA, where TA is the 8th generation generator of the SU3 group, and TB, so I do the commutation relation between 2 generators of the SU3 group, I get I, F, A, B, C, TC. Okay, so this FABC is the number that appear here. Okay, this is the way the field must transform under SU3 color transformation, and once I have this modification here, so once I modify the covariant derivative to be like this, okay, now the Lagrangian is invariant under not only SU2 left times U1 hypercharge transformation, but SU2 left times U1 times SU3. So we have an invariance, which is a symmetry group, which is SU3 color times SU2 left, U1 hypercharge, local transformation. So the full standard model Lagrangian is invariant under this symmetry group. Okay, what does it mean? Because this guy here, I bet that you saw it multiple times if you are in particle physics. Now we are really understanding what this means. This means that the Lagrangian of the standard model is invariant under this local gauge transformation. If I take my fields inside the Lagrangian of the standard model, which I didn't write here yet, so patience, but we will come to that. But if I take this transformation here, and I transform the field using this transformation, the Lagrangian of the standard model remains exactly the same. It describes the same physics. How this transformation works? As you can see here, we have 3 symmetry groups that act independently on the components that I put inside my Lagrangian. And now it's the moment to see how they act, at least in a, let's say, not so deep level, but just intuitively. How do they act? And why do they act separately? Let's take this this triplet made of doublet, so this effectively is made of 6 fields, and let's say what happens if I apply a U1 hypercharge transformation? Well, it simply happens that the field phase changes. The U1 symmetry is associated to a phase shift in the field. So it simply takes one of these fields and sends it to himself. So let's say, for example, this U1 symmetry, I write it in blue, U1 hypercharge. The thing it does, it's taking one field, for example, U left, and transforming it into himself, mixing it to himself, which is not even true, but it's shifting the phase of this field. But my point is that it doesn't mix the field with anything else, okay? It keeps mixing the field with himself. Then the SU2 left transformation, this transformation here, this applies only to the left-handed chiral component of the fields, and it takes the up quark and the down quarks and mixes them. Okay, so this transformation, what it does, it's mixing these two components, and these two components. Okay, if we had neutrino and electron, SU2 transformation applies to neutrino and electron, and it will mix, for example, neutrino left, electron left. The SU2 transformation mixes these two components inside the Lagrangian. Now, what does SU3 color do? SU3, so when I apply an SU3 color transformation, who gets mixed are these components here. So it takes up quarks and mix it to the other up quarks of the other color. So it takes these three components, up green, up red, and up blue, and mixes them. And it takes down green, down red, and down blue, and mixes them. Okay, so this is how the SU3 transformation acts. Of course, the SU3 color transformation does not act in doublets that are made of leptons. So, for example, neutrino and electron doublet. This has no SU3. Okay, does not act in this doublet. As you can see, the three transformation acts independently in different parts of the standard model Lagrangian, but doing any of these transformations or a combination of these transformations leave the Lagrangian invariant. So this is why we say that the Lagrangian of the standard model is built upon an SU3 colors times SU2 left times U1 local symmetry group. This is something, this transformation here, this symmetry group, is something that as a student I always had struggle understanding how it really acts on the Lagrangian of the standard model. So if you didn't understand this completely 100%, it's very normal, it's not so intuitive, but just think about it. And at some point you will be enlightened on how this symmetry acts on the standard model Lagrangian. Now, for building the standard model Lagrangian, we need actually another piece, because yes, this term here, this Lagrangian, this Electroweak Lagrangian with quark content, now after modifying the covariant derivative, is invariant under SU3 color transformation, but SU3 color transformation comes with 8 new gauge fields. So we also need to add to this Lagrangian, and then we can discuss the whole Lagrangian, but we need to add to this Lagrangian a piece which is minus 1/4 G mu nu G mu nu. And also in this case we can add indices A, as we should have added before with W mu nu, but we didn't do, but the meaning is the same. So this piece here, it's not simply a kinetic term for the gluon, but it contains a kinetic term for the gluon plus interaction term for the gluon. And we will discuss later about these interaction terms, but let's see just how this term here looks like, which is completely analogous on how W mu nu looks like. So W G mu nu A is equal to the mu no and then here we have minus GS F A B C this is how the G mu nu piece inside the Lagrangian looks like, and this piece here comes from the fact that the SU3 symmetry group is not abelian, and so we have interactions between gluon in the standard model Lagrangian. So now we have this little Lagrangian that describes quarks, describes the kinetic term plus the interaction term of the gluons, and we are just having under the hood all the piece about the standard, about the Higgs boson, so that gives mass to the gauge bosons. In this case, the gluon will not receive a mass because they are massless. And then we have also all the piece that gives mass to the quarks, the quark up and quark down. Now let's write down the whole Lagrangian with also the pieces that we are skipping, and then commenting piece by piece this Lagrangian, which will be very, very, very close to the standard model Lagrangian. To get the standard model Lagrangian, we will also need another modification, but let's see it one step at a time. The standard model. Finally, we can put together all the pieces that we have been looking at and build the standard model Lagrangian. We are ready. The standard model Lagrangian is based on a symmetry group, which I write here, which is, we just commented it, but let me write it here, SU3 color times SU2, I don't put the X because I'm more compact, SU2 left times U1 hypercharge. This is the symmetry group associated with the standard model Lagrangian. We just commented how this symmetry group works. And let's just construct the standard model Lagrangian, so LSM, for the thing we have been looking at. So we start by building the standard model Lagrangian considering only 4 fermions, which are the ones that we have been discussing until now, which are the electron, the neutrino and the electron, and the up quark and down quark. With these 4 fermions, we are forced, when we apply this symmetry group and we force this the Lagrangian of the standard model to be locally invariant under this symmetry group, we get the gluon, the photon, the Z boson, the W plus and W minus boson. These arise naturally from asking this symmetry to be local, sorry. And then for giving mass to all of these particles, we saw that we also have to activate a piece in the Lagrangian which is connected to the Higgs mechanism. So now let's go piece by piece to see all these pieces in the Lagrangian. I remind you that in the end of this lecture there will be an animation in which we will see the mass of these particles, the quantum numbers of these particles. So for now it's just a collection of particles like this. But this will be the particles described by the Lagrangian that I write now. So let's put together everything we have been discussing. First of all, we need a gauge piece, like the piece of the Lagrangian associated to the gauge fields that we turn on for making this symmetry local, which are 3 almost structurally identical pieces, which are -1/4. Let's call one G mu nu, G mu nu, and this I put index A, where big A goes from 1 to 8, and these are associated to quarks, to gluons. Then we have -1/4. Then I'm just writing it down, commenting it, so that we can see every piece where it comes from, and then we will see for every class of piece, we will see the interactions inside that piece and what those pieces actually contain. So then we have 1/4 W mu nu, W mu nu, and in this case the index is little a. Big A goes from 1 to 8, So, and little a goes from 1 to 3. So 1 to 3. Another thing which is important, yes, of course, because we have 8 gauge fields associated to the strong interaction and 3 gauge fields associated to the weak interaction, and then we have, or better, to the SU2 left symmetry group, and then we have 1 gauge field associated to this U1 symmetry group, which is B mu. So minus 1/4 B mu nu B mu nu. And this is the bosonic content, or part of the bosonic content in the standard model Lagrangian. Then we will have plus another piece which accounts for, let's go for quarks. So we have QI gamma mu de mu, where QL is a triplet of doublets, but we will define it later. Then we have here QL. So these are the left-handed components of the quark fields of up and down, and these are 3 copies of this, 1 for every color. And then we have plus U R bar. So the same pieces, but with the singlets, which are not singlets. These are isospin singlets, but color triplets. We will also comment about this, but we just saw it, but I'm re-commenting everything because probably someone will just jump to this lecture with the standard model Lagrangian and want to know piece by piece what it is. So this part here I let it from the previous lecture, just to remember what is this G mu nu. And then the structure of these two will be very similar to this one, but we will comment later when we will see piece by piece. Now, this piece here also we will re-comment it later, even though I just commented a few minutes ago what these are. So gamma mu, de mu UR again. And then we have one of these pieces associated to the down quark. So the R I gamma mu big D mu dr. Then we have the same thing, which contains, these pieces here contain interaction between the Spinor fields and the gauge boson fields. So we have this for quarks, for up and down quarks, and then we also have this for electron and neutrinos. So we have plus L I gamma mu de mu L, where this L is the doublet composed of left-handed neutrino and left-handed electron. We will also comment this, plus electron right bar, again I gamma mu de mu, and then electron right. We don't have this piece corresponding to the neutrino because we have not in the standard model Lagrangian a right-handed neutrino component. Okay. Now we have pieces in the standard model Lagrangian which are associated to the mass of the electron and mass of the quarks. But before this we need to activate the Higgs mechanism to give mass to the gauge bosons, to the gauge fields. So in this case the Higgs mechanism is something like plus d mu phi d mu phi, and this one it's dagger. Then we have minus v phi, which is the Higgs potential, and then we have, so this piece here will give mass to the gauge boson and will contain interaction between Higgs gauge boson and Higgs and himself. Also this one we will comment it later. And then we have a term that gives mass to the quarks, so to the up quark and down quark that we commented before, which is minus, let's do for up quark, minus G up, and then we have QL bar phi bar, which we also defined before, upright plus Hermitian conjugate. And this is for the up quark. We have an analogous term for the down quark, which is minus G down QL UR, down R, but with a different field here. So QL phi down R plus Hermitian conjugate. And then same piece for the electron. So minus this piece here. We will cancel it later, but for now let me keep it here. Also, yes, let me keep it here. We have G electron, left-handed component, L bar, phi, and then L ER plus Hermitian conjugate. We commented all these pieces in the previous lectures. In particular, all these pieces here you can find the precise comment in the lectures about the Higgs boson and the Higgs mechanism. But we do not have a term associated to the neutrino because the neutrino in our picture now does not have a mass. Okay, so plus 0. This is the standard model Lagrangian containing these particles here. Okay, there is nothing more. Now let's go and comment piece by piece, because we will have, let's divide it in various pieces. This is the first piece we will comment. Let me call it 1. Then we have this second piece here, which is the quark content and interaction between quark and gauge bosons. And let me call this piece 2. Then we have this piece here, which is practically the same, but for leptons, and I call it piece 3. Then we have an Higgs boson piece, which is this one. Okay, and allow me to call it 4. And then we have a Fermion mass term, which I ran out of colors. Let's do it in red, which is this piece here. Yes. Okay, and let me call this piece here 5. This 4 here, I put it here. Okay. Let's go piece by piece in the standard model Lagrangian that we built in these lectures. Now, if you followed everything and you understood everything in the lectures, every one of these pieces, it's already familiar to you, and you could already know what every piece is associated to, but let's comment them one by one. Okay, let's start by piece number 1, which is this piece here with the gauge boson piece in the standard model Lagrangian, or call it however you want, because the gauge bosons are also in other pieces in the Lagrangian. But let's call this piece the gauge content of the standard model Lagrangian, even though it's not the only gauge content. I let here this relation here because the way G mu nu is defined is the same way, is the same structure of the way W mu nu is defined, okay? In which the only difference here is that this G becomes a W, this A index becomes a lowercase a, so we have 3 pieces inside instead of 8 pieces, but it's exactly the same stuff. And of course, this the coupling becomes not the strong coupling anymore, but the W coupling. But anyway, just to say that this piece here will contain, first of all, kinetic terms, so kinetic pieces for W1, W2, W3, kinetic pieces for the gluon, GA, and kinetic piece for the for B, which is the photon-like field associated to this field here. Now, remember that this field here is not the photon, but is the field associated to this U1 hypercharge symmetry. And also remember that B mu nu is not defined as G mu nu and W mu nu because because this U1 hypercharge is a group which is non-abelian. So for it, this piece here is not there. So when we define B mu nu, we have B mu nu equal d mu B nu minus d nu B mu. Okay, just to say that the only piece inside this first piece of the Lagrangian associated to B mu nu is the kinetic term. Okay, since SU3, which is associated to this gluon here, so to this this collection of fields, and SU2 left, which is associated to this collection of fields, are transformations that are non-abelian, we have pieces in which we have interactions. So second piece in this first term is interactions. And which kind of interaction we have? Well, in this case here, if we do G mu nu, which is this piece, times itself, more or less, we have pieces in which we have a 3-gluon interaction, so a 3-gluon vertex, something like this, in which we have gluon, 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 and vertices with 4 gluons, something like this. So we call G, 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 G. Okay, so there is self-interaction with the gluons. When we do the same thing with W mu A and W mu, when we do the same thing with W mu, no, sorry, okay. When we do the same thing with W mu nu, we have the same thing, but in this case, the physical fields are not W1, W2, and W3, but are W plus, W minus, and the Z boson. So if we write this relation here in terms of W plus, W minus, and Z boson, the interaction that come out from this piece here are the following. To remember these interactions, you just need to remember that that the charge must be conserved. So we can have this kind of interaction in which we have W plus, W minus, and something here. So a vertex with 3 particles, and this something can be either a Z boson, so we have an interaction which is W plus, W minus, Z, or a photon, because they are the only non-charged particles. So gamma. So other interaction is W plus, W minus, photon. Okay. Then we can have, as in the case of gluons, an interaction vertex with 4 particles, and the 2 other particles that can be here can be either again W plus and W minus, W plus, W minus. So I can have an interaction which is W plus, W minus, W plus, W minus, or ZZ. So another kind of interaction that I can have all in this term here. In the first term of the Lagrangian, it's W plus, W minus, ZZ, and then I can have, so these particles here are Z and Z, and then I can have the same with Z photon or photon photon. W plus, W minus, Z photon, W plus, W minus, photon photon. Okay, so we have in total all this kind of interaction. 3-gluon interaction, all these interactions with 4 particles associated to the SU2 left symmetry, all these 3 particles interaction associated to the SU2 symmetry, and then another one which is G, G, G. Okay, perfect. These are the interactions, or at least the classes of interaction, that can emerge from the first part of the Lagrangian. Now I have not any more space, so I will erase the first part of the Lagrangian and we pass to the second part of the Lagrangian. Also, the definition of how G mu nu is made, it's not needed anymore, so I will also cancel this part here. So yes, first part done. Part number 1 done. Second part of the Lagrangian, what we need to define is first of all, who is this QL. This QL, it's simply a triplet of doublets, or at least this is the way we defined it. So it's up, down, up, down, up, down. Okay, every one of these doublets is left-handed component of the fields, and then I have a red version, a green version, and a blue version. Okay. Then we have UR and DR that are the same, and they are a triplet of singlets. DR is equal to DR right, DR green, and DR red, green, and blue. And the same goes for UR. So this is how they are defined, and of course when I say I put a bar here, they become a row vector, so that when I expand all these terms here, we get a lot of pieces in the standard model Lagrangian. So this is a very, very, very compact way of writing down this. And of course, the symmetry group that applies to these triplets, it's all the symmetry group, or at least the symmetry group that applies to this guy here, it's the whole symmetry group of the standard model Lagrangian. So if I apply an SU3 color transformation, I mix component in this one, and as well as SU2 and as well as U1 hypercharge. This guy here instead, since it's made of right-handed chiral component of the downfield, does not, how do you say, does not couple or is not influenced by this part here of the symmetry group. So it's not influenced by SU2 left, because SU2 left acts only on the left-handed chiral component of fields. So this guy here and these guys here, they are called SU2 singlets, so they are not influenced by this symmetry group. This is just to say. What we introduced was the covariant derivative, and the covariant derivative must be made in such a way that the total Lagrangian of the standard model is invariant under this huge symmetry group. So let's write down how the covariant derivative looks like, and then from that expanding the terms that we will not do whatsoever. Expanding the term, though, you can find every possible interaction that is encoded in this piece here of the Lagrangian. We will just list the interaction without expanding and without, of course, making all the calculation, otherwise we stay here like for other 10 hours. So the covariant derivative in this piece here is defined as demu equal to demu plus IGW isospin sigma W mu. This will be sigma A W mu A. Then we have plus IG first, I have no space anymore. IG first hypercharge divided by 2. These are quantum number of particles. So this guy here, it's isospin. So who does not have isospin or isospin equal to 0? UR and DR, they have isospin equal to 0. They do not participate in the weak interaction or in the charged part of the weak interaction. And then this is the hypercharge, and every particle has a value of hypercharge. And this is BMU. And then we have the part of the covariant derivative associated with SU3, which is IGS. GS is the strong coupling, lambda big A divided by 2 times GA. Okay, this is the way the covariant derivative is defined. So this guy here is actually a 2 by 2 matrix, and this guy here is a 3 by 3 matrix, because it's the Gell-Mann matrices multiplied by the 8 component of this gluon field, and here is the Pauli matrices multiplied by the 3 component of this vector field here, okay? And this guy here is a 1-by-1 matrix. But then when we sum everything, it becomes a huge object. Then we put this huge object inside these various components, and we get the interactions between quarks and the gauge bosons in the standard model. Let's see how they look like. Let me erase this part. So for quarks, we have the whole package. We have every possible interaction. So we have one strong interaction, which is associated to this SU3 color symmetry group. And so the SU3 color symmetry group is associated in the covariant derivative to this piece here. So this is the piece associated to SU3 color symmetry and turns on strong interaction. And the strong interaction is actually very simple because it's vertices of the type we have up, down. So let's call both up and down, we call them Q. So we have Q, Q, gluon. A vertex like this can be, for example, a gluon that turns into a, I don't know, up bar, or a gluon that turns into a d bar, d bar, or, for example, an interaction like this, in which we have a down quark that absorbs a gluon. Okay, so these are all the possible vertices encoded in this, like in this class of vertices, in which we have two quarks and a gluon. So this is the first class of vertices that we see, and is associated with a strong interaction. Then we have vertices associated to the weak interaction. So number 2, weak. And of course we have two kinds of vertices. The one in which the flavor changes. So from an up quark it becomes a down quark, and these are all the vertices in which of the class in which I have, for example, up, down, and a W boson. For example, I don't know, an up quark becomes a down quark, so this has charge plus 2/3, this has charge minus 1/3, and they emit a gauge boson. This gauge boson must be W plus, because W plus has charge +1 minus 1/3 gives me 2/3. But I can have a lot of possible vertices. For example, if in the initial state I have a down quark, and in the final state I have an up quark, this have to emit a W minus boson, okay, etc., etc., etc. So this is just a class of vertices of this type of interaction, so in which I have an up, a down, and a W boson, and then the particular particles involved in the interaction depend by the initial state and the final state. And then I have the third type of interaction. Also weak interaction, this is charged. And then I have another type of weak interaction, which is neutral, in which also in this case I have, for example, quark and Z boson. In this case I don't distinguish between up and down, because it's always the same quark that participates in the weak interaction when there is a Z boson. So the Z boson does not change the flavor of the quarks. So for example, just to make an example, can be, for example, a down quark that remains a down quark and emits a Z boson, okay, or down bar that becomes a Z boson, and any other possible kind of vertex that you can think about, in which we have two quarks and a Z boson. Then we have the last type of interaction, which is the electromagnetic interaction. Okay. So third type of interaction, we are always talking about this second part of the Lagrangian. It's electromagnetic. And in this case, we just have quark-quark photon. Also in this case, the photon does not change the flavor of the quark. So if I have an up quark in the initial state, I will also have a down up quark in the final state. Okay, the electromagnetic interaction, it's something like this. So, for example, a photon in the initial state, and then a quark and an anti-quark in the final state, where Q and Q bar must be the same family of quark, no, the same flavor of quark. So if this is up, this is anti-up. If this is down, this is anti-down. Okay? And these are the classes of vertices that are turned on by the electromagnetic interaction. So as you can see, the quark sector in the standard model Lagrangian turns on every kind of possible interaction. This interaction here is associated to the SU3 symmetry group, while these two interactions here are associated to the SU2 left times U1 symmetry group. So this big symmetry here, which gives us the W boson, the Z boson, and the photons, are associated to this piece here in the covariant derivative. For a discussion on how this W1, and also this piece here. For a discussion on how the W1, W2, W3, and the BMO mix to form W, Z, and photon, refer to the lecture about the weak interaction that we did few times ago. Yes, now things are getting simpler because this sector here in the standard model Lagrangian, which is associated to the leptons, so not to the up and down quarks, but to the doublet, which is nu and e, so neutrino left and electron left, plus, of course, electron right, they do not participate in the strong interaction. So this symmetry group here, it's not involved in the covariant derivative. So in this case, the covariant derivative for this piece of the Lagrangian here does not involve this last piece here. And this ER, it's not a triplet of color, but it's just a singlet. It has no color charge. This guy here, we defined it here, it's not a triplet of doublets, but it's just a doublet, which is a doublet with respect to this SU2 left symmetry group. So what does it mean? That means that for the leptons, so electron and neutrino, the strong interaction, it's not there. So this part, these vertices associated to the strong interactions are not there. So we have, first of all, the weak interaction, number one, weak, and we can have flavor-changing weak interaction, flavor-changing interaction in which we have the W particles involved. So in this case, we have neutrino, electron, and a W in any kind of possible combinations, because of course we can have a neutrino that turns into an electron emitting a W, or an electron that turns into a neutrino emitting a W, or absorbing a W in any possible way. So this simple text here includes a lot of vertices. Then we can have, associated to the Z particle, we can have nu Z, and of course electron electron Z. So the Z particle is not associated with something that changes the flavor. Concerning the electromagnetic interaction, when we talk about quarks, both up and down interact electromagnetically. So we have a vertex which is up photon and a vertex down photon. In this case, in the case of neutrino and electron, only the electron part interacts with the photon, so interacts electromagnetically. So the only vertex here we have is electron-electron gamma particle, in which, of course, as before, this accounts for all the possible vertices in which we have couplings between an electron and anti-electron and a gamma, or an electron, another electron in the final state and a gamma, etc., etc., or a positron and a positron in the final state, etc. There is no vertex associated to the nu gamma. So neutrino interaction with the photon, it's not there. Okay, so now let's, this part here was easy because was very much mirroring the part of quark, the interaction between quarks and the gauge bosons. We just removed the gauge boson associated to the strong interaction. And And now let's pass to the fourth part of the Lagrangian in the standard model, which is the Lagrangian associated to the Higgs mechanism that will give mass to the gauge bosons. Of course, another thing, we listed the fact that there are kinetic terms for this gauge boson in the first part of the Lagrangian, of course also in the second part of the Lagrangian and the third part of the Lagrangian, since the covariant derivative contains this operator here, the derivative operator, they contain kinetic terms for quarks and kinetic terms for electron and neutrinos. So both 2 and 3 contains kinetic term for the fermions, which are also the spinor fields. Okay, let's see what the fourth term in the standard model Lagrangian contains. So in the fourth term, which is associated to the standard model Higgs, the Higgs field is a doublet of isospin, and it's a singlet with respect to color. So the covariant derivative that we have in the fourth term is exactly the same covariant derivative that we have in the third term, with no fields associated to gluons. Okay, no fields associated to the SU3 color symmetry, because the Higgs boson is a doublet of isospin and a singlet of color, let's say. This means that the gluons in the standard model do not acquire a mass. So we have two pieces now here, which are this first piece with the covariant derivative that contains one kinetic term for the Higgs boson. Then it contains interactions between Higgs boson and gauge boson, and the interaction between Higgs boson and gauge boson will be of various forms. Oh no, let's say second part, mass terms. So it contains a term which is mz squared zz. Let's put this before, and then mw squared ww. We will see how big are the mass of the z and the mass of the w in the animation at the end of this lecture. But just to say that these are the terms that give mass to the Z boson. Of course, ZZ, and this is WW. This is the term that give mass to the Z boson, and this is the term that give mass to the W boson. And then 3, it contains interactions. Yes. Since we are talking about mass terms, this particular term here with the covariant derivative that couples the Higgs with the gauge boson contains the mass term for the gauge boson. And then we have another piece, which is this Higgs potential, in which we have a term which is MH squared HH, in which we have the mass term for the Higgs boson. So it contains mass term for gauge boson and Higgs boson, all this fourth piece of the Lagrangian. And then 3, it contains interactions of the type, so interactions, and the interactions in this kind of piece here are of the type W plus W minus Higgs, so vertices in which I have participating a W plus, a W minus, and a Higgs boson. Then I have vertices in which I have Z plus Higgs, and then I have, so these kind of vertices are something like this: a gauge boson, and then a Higgs boson. Then I have the same kind of vertices, but in which 2 Higgs boson participate, so W plus W minus Higgs 6, or ZZ Higgs 6. As you notice here, the photon, it's not coupled with the Higgs boson, because the photon in the standard model does not have a mass, and the same goes for the gluon. And so these 2 kind of vertices here are vertices in which I have 2 gauge bosons and 2 Higgs bosons. And all these vertices here come from the first piece in which I have the covariant derivative, and then from the Higgs potential I have Higgs boson self-interaction. So I have terms like Higgs, 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 or Higgs, 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 okay? So interaction in which I have 3 Higgs bosons, or interaction in which I have, or vertices in which I have 4 Higgs bosons, okay? So these are all the ingredients or the vertices that appear in the 4th piece of the standard model Lagrangian. And after commenting this, which we did very fast, but there is not much to say, we go to the 5th piece of the standard model Lagrangian, which is the piece that gives us interaction between the Higgs and fermions. This will give us the mass of the fermions, of course, and interaction terms between Higgs and fermions. So the piece number 5, this is the easiest one because we only have 2 kinds of interactions. This term here, this first term here gives us the mass of the up quark. So we have m up. Then we have this term here that gives us a mass for the down quark. We have the mass term for the down quark, and then we have a mass term for the electron. In the standard model, we don't have a mass term for the neutrino, in this case here. Even though we know that experimentally the neutrino have a mass, in this Lagrangian here, we do not have a term for the mass of the neutrino. Then we have interaction, so these again are mass terms for mass term of fermionic mass term, and then we have interactions in which I have, for example, interaction between, let me check. Yes, we have interaction like electron-electron Higgs, and then we have up quark Higgs, and down quark Higgs. We do not have neutrino Higgs because also, as you can see here, the neutrino part of the Lagrangian is not coupled with the Higgs boson part of the Lagrangian. Even though, as you notice here, the neutrino appears in this doublet here, but then this field here, which is the phi, it's after symmetry breaking, so after the mechanism that gives mass to particles, it's 0 v plus h over square root of 2. So, as you can see, when I multiply this doublet times this doublet here, the term associated to the neutrino goes to 0. So that is to say that we have no interaction in which the neutrinos are coupled with the Higgs boson, and we have no interaction or no piece in the Lagrangian that gives us a mass term for the neutrino. Great! We have now all the standard model Lagrangian for neutrino, electron neutrino, up quark and down quark. We commented every piece of this standard model Lagrangian, and you practically have now the basics of particle physics. And with this knowledge, you can do practically everything in particle physics and go deeper in every subject which is more deep in particle physics. Of course, we skipped a long, an incredible amount of complications. For example, we didn't talk about renormalization, we didn't talk about quark confinement and quantum chromodynamics in a deeper level, but because this, of course, will need another full course on particle physics, and that is not what we want to do. What we want to do is that you now understand more or less this Lagrangian and every piece inside this Lagrangian, and once you are super familiar with every single piece in this Lagrangian, then you can really understand at a deeper level everything else in particle physics. But we are still missing a piece in this Lagrangian, which are the other lepton and quark families. In particular, as I told you already multiple times, we have in this case quarks. So the quarks included in this Lagrangian are just up and down. Okay. And the leptons included in this Lagrangian are just neutrino, electronic neutrino and electron. But we have other 2 families of quarks and other 2 families of leptons. In particular, the other 2 families of quarks are a quark that is called charm and strange. So a quark that is called charm, a quark that is called strange, a quark that is called top, and a quark that is called bottom. And the other two families of lepton are the muon neutrino and the muon, and then the tau neutrino and the tauon. Okay, how to include these families in the standard model Lagrangian? We will skip the complications and do it in a very, very simple and elegant way, which is the following. First of all, let's define, instead of defining the families in this way, so instead of calling the particles with a different name, we just define this second family as neutrino 2 and electron 2, and this third family as neutrino 3 and electron 3. So if I say, for example, E3, this will be the third generation electron-like particle. Okay, the same thing applies to applies here. If I say, for example, up 3, this means the third generation up-type quark. So this is the first generation, this is the second generation, this is the third generation. This means top. Okay? If I say down 2, this means the second generation down-type quark. This is the second generation, and this is the down-type quark. So this means S. Okay? So that we can label in the standard model, and we can keep this Lagrangian exactly as it is, but in which this up quark is not anymore only the up quark, but is an up-type quark. So it accounts for this generation, and this generation. This down quark here is a down-type quark, so it can be a down, a strange, or a bottom. Same goes for this electron. This is not the electron anymore, but it's the electron-type lepton. So it can be the electron, the muon, and the tau. And this we do it practically, applying a label, which is this label F, to every part which is fermionic inside the Lagrangian. F, 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 which stands for family, and then we will sum over all the three families. So F, 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 and this is the standard model Lagrangian almost. We also need to comment this piece, but this is the standard model Lagrangian with 3 generations of leptons and 3 generations of quarks. Of course, we need to sum over the families F, where F can be 1 to 3, plus we have already F goes from 1 to 3. And then the biggest modification comes in the Yukawa sector of the Lagrangian, because in the Yukawa sector of the Lagrangian there is a complication, which is that these guys here, which are coupling constant now between Higgs boson and the up quark, for example, Higgs and the down, Higgs and the electron, now they change and they become matrices. Okay, so we have no more a coupling in which this field here is the same family, is the same generation as this field here, but they can also be different generations. So in this case I have 2 indices, one is F and one is G. Also in this case I have F and G and Hermitian conjugate. In this case I also have F and G. And now I have to sum this piece not over F, but over F and G. And also this piece I have to sum it over F and G. And so this piece here, G mu, G U, becomes what we call a Yukawa matrix. And here in the sum I have the elements of this Yukawa matrix. So I have the F, G element of this 2-dimensional matrix. This G, it's not a number anymore, but is a matrix. And in this piece here, I have the F, G element of the Yukawa matrix, and this applies also for the electron. So this one becomes a Yukawa matrix. and here in the standard model Lagrangian I have the element Fg of this matrix here. Okay, we will not go further in commenting this. Let me just say that these Yukawa matrices are diagonal in the mass basis. So when we will go and try to find the mass of fermions, we will figure out that the states that diagonalize, or the, let's say, the weak interaction basis, so the fields that participate inside the weak interaction and that participate inside this piece of the Lagrangian, are not the same fields that diagonalize these matrices here. This fact that the fields that diagonalize these matrices are not the same fields that participate in the weak interaction give rise to the CKM matrix, so the Kabib-Kobayashi-Maskawa matrix, CKM, and this gives rise to a lot of interesting physics that we will not comment. But before studying this matrix here and this and all this physics associated to this part here, make sure you understand the standard model Lagrangian in the simplest case, in which you do not have the families of fermion, so families of quark and families of lepton going around. Because once you understand very deeply this Lagrangian, then you can start understanding this mechanism here. So this very messy formula here, it's now finally this standard model Lagrangian that describes every quarks, every lepton, and the interaction between them. Just for your convenience, I wrote down the Lagrangian of the standard model in a way which is a little bit more clean than the mess that we had before, but is exactly the same amount of information. Just take a screenshot of this, because this is the peak that we reached in our lectures about particle physics. We really reached the top of the mountain, but this is just the starting point for everyone working in particle physics. Okay, this is the, it's almost like a code. Inside this code, inside this huge dictionary, we have all the particles and all the interactions, and we have practically everything we know about particle physics. But then using this code, it's a lot of work. For making theoretical predictions about processes that involve particles, the mechanism is actually the same that we saw for quantum electrodynamics, but it's just more and more complicated, because for electromagnetic interaction and weak interaction, we can just make Feynman rules starting from this big Lagrangian and then computing amplitudes associated to every process using perturbative theories, because the couplings associated to weak interaction and electromagnetic interactions, which are this one and then the electromagnetic coupling and this one, are small at normal scales. But when it comes to quarks, I cannot use in every regime the perturbative quantum chromodynamics. This means that since this coupling here, it's not small, it's strong, this one, for example, GS is of the order of magnitude of 1 at energy around, let's say, this one, it's around 1 GeV of order of magnitude of 1. When I'm at low energy, so when I'm trying to make predictions with processes that involve exchanged particles, in which the momentum of the exchanged particles here is around 1 gigaelectron-volt, I cannot use Feynman rules and Feynman diagrams for computing amplitudes. So I need to use some non-perturbative techniques for making predictions when it comes to quarks. This, I just wanted to mention it, because then I don't want you to be under the illusion that this standard model used with the Feynman rules can solve every possible problem in particle physics. And the reason why many particle physicists have a job is that this coupling here is strong at low energy. Okay, then when I go up and I go to energies, for example, around 10 GeV or even more, for example, 91 GeV, which is the energy of the, let's say, the mass of the Z boson, this coupling becomes small. So for all these processes in which the energy, the exchanged energy in the process is large, I can make perturbative predictions. This Lagrangian here is just the starting point in physics, and we are very far from from covering everything that there is to know in particle physics. In particular, we skipped all the part about renormalization, and how can I get rid of the infinities that emerges in Feynman diagrams, and we just came across quantum chromodynamics. But quantum chromodynamics is a huge field, and there is a lot of work to do and a lot of things to talk about in quantum chromodynamics, and that could be a whole new course. Now it's time for fun, and instead of listing every possible particle and every possible interaction that take place inside this standard model Lagrangian, just giving you the mass of this, the spin of this, the spin of this, and the mass of this, I want to show you an animation that contains inside every possible quantum numbers of every particles in the standard model Lagrangian. In particular, in the animation we will see there will be the mass of particles, which is associated to the dimension. So the more a particle is big, the more the particle is massive. This is not physically true. It's not true that a massive particle is bigger than a non-massive particle. If anything, it's the opposite, but let's not dive into this. Then we have the spin of the particle. Every particle that has spin 1/2, it's rotating in a weird way. You will see what I mean. Every particle that has spin 1 is making a rotation only around the z-axis, and every particle that has spin 0, so the Higgs boson, it's not rotating. And then we have the charge of the particles. Let me cancel this part here, covariant derivative. Yes, then we have in this animation that you will see the charge of the particles. In particular, every particle that is negatively charged, so minus, it's green. Let's put it like this. So it has a green ball inside. Every particle that is charged positively has a red ball inside. And then the dimension of the ball, it's related to the dimension of the charge. So if a ball is minus 1/3, for example, it will be a little ball green. If a ball is plus 2/3, will be a little bit bigger than the minus 1/3 ball, but red. Okay, but you will see that in the animation. And then last thing that we will see in this animation is the color charge. And in case of the color charge, only the quarks are charged with color, and the only particles that are colored, that have a fixed color in their rotating shell, are the ones that have color charge. Now I let you admire all these particles. This is just for fun. Of course, I'm not expecting that you will learn every quantum number of every particle just looking at this animation, but it's just for having an idea on the variety of particles that we have in the standard model, and on how these particles are related to each other and what are the numbers of this particle. And of course, we also have all the numbers associated to every particles in this animation. Final remarks about this course. Making these lectures was amazing. I had amazing time, and I'm probably the one who learned most by making this full course on particle physics, and I'm very, very, very proud of the result. Now, what to do next? I wanted to do a final recap of everything, but it's already in the introduction. So I send you back to see the introduction, and you will find the final recap of everything we saw in these lectures. And I invite you to go back to the introduction, rewatch the introduction, and have a sense of how much you learned in this course and how much you still have to learn. Because in the introduction you will figure out what are the gaps and what are the things that are still missing in your understanding of basic particle physics. Then the lecture notes for this course will be uploaded in the description of this course as soon as they will be ready, and I hope they will be ready very, very soon. This is all. See you in the next 20-hour course about something.